Hello everyone. So could you please confirm me once in the chat box that am I audible and visible? Yes. Am I audible and visible everyone? Could you please confirm me once in the chat box? How are you all? How are my Avengers? Doing great? Yes everyone. So please confirm me once in the chat box that am I audible and visible? Yes, I'm perfectly audible, perfectly visible. Good evening. So let me just ask all of you to join. Join fast everyone. We are starting. Okay. So I have messaged, right? Let all your friends join as quickly as possible. Very good evening everyone. Good evening, good evening, good evening, good evening, good evening. Very good evening. How are you all? If you guys are doing great, you guys are fit, you guys are fine, then I want a rain of green and red hearts, okay? Right? Ma'am, now one of the person is asking, ma'am, why there are so much of exceptions in inorganic, okay? See, there are exceptions, but I haven't, ever worked without telling a trick, okay? So I think that is also something which should be appreciated, yaar. Why I can see very less green and red hearts, yaar. I want lot of green and lot of red hearts, everyone. Yes, lot of green and lot of red hearts, okay? Tell your friends wherever you can that you guys have to join as quickly as possible in your chapter coordination and compound, where we are going to smash this chapter in one go, okay? So here we are going to, yeah, Khush, I remember you. So here we are going to smash this chapter in one go, everyone, okay? In one go, fine? So yeah, yes, I can see lot of green and lot of red hearts. There are a lot of students who are joining my class for the very first time. So I hope you guys get a wonderful experience and you guys join this class again and again and again, okay? Right? Yes. Fine. One of the person is asking, ma'am, is this series is enough? Better see, I am teaching in this online sector from lot of years now, right? So what I have experienced, what I have observed, that on this channel, everybody teach serious things, okay? They teach you the content which is relevant. They teach you the content which is appropriate for NEET exam, right? So this series is well and sufficient if you are targeting for your NEET 2025, everyone, okay? Right? Now again, if you guys are ready, then I want lot of green hearts, okay? Somebody is asking that, ma'am, why you like green hearts? Heart is just because it's a symbol of love and green stands for go. So that is why I want green hearts in the chat section, so that I can begin this session with great energy, great enthusiasm, and we can go a long way, because I know this chapter is really big, yeah. There are a lot of topics which we need to discuss. So I need some energy, yeah. I need some energy. So you guys are my power bank and these green hearts are my power bank. So give me lot of energy, bacha. Okay, give me lot of energy. Duration is going to be a big marathon, right? Okay, so it will going to be of 8 to 9 hours. Fine, might be 10 hours. If you guys are energetic enough, you guys will keep me energetic and we will be able to complete it very soon, right? So that depends on your energy and my energy, right? Minimum 9 hours, okay? 9 hours are going nowhere, okay? It's going to take minimum of 9 hours, right? So can we just start this session, everyone? Can we just start this session? Yes. Can we just start this session? Okay. Now we are about to start this session, everyone. So in this particular session, we are going to smash the chapter coordination compounds, okay? Right? So now let's just begin with today's session. Bacha, in order to understand coordination compounds, we need to understand that what are simple salts and what are double salts, okay? If we have to understand that what are coordination compounds, everyone, we need to understand two terms. The very first term is, bacha, salts, or I should say simple salt. The other word is, my dear students, addition compounds, or I should say addition salt. Am I clear, everyone? Yes. Am I clear, everyone? Clear? Okay. Now, first of all, I will talk about simple salt. Now, what is the simple salt? We are studying since our foundations, right? Since our 9th and 10th, that whenever acid reacts with base. They basically forms salt plus water, right? What we get to see, bacha, what we get to see that whenever, right, whenever acid, okay, acid reacts with base, right, it basically forms, okay, it basically forms what, my bacha? It basically forms salt plus water, right? Salt plus water. Fine. For example, let's take your favorite acid. Now, what is your favorite acid, beta? HCl, right? What is your favorite acid, beta? HCl. So, if I take HCl and I take a base NaOH, right? They will react, bacha. What they will do? They will react to form which salt? Please tell me in the chat box, which salt will be formed right here, beta? They will form NaCl plus they will form water. Am I correct, everyone? Right? Now, this NaCl, bacha, consists of two ions, right? One, it basically consists of sodium cation, and other, it basically consists of chloride anion. Am I clear, everyone? Okay, that means there is one particular type of cation present right here and one particular type of anion is present right here. Am I correct, everyone? Fine. So, all those salts, okay, all those salts which basically consist of one particular type of cation and one particular type of anions, beta, all those salts are known as simple salts, okay. Now, what are salts or what are simple salts, beta? I will write, ma'am, they contains what, my bacha? They contains only one type of cation, only one type of cation and anion, beta. Only one type of cation and anion is present. The very first example we have taken into consideration, bacha, the example is NaCl. Am I clear? The example is NaCl, right? The very first example which we have taken into consideration is, bacha, NaCl. Now, the other examples which you can take into consideration are, my dear students, it's KCl. You can take KCl into consideration. You can take K2SO4, okay. Now, K2SO4 also consists of only one type of cation and one type of anion. For example, potassium cation and sulfate anion, right? We know that here K plus and SO4 2 minus basically forms what, beta? They forms K2SO4. We all have studied that in our 9th and standard year. Come on, we all know that, right? Fine. Okay. So, here we got our simple salt, right? You can take other examples also into consideration. Some of you are saying, ma'am, MgCl2. Yes, MgCl2 is also basically a beta simple salt, right? It is also a simple salt. Fine. Okay. Moreover, we can take another examples into consideration as well, okay, right? For example, you have aluminium sulfate, bacha. Fine, you have aluminium sulfate, you have KCN, you have FeCN whole twice, right? Now, all these compounds basically consist of one type of cation and one type of anion, and that is why they are basically known as simple salts, okay? They are basically known as simple salts. Am I clear, everyone? Fine. They are basically known as simple salts. Now, ma'am, you told that in order to understand coordination compounds, we need to understand, ma'am, addition compounds, right? Okay, I was absolutely correct at that point, beta. Now, what happens? We already know what are simple salts, right? We already know that what are simple salts. So, what we will do, beta? We will take aqueous solution of simple salt 1. Now, it could be any simple salt. Say it is KCl, okay? Right. Similarly, we will take the aqueous solution of another simple salt. Suppose it is MgCl2. Okay. So, what I will take, bacha, in order to prepare addition compounds, I will take the aqueous solution of two simple salts. Fine. Suppose this is simple salt 1. Am I clear, bacha? This is simple salt 1, right? I am taking its aqueous solution, Raji. I am taking its aqueous solution, right? Similarly, I am taking the aqueous solution of another simple salt. Okay, this is simple salt 2. I am taking its aqueous solution as well. I am taking its aqueous solution as well. Okay, bacha, right? Now, what we are doing, we are basically heating the two. we are mixing the two and then we are heating the two. Okay, so what we are doing, we are heating the two and we are mixing the two. Now how long we are heating beta? We are heating till all the water which is present, okay, all the water which is basically present right here evaporates beta. Okay, we are heating till all the water which is present in the solution basically gets evaporates. Okay, right. So here what will happen bacha? Evaporation will take place, right? And after evaporation we will left with the crystals, and these crystals are basically of our desired product, which is addition salt or addition compounds. Okay, so what I will get beta? I will get crystals. Okay, I will get crystals of addition compound, or I should say addition salt. Am I clear everyone? Fine. Now here, two things we need to take into consideration. The very first thing, the process by which we have prepared the crystal of addition compound. Now this particular process is basically known as crystallization. Am I clear bacha? This particular process is known as crystallization. Am I clear my bacha? This particular process is known as crystallization. Am I clear? The very first point. Fine. Now the second thing which we need to take into consideration is that ma'am, can we take any much mole of simple salt 1 and any much mole of simple salt 2? No beta. We take definite proportion of them. Okay, that means if we will take 1 mole of simple salt 1 and 1 mole of simple salt 2, so the molar ratio of the two is 1:1. Okay, that means we have taken them in definite ratio or definite proportions. Am I clear everyone? Right. So what I am saying right here bacha, what I am saying right here, that they both are taken in a definite proportion, in a definite molar ratio. Fine. So what I am writing here beta, I am writing here that they both are taken in definite proportion. Okay, they both are taken in definite proportion. Am I clear everyone? Definite proportion. I hope I made my point really clear to you guys. Okay, right. Somebody is saying ma'am, it is dehydration. See, dehydration is also the elimination of water, but dehydration is basically absorption of water. This is evaporation beta. Evaporation means here vapors are forming till water is getting disappear. Am I clear? There is a small difference you need to take into consideration. Am I clear? Now somebody is asking ma'am, please give us certain examples. Yes, I will give you certain examples, but you need to understand one thing right here, that here the crystals of addition compounds which are basically formed. Now these addition compounds could be of two types. Okay, these addition compounds could be of two types. Am I clear everyone? Right, these addition compounds could be your double salt bacha, right? These addition compounds could be your double salt bacha. Am I clear? Okay, or these addition compounds could even be coordination compounds or complex salt. Okay, so these addition compounds could even be your coordination compounds, they could be your coordination compounds, or my bacha complex salt. Okay, or complex salt. Am I clear everyone? Am I clear everyone? Right, that means here the chapter coordination compound which we are going to study in this chapter, the coordination compound is nothing but it is basically a addition compound. Am I clear everyone? Okay, now you must be thinking ma'am, what are the conditions in which the addition compound is a double salt, and what are the conditions in which this addition compound is basically a coordination compound? We want to know ma'am. This is our birthright. I said okay, I'll tell you my bacha, I will tell you. Right, see what I am doing right here. First I am telling you an example of double salt. Okay, so I am telling you what kind of addition compounds are basically double salts. Okay, right, now here what I am taking, I am taking aqueous solution of KCl. Fine, what I am taking bacha, I am taking aqueous solution of KCl. Fine. Okay, similarly here I have taken aqueous solution of two simple salts beta. So one I have taken is aqueous KCl. Fine, the other simple salt which I am taking right here is basically aqueous MgCl2. ठीक है बच्चा? So now another salt is basically aqueous solution of MgCl2. Okay, now what I am doing, bacha, I am making the two heat, right, and I have taken both of them in a proportion 1:1. That means I have taken 1 mole of KCl and I have taken 1 mole of MgCl2, right? Fine. So what I am doing, beta, I am heating them till all the water gets evaporated, because I have taken aqueous solution, right? So water needs to be evaporated. So I am heating them till all the water is basically evaporated, right? And after that bacha, what I will get KCl dot MgCl2 dot 6H2O. Now this 6H2O is nothing but the water of crystallization, right? Now what happens, bacha, when this addition compound has been prepared, right? What I am doing, I am putting this addition compound into water. I am adding this compound into water. Okay, what I am doing, bacha, I am adding this addition compound into water, right? Fine. Okay, so what will happen, beta? I will get K plus, I will get Mg2 plus, okay, right, plus I will have how many chlorine ions, bacha? 1 Cl minus ion from here and 2 Cl minus ions from here. That means I will get 3 Cl minus ions from here. That means when this addition compound is added to water, right, this addition compounds break up into its ions, right? That means this addition compounds basically loses its identity. Okay, this addition compound loses its identity when this is added to water, right? Now all those addition compounds, mark my words, all those addition compounds which basically loses their identity in water, they are basically known as double salt. Am I clear, bacha? They are known as double salt. Somebody is asking, addition compounds, do they react or do they form new compounds? See, bacha, addition compounds are nothing but a type of double salt only, right? Here, either a double salt or a coordination compound. Yes, they can react. The condition varies, but yes, they can react. However, when you will put an addition compound into water and it's split up into its ions, okay, it gets just splitted up into its ion, it breaks into its ion, then such addition compound is basically known as double salt. Okay, right. So what I will say, bacha, I will say that this addition compound is basically double salt. Am I clear, Rajay? Right. Now this double salt is a type of addition compound which it loses, okay, it loses its identity. It loses its identity in aqueous solution. Why it loses its identity in aqueous solution, bacha? Because it gets break down into its constituent ions. Am I clear, everyone? Yes, am I clear, everyone? Okay, now listen to me once, listen to me once. Suppose you have individual aqueous solution of KCl and individual aqueous solution of MgCl2. Now these are nothing but ionic compounds, right? If you have their aqueous solution, beta, and in that aqueous solution you perform the test for K plus cation, okay, you perform the test for Cl minus anion, or you perform the test for Mg2 plus cation or Cl minus anion, you will get a positive test. Am I clear? You will get a positive test, right? Fine. Similarly, if you are taking this aqueous solution of double salt, which basically contains all these, cations, right? You perform the test for individual cation and anion here. Here also you get the positive test, right? Here also you get the positive test, beta. That means here all ions give their positive test, okay, right? Here all ions give their positive test, bacha, okay? All ions give their positive test, right? All ions give their positive test. Now what do you mean by this, bacha? See, whenever you want to test Cl minus, okay, whenever you want to test Cl minus, what you do, bacha? Basically, whenever Cl minus reacts with AgNO3, okay, it basically forms the white precipitate of AgCl, right? It basically forms the white precipitate of AgCls. So what we are doing in this particular aqueous solution, we are adding 3 moles of AgNO3, right? Fine. So what we will get, beta? We will get 3 moles of AgCl. Now these 3 moles of AgCl confirms, and in this particular solution Cl minus is present. In a similar manner, we can perform a test for K+, we can perform the test for Mg2+. That means ions still give their positive test, right, as they used to give in their individual aqueous solution. That means here ions do not loses their identity. Am I clear, bacha? Now what we get to understand? Here ions do not loses their identity. Okay, so I am writing here that here ions, okay, ions do not loses their identity. Okay, so we should say that ions have retained their identity, they haven't lost their identity. Am I clear, everyone? Is my point clear to you all, everyone? Clear? If K+ and Ca2+ are present in the salt and it was made into a paste and then brought into the Bunsen burner, bacha, we will get the flame test. Okay, we will get the flame test. Earlier we used to study these flame tests in S block, so now you don't have to go into details. Am I clear? Okay, fine. Am I clear? Now let's just move ahead, beta. Now suppose we are taking the example of the another type of addition compound, which are coordination compound or complex compound. Okay, suppose we are taking, bacha, 4 moles of KCN, right, aqueous solution of 4 moles of KCN, fine, and we are taking, bacha, 1 mole of FeCN whole twice. Okay, we are taking the aqueous solution of it. That means here also we have taken a definite proportion, which is 4:1. Am I clear, everyone? 4:1 is a definite proportion which we are taking it right here. Now they are basically made to react. What we will get, beta? We will get 4 KCN dot FeCN whole twice, or this can even be written as K4 FeCN6. Okay, they can even be written as K4 FeCN6, right? Now here again an addition compound has been formed once we have heated it till evaporation, right, till all the waters get dried up in the aqueous solution. Fine. Now what we are doing, beta? We are getting again an addition compound. Okay, we are getting again an addition compound. Am I clear, everyone? Right. Now what I am doing right here? I am putting this addition compound into water. Am I clear, bacha? I am putting this addition compound into water. Now what will happen, beta? It will breaks as follows. It will give 4 K+ ion plus it will give FeCN whole 4 negative ion, my bacha, right? Fine. That means here it haven't broken up, or it haven't broken up into all the individual ion, right? It haven't broken into all the individual ions right here, my dear students, right? Okay, so if it haven't broken into its individual ions right here, that means this particular addition compounds does not, loses its identity into aqueous solution, right? Why? Because it does not completely ionizes into its individual ions. Now what are its individual ions, beta? K+, Cn, Fe2+. These are the individual ions. Now we haven't got the individual ions when we have put it this particular addition compound into water. Am I clear, everyone? Okay, right. So what we will write here, beta? This particular compound retains, okay, it does not loses its identity. If it would have lost, it would have broken up into the individual ions, right? But it haven't just broke up into its individual ion. That means this particular addition compound retains its identity. Okay, it retains its identity in aqueous solution, or we can say it does not loses its identity. Okay, it does not loses. See, it is in English, right? Either you can say it does not loses its identity in aqueous solution, or you can say it retains its identity in aqueous solution. Both are one and the same thing. Am I clear, everyone? Am I clear? Yes, am I clear? Okay, so we can say it retains its identity in aqueous solution. Now all those type of addition compounds which do not break up into individual ions, or we should say which retains their identity in aqueous solution, all those addition compounds are basically known as coordination compounds. Am I clear? All those addition compounds are basically known as coordination compounds. Am I clear, bacha? Right? Okay. Now this particular compound is an coordination compound. Am I clear, everyone? Yes. Am I clear? Is my point clear to you all? Is my point clear to you all? Okay. Now listen to me once, beta. Listen to me once. Here, we will get the test for all the individual ions. That means we will get the test for K plus right here for sure. But we will get the test for Fe2 plus and Cn minus ion right here? The answer to that is complete no. Am I clear, everyone? The answer to that is complete no. Somebody is asking, ma'am, do we need to balance? No, we do not need to balance. Please, we do not need to balance, okay, right? Now what I am saying, please tell me in the chat box, please tell me in the chat box, we will get the test for Fe2 plus and Cn minus ion right here? No, no beta, why? Why? Because they are not present as an individual ions right here. They are present in form of this complex. Am I clear, everyone? So here we won't be able to get separately the test of Fe2 plus ions and Cn minus ions. Okay. So what I will say that we will not get the positive test. Okay, we will not get the positive test for all the ions. Am I clear? For all the ions. Am I clear, everyone? So we will not get the positive test for all the ions, right? Am I clear, Rajay? Am I clear? Fine. That means here ions are not giving their positive test. That means ions have lost their identity. You know, earlier when here we used to perform the test, here each ion used to give their specific test. Okay, Fe2 plus used to give its test, Cn minus used to give its test, here K plus is used to give its test, but here the individual ions are not able to give their test. That means bacha ion have lost their identities. Okay, so what we will say beta here, ions have lost their identity. Ions have lost their identity. Am I clear, bacha? Ions have lost their identity. Am I clear or not? Yes. Am I clear or not? Clear, everyone? Okay. Here ions have lost their identity. Clear? Right? So you must have got the basic difference between double salt and your coordination compounds. Okay, so first thing we got to understand about double salt is that whenever we put the double salt into water, it's completely break up into its ion. That means it loses its identity into aqueous solution. Clear? Right? However, if I talk about coordination compound, whenever we put a coordination compound into its water, it does not splits up or it does not breaks down into individual ions. That means it retains, okay, it retains an identity in aqueous solution, or I should say it does not loses its identity in the aqueous solution. Am I clear, everyone? So here I have written all the major differences, right? The very first difference is to sum up beta. The very first difference right here to sum up is, see, if I talk about double salt, what happens beta? It completely ionizes into aqueous solution. That is why it loses its identity in aqueous solution, right? However, if I talk about coordination compound or complex salt, bacha, what happens beta here? It do not completely ionizes into aqueous solution and it retains its identity into the aqueous solution. Now somebody is asking, just a second, let me see, the chat is very fast. Should anions be same in the given addition salt compound? It's possible? No. Bacha, if you are taking Cl minus anion initially, then the addition compound will contain the anion Cl minus only, na? The generation of new ion is not possible. Am I clear? Okay, right, fine. Okay, you have studied now the principle of atom conservation. The atom always remains conserved, right? Matter can neither be created nor be destroyed. If you have taken Cl, then at end also you will get the Cl. Am I clear? Okay. Now, bacha, here if I talk about double salts, beta, here in the case of double salts, what I can see, beta, each ion give its positive test. That means individual ion retains their identity, they do not loses their identity. Talking about that of coordination compound, beta, what happens here? Each ion do not gives its positive test. That means each ion loses their own identity. Okay, so individual ion have lost their own identity. Fine. I hope all the points regarding double salt and coordination compounds are clear to you all. I hope they are clear to you all. Right? Can I move ahead? If these two differences are clear to you all, please give me red hearts, please give me green hearts. If these points are clear to you, please give me green hearts and red hearts. Yes, clear or not? Clear, everyone? Okay, now let's just move ahead. Okay, now I have a question for you guys. Right? My question is, if I have a coordination compound Cu H2O whole 4, okay, Cu H2O whole 4 SO4, okay, right? Now please tell me in the chat box what all ions will form when we put this coordination compound into water. Quickly tell me in the chat box. Yes, quickly tell me in the chat box. I can see some of you are saying, ma'am, here we will get one sulfate ion, right? Here we will get, ma'am, one sulfate ion, that is SO4 2 minus ion, ma'am, right? And here, since we do not have anything in the subscript, that means here the part is CuH2O whole 4 2 plus. Am I clear, bacha? See, it's very simple. If I have ASO4, beta, ASO4 is possible only when I have taken a cation A2 plus and anion SO4 2 minus, right? Then only A2SO4 can be formed, right? Then only it can be formed, and we write it in a simple ratio. The simple ratio is ASO4. Right or not? Right? That means here, if nothing is written in the subscript of this particular part and on the subscript of sulfate, that means both are said to have equal and opposite charges. That means +2 and -2. Am I clear? Right? Okay. Now, this will give test only for sulfate ion, not for copper 2 plus ion. Am I clear, everyone? Yes. Am I clear, everyone? Is it clear to you all? Clear or not? Clear, everyone? Right? Yes, I can see many of you are giving me the correct answers. Keep it up. Yes, Pujasvi, absolutely correct. Okay, now let's just move to the another point, that is why D block elements form large number of coordination compounds. So, bacha, the answer for the fact that D block elements form large number of coordination compound is that they are said to have vacant d orbitals. Okay, they are said to have vacant d orbitals. Okay, they are said to have vacant d orbital, beta. That is the reason that they are said to have, okay, they are said to have large number of coordination compound. One reason is that they are said to have vacant d orbital, beta. The another reason is they are said to have high charge density. Okay, they are said to have high charge density. Okay, bacha, they are said to have high charge density. Now, what is this high charge density, beta? Charge density is said to be the ratio of charge with size. Okay, it is said to be the ratio of charge with size. Now, we know that, bacha, the size of D block elements is very small. Okay, so size is small, that means sizes decreases, and they are said to have large number of, okay, they are said to have large number of charges. Okay, they are said to have +2, +3, +4, right? I have told you in 3D manganese is said to have +7 oxidation state or a charge, right? So they are said to have large sized charges, beta. Okay, now see, denominator is small, numerator is large. That means, beta, charge density is really high. Fine. So these two are the reasons for the fact that why Why? D block elements form large number of coordination compounds. Am I clear, everyone? Right. Now, I will tell you what is the use of this vacant d orbital and what is the use of this high charge density on the next slide. Right. Why these two factors are favoring the D block elements, I will tell you in our next page. Okay. I will tell you in the next page. Till here, please tell me in the chat box that each and every point is clear to you all. Any doubt, any confusion, beta ji? Each and every point is clear or not? Yes or not? Yes or not, beta? Yes or not? Yes or no? Yes or no? Each and every point is clear? Clear? Yes, clear, clear, clear. Great. See, beta, see. Now, what happens, beta, in the formation of coordination compounds, right? There is one species which is known as metal and there is one species which is known as ligand. Okay, right. In the formation of coordination compound, there is one species which is known as metal and there is one species which is basically known as ligand. Am I clear, beta? Right. Now, here metal is said to have vacant orbital. For example, if the metal is of D block, then it is said to have vacant D orbital. Am I clear, everyone? Right. Now, here next we have basically is the ligand. Okay. Now, ligand is said to have, suppose, lone pair of electron, right? Ligand is said to have, suppose, lone pair of electrons. Now, you must have studied the formation of a covalent coordination bond, right? You must have studied the formation of covalent coordination bond in the chemical bonding chapter, right? Now, what happens, beta? This ligand is said to have a lone pair of electron. Now, this metal is said to have a vacant d orbital. Now, what will happen, beta? This ligand will donate this lone pair of electron to the vacant orbital of the metal and there occurs the formation of covalent coordinate bond, right? Whenever the charge density of metal is high, it will attract more the lone pair of electron from the ligand. First point, that is why we need a metal of high charge density. Secondly, it is said to have a vacant d orbital. That is why it is going to attract the lone pair of electron from the ligand. Am I clear, everyone? Yes. Am I clear, everyone? Yes. Is it clear? Okay. So, what we will write, bacha? We will write here that in formation of coordination compounds, in formation of coordination compounds or complex compounds, okay, coordination compounds or complex compounds there occurs the formation of covalent coordinate bond between metal and ligand, beta. Make sure to write all these points in your notebooks, please. Although I will share the notes on my Telegram channel, but still I will suggest you all to make sure to write all these points into your notebook. Am I clear, everyone? Okay, right, fine. So, here the necessary condition. So, the necessary condition for the formation of coordinate bond will be that metal should have the vacant d orbital, right? So, here we got the necessary condition is that metal should have, okay, the metal should have vacant d orbital, Am I clear, everyone? Am I clear? Is this point clear to you all? Fine. For example, we have form a coordination compound K4FeCN6, right? Okay. So, we can see that in this particular compound, we have 4 K plus ions, bacha, plus we have FeCN whole 4 negative ion right here, right? Okay. Please make a correction. It is 6. Okay. It is 6. Make a correction. Am I clear everyone? Okay, so FeCN whole 6 4 negative ion. Am I clear everyone? Now here what will happen beta, each cyanide ion is said to have a lone pair of electron, right? So here each cyanide ion will make a coordinate bond, right? It will make a coordinate bond with Fe2 plus, which is present right here. Okay, it will form a coordinate bond with Fe2 plus, which is present right here. Am I clear beta? So it is going to form the coordinate bond with Fe2 plus, which is present right here. Am I clear everyone? Am I clear everyone? Yes. Am I clear everyone? Okay, fine. Yes, clear. Okay, so I can see, yeah. I told you in the first slide, ma'am. What you told me in the first slide, beta? You have to tell me again. I have skipped it. Okay. So here I can see that beta, in the formation of complex compound, there occurs the formation of a coordinate covalent bond, for which the necessary condition is that metal should have a vacant D orbital, right? And it should have high charge density. Am I clear everyone? Okay, now let's just move ahead beta. Now let's move to the representation of coordination compound. Now from here the actual chapters basically starts. Okay, now here the actual chapter basically starts. See, we basically represent the coordination compound as like K4FeCN6. Now it is basically a coordination compound. Am I clear everyone? Fine. Now in this particular coordination compound beta, we have Fe. Okay, we have Fe. Now Fe is basically said to be a central metal atom or a central metal ion. Okay, in this representation, what is Fe? What is Fe? Fe is said to be beta either central metal atom, right? It is said to be a central metal atom, right? Or it is said to be a central metal ion. Am I clear? It is said to be a central metal ion. Am I clear everyone? Right? Now listen to me once beta, listen to me once. Here the Fe could have an oxidation state, right? How to find that oxidation state? I will teach you in some time. Am I clear? How to find the oxidation state? I will tell you in some time. Right? How to find the oxidation state? I will tell you in some time, bacha. Right? However, here, suppose the oxidation state is plus X. Okay? So this plus X, it stands to be the oxidation number or oxidation state of Fe. Okay? It is said to be the oxidation number of central metal atom, or I am writing central metal ion. This is a short form which I am writing right here. Am I clear everyone? Okay, am I clear everyone? Clear? Now, bacha, here Cn, okay, Cn, it is said to be the ligand. Okay, here Cn is said to be the ligand. Am I clear everyone? Here Cn is said to be the ligand. I hope I made my point clear. Right? Okay, now this metal and this ligand collectively constitute coordination entity. Okay, bacha, what I am saying, this metal and this ligand, they collectively constitute what beta? They collectively constitute coordination entity. Okay, they collectively constitute coordination entity. Am I clear everyone? Okay. However, listen to me, it's very important. Students usually commit this mistake and it's clearly mentioned in the NCERT beta. What? If I take only metal and ligand, then they will basically known as coordination entity. Okay, they will basically be known as coordination entity. However, if I will take this metal and this ligand in this square bracket, you can see a square bracket right here beta. Okay, so if I take metal and ligand in this square bracket, then it is basically known as coordination sphere. Am I clear, bacha? Then this is basically known as coordination sphere. Okay, this is basically known as coordination sphere. Okay, this is basically known as coordination sphere. Right? Now tell me one thing. What is this 6 right here, beta? What is this 6 right here? For now, if this Cn, all the 6 Cns are said to be 1 electron pair donor, that means each Cn basically donates only 1 electron pair to the vacant orbital of Fe, then the 6 which is written in the subscript beta, the 6 is basically known as coordination number. Am I clear beta? This 6 which is written right here, this basically is known as coordination number. Am I clear? This 6 is basically known as coordination written number. Am I clear, everyone? Yes, am I clear? Crystal clear, everyone? Crystal clear? Right now, bacha, tell me quickly in the chat box, what is written outside the square brackets. Quickly tell me in the chat box. Yes, quickly tell me in the chat box what is written outside the square bracket. What is written outside the square bracket? Quickly tell me in the chat box. Yes, what is written outside the square bracket? Yes, everyone, what is written outside the square bracket? Quickly tell me. Absolutely correct. Potassium is written outside the square bracket. Now, whatever ion, okay, whatever ion, it doesn't matter whether that ion is a cation or an anion. If that particular ion is written outside the square bracket, then this particular ion is known as counter ion. Am I clear? Right? So here, potassium is basically the counter ion, okay. This potassium is basically the counter ion. Am I clear, everyone? Right. Now, listen to me, beta. Listen to me. Listen to me. Here, bacha, I am giving you 2 to 3 complexes, okay. Now, in these 2 to 3 complexes, you basically have to tell me what is the counter ion, okay. What is the counter ion? And you know, before proceeding into this, one thing I would like to tell you is that beta, in this particular complex, I have K4FeCN6, okay. I have K4FeCN6. Okay, I have K4FeCN6. Now, if I split this complex, bacha, if I split this complex, I will have 4K plus, right? And I will have FeCN whole 6 4 minus, yes or no? I will have this, yes or no? Yes, I will have this. Now, here what I can see, beta, here the cation is simple, okay? This is basically a salt, right? And this particular salt, we have a simple cation. However, the complex is anion, okay. Anion is said to be a complex. It is said to be a coordination complex. Am I clear? Anion is said to be a coordination complex, right? So that is why, beta, that is why this particular complex is altogether is known as anionic salt, okay. It is basically known as anionic complex or anionic salt. Why, beta? Why it is said to be an anionic complex? Because here the anion is said to be complex. Raja, it's very simple. See, if you have A4B, how this A4B is formed, beta? It is basically formed with the cation A plus and anion B4 minus, right? Then only you are going to have A4B, na bacha? Yes or no? So this is also a salt, beta. So when the salts get break up, we basically get K plus, here we get 4K plus, and here we basically get FeCN whole 6 4 minus. Am I clear? For example, if you break this salt, you will get 4A plus, plus you will have B4 minus in a similar way, right? So here when we split this particular coordination compound, we find the cation is simple and the anion is complex. Whenever we have a complex anion, then that particular complex is known as anionic complex. Am I made my point clear or not? Yes, am I made my point clear or not? Okay. Now here, quickly tell me what is the counter ion, beta? Here K plus is said to be the counter ion, okay. Here K plus is said to be the counter ion, right? Now, similarly, I have many complexes which are written right here, okay. Now, what you have to tell, beta? First, you have to tell me the counter ion in all these complexes. The very first job is to tell me the counter ion in all these complexes, and then you have to tell me that whether these complexes are cationic or these complexes are anionic. Am I clear, everyone? Am I clear, everyone? Right, clear. So, very first complex we have right here is Na3AlF6, beta. See, when it will get breaks, it will breaks into 3Na plus, right? Plus we will have AlF6 3 minus, yes or no? That means here counter ion is Na plus. Whatever ion is written outside the square bracket is the counter ion. So here the counter ion is Na plus. What is this Na plus, beta? This Na plus is said to be the counter ion, right? Am I clear? And here the anion is complex, beta. Here the anion is complex. That means it is an anionic complex, okay. Here the complex is anionic complex. Am I clear, everyone? Yes, am I clear? Okay. Now, quickly tell me in the chat box what is the counter ion in the next complex and whether it is cationic or whether it is an anionic complex. It's very simple, bacha. See, if this particular complex breaks up into ions, okay. So, what I will get, beta? I will get CO En whole thrice 3 plus I will have 3Cl minus beta. Now what is written outside the coordination sphere? Cl minus is written outside the coordination sphere. That means here Cl minus is said to be the counter ion. Am I clear, beta? The Cl minus is said to be the counter ion, right? And here, beta, we know that first we write cation and then we write the anion. Okay, first we write the cation and then we write the anion in any salt. For example, if we write NaCl, first we write Na plus cation and then we write the Cl minus anion. That means here the first part which is written, the cation, it is said to be the complex, right? Okay, that means this particular complex is cationic complex. Am I clear, beta? This particular complex is cationic complex. I hope I made this point clear to you all, everyone, right? Next we have is CONH3 whole 6Cl3. Okay, now what I am doing right here, beta, I am splitting up it into its ion, or putting this coordination compound into water and breaking up into its ion. So what I will get, beta? I will get CONH3 whole 6, okay, CONH3 whole 6 3 plus 3Cl minus, right? Now what is the counter ion, beta? Cl minus is the counter ion. Yes, Cl minus is the counter ion. Yes or no, beta? Right, we have Cl minus as the counter ion, right? And in this particular coordination compound, what I can see, my bacha, I can see that here the cation, the first part is said to be the complex. That means here this is basically known as cationic complex. Okay, this is basically known as cationic complex, right? This is basically known as cationic complex, right? Can we just move ahead, everyone? Can we just move ahead? Okay, tell me in the next coordination compound. I am not telling, you have to tell me. Yes, quickly tell me in the chat box, in the next coordination complex, what is the counter ion and whether this coordination complex is cationic or anionic. Quickly tell me in the chat box. Yes, quickly tell me in the chat box whether this complex is cationic or anionic. Yes, everyone, quickly tell me in the chat box. Yes, quickly tell me in the chat box. Very good. The counter ion is K plus and the complex is said to be anionic. Absolutely incredible, beta. See, now this complex will break up. See, we have 3 cations, simple cations. We have simple cations, beta. Okay, K plus. So we have 3 K plus right here. Plus we have FeF6. 3 minus, beta. We have FeF6 3 minus. So here K plus is said to be the counter ion. Am I clear? Here K plus is said to be the counter ion. Am I clear? Okay. And FeF6 3 minus. FeF6 3 minus. See, it is an anion, right? Afterwards, always anion is written. First cation is written, then anion is written. And anion is written in the square bracket. That means here anion is complex. That is why this particular coordination compound is known as anionic complex. Am I clear? This is basically known as anionic complex. Now, is the representation of coordination compounds clear to you all? If it is clear to you all, please give me green hearts in the chat box and write go. Okay, and write go. If this concept is clear to you all, please give me green hearts in the chat box and do write go. Okay, bacha, right? So now let's just move ahead. See, I have told you the representation of coordination compound, and further I have also even told you, all the terminologies which are essential in order to write the coordination compound, right? However, we are doing a formality right here, beta. We are just, quickly reading up the definitions of NCERT. Why? Because they can ask statement based question. These days, statement 1 and statement 2, both are correct, both are false. One is correct, one is false, the other one is correct. There's so much in. Okay, that is why we are just first of all quickly reading them. Okay, the very first right here is coordination entity or coordination sphere. Beta, I have already told you coordination entity consists of 2 things. One is central metal atom, beta ji, right? And it is basically bonded to a fixed number of ions or fixed number of molecules, and these molecules are basically known as ligand. That means if in general I have a complex in which the central metal atom is represented by M and it is said to consist of n number of ligand, then this MLN, it basically constitute coordination entity. Okay, this basically constitute coordination entity. I have just told you. Yes or no, bacha? I have just told you. Am I clear, everyone? Right? And when we enclose this coordination entity, okay, so when we enclose this coordination entity into square bracket, quickly tell me what is it known as? If I enclose this coordination entity into square bracket, quickly tell me what it will be called as. Quickly tell me, beta. Yes, quickly tell me what it will be called as. Yes, Hanji, what it will be called as? Quickly tell me, everyone, what it will be called as. Yes. What it will be called as? Yes, yes, yes. Very good, bacha. It will be called as. It will be called as what? Coordination sphere. Okay. It will be called as coordination sphere. Am I clear, beta? Yes, am I clear? It will be called as coordination sphere, right? So we have studied the lines of NCERT. Now, the next terminology which has been given in the NCERT for coordination compound is central metal atom or central metal ion. So, bacha, in coordination entity, the atom and ion to which a fixed number of groups or ions, or I should say ligand, are bound in a definite geometrical arrangement, right? Now, this atom or this ion to which fixed number of atom or group or fixed number of ligands are coordinated or are forming coordinate bond and forming a definite geometry around the central metal atom or the central metal ion, beta. This atom and ion is basically known as central metal atom and central metal ion, right? Now, I have told you what is the necessary condition for a central metal atom, beta, that it should have vacant d orbital. Okay, vacant d orbital. Then only it can form a sigma coordinate bond with beta G ligand. Okay, then only it can form a coordinate bond with the ligand, right? Then only there is a possibility of formation of coordinate bond. Okay, right? That means here metal should have a vacant orbital, then only it can accept an electron pair from ligand, right? Okay, so here metal is electron pair acceptor, okay, or I should say metal is electron deficient, right? Metal is electron deficient, and you must have studied any species which is electron deficient, which accepts the electron pair. This is basically known as Lewis acid. That means metal behaves as Lewis acid. Am I clear, bacha? Metal behaves as Lewis acid. Am I clear? They can ask you, metal behaves as Lewis acid, yes or no? Yes, metal behaves as what? Lewis acid. Am I clear, everyone? Yes, am I clear, everyone? Clear? Okay. Now, ligand basically donates an electron pair. That could be a lone pair, right? Fine. That means ligand is electron donor, right? That means ligand is electron rich, right? Ligand is electron rich, and any species which basically donates the electron pair, it is said to be what? It is said to be what, beta? It is said to be Lewis base. Am I clear? It is said to be Lewis base. Okay, it is said to be Lewis base. Am I clear, everyone? It is said to be Lewis base. Okay, so central metal atom or central metal ion is Lewis acid, and ligand is said to be Lewis base. Ligands basically forms the coordination bond or coordinate bond around the central metal atom or the central metal ion, and they arrange them in a definite geometry. I will tell you in which geometry they arrange themselves once I will tell you the valence bond theory. Am I clear, everyone? Okay. Now, let's just move ahead, beta. Let's just move ahead. Now, let's come to ligands. I have already told you, beta. I have already told you what, beta. Ligands are the species which basically donates the electron pair to the vacant d orbitals, right? Ligands are the species which basically donates the electron pair to the vacant d orbital. Am I clear, everyone? Right, right, right. And what they do, beta, they basically form the coordination bond with central metal atom and central metal ion, right? Now, since ligands basically donates the electron pair, Okay, ligands basically donates the electron pair. That is the reason beta, that is the reason that ligands, okay, that is the reason beta, that is the reason that ligands are basically known as electron pair donor. Okay, ligands are basically known as electron pair donor. Am I clear? They are basically known as electron pair donor, as well as they are known as Lewis bases. Am I clear, everyone? Yes, am I clear? Okay, now my question to you guys is, you quickly have to tell me, this is really important, this is really important. Listen to me once, listen to me once. You have seen that you have C triple bond N, right, in which we have one lone pair of carbon and one lone pair of nitrogen. Now, since whenever nitrogen forms 3 bond, it do not carries any formal charge. However, whenever carbon forms 3 covalent bond, it always carries 1 negative charge, right? Now here carbon is said to have one lone pair of electron and it is said to have a negative charge, right? Now when we form K4FeCN6, okay, so whenever we form K4FeCN6, right, okay, so in K4FeCN6 beta we have 4K plus ion and plus we have FeCN whole 6 4 minus ion. Am I clear beta? Right. Now in FeCN whole 6 beta, we have 6 Cn minus ions, right? Now each Cn is said to have a lone pair of electron on carbon, right? And this lone pair of electron which is present on carbon is basically donated by the Cn into the vacant d orbital of Fe2 plus, yes or no? Right, fine. And due to this beta, there occurs the formation of 6 coordinates bond right here. Okay, there occurs the formation of 6 coordinate bonds right here. Am I clear beta? There occurs the formation of 6 coordinate bonds right here. Am I clear everyone? Am I clear everyone? Okay, right, fine. Now here quickly tell me, one Cn can donate how many electrons beta? One Cn can donate how many electrons? Quickly tell me in the chat box. Yes, quickly tell me in the chat box beta. Quickly tell me in the chat box. One Cn can donate how many electrons? Quickly tell me in the chat box. Yes. How to beta? See, I agree. C, that is carbon, has a lone pair of electron, nitrogen has a lone pair of electron, but at one time only one species, either carbon or nitrogen, can donate the electron pair. Yes Lahari, yes, you are absolutely correct beta. Here only one time one electrons can be donated. Okay, now number of electron pairs, right, number of electron pairs that are donated by the ligands basically constitutes the denticity of ligand. Am I clear? Am I clear or not? Am I clear? Right. What I am trying to say beta, what I am trying to say, I am defining a word denticity. What is denticity? What is denticity beta? What is denticity right here? It is basically the number of electron pair donated by one ligand. Okay, right, fine. Okay, so it will be number of electron pair donated by one ligand. Okay, right, we know that beta here only carbon is donating this electron pair, right? That means here the donor atom is carbon, right? Here the donor atom is carbon. So from here we can have the another definition of denticity as well. The another definition of denticity will be beta the number of donor atoms which are present on one ligand. Clear? Okay, bacha. Here the next definition is number of donor atom. Okay, number of donor atoms. Number of donor atoms present on one ligand. Okay, number of donor atoms present on one ligand. Am I clear everyone? Number of donor atoms present on one ligand. If one donor atom is present, it will donate one electron pair. Clear? Okay, so denticity basically stands for number of electron pair donated by one donor atom. Please correct the spelling, it is den denticity. Okay, I have written density, it is denticity, denticity. Please make a correction. The spelling I have written density by mistake, it is denticity. So it is denticity, denticity. Am I clear? Okay, right. I hope it is clear to you all, beta. Right, now see, depending how many donor atoms are present on the ligands or how many electron pairs are donated by one ligand, we decide the denticity of the ligands. That means we can classify the ligands on the basis of their denticity. Am I clear, everyone? Yes. Am I clear, everyone? Fine. So that means we can decide ligands on the basis of their denticity. Clear? If a ligand which is bound to central metal atom or central metal ion and it is said to have only one donor atom, that means it can donate only one electron pair, only single electron pair, right? There is only single donor atom present on that ligand, then that particular ligand is said to be a unidentate ligand or a monodentate ligand. Am I clear, beta ji? Is this point clear to you all? What I am trying to say, if our ligands donate only one electron pair to the vacant d orbital of metal, or a ligand is said to have only one donor atom, then that particular ligand is said to be a unidentate ligand or a monodentate ligand. Clear? Okay. For example, we have Cl minus, bacha, we have NH3. Am I clear? We have NH3, we have H2O, right? They all are said to be monodentate or unidentate ligands. Am I clear, everyone? Right? Now, what if a single ligand is said to have two electron pairs, right, present on two different donor atoms? That means here, suppose there is a ligand which is bounding to the metal ion through two donor atoms. Clear? How many donor atom, beta? Through two donor atom, right? So suppose a ligand is binding to the metal ion through two donor atoms. How many donor atoms, beta? Two donor atoms. Then that particular ligand is said to be a didentate ligand or a bidentate ligand. Clear? Right? If I have to take into consideration the example of didentate ligand, okay, didentate ligand or bidentate ligand, beta, or bidentate ligand, bacha, then here I can take the examples of the very first famous didentate ligand is basically, beta, CH2NH2, CH2NH2, single bond, CH2NH2. Okay, so here we have one nitrogen which is said to have a lone pair of electron, and we have another nitrogen which is said to have the another lone pair of electron, right? That means here on a single ligand we have two donor atoms, right? Two nitrogen donor atoms. So it is an example of a bidentate ligand or a didentate ligand, right? The name of this particular ligand is, beta, either ethane 1,2-diamine, okay, either ethane 1,2-diamine, my bacha, right? Or the second name of this particular ligand, or the second name of this particular EN is ligand, beta, is ethylene diamine. Okay, it is ethylene diamine. Am I clear? It is ethylene diamine. Am I clear, everyone? Yes. Am I clear? Clear or not? Clear, everyone? Right? Yes, you are absolutely correct. The short form of this particular ligand is EN, right? The short form of this particular ligand is EN. Am I clear, everyone? Yes. Am I clear? Clear or not? Clear, bacha? Okay. Now you can see that here two donor nitrogen atoms can form a coordinate bond with a single metal atom or a single central metal atom, right? That means per ligand two coordinate bonds can be formed. Two donor atoms are present right here, right? Okay. In a similar manner, the another example which we have right here, beta, is oxalate ion. Okay. The next example which we have right here is oxalate ion, right? Now, if I talk about this oxalate ion, beta, it is said to consist of two donor oxygen atom, right? Now, here again, if we have two donor oxygen atom, bacha, so it means that here two donor atoms are present, and whenever two donor atoms are present, then that type of ligand is basically known as a didentate ligand or a bidentate ligand, right? That means here oxalate, whose short form is OX, right? It is also a bidentate ligand, okay? It is also a bidentate ligand. So, it is oxalate ion. Okay, bacha, right? It can form 2 coordinates bond per ligand with a single central metal atom or central metal ion. Am I clear, beta? Right? So, in the first case, we have 2 donor nitrogen atom. Okay, in the first case we have 2 donor nitrogen atom, and in the second case, bacha, in the second case we have 2 donor oxygen atom. Okay, we have 2 donor oxygen atoms. Am I clear, everyone? Yes. Am I clear? Yes. Clear or not? Clear? Okay, fine. Okay, let's move ahead, beta. Let's move ahead. Now, let's come ahead to polydentate ligand. See, when the denticity of a ligand is more than 2, that means either it is 3, either it is 4, either it is 5, either it is 6, right? But the denticity should be greater than 2. What I am trying to say, beta, if the denticity of ligand is greater than 2, right? It could be 3, it could be 4, it could be 5, 6, 7, 8, 9, so on as we move ahead. Then that particular ligand is known as polydentate ligands, right? That means polydentate ligand is said to have several donor atoms present on a single ligand. Am I clear? It is said to have several donor atoms present on a single ligand, right? The example of polydentate ligand is basically EDTA. Right, EDTA. Now, what is this EDTA, beta? EDTA is ethylene diamine tetraacetate. Am I clear? What is this EDTA, beta? What is this EDTA, beta? EDTA is ethylene. It is ethylene diamine tetraacetate. Am I clear? Ethylene diamine tetraacetate. Okay. If I'll draw the structure of EDTA, this is the structure of EDTA, bacha. Right? This is the structure of EDTA. Just see it right here. Now, quickly tell me in the chat box how many donor atoms you can see in the single molecule of EDTA. Yes, quickly tell me in the chat box how many donor atoms can we see in the single molecule of EDTA. Yes, everyone. How many donor atoms can we see in a single molecule of EDTA? Quickly tell me. Yes, quickly tell me, everyone. Yes. How many donor atoms? Yes. Some of you are saying 6, some of you are saying 4, beta, it is 6. It is much evident, okay. See, we can see 2 nitrogen atoms right here, which act as donor, and then we have 4 oxygen atoms, beta. 1, 2, 3, 4. That means here we have 6 donor atoms, okay. Here we have 6 donor atoms, okay. Here we have 6 donor atoms, right? Okay, here we have 2 donor nitrogen atoms plus we have 4 donor oxygen atoms. Okay, bacha. So that is why it is known as hexadentate ligand. Okay, that is why it is basically known as hexadentate ligand. Am I clear? That is why it is basically known as hexadentate ligand. Am I clear, bacha? That is why it is basically known as hexadentate ligand. Beta, why the live watching is dropping? See, you have to be consistent throughout the session. Some of the things will be boring, some of the things will be interesting, but what is the use of these sessions? What are the use of the sessions? Now, what do you think? What is the best use of a session? When we will say the session is best utilized, beta, when you will attend the session since the starting and end it once it gets ended up, so that your complete chapter just get winded up in a single shot. Am I clear, beta? Then only your single chapter can be winded up in a single shot. Yes or no, everyone? Yes or no? I know we have done coordination compound, beta, but think of it. There are 8 lectures, right? Each lecture is approximately 2.5 hours or 2 hours long, right? So that means it will take 16 hours, and today we will complete in 10 hours entire chapter. Plus, I will teach you some additional concepts as well, right? I will teach you some additional concepts as well. Right? Okay, fine. So try to maintain the peace inside you, beta. I have to tell you each and every point, whether it is important, whether it is you feel like that, oh ma'am, you're telling this point again, beta. I have to go through each and every point of NCERT. That is a harsh reality of inorganic that we have to take into consideration each and every point, bacha. Right? So you have to maintain the peace. Consistency is the key. Absolutely, bacha. Ma'am is being consistent in telling you each and every point, each and every concept. Then why you guys are not being consistent in maintaining the watching? Right? Why? We have done DNF block. You guys were so interested in DNF block because we did it for the first time. And now since we are doing coordination compounds, we have already did it. That doesn't mean you don't have to, you don't, yeah, I will do the PYQ. I will do the PYQ. I will give you the DPP. I made an arrangement for you guys for giving you DPPs. I am working hard for you guys. But you guys have to be consistent in the sessions. Otherwise, there is no point. Am I clear, everyone? Okay. Consistency is the only thing. Nothing can help you to sustain. You have to be consistent. That's all. That's all. Okay, everyone. So let's just move ahead. We have done EDTA, which is an hexadentate ligand. Now let's just proceed ahead, bacha. Let's just proceed ahead. See. Now, next concept is basically chelation, okay. Next concept is basically chelation. Now, what is this chelation? Now, what is this chelation? See, bacha, whenever we have a ligand whose denticity is 2 or more than 2, okay, whenever we have a ligand whose denticity is 2 or more than 2. For example, if we have oxalate, beta, right, for example, if we have oxalate is COO minus, COO minus. Yes, this is an oxalate ion, which is a ligand, which is a bidentate ligand. Am I clear, everyone? Am I clear, everyone? Okay, now see, whenever this oxalate will form the coordinate bond with the central metal atom or the central metal ion, bacha, here I can see that per oxalate ion we have 2 donor atoms, right? Per oxalate ion we have 2 donor atoms. Am I clear, everyone? Right? Now both these donor atoms can form coordination bond with the metal, right? They can form the coordination bond with the metal, and in this process, beta, in this process of formation of coordinate bond, can you see the formation of a ring right here? Yes, can you see a formation of ring right here, beta? Right, so there occurs a formation of ring. How many member ring, beta? How many member ring? It is 1, 2, 3, 4 and 5. That means here we have 5 membered ring. Am I clear? Here we have 5 membered ring. Am I clear, bacha? Right. So here a 5 membered ring is being formed, right? So the phenomenon in which we have a ligand whose denticity is 2 or more than 2, right? Whenever that ligand forms a bond with a central metal ion, there occurs the formation of ring. Now this phenomenon is basically known as chelation, and the ring which is formed right here is basically known as chelating ring. Am I clear, bacha? Right, the ring which is being formed right here is known as chelating ring, and this ligand, beta, and this ligand which you can see right here, okay, the ligand which you can see right here, this ligand is basically chelating ligand. Am I clear? This ligand is basically known as chelating ligand. Am I clear, bacha? This ligand is basically known as chelating ligand. Am I clear? Right, this ligand is basically known as chelating ligand. Am I clear? Okay, right. Now let's just move ahead and read the lines of NCERT, beta. Whatever I have told you, I have written right here, right? The very first line is when a di or a polydentate, that means any didentate, tridentate, tetradentate, pentadentate, hexadentate, doesn't matter. Denticity should be 2 or more than 2. Okay, so whenever we have a didentate or a polydentate ligand, right, and that ligand basically uses its 2 or more donor atom, right? That ligand basically uses its 2 or more donor atom, right? For what, beta? For forming a bond with a single metal ion, right? In that particular case, beta, that ligand is basically known as chelating ligand. Am I clear? That particular ligand is known as chelating ligand. Am I clear? Right. Now, beta, donor atom position them around the central metal atom in such a manner that there occurs a formation of ring, and that ring is basically known as chelating ring, right? Here 2 donor oxygen arrange themselves around the metal in such a manner that there occurs a formation of a 5-membered ring, right? And this 5-membered ring is nothing but it is the chelate ring or the chelating ring. Clear? This 5-member ring is nothing, beta, but it is the chelate ring. Am I clear, everyone? Yes. Am I clear? Okay. Further, beta, further, here the complex which basically results, okay, the complex in which this phenomenon of chelation has been occurred, that particular complex is known as metal chelate. Am I clear, beta? That particular complex is known as metal chelate, Clear, right? And further, the phenomenon which has been occurred right here, in which there occurs the formation of ring, chelate ring. This phenomenon is basically known as, or this property is basically known as chelation. And this property is basically exhibited by didentate ligands or polydentate ligand. That means whenever there occurs the presence of a didentate ligand or a polydentate ligand in a complex, then there occurs the formation of ring, and this phenomenon is basically known as chelation. Am I clear, everyone? Yes, am I clear? Clear? Can we move ahead, everyone? Can we move ahead? Yes, can we move ahead? Okay, now let's come to the another definition. It is an ambidentate ligand. Okay, it is an ambidentate ligand, right? Now, what is this ambidentate ligand, beta? See, ambidentate ligand is such type of ligand which although have two donor atoms, right? Ambidentate ligand will have how many donor atoms? Two donor atoms. However, it can coordinate to central metal atom or central metal ion through one donor atom. Am I clear, beta? Right. For example, see, if you have beta C triple bond N, right? Some of you have told that, ma'am, here the lone pair is also present on nitrogen and also on carbon. Right, fine. That means, ma'am, here carbon and nitrogen both can form coordination bond with central metal atom. Right, right. However, at what particular instant or at a what particular time, only one of them, either carbon or nitrogen, basically forms the coordinate bond with the central metal atom or the central metal ion. Am I clear, everyone? Am I clear, everyone? Right. That means here, although it has two donor atoms, but at one particular instant of time, only one of them can form coordinate bond with the central metal atom or the central metal ion. Then such type of ligand is basically known as ambidentate ligand. Okay, such type of ligand is basically known as ambidentate ligand. Am I clear? Ambidentate ligand. Okay, bacha, right? Such type of ligands are known as ambidentate ligand, and please write in bold letters in your notebook. Okay, make sure to write in bold letters in your notebook that ambidentate ligand is basically a monodentate ligand. Okay, it is basically a monodentate ligand. Am I clear? It is basically a monodentate ligand. Am I clear, everyone? Yes, am I clear? Right. Now you must be thinking that, ma'am, why both carbon and nitrogen cannot form coordination bond with the central metal atom or the central metal ion? But a reason to that is that here there occurs the formation of three-member rings, and you must have studied in your journal organic chemistry that three-member rings are not at all stable. Okay, they are said to have a lot of angle strain. Am I clear? They are said to have a lot of angle strain, so they are not at all stable. Am I clear, everyone? They are not at all stable, right? Fine. Okay, so this won't be occurring. Why? Because three-member ring. Why? Because three-member rings are not stable. Okay, three-member rings are not stable. They are not at all stable. Am I clear, everyone? So that is the reason that at one particular instant of time, either carbon or nitrogen can form coordinate bond with the metal atom, right? Either it can form coordinate bond with the metal through carbon site, beta. Okay, right? Or it can form the coordinate bond, beta, from the nitrogen side. Clear? So that means they both are ambidentate ligand, right? It is a one ligand only, but they differ in the donation atom. It could either be nitrogen, it could either be carbon. Am I clear, beta? Right? In a similar manner, beta, NO2, okay, NO2, fine, NO2, clear? Now his NO2 also, beta, can coordinate through metal, through the nitrogen, right? It can coordinate through the metal, through the nitrogen. Am I clear, everyone? Am I clear, everyone? Am I clear? Right? Or it can coordinate through central metal atom or central metal ion, beta, through oxygen. Okay, through oxygen. That is why this NO2 is also known as ambidentate ligand. Am I clear? This NO2 is also known as ambidentate ligand. Am I clear, everyone? Okay, in a similar manner, right? You might have heard of SCN, beta, SCN, right? Now SCN, in SCN the donor atom could be sulfur. This is thiocyanide. Okay, SCN is basically thiocyanide. This is cyanide, this is nitro, this is thiocyanide. Okay, so in thiocyanide, sulfur can also act as a donor atom, or bacha, or nitrogen can also act as a donor atom. Okay, nitrogen can also act as a donor atom. Am I clear, everyone? Right. So this is also an example of what? This is also an example of, my dear bacha, ambidentate ligand. Am I clear? This is also an example of ambidentate ligand. Am I clear or not? Yes. Am I clear or not? Quickly tell me in the chat box. Is ambidentate ligand clear to you all? Yes, everyone. Clear? Right? Okay. If it is clear, now let's just come to one question right here. You all have to tell me the answer. It is a multiple select question. That means more than one options can be correct right here. Okay. Right. Here, more than one option can be correct right here. Question is, identify the correct statement for the behavior of oxalate ion ligand. Okay. So they are asking, you have an oxalate ion, beta. Okay. You have an oxalate ion. You have to tell me what are the correct statements for the oxalate ion. Option A, it is a neutral ligand. Option B, it is a bidentate ligand. Option C, it is a chelating ligand. And option D, it is a unidentate ligand. Very first statement, that it has a neutral ligand, it is absolutely incorrect, beta. It is an ionic ligand. It is said to have a negative charge. Okay, so the first option is absolutely wrong. Absolutely wrong. Okay, next, it is a bidentate ligand. Yes, it is absolutely correct, beta. It is said to have two donor atom. Okay, it is said to have two donor atom. That means statement B is absolutely correct. Right, bacha? Fine. It is a chelating ligand. Yes, every didentate and a polydentate ligand is a chelating ligand. That means option number C is also absolutely correct. Then beta, it is a unidentate ligand. No, it is a bidentate ligand. Am I clear, everyone? Yes. Am I clear? Okay, right, fine. Now, let's just come to the another category of ligand, and these are basically flexidentate ligand. Now, see, all those students who are thinking that, ma'am, you are just teaching the same topics which you have told us in the series in which we used to have a class of 2 hours. Now, see, I have gotten another term for you, flexidentate ligand. Now, you must haven't heard the name flexidentate. Am I correct? Have you heard the term flexidentate? No. Beta, what are flexidentate ligands? Now, flexidentate ligands are those ligands which shows variable denticity. That means here, denticity in some of the cases of that particular ligand could be 2, and in some of the cases it could be 1. In some of the cases it could be 3. Right. So, there are certain type of ligands which basically shows variable denticity. So, such type of ligands are known as flexidentate ligands. So, that's what I'm trying to say. I have learned a lot of new concepts as well, but I have to teach a chapter in an order. Why? Because there are few students who are, here to learn this chapter from the scratch. Am I clear, everyone? Okay, so that is the reason. That is the reason I have to take this chapter from the scratch. Okay, right. Now, flexidentate ligand. What are the examples of flexidentate ligands, beta? Here, in flexidentate ligand, we have CO3 2 minus. Okay, CO3 2 minus. Right. Here, the denticity of CO3 2 minus in most of the cases is 1. Okay, in most of the cases is 1. However, at certain cases, in certain cases, it also shows the denticity of 2. Am I clear? In certain cases, it also shows the denticity of 2. Why? Because whenever we draw the structure of carbonate ion, we will see that here we have 2 oxygen atoms which can act as a donor, right? That means here CO3 2 minus is a flexidentate ligand, right? In most of the ligands, in most of the cases, it is said to be a unidentate ligand, right? However, in certain cases, it can also act as a bidentate ligand. Am I clear, everyone? Okay, so what we will write, in most of the cases, bacha, it acts as unidentate ligand. Okay, unidentate ligands. However, in certain cases, okay, in certain cases, it may act as bidentate Bidentate ligand. Okay, Bidentate ligand. Am I clear, everyone? Bidentate ligand. Okay, is this point clear to you all? Yes, is this point clear to you all, everyone? Right. In a similar manner, beta, in a similar manner, if I talk about SO4 2 minus, okay, if I talk about SO4 2 minus, right, in majority of cases the denticity is 1. However, in certain cases it may show the denticity as 2. Beta, it is a pH dependent thing, right? If pH may vary, denticity may vary. It is a pH dependent thing, right? SO4 2 negative is a monodentate ligand. However, in certain cases it could have a denticity 2. That is why SO4 2 minus is a flexidentate ligand. Am I clear, beta? Right. If I talk about EDTA, okay, if I talk about EDTA 4 negative, quickly tell me in the chat box what is the most frequent denticity which is shown by EDTA. Yes. Till that, I will message for the AC because it's highly suffocating. Yes, everyone, quickly tell me in the chat box. Yes, yes, Telugu industry, you are going to be the mafia of Telugu industry. Am I clear, everyone? The mafia of Telugu industry. So here, the denticity is said to be 6, right? Here, the denticity is said to be 6, bacha. But it depends upon various condition, right? The denticity could be 5, it could be 4, it could be 3, it could be 2, or it could even be 1. Am I clear, everyone? Am I clear, everyone? Okay, right. So EDTA is also a flexidentate ligand. Am I clear, bacha? So these were certain examples of flexidentate ligand. I hope it is clear to you all. Am I clear, everyone? Now here we have a question. Question is EDTA is option A, option B, option C, and option D. Quickly tell me in the chat box what will be the answer of this particular question. Quickly. Yes, yes, P. Lakshmi, Gauri, very good, beta. It is all of these. See, EDTA is a polydentate ligand. Why? Because it is a hexadentate ligand, right? Second, it is a chelating ligand. Yes, because it has more than 2 donor atoms. Absolutely correct. Beta, it is a flexidentate ligand. Yes, its denticity might be varied. That is why here all of these is the correct answer. Am I clear? All of these is the correct answer. Am I clear, everyone? Yes, clear? Okay, fine. Let's just move ahead. Fine. So here first we have classified the ligand on which basis, beta? We have classified on the basis of denticity. That means depending on the number of donor atoms which are present on the ligands. Am I clear, beta? Right. Now we are doing the another classification of ligands, bacha. Now we are doing the another classification of ligands, beta. And this type of classification is on the basis of, my dear bacha, on the basis of charge. Okay. Now this classification is on the basis of charge. Am I clear, bacha? This classification is on the basis of charge. Okay, on the basis of charge. Right, now it is very simple, beta. If a ligand is said to be negatively charged, right, that means if a ligand is said to have a negative charge, beta, then it is said to be a anionic ligand. You must be familiar with many examples of anionic ligand, right? You must be familiar with many examples of anionic ligands, right? There are many examples, yeah. Cl minus, okay, Br minus, right? We have studied SO4 2 minus, right? We have studied EDTA 4 minus, okay? We have studied oxalate, ma'am, COO negative, which could in a condensed form be written as C2O4 2 minus. Am I clear, beta? All these are basically your anionic ligand or negatively charged ligand. Am I clear? NO2 is also an example. Very good. Beta, neutral ligands are those ligands which do not carry any charge. That means they are uncharged ligands, right? Right. For example, beta, for example, we have seen ammonia. Okay, we have seen ammonia, we have seen water, that is H2O, it is also a neutral ligand. Then further beta, then further we have seen CO, CO is also a neutral ligand bacha, right. Further we have seen ethylene diamine, that is CH2NH2, CH2NH2. Here also it does not carries any charge, right. Here also it does not carries any charge bacha, that means it is also a neutral ligand. Am I clear beta? Right. And then we have the last category of ligands. Okay, then we have the last category of ligands beta. These are the cationic ligands. Now cationic ligands are very rare. Okay, these are those type of ligands which are said to have positive charge. Okay, they are those types of ligands which are said to have positive charge. Am I clear beta? Here we have NO plus, right, that is nitrosonium, and then we have hydrazinium, that is NH2 NH3 plus. We all are aware of hydrazine. Okay, you guys are dropper, you must be aware of hydrazine. It is NH2 single bond NH2. So whenever any H plus basically is get attacked by the lone pair of electron which are present on the nitrogen beta, right. Okay, so then what happens, Rajay? There occurs the formation of hydrazinium ion. Okay, now this hydrazinium ion is basically a positively charged ligand or basically a cationic ligand. Am I clear everyone? Is this clear to you all? Yes, clear to you all. Yes, rarest. Yes, Lahari, it is rarest. Am I clear? Okay, right, fine. Let's just move ahead beta. Let's just move ahead. Now, bacha, see, we have a third category of ligands as well. Okay, we have a third category of ligands as well. That means type of ligands on the basis of electron pair donation, right. They have classical ligands and non-classical ligands, but I will discuss this category after a particular instant of time beta. Now I am not discussing this category, I will discuss it after nomenclature. Okay, but for now just keep one thing in your mind, that yes, there is another category of ligands as well. Am I clear everyone? There is one another category of ligands as well. Am I clear everyone? Yes, am I clear? There is one another category of ligands as well. I will discuss later on. Fine. Now these are classical and non-classical, and I haven't told you this type of ligands in previous lectures. So this is something new for you all. Am I clear? This is something new for you all. So please make sure to be attentive throughout the session. Okay, so I will tell you at the end. This is the third category of ligands. Okay, first we have classified on the basis of denticity, then we have classified on the basis of charge, and the third is on the basis of whether they donate electron pairs or whether they accept electron pairs. Okay, so here we have two categories, classical and non-classical ligands. Okay, I will discuss it later on. Now let's come to the another terminology beta. We have studied the coordination entirety, we have studied the central metal atom, we have studied the ligand. Now the another terminology which we need to study beta is coordination number. Now what is this coordination number beta? Some people define that coordination number is basically the number of donor atoms of ligands which are surrounding the central metal atom or the central metal ion, right. For example in K4 FeCN6. Okay, in K4 FeCN6 bacha. Fine. In this particular complex, I have 4 K plus ion beta plus FeCN whole 6 4 minus ion. Am I clear everyone? Yes. Am I clear everyone? Right. Okay, so here bacha, if I will see, Fe is basically, Fe2 plus is basically surrounded by 6 Cn minus ions. Okay, 6 Cn minus ions. Right. Fine. That means 6 donor carbon atoms, right? 6 donor carbon atoms are basically surrounding the central metal atom or the central metal ion. Right. Okay, so the number of donor atoms which are actually surrounding the central metal atom or central metal ion is basically known as coordination number. So in this particular case, we will say that the coordination number is said to be 6. Am I clear beta? The coordination number is said to be 6. Yes, Lahari, all these slides are the lines of NCERT. Am I clear beta? Right. Okay. Now here keep one thing in your mind beta. all the donor atoms which are being counted in the coordination number, they should be directly bonded through central metal atom. Okay, they should be directly bonded through central metal atom, and that also through sigma bond. Okay, that also through sigma bond. How beta? Through sigma bond. Am I clear? Through sigma bond. Now what do you mean by sigma bond, ma'am? See beta, here metal and ligand are forming a coordinate bond right here beta. They are forming a covalent coordinate bond. Okay, they are forming a covalent coordinate bond beta. Now this coordinate covalent bond could occurs either through internuclear overlap between the metal and the ligand, or through the sideways overlap. So whenever there occurs the overlap through internuclear axis beta, there occurs the formation of sigma bond. And whenever we count the coordination number beta, in the coordination number we count only those donor atoms which basically forms sigma bond with the central metal atom and the central metal ions. That means here, if I will count the number of sigma bonds, okay, the number of sigma bonds which are formed by, you know, the ligands, then also I can find the coordination number. Am I clear, everyone? Am I clear? Okay, right. So what I got to know, that coordination number of the central metal atom and the central metal ion is determined only with the help of sigma bond which are formed by the ligand, not by the pi bond. Am I clear, everyone? Am I clear, everyone? Quickly tell me in the chat box. Yes, am I clear? Right. Am I clear? Fine. Yes, am I clear? Okay, right. So the conclusion is coordination number is nothing. Either it is a number of donor atoms of the ligand surrounding the central metal atom, or the number of sigma bonds which are formed by the ligands with the central metal atom or the central metal ion, right? Okay, so coordination number is nothing. It is nothing, but it is the number of, sigma bonds. Okay, it is basically the number of sigma bonds formed. It is basically the number of sigma bond formed by central metal atom hash central metal ion with the ligands. Am I clear, beta ji? Am I clear? So the conclusion is clear to you all. Is it clear to you all? Always keep one thing in mind, beta. Always keep one thing in mind. Please, it's a very important point. It's a very important point, beta. If I'm talking about Cn minus right here, okay, right, it is said to be one electron pair donor, right? And if it is one electron pair donor, right, ligand is one electron pair donor, bacha, right, it is one electron pair donor, then it can form, beta, only one sigma bond. Right, you have seen the formation of the sigma coordinate bond in the case of NH3 and BF3, right? BF3 is said to have a vacant 2p, NH3 is said to have a lone pair of electron. Yes or no? Right? Yes or no, bacha? Fine. Right? Am I clear? Right? You guys have seen or not? Bacha, you must have studied in chemical bonding that in NH3, nitrogen is said to have a lone pair of electron and BF3 is said to have a vacant 2p beta. So what happens? There occurs a formation of a covalent bond, but it is a special type of covalent bond. Here, the electron pair is donated by one, but it is shared by both, right? So this is basically a sigma coordinate bond. Right, right. That means here this NH3 is one electron pair donor. That is why there occurs the formation of only one sigma bond. Am I clear? Right, fine. So if any ligand is forming one sigma coordinate bond beta, then it is definitely one electron pair donor. Okay, then it is said to be one electron pair donor. Am I clear, beta? It is said to be one electron pair donor. That means a ligand which is present right here. Okay, that means a ligand which is present right here, beta, L, it is said to be one electron donor, right? It is said to be one electron donor. That is why there occurs the formation of one sigma bond between metal and ligands, right? Here each Cn is one electron pair donor. That is why 6 coordinate sigma bonds are being formed, and that is why the coordination number of central metal atom or central metal ion, which is Fe, it is basically 6. Am I clear? Now is this clear to you all? Can we proceed ahead? It is a very important point. People never understands this. People never understands this. Am I clear? Okay, fine. If you want to make it more clear, bacha, what people do, they usually, get confused, right? They usually get confused between coordination number and denticity. They say, ma'am, denticity and coordination number are one and the same thing. No, beta. Please keep one thing in your mind, that denticity is defined for a single ligand, right? We always define denticity for a single ligand, right? Number of donor atom present on a single ligand or number of electron pairs donated by a single ligand, it is basically the denticity, right? However, coordination number is defined with respect to central metal atom or the central metal ion, right? The number of sigma coordinate bonds which are formed by central metal ion with the ligands, right? They basically contributes to the coordination number. Now am I clear, everyone? Now am I clear? Okay, right, fine. Okay, so please do not get confused. Beta, coordination number are nothing. They are the total number of sigma bond formed by the ligand donor atom around the central metal ion in a given complex. Right, right. However, denticity is first of all defined for a single ligand, and then it is nothing but the number of sigma bond which are formed by single ligand or number of lone pair or electron pair which are donated by a single ligand. It is said to be its denticity. Am I clear, everyone? So now I hope you guys will never get confused. I hope you guys will never get confused between denticity and coordination number. They both are separate things. Am I clear? They both are separate things. Never get confused between denticity and coordination number. They both are separate things. Am I clear? Okay, right. Let's just move ahead, beta. Let's just move ahead. Now, let's come to the calculation of coordination number. How do we find the coordination number? Beta, first I am directly telling you the formula, and then what I will do some questions on the basis of it. Okay, so the formula for coordination number. Okay, how to find the coordination number? So the formula for coordination number, bacha, the formula is summation. Okay, summation Ni di. Right. Now, what is this Ni? Beta, Ni stands for the number of ith ligand. That means the number of type of ligands. Right. You have only Cl ligands. You have only NH3 ligands. Okay. So, these are basically the number of ith ligands. Clear? Right. Now, what is Di right here, ma'am? What is Di right here, ma'am? Di basically stands for the denticity of ith ligand. Am I clear? Di basically stands for the denticity of ith ligand. Am I clear? Okay, right. Denticity basically stands for the, Di stands for the denticity of the ith ligand. I hope this point is clear. Now, if I have PtCl6, now quickly tell me if I have to find the coordination number with respect to central metal atom or central metal ion, then how many one particular type of ligands are present right here, beta? Here we have only one type of ligand, which is Cl. Okay, here we have only one type of ligand, which is Cl. Yes or no, bacha? Yes or no? Cl. Okay, and that also, beta, we have 6 Cl ligands. Am I clear? We have 6 Cl ligands. Okay, right. So the number, listen to me, number of one type of ligands or number of Cl ligands are basically 6. Clear? However, the denticity of Cl ligand, is 1. So, we will do 6 into 1, beta. So, the coordination number is 6. Okay. Next we have is NiNH3 whole 4. Now, tell me how many particular type of ligand we have. We have only one type of ligand, which is NH3. And how many, beta? 4. That means Ni right here is 4. And what is Di, beta? What is denticity of NH3? I have just told you it is a single electron pair donor. So it is basically a monodentate ligand. Am I clear, everyone? Right. Talking about FeC2O4 whole thrice 3 minus C. Beta, tell me what is Ni, beta? Here I have only oxalate ligands, and the number that is Ni is basically 3, right? And what is the denticity of oxalate ligand, beta? I have just told you the denticity of the oxalate ligand is 2. Okay, it is 2. So we will multiply it by 3. Okay, so it will be 6. Am I clear, everyone? It will be 6, right? Next we have is COEN whole thrice 3 plus. Okay, En stands for ethylene diamine or ethane 1,2-diamine, which is a bidentate ligand. Okay, so here Ni is basically 3, beta. Written in the subscript, Ni is basically 3, right? And what is the denticity of En? What is the denticity of En, beta? Denticity of En is 2. Denticity of En is 2. So what we will do? We will multiply 3 with 2. We will multiply 3 with 2. So denticity comes out to be 6. Okay, denticity comes out to be 6. Am I clear, everyone? Yes. Am I clear? Okay, right. Next we have CONH3 whole 4H2OBr. Now see, I have here three types of ligands, right? First type of ligand is NH3. What is Ni or what is number for it? Beta, number is 4, right? Number is 4. So we will multiply 4 with the denticity. NH3 is said to be a monodentate ligand, beta. It is said to be a monodentate ligand, right? So it is 4 into 1. Am I clear, bacha? Plus we have the another type of ligand, it is H2O, right? Now H2O is again only one H2O is present, so Ni for H2O is 1, and talking about the denticity of H2O is again 1, so we will multiply with 1. Next bacha, next, right? Beta, Br is said to be again the number of Bi, that is Ni for Br is 1, right? And denticity for it is again 1. So it is 4 plus 1 plus 1, it is 6. I hope it is clear to you all how to find the coordination number. Yes, can you guys now find the coordination number? Can you guys find the coordination number? Absolutely correct, absolutely correct. Yes, everyone, absolutely correct. Okay, right. Now, next, let's just come to the oxidation number of the central metal atom or the central metal ion. Okay, now next let's come to the oxidation number of central metal atom and central metal ion. Am I clear, everyone? Right. Now, what is oxidation number? It is nothing but it is a charge. Okay, it is a charge which is actually being carried by central metal atom or central metal ion. Am I clear, beta ji? What is oxidation number? It is nothing but it is merely, okay, it is merely the charge which is carried by the central metal atom or central metal ion. Am I clear, everyone? Am I clear, everyone? Yes, clear. Okay, now whenever we write the oxidation number in the nomenclature, we usually write in Roman numeral. You will get to understand the second point when we will study the nomenclature. So for now you can skip this line of NCERT. Am I clear? I will tell you this line of NCERT when I will be covering nomenclature, which I will be doing in next coming 20 minutes. After nomenclature only, I am going to give you the dinner break of 25 or 30 minutes. Am I clear, everyone? Okay, right. Now, ma'am, how to find the oxidation number? See, if you have studied redox, then I don't think there could be any problem in finding the oxidation number of central metal atom or central metal ion. Now, in these particular questions, what we have to do, beta, we have to find the oxidation number as well as the coordination number. Okay, we have to find the oxidation number as well as the coordination number. Okay, okay. So in these particular cases, beta, coordination number you can find it by yourself. I've just told you. Now what I will told you right here is the oxidation number. Okay. Yes, Maleshwari NCRT is enough. Okay. NCRT is perfectly enough for inorganic chemistry. Am I clear? NCRT is perfectly enough for inorganic chemistry. See, soon I will teach you P block as well. Okay, soon I will teach you P block as well, for sure. Right, so there I will tell you that yes, NCRT is merely enough. For coordination, there are 2 to 3 topics which are actually not present in the NCRT, but from them frequently questions are being asked. And what I will do, I will tell you those topics in this particular session. However, for rest of the chapters, that is for D block, for periodicity, for your P block, NCRT is merely enough. And there is one more topic which is salt analysis, right? That actually do not have any book. Right, so for that is you totally have to depend on me. Am I clear, everyone? Okay, right. Now let's come to the calculation of oxidation number. So beta, in redox, whenever you have to find the oxidation number of any particular atom, right, of any element, you actually mark the oxidation number as X. Okay, you mark this at as X. For example, if you want to find the oxidation number of Fe, you mark it as X, right? Fine. You know that sum of oxidation number of each and every element's atom is always equals to the overall charge. For example, here if we will add the oxidation number of Fe, beta, Cn, right, 6 Cn, right, or we can say 6 carbons and 6 nitrogen, then the sum of oxidation numbers will always be equal to -3, right. So here, if the oxidation number of Fe is X, see what you can do, you can take individual oxidation numbers of carbon and nitrogen, it's your choice, or you can take the submissive charge of Cn, which is -1. Okay, so you have 6 CN right here, and each CN is said to have a charge of -1 everyone. Each CN is said to have a charge of -1 everyone. Okay, so you can put it equal to the overall charge, and the overall charge right here is -3. Am I clear, bacha? The overall charge right here is basically equals to -3, right? So when you will solve it for x, okay, so when you will solve it for x, so x will be +6 -3, that is, it comes out to be +3. Am I clear, everyone? Right? So the oxidation state of Fe in this particular case is equals to +3. Am I clear, everyone? Yes. Am I clear? Clear? Okay. Now, beta, next we have is K3 Fe C2O4 whole thrice. Okay, we have K3, then we have Fe, then we have C2O4, and then we have whole thrice. Okay, then we have whole thrice. Am I clear, everyone? Okay, so here what I can see, bacha, here what I can see, that you guys can adopt two methods, right? You can adopt two methods in order to find the oxidation number of Fe. Right? How many methods you can adopt, beta? You can adopt two methods in order to find the oxidation number of Fe. Right? The very first method is you actually do the sum of oxidation number of all the ions and the atoms which are present right here and make it equal to 0. Or you can individually do it for cation and anion. Don't worry, I will explain you. Come here, bacha. See, what you can do, that potassium is said to have always a charge of +1 or always an oxidation state of +1. You must have studied in redox that all the alkali metals are always said to have an oxidation number of +1, right, everyone? Okay. Now, Fe oxidation number we have to find, and we have here 3 oxalate ion, and each is said to have a charge of -2. Okay. So, what we can do, beta, here we have 3 potassium, so 3 into +1, plus for Fe we have the oxidation number as X, that we basically have to find. Okay, plus we have 3 oxalate ions which are said to have a charge of -2 equal to 0. So we have +3 plus X -6 equals to 0, X -3 equals to 0, or X is basically equals to +3, bacha. Okay, X is basically equals to what, bacha? X is basically equals to +3. Am I clear? This is one of the method you can adopt. Now, what is the another method, beta? What is the another method? See, it's very simple, bacha. If you have to split K3 Fe C2O4 whole thrice into its individual ions. Okay, if you have to split it into its individual ions, so how you can split it, beta? I've just told you it will give 3K plus ion, right? Plus it will give Fe C2O4 whole thrice 3 minus ion. Now I've already told you how to split the cation and anion. You must be aware of it, right? So what you can do, you can take this complex anion individually. What you can do, you can take this complex anion individually, beta, right? You can take this complex anion individually, right? Now, if you will take this complex anion individually, beta, you can mark its oxidation number as X, right? You can mark its oxidation number as X, right? So, you have X plus we have 3 oxalate. Each oxalate is said to have a charge of -2, right? It will be equal to the overall charge, which is -3. Am I clear, bacha? Right. So, here X -6 is equals to -3. So, X is basically equals to +6 -3, or X is basically equals to +3. Am I clear, bacha? X is basically equals to +3. Am I clear, everyone? Am I clear, everyone? Yes. Am I clear? Yes, clear or not, bacha? Clear? Right. If it is clear to you all, then quickly find the oxidation number of these through coordination number also and oxidation number also. Okay. So you have to tell me the coordination number and the oxidation number of all these, right? Here is the section of oxidation number. Here is a section of oxidation number, and here is the section of coordination number. Okay, here is the section of coordination number. Am I clear? Quickly tell me in the chat box what could be the oxidation number and what could be the coordination number. Now, Kaja Nagar is basically asking for a break, but a break You guys must be aware. Please don't laugh, yaar. I usually lack in pronunciation, yaar. You guys are very typical names, yaar. See, I have a name of 6 letters, yaar. Sonali. It's ending. Yaar, you guys have such a big names and big surnames, beta. You actually have a this much bigger name. My entire family don't have it, beta. If I'll surplus the name of each and every member of my family, then also this much bigger name is not possible. So how can I pronounce your name, yaar? Right? एक तो वैसे भी it's very difficult to teach in English, यार. है? एक तो it's very difficult to teach in English, right? Entirely you have to teach in English, right? Okay, right? Yeah, so Tillu is a very cute name, simple name. Everybody can remember Tillu. Right, Vinuta is a simple, okay, okay, so Kajanagar is basically the state from which she belongs. Her name is simple, Vinutha, okay, Vinutha, Deepika. You want me to give you shout outs? You want me to give you shout outs? Ha, Lahari, you want me to give me I can give shout outs, right? But the coordination compound is a very big chapter, beta. I don't have that much amount of time that I can give shout out to each and every student. But nevertheless, it's okay. Yes. Okay, so Pujasvi is giving the correct answers. Okay. Fine, let's just move ahead, beta. Let's just move ahead. So here we have CONH3 whole 4 H2O BrNO3 whole twice. See, bacha. Let the oxidation state of cobalt be X right here. Fine. We have 4 NH3 and NH3 is said to be a neutral ligand. That means the overall charge present on NH3 is said to be 0. Right. So here we will have 4 multiply by 0. Again H2O, which is water, again a neutral ligand. Right. So 0 for that. Talking about Br, it is said to have a -1 charge. It is an anionic ligand. Don't worry, I will give you a list of ligands with their denticity, with their charge. Don't worry, okay? Right, so the charge is -1 for it, plus we have 2 nitrate ion, and each nitrate is said to have a charge of -1, okay? So x minus 3 equals to 0, or x is equals to +3, okay? X is equals to +3. So for first, the oxidation number is +3. Now what is the coordination number? What is the coordination number, beta? Again, you have to take just the complex part or the part in the coordination sphere in order to find the coordination number, bacha. Okay, so number of ligand, 3 different type of ligands, beta. 1, 2, 3 are present right here. Talking about Ni, in the case of NH3, it is 4 beta G, right? And its denticity is 1. Right, H2O is 1 and its denticity is also 1, and Br is also 1 and its denticity is also 1. So the coordination number is 6. Am I clear, everyone? The coordination number is 6. Talking about next one, beta. Next one is K3FeC2O4 whole thrice. I think it's pretty simple, beta. You have already done it. You have already done it. Okay, you have already done it. Right, so we can skip it. In the previous page, we have already done it. Right, we have found out now. You can find it by yourself, beta. The oxidation number on Fe is +3 and the coordination number is 6. We have done on the previous page. Skip it. Next we have is beta NIEDTA 2-. Now it is important. Now it is important. See, beta. Let the oxidation state of nickel be X right here. What is the oxidation state of nickel right here, bacha? Let it be X. Okay. Right. Now let the oxidation state of nickel be X. Now quickly tell me in the chat box, what was the overall charge on EDTA? What was the overall charge on EDTA? I have just told you. What was the overall charge on EDTA? Yes. Hi, sweetie. What is the overall charge on EDTA? I've quickly told you, beta. I've quickly told you. What was the overall charge on EDTA? Absolutely correct. -4. Okay. Equals to what? -2. Equal to what? -2. Am I clear, everyone? Am I clear, everyone? Okay. So X is +4 -2. So it comes out to be +2. Clear, everyone? So now let's come to the coordination number. Beta, coordination number is summation NIDI. Yes or no? Right? Now number of EDTA which are present right here is 1. Number is 1. Right? And denticity of 1 EDTA is 6. Right? So you have to do 1 into 6. That means coordination number will be 6 right here. Am I clear, everyone? Yes. Am I clear, everyone? Absolutely clear? Absolutely clear? Yes or no? Absolutely clear. Okay, okay. Let's just move ahead, everyone. Now, we have one more complex. Do it in your homework, right? You have to find the oxidation number, right? It's very simple. You can do it in your homework. Now, let's just move ahead. Let's just move ahead. And now, let's come to the classification of coordination complexes. See, I have already told you, beta, the classification of coordination complexes on the basis of charge on complex ion, right? I have told you a coordination compound might have a cation which is complex, right? And a coordination compound might have an anion which is complex. On the basis of that, we have either cationic complexes or anionic complexes, right? I have already told you, everyone. I have already told you or not? Yes or no? I have already told you, bacha, cationic and anionic complexes. Yes or no? Right? Right? For example, beta, I have told you, if I have a complex CONH3 whole 6 Cl3, right? So, if this complex is put it into the aqueous solution or just broken up into its ion or broken up into its ion, it will form CONH3 whole 6 3 plus 3Cl minus ion, beta, right? That means here the cation is complex, right? That means here the cation is complex, and whenever the cation is complex, it is said to be a cationic complex. It is said to be a cationic complex, okay? So, here cation is complex, and whenever cation is complex, such type of complex are known as cationic complex. Am I clear, bacha? Am I clear? Right. And similarly, when you have anion as complex, right? When you have anion as complex, for example, if we have K3 Fe F6, okay, right? Now, when it is broken up, it will form 3K plus, right? Plus it will form Fe F6 3 minus, right? That means here anion is complex. That means here anion is complex, right? Yes or no, bacha? Here anion is complex, and whenever in a coordination compound we have complex anion, that particular complex is said to be anionic complex, okay? So, these are basically the classification of coordination complexes on the basis of whether the cation is complex or the anion is complex, right? Okay, so on the basis of charge on the complex, right? Now, quickly tell me in the chat box, first one is cationic or anionic without breaking the complex. Now, this is the deal. This is the deal. You don't have to break this. You just have to tell me whether it is a cationic complex, whether it is an anionic complex. It is a deal. You don't have to break it, beta. See, it's very simple, right? We know that in a salt, first cation come, then the anion come, right? And here the cation is written in the square bracket. That means here the cation is complex, right? That means here the cation is complex. That means the first salt is single-handedly cationic complex. Am I clear? It is single-handedly cationic complex. Am I clear? Am I clear? Am I clear? Okay, if I see the another complex, see, it's very simple, beta. First cation comes in a salt, then anions comes in the salt, and coordination compound is nothing but an addition salt, right? So, here first will be the cation and the second one will be the anion. Now, anion is written in the square brackets. That means here the anion is complex. Then without applying a lot of brain, you will write it here that it is a anionic complex. Okay, it is a anionic complex. Am I clear, beta? It is a anionic complex. Is it clear or not? Yes. Is it clear or not? Clear, everyone? Clear? Okay. Right. Fine. Beta. Now, the third category of complexes are neutral complexes. Now, here, bacha, the complex is said to have an overall zero charge. For example, if I have NiCO whole 4, okay, NiCO whole 4, here the complex is overall said to have a zero charge. There is net charge which is equals to 0. Okay, there is net charge which is equals to 0. That means it is a neutral complex, right? It is said to be a neutral complex, right? In a similar manner, if I have CO NH3 whole thrice Cl3, here also you can find the overall charge. Generally, whenever cobalt form complexes with coordination number 6, here the coordination number is 6, beta. We have 3 NH3 and we have 3 Cl, right? Generally, the oxidation state of cobalt is +3. So, +3 charge for cobalt and 3 Cl are present right here. So, -3 for it. +3 plus minus 3. Overall charges again 0, right? And in the above case, carbonide is a neutral ligand, and here nickel is also said to have a 0 oxidation state. So overall it is 0, right? So whenever the overall charge on the complex is said to be 0, such type of complex are basically known as neutral complexes. Such type of complexes are basically known as neutral complexes. Am I clear, everyone? Yes, am I clear? Right? Okay. Now this is an important topic, beta. From this topic, now you must be thinking, ma'am, why are you teaching such kindergarten topics, ma'am? Teach us some high level topics like isomerism, effective atomic nuclear charge, ma'am, effective atomic number, ma'am. Why you are teaching this, ma'am, third level topics, ma'am? Bacha, the reason for that is last year from this topic you have actually got questions, right? Again, I am telling you, cationic and anionic complexes can be asked in the NEET exam. They can ask you these types of questions as well. I will tell you the question which has been asked in NEET 2024, right? I will tell you that question as well. That is why each and every topic is damn important. Am I clear, everyone? That is the reason that each and every topic is damn important. Am I clear, everyone? Yes, am I clear? Okay, right. Now, let's basically classify. We are studying the second classification of coordination compounds, beta, and that is basically on the basis of types of ligands. Okay, here we are classifying on the basis of types of ligand. See, beta, if in a coordination complex we have a coordination sphere, and in that coordination sphere, right, that means the part which is present in the square bracket, we have all similar ligands, right? Inside the coordination sphere, what we have, beta, we have all similar ligands. Am I clear? What we have, beta, we have all similar ligands, right? Then in that particular case, that complex is known as homoleptic complex, okay, right? So the complexes in which metal is basically bound to only one kind of ligands, right? Only one kind of donor group, such complexes are known as homoleptic complexes. Am I clear, beta? Right? For example, I have NiCl whole 4 minus, okay, right? I have a PtCl whole 4 2 minus, okay, I have PtCl whole 4 2 minus, NiCl whole 4 2 minus, okay. So where nickel is bounded only to chlorine, here platinum is bounded only to one type of ligand, chlorine. So these are the example of homoleptic complexes. Clear? Similarly, if I have K4FeCN6 beta, here I have K4FeCN6 beta. Clear? Now here K4FeCN6, again, beta, if you look at the coordination sphere, that means the part which is present inside these square brackets, it consists of only one type of ligand, which is Cn, right, which is Cn, right. So it is also an example of a homoleptic complex. It is also an example of a homoleptic complex. Is it clear, everyone? Okay. Now, whenever in a complex part or in the coordination sphere, right, metal is bounded to more than one type of ligands or to the more than one type of donor groups, right, then that particular complexes are known as heteroleptic complexes, okay. That particular complexes are known as heteroleptic complexes. For example, we have CONH3 whole thrice Cl3, right. Here, beta, here cobalt is bounded to two types of ligands, beta. One is NH3, other one is Cl minus. So this is said to be an example of a heteroleptic complex. Am I clear, everyone? Am I clear, everyone? Right. Okay. Now quickly tell me in the chat box which of the following complexes are homoleptic and which of the following complexes are heteroleptic. Quickly, first one, beta. In first one, we can see that cobalt is bound to only one type of ligands, which are NH3, right. So the very first complex is an example of a homoleptic complex, okay. The very first complex is an example of a homoleptic complex. Am I clear, everyone? Yes. Am I clear, everyone? Clear, right. Now if I look at the second one, beta, here cobalt is bounded to NH3 as well, okay, as well as to Cl2 beta G, right. So that means here two type of ligands are present. So it is an example of a heteroleptic complex, okay. It is an example of a heteroleptic complex. Am I clear? It is an example of a heteroleptic complex. Am I clear, everyone? Yes. Am I clear? Clear? Okay. Next we have beta. See, here nickel is bounded to only one type of ligand, and that is CN, right? That means it is again homoleptic, right? I am writing in a short form. And the other one beta. Here nickel is bounded to both Rajay, NH3 as well as Cl2. Okay, NH3 as well as Cl2. So again, it is bound to two types of ligands. So it is a heteroleptic complex. Okay, it is said to be a heteroleptic complex. Am I clear? It is said to be a heteroleptic complex. Is it clear to you all, everyone? Yes. Is it clear to you all, everyone? Fine. Okay. So now let's come to the question which has been asked in NEET 2000. Right? This question has been asked in NEET 2024. Okay. So this question has been asked in NEET 2024, beta. The question is in front of you. You have to tell me, the statement 1 is written, the statement 2 is written. You have to tell me among option A, B, C, D which is correct. If you have understood the concept of a homoleptic and a heteroleptic ligand, then this question is very simple. Okay, so quickly tell me beta, which is the answer? Option A, B, C and D. Most of you are saying it option 1. That means you guys have understood the concept beta. Statement 1 which is written right here. Statement 1 which is written right here is beta, CONH3 whole 6 is a homoleptic complex, whereas CONH3 whole 4 Cl2 is a heteroleptic complex. Absolutely correct. Okay, that means statement 1 is absolutely correct. Coming to the statement 2, complex CONH3 whole 6 3 plus has only one kind of ligand, but CONH3 whole 4 Cl2 has more than one kind of ligand. This is also absolutely correct. Okay, so here both the statement 1 and statement 2 are absolutely correct. Now you can see this question has been asked in NEET 2024. That is why I have told you this complex with such clarity. Am I clear, everyone? Right, now let's just move ahead, bacha. Let's just move ahead. And now let's come to the third classification of coordination complexes. Now this is basically the third classification of coordination complexes, beta. Now you will see that there are certain coordination compounds. Okay, there are certain coordination compounds in which only one central metal atom is present, or only one central metal ion is present. Okay, what I am trying to say, beta, there are certain coordination complexes. For example, you have CONH3 whole thrice Cl3. Okay, CONH3 whole thrice Cl3, right? So what I can see, beta, in this coordination compound only one central metal ion is present, which is cobalt 3 plus. Okay, which is cobalt 3 plus. Yes or no, everyone? Yes or no? Yes, ma'am. Right? Similarly, if I have a complex PT NH3 whole twice Cl2, right, and I will write Cl2 outside the coordination sphere as well, right? So in this particular compound, in this particular complex also, beta, in this particular complex also, we have only one central metal atom, or we have only one central metal ion. Yes or no, everyone? Yes or no, everyone? Yes. Okay, so such type of complexes which are said to consist of only one type of central metal atom or only one type of central metal ion, everyone, such type of complexes are known as homonuclear complexes, or I should say mononuclear complexes. Okay, such type of complexes are known as homonuclear complexes or mononuclear complexes. Am I clear, everyone? Yes. Am I clear, everyone? Clear? Okay, right. Now there is another category of complexes which are heteronuclear or polynuclear. Now these complexes are said to have more than one central metal atom or more than one central metal ion, right? Okay, so this is a mother which have twins. Okay, this is a mother which have twins, right? The twins could be alike, the twins could not be alike. Am I clear? The twins could be alike and the twins could be not alike. Am I clear, everyone? That means here we have two central metal atom, and these two central atom might be same, might be different. Okay, for example, if I have PT PY whole 4 PT Cl whole 4. Okay, so here the cationic part is also complex and the anionic part is also complex, right? Here the cationic part is also complex and the anionic part is also complex, right? And here two central metal atoms are present. Here two central metal atoms are present. So this is an example of a polynuclear complexes, or I should say heteronuclear complexes. Am I clear everyone? Am I clear? The name of this complex, beta, I will tell you how to write in nomenclature. Don't worry, nomenclature is going to start in next 10-20 minutes. Fine. So I will tell you how to write the name of this particular compound. Am I clear, beta? Right. And another one, here we have CrNH3 whole 6, okay, right, we have CrNH3 whole 6 and we have CN whole 6, right. Here also the cationic and the anionic, both the parts are complex, right, and here also beta two different central metal atoms are present, one is chromium and one is cobalt. So this is also an example of a heteronuclear complexes, right. So heteronuclear complexes will contains two central metal atom. These two central metal atom might be same or they might be different. Am I clear everyone? They might be same or they might be different. Is this point clear to you all? Yes. Is this point clear to you all everyone? Clear? Can I move ahead? Can I move ahead? Can I move ahead? If I can move ahead, then I want green hearts. Tell me. If I can move ahead, I want lot of green hearts. Yes. Is this point clear to you all everyone? Clear or not? Clear? Yes. Clear? Clear everyone? Clear or not? Clear? Yes. If it is clear, I want lot of green hearts. Clear everyone? Don't get scared, it was just the echo which happened inside the bottle. See, so I have 56 students right here. I want these 56 students to retain till the end of this marathon, and that is the power of consistency, beta. That is the power of consistency. The thing which we lack, okay, the thing which actually, you know, the thing which actually stop us from achieving that goal of being at the top is just bare consistency, right? The series has been organized. We all have promised, sir, that yes, sir, we will be consistent. Yes, sir, we will attend all the marathons. Yes, sir, we will revise 75 chapters in 75 days and we will be well prepared for our NEET exam. But what happened at the end, right? We are at the 24th session, I guess. In every session, what I can see a drastic drop in the live watching. Why? Because people are giving up. The people are not able to be inconsistent. Am I clear? Am I clear, everyone? Right? Right? This session is worth even for freshers. Even for a person who haven't even studied any basic. This session is well and sufficient. Am I clear, everyone? Okay. So now, please keep one thing in your mind. Keep one thing in your mind. Be consistent throughout the session. It's very difficult for me also to speak for 10 hours, but I am having that patience. So you guys also should have that patience, beta. You guys should also have that patience. Okay, everyone. So now let's just move ahead. Everyone. Fine. Let's just move ahead. Okay. Fine. Let's just move ahead, everyone. Right? Let's just move ahead. Okay, now, let's just come to the listing of ligands or the name of the ligands. I have told you that we can have three types of ligands on the basis of charge. One are your cationic ligands, one are your anionic ligands, and the other one are neutral ligands. Okay, so now what we are going to do, beta? See, after this we have to study nomenclature, right? So what we will do, we will study the type of ligands on the basis of charge, then we will see what is the charge on them, and then at the same time we will study their IUPAC name, okay, or the name which we are going to use for these ligands in IUPAC. Now this 15 minutes are damn important, right? If you will listen to me carefully, if you will listen each and every point which I am saying right now, then you will become pro in the entire chapter and you will become pro in nomenclature. Okay, so make sure to listen each and every word which I'm going to utter, right, consistently throughout. Okay, right. Now let's come to the list of ligands. Bacha, first we are studying the negative ligands or the anionic ligands, right? Fine. So the very first ligand is Cn minus, right? Now the Cn minus is said to have a charge of -1, bacha, and beta, since it is an anionic ligand and in IUPAC right? IUPAC is International Union of Pure and Applied Chemistry. Like in an organic, we have a name of every organic compound, beta. In coordination chemistry also, we have a name of every coordination compound, right? And that name is given by certain sets of IUPAC rules, right? So in those IUPAC rules, beta, if we have an anionic ligand or we have a negatively charged ligand, the name of that particular ligand basically ends with O. Am I clear? The name of that particular ligand basically ends with O. Am I clear, beta? Right. So anionic ligands basically ends with O. Am I clear, everyone? Anionic ligand basically ends with O. Is this point clear to you all, everyone? Okay, next, bacha, if I talk about this ligand, beta, this is cyanide, right? So the name of this ligand in IUPAC will be cyanido, right? Ide, E will be replaced by O, so the name is cyanido, right? All anionic ligands will end with O, right? You can even use the name cyano for this particular ligand in IUPAC. Am I clear? Okay, next we have is the halide ion, beta, X minus. Now it could be chloride, it could be fluoride, it could be iodide, it could be bromide. All of them are said to have a -1 of charge, and the name for them is either fluoro-chloro-bromo-iodo, right, or fluorido-chlorido-bromido iodido. Right, you can use any of the two names, right, while writing the IUPAC name of a coordination compound consisting of this ligands. Am I clear? Right, for hydride, the charge is -1 and the IUPAC name is hydrido. Then beta, if I talk about nitro, that is NO2, it is an ambidentate ligand, right? I have just told you, Rajay, what that NO2 is an ambidentate ligand, right? It can coordinate either through nitrogen to the central metal atom, or it can coordinate either through oxygen through central metal atom, beta, right? It is an ambidentate ligand, right? So it depends whether the NO2 group has coordinated through nitrogen or through oxygen. The name of this particular ligand in IUPAC varies. Okay, now if it basically coordinates through nitrogen, right? It basically coordinates through nitrogen, then it is written as NO2, charge is -1, and the name which is used for this is either nitro or nitrito N. Now N symbolizes here that the donor atom in this particular ligand is nitrogen. Am I clear, everyone? Okay, am I clear? Right. Further, beta, here since it is an ambidentate ligand, it can also coordinate through oxygen, right? It can coordinate through oxygen, right? So whenever it coordinates through oxygen, bacha, then in that particular case, the name is either nitrito or nitrito O. Now O here signifies that the donor atom is oxygen. Am I clear, everyone? Donor atom is oxygen, right? Fine. So for NO2 we have nitrito N or nitro, and for ONO minus we have nitrito O or nitrito. Am I clear? Okay. Now, bacha, if I move ahead, Rajay, if I have nitrato, nitrato is NO3 minus. So if I have nitrate ion, it is said to have a -1 charge, and the IUPAC name is nitrato. Am I clear? The IUPAC name is nitrato. Is it clear to you all, everyone? Okay. Now let's just move ahead. Beta, let's come to the another set of ligand, Rajay. Here we have is OH minus, charge is -1. The name is hydroxo, right? Then we have is NH2 negative, right? So it is basically amide. NH2 minus is amide. So here the charge is -1, right? And the IUPAC name is amido. Am I clear? The IUPAC name is amido. Clear? Bacha, now further I have told you that thiocyanate, okay, that means SCN minus, it can either coordinate through sulfur, through the central metal atom and the central metal ion, or it can either coordinate through nitrogen through central metal atom or central metal ion. Am I clear, everyone? It can either coordinate through sulfur or it can either coordinate through nitrogen. Am I clear? It can either coordinate through nitrogen, everyone, right? Yes or no? Fine, that means it is also an ambidentate ligand. Now, depending upon through which donor atom it is coordinating to the central metal ion, beta, we have two different IUPAC names, right? Okay, for example, if it is coordinating through sulfur, bacha, right? It is coordinating through sulfur, bacha. Then here the charge is actually -1, and the name which is written in IUPAC is either thiocinato or it is thiocinato S. Now S basically symbolizes that here the donor atom is sulfur. Am I clear? Okay, right. In a similar manner, beta, it can coordinate through nitrogen as well, right, to the central metal ion. Charge will again be -1, but however the IUPAC name is different, right? Either you write isothiocyanato. Isothiocyanato means automatically you have to understand the donor atom is nitrogen, right? Or you have to use thiocinato N. Now N symbolizes that here the donor atom is nitrogen. Am I clear, everyone? Yes. Am I clear? Clear, everyone? Okay, next I have is basically O2 minus, which is oxide, right? So here the charge is -2 and the name of this particular ligand is special, it is oxo. Okay, what is oxide ion? Known as a ligand, it is basically known as oxo. Am I clear, bacha? Okay, the name is oxo. Now, next I have is O2 minus beta. We all know that this is basically an peroxide ion. The charge on this is -2 and this IUPAC name is peroxo. Am I clear? The IUPAC name is peroxo, right? If I talk about superoxide ion, which is O2 minus. Now, beta, if I talk about O2 minus, it is said to have a charge of -1, right? It is said to have a charge of -1, right? Fine. I think I haven't written superoxo right here. It has been written sulfido. Sulfido. Okay, so they haven't mentioned it, so I am writing it at the bottom, beta. So this is basically O2 minus, right? The charge on it is -1, right? And this is basically superoxo. Okay, this is basically superoxo, or you can say it as superoxide ion. Am I clear? You can say it basically as superoxide ion. Am I clear? This is basically superoxo. Okay, superoxo, or you can even use superoxido. Both are valid. Superoxo is also valid and superoxido is also valid. You can add it. Okay, you can add it. Am I clear, everyone? Now, talking about the next ion. The next ion is basically bicha S2 minus. It is said to have a charge of -2. This is sulfide ion, right? The IUPAC name is sulfido. Okay, the IUPAC name is sulfido. Am I clear, everyone? Right. Similarly, next ion we have is SO4 2 minus. Okay. The next ion we have right here is SO4 2 minus. This is sulfate ion. Charge is -2 and the IUPAC name is sulfato. Okay. The IUPAC name is sulfato. Is it clear to you all, everyone? Clear? Right. Now, beta, next we have the another sets of ligands. Next we have is the another sets of ligands. Okay, the another sets of ligands which we have right here is thiosulfate, beta. You must have studied in redox reaction S2O3 2 minus. This is thiosulfate ion, right? It is said to have a charge of -2, bacha, right? It is said to have a charge of -2 and the IUPAC name of this particular ion is thiosulfato. Am I clear? The IUPAC name of this particular ion is thiosulfato, right? The IUPAC name of this particular ion is thiosulfato, right? Okay, next we have is CO3 2 minus. This is carbonate, charge is -2 and the IUPAC name is carbonato, right? Then you have is imide. Imide is NH2 minus, beta. Amide is NH2 minus and imide is NH2 minus. Am I clear? Fine, the charge is -2 and the IUPAC name is imido. Okay, you can remember in this particular manner, beta. NH2 minus is amide. It is amide and the IUPAC name for this is amido. Clear? Right. And NH2 minus is basically imide and the IUPAC name is basically imido. Am I clear, everyone? Okay, right. Now, if I talk about the another ion, it is basically oxalate, Raji. It is basically oxalate, right? This is basically oxalate ion, Raji. Right. Now, oxalate ion is said to have a charge of -2 and the IUPAC name is oxalato. Right. IUPAC name is oxalato. Now, here one thing I would like to tell you, beta, this oxalate ion which you can see right here. Okay. This oxalate ion which you can see right here, how it is basically formed. It is basically formed with the help of oxalic acid. Okay. It is basically formed with the help of oxalic acid. I have C double bond OOH. I have C double bond OOH. Right. Now, when this oxalic acid basically loses its 2H plus ions, right? It basically forms COO negative, COO negative, right? Now this ion is basically known as oxalate ion, okay? This ion is basically known as oxalate ion. Now this oxalate ion is a potential ligand, right? It is a bidentate ligand, right? It is a bidentate ligand, and it can form two coordination bonds with through donor oxygen atom to the metal, right? How many donor beta it has? It has two donor oxygen atom, okay? Two oxygen atom as the donor, right? So can you tell me the size of ring which is formed by this ligand? It is a didentate ligand, and didentate ligand can act as a chelating ligand, right everyone? So can you please tell me the size of ring which is formed by this didentate ligand? Yes. Can you please tell me the size of ring which is basically formed by this didentate ligand? Yes everyone. Yes. Could you please tell me the size of the ring or the number of members? Very good beta, very good. I can see it is basically forming 1, 2, 3, 4 and 5, right? So it is basically forming a 5-membered ring. Am I clear, bacha? It is basically forming a 5-membered ring. Is it clear? Yes, it is basically forming a 5-membered ring. Fine. Let's just proceed ahead, bacha. Let's just proceed ahead. See, I am discussing all the important ligands in one go. At the same time, wherever I feel I need to tell you some addition points, I need to tell you the number of rings, number of membered rings, like how many membered rings are being formed. I am telling you in this go only, right? So that we don't have to repeat it again and again, because these questions can be asked. These are very basic questions. They can be asked. Okay, right, fine everyone. So next we have is azide ion, beta, azide ion. Okay, now azide ion is basically N3 minus. This is azide ion. Okay, it is said to have a charge of -1 and the IUPAC name is azido, right? Next we have is nitride. Nitride is N3 minus. The overall charge is -3 and the IUPAC name for this is nitrido. Am I clear? The IUPAC name for this is nitrido. Okay everyone, right? If I talk about superoxido, I have already told you beta, O2 minus is said to be a superoxide ion. Its IUPAC name is superoxido. I have already told you. So I am just proceeding ahead because I have to do a lot of ligands. Okay, so next is acetyl acetone. Okay, next is acetyl acetone. Now this is a special kind of ligand. How it is formed, beta? In organic, if you have studied reaction mechanism, sir must have told you about active methylene compounds. Now what are these active methylene compounds, beta? See, all those compounds, please do not get scared first of all, this term active methylene compound. It is very simple. It is very simple. Please do not get scared. Okay, see, if I have C double bond O, CH2, C double bond O, CH3. Now this CH2 is basically a methylene group. CH2 stands to be methylene. Am I clear? CH2 stands to be methylene, right? Now beta, here we have two electron withdrawing carbonyl groups which are highly electron withdrawing, right? So what happens, beta? They withdraw the electrons to such an extent that the hydrogen which is present in this methylic group is highly acidic. Am I clear, beta? The hydrogen which is present right here is highly acidic. Am I able to make this point clear to you all, beta? The hydrogen which is present right here is highly acidic. Am I clear? Okay, right, it is highly acidic. Fine. So it can lose this hydrogen, beta. It can lose this hydrogen. Fine, to form CH3, C double bond O, CH2 negative, C double bond O, CH3. Am I clear, bacha? Right. Now this is acetyl acetonato ion. Okay, right. This is the ion, beta. This is the ion. Now this ion can occur in a resonating form as well. That means either it can coordinate through metal through these oxygen. Right, this is basically ACAC ion, acetyl acetonato ion. Am I clear? This is basically ACAC ion. Right, this is acetyl acetone. Right, this is acetyl acetonate ion. This is acetyl acetone. Right, this is acetyl acetone. This is acetyl acetonate ion. Am I clear, everyone? Right, now here either through these oxygen they can form a coordinate bond. If they form the coordinate bond through these particular oxygens, bacha, right? Ma'am, not visible in red. Red is not visible. Okay, 1 second. But this is basically acetyl acetonate ion, that is ACAC ion. This is ACAC, that is acetyl acetone. Okay, this is ACAC, that is acetyl acetone. Am I clear, everyone? This is acetyl acetonate ion. Am I clear? This is acetyl acetonate ion. I am writing it here, beta. This is acetyl acetonate ion. Am I clear, everyone? Yes, am I clear? Now, either it can exist in this particular form and coordinate through the metal, right? It can coordinate through the metal in this way as well, or beta it can undergo resonance. I can see there is a conjugation right here, which is a carbon bearing negative charge, then a single bond, then a pi bond. You can see there is a conjugation right here. Yes, everyone, there is a conjugation right here. So this negative charge will get transferred to the single bond, and this pi bond will get transferred to the adjacent oxygen atom. Right, bacha? Right. So there occurs the formation of CH3 double bond O, CH double bond C, O negative CH3. Am I clear? So it can exist in any of the resonating form, this or this, right? It can coordinate through these two oxygens, through the central metal atom or the central metal ion. That means it is a bidentate ligand, right? It is a bidentate ligand. Here we have two donor oxygen atom. Okay, we have two donor oxygen atom. That means it is a bidentate ligand, right? That means it is a bidentate ligand, beta, right? It is a bidentate ligand, Rajay. Okay, it is a bidentate ligand, right? And it can coordinate through central metal atom or central metal ion through any of its structure, either in this way, right, or in this way. Both are absolutely correct. And in both the structure, if I have to count how many membered rings are formed, how many membered rings are formed, beta? How many membered rings are formed, Rajay? This is 1, 2, 3, 4, 5 and 6. That means 6 member ring is formed, right? And here also if we have to count 1, 2, 3, 4, 5 and 6, that means here also 6 membered ring is formed. Okay, so in both of the cases we can easily see that here a 6 membered ring is formed. Am I clear, everyone? Here 6 membered ring is formed. Is it clear to you all, everyone? Yes, is it clear to you all, everyone? Fine. So we have done the another ligand, acetyl acetone, or we should say ACAC negative, right? The structure is CH3 C double bond O, CH negative C double bond O, CH3, right? It is said to have a negative charge. See, it is acetyl acetonate ion, and if I have to write the IUPAC name, it is acetyl acetonato, right? What is the IUPAC name? What is the IUPAC name, beta? It is acetyl acetonato. Is it clear to you all? Is it clear to you all? Acetyl acetonato. Fine. Okay. So now let's come to the another ligand. This is glycinate ion. Now what is this glycinate ion? Yeah, you guys are bio people, right? You guys are definitely bio people. So if you are bio people, you must be aware of the amino acid glycine, right? You guys must be aware of the amino acid glycine. It is NH2 CH2 COOH, bacha, right? Now here this hydrogen which is present on this carboxylic acid group, this is highly acidic, right? This is highly acidic. Am I clear, everyone? This is highly acidic, right? So it can undergo the removal of H plus because it is acidic in nature, right? Now here if I form NH2 CH2 COO negative, this is glycinate ion. This is glycine, bacha. This is glycine. Am I clear? This is glycine, bacha, right? And this is glycinate ion. Okay, this is glycinate ion. Okay, this is glycinate ion, right? Now this glycinate is also known as GLY negative, right? GLY negative. GLY stands for the short form. Okay, GLY stands for the short form, glycinate ion. Am I clear, everyone? Okay, right. So what is this glycinate ion? What is this glycinate ion, beta? It is NH2 CH2 COO negative, right? Now, here, if I talk about this glycinate ion beta, can I write this glycinate ion as CH2, NH2, and C double bond O negative, right? It has one donor nitrogen and it has one donor oxygen, right? It can coordinate through both of these donor to the central metal atom or the central metal ion, right? It can coordinate through both these donor atom through the central metal atom or the central metal ion. Yes or no, everyone? Yes or no, right? So can you tell me how many members ring is being formed? How many members ring is being formed, beta? It's very simple. See, I have 1, I have 2, I have 3, I have 4, and I have 5. That means in this particular case, 5-membered, okay, in this particular case, 5-membered ring is being formed. Am I clear, bacha? In this particular case, 5-membered ring is being formed, okay, right? 5-membered ring is being formed, and here we have 2 donor atoms, okay, here we have 2 donor atoms, bacha. Am I clear? Here we have 2 donor atoms, beta. Here we have 2 donor atoms. One of the donor atom is nitrogen and the other donor atom is oxygen. Am I clear, beta? One donor atom is nitrogen and the other donor atom is oxygen. Am I clear, everyone? Yes. Am I clear? Yes. Clear or not, everyone? Clear? Okay, right. So this glycinate ion is said to be a bidentate ligand. It is said to have a -1 charge. Okay, it is said to have a -1 charge. And when I have to write the IUPAC name, it is glycinato. Right? For acetyl acetone, it is acetyl acetato, and bacha, and for glycine or glycinate ion, it is glycinato. Can you guys do it? Can you guys do it? Yeah, is it easy or not? Yeah, quickly tell me the chat box. It is easy or not? You can do it by yourself. Yes, is it easy or not? Yeah, quickly tell me. Is this chapter really difficult? Is this chapter really difficult? I don't think so. It is difficult at all. Yeah. I really don't think so. It's very easy. It's very easy, Madhubita. It's very easy. It's very easy, bacha. Right? You just have to, get the proper technique to remember the things. If you will ratify, if you will cram, then definitely you won't be able to make it up. However, if you understand the concepts, if you understand that how this particular ligand is coming, it will be easy for you to remember. It will be easy for you to remember the charge, the name, right, the denticity, the donor atoms, the number of ring membered formed, right? So it's very easy. Okay, everyone, fine. Now, let's just come to next ligand. It is dimethyl glyoxime. Okay, it is dimethyl glyoxime, or I should say DMG. Okay, dimethyl glyoxime, or I should say DMG. It is very, very, very important. If you are doing anything, please keep it aside. Please listen to me. The coming 5 minutes are really important 5 minutes of your life. Please, please, please listen to me. Please, please, please listen to me. If you're doing anything, please keep it aside. Please keep it aside. Please keep it aside. But break. Once I'll complete the list of ligands, I will give you the break. First, let me just complete the list of ligands. I have told you, first break will be in between 8 to 8:15 to 8:20. So, I will give you that break, right? Now, let me just complete this topic. Am I clear? Okay. Beta see, if I have DMG, DMG is basically dimethyl glyoxime. Okay, dimethyl glyoxime. It is very important, beta. They can ask question based on this. Please listen to me very quickly and very carefully, beta. See, the structure of dimethyl glyoxime is we have carbon, single bond carbon, we have CH3, we have another CH3. Then this carbon forms double bond with nitrogen. This carbon also forms double bond with nitrogen, and oxime means you have NOH group. Okay, so we have 2 NOH groups right here. Am I clear, everyone? Okay. Am I clear, everyone? Yes, am I clear, everyone? Okay, now listen to me, listen to me, listen to me. What happens, beta? What happens that whenever this particular groups comes in contact with a basic medium, suppose it comes in contact with OH minus ion from somewhere, right? Okay, this basic medium or this OH minus has a tendency to abstract this H plus. H plus and OH just eliminates in the form of water, right? H plus and OH just get eliminated in form of water. Am I clear, everyone? They just get eliminated in form of water, right? And here they basically forms what? Beta, here they basically forms CH3, C, CH3, okay, CH3, C, CH3, double bond NO minus and double bond NOH. Am I clear, everyone? Am I clear, everyone? Yes. Am I clear, everyone? Fine. Am I clear? Okay. Am I clear? Fine. Am I clear? Fine. Now here, if I talk about, bacha, here, if I talk about this nitrogen, this is said to have O minus, this is said to have OH, right? However, this nitrogen and this nitrogen, they both have a lone pair of electron, right? If I talk about this nitrogen or if I talk about this nitrogen, both the nitrogen, they are said to have a lone pair of electron. Yes, they are said to have a lone pair of electron. Am I clear, everyone? Right? So these both nitrogen can ligate or coordinate through central metal atom or central metal ion, right? They can coordinate through central metal atom and central metal ion, and there occurs a formation of ring. If I have to talk about the size of the ring, beta, it will be 1, 2, 3, 4 and 5, bacha. So it is a 5-membered ring. Am I clear? It is a 5-membered ring. Am I clear, beta? It will be a 5-membered ring, right? It will be a 5-membered ring, right? Yeah, I want some green hearts, yaar. Why such low charts, yaar? I want some green hearts, yaar. And I'm not able to teach like this, yaar. Give me some green hearts, bhai. Are you guys still active? Are you guys still excited? Bhaiya, my voice has gone down because I am shouting from past 3 hours, yaar. I'm just shouting from past 3 hours, bhai. Right? I am shouting from past 3 hours, yaar. Right? I know my voice should get low at this point of time. It is valid. But why you guys are low, bhai? Why you guys are low? Why you guys are low? You should be active, hyperactive in fact. You guys should be hyperactive right now. Fine. Okay, so bacha, see, here I have a 5-membered ring and I have 2 donor nitrogen atoms. Right, here I have 2 donor nitrogen atoms, bacha. Here I have 2 donor nitrogen atoms, bacha. Right, here I have 2 donor nitrogen atoms, bacha. So it is a bidentate ligand. Okay, so it is a bidentate ligand. Am I clear? It is a bidentate ligand. Am I clear, bacha? It is a bidentate ligand. Am I clear? It is a bidentate ligand. Right. Okay. Now, see, I have a very important points for you all, but I have a very important points for you. Now, this DMG is basically used for the quantitative analysis of nickel. Okay, this DMG, or I should say dimethyl glyoxime, is basically used for the quantitative analysis of nickel. Am I clear, bacha? Right. What happens is that this DMG is basically used for the quantitative analysis of nickel. Right. What happens is that in any of the salt, right, if any of the salt, nickel 2 plus is present, right, if in any of the salt, beta, nickel 2 plus is present, am I clear? Nickel 2 plus is present, any of the salt. You must have studied quantitative analysis, right, in your laboratory in schools. Lab attendant used to give you one particular salt and you have to find the cation and an ion in that particular salt. If you are testing for nickel 2 plus as a cation, right, so the test for that is that you take the salt which basically contains nickel 2 plus, right, you treat this with DMG, okay, you treat this with DMG in basic medium, beta, in basic medium, beta, right. So what will happen? It will form Ni DMG whole twice complex, right, and this nickel DMG complex, right, this nickel DMG complex is said to have a red color. Am I clear? This nickel DMG complex is said to have a red color, right. So whenever there occurs the formation of this red color, people just estimate it. Oh, here a cherry red, not the exact red, here the cherry red precipitated is formed. Then that is only possible when nickel is present, and that basically reacts with DMG. Am I clear, everyone? Am I clear, everyone? Okay, right. Now here, bacha, what happens that whenever you treat nickel with DMG in basic medium, I have told you that in basic medium, if I have DMG, right, this is DMG. If I have basic medium, bacha. So in basic medium of NH4, OH, what will happen, beta? What will happen? Raji, this H plus will get abstracted, right? This H plus will get abstracted, and I will have C single bond C. Here I have CH3, here I have CH3, right? Here I have N double bond N, here also I have double bond N, beta. Here I have this O negative, and there I have a OH. Right. Now what happens, bacha? What happens? Listen to me very quickly. Listen to me very quickly, beta. Whenever you have this DMG ion, this is DMG, right? This is dimethyl glyoxime. This is dimethyl glyoxime ion, that is DMG negative. Am I clear, everyone? Why it is negative? Because this oxygen is said to have a negative charge, right? Why it is negative? Because this oxygen is said to have a negative charge. Am I clear, everyone? Now listen to me very carefully. Now, beta, listen to me. This DMG minus ion, right? This DMG minus ion has a huge tendency to form symmetrical hydrogen bonding, right? To form symmetrical hydrogen bonding with the another DMG ion. Am I clear? It has a huge chance to form the, yes, it is in the NCERT Telugu industry. It is there in the NCERT when you will find the application of coordination compounds, but you won't find it, right? Because you don't read applications, you always skip it. And from there only the examiner is about to ask the question, right? So what I am saying, beta, this DMG ion has a huge tendency to form a symmetrical hydrogen bonding with the another DMG ion, right? Fine. So here I have the another DMG ion, beta. This is N double bond C, then I have C, again double bond N, and then this is O negative. Am I clear? Right, and here I have CH3 and here I have CH3, right? So there occurs the formation of symmetrical strong hydrogen bonding, beta, right? There occurs the formation of symmetrical hydrogen bonding, right? Symmetrical hydrogen bonding. Am I clear, everyone? Between the electronegative oxygen and hydrogen, right? Fine, there occurs the formation of symmetrical hydrogen bonding, and there occurs the dimerization, right? There occurs the dimerization of DMG minus ion, right? There occurs what, beta? There occurs dimerization, okay? There occurs dimerization. Now, once this dimer is formed, beta, they will trap nickel 2 plus inside them, and this nickel 2 plus will form two coordinate bonds with each DMG. They form two coordinate bond with each DMG, and this complex is basically water insoluble, right? This complex is basically water insoluble, right? This complex is basically water insoluble, and due to formation of this insoluble complex, there occurs the formation of a precipitate due to this complex, and this precipitate is a cherry red precipitate, and this cherry red precipitate is because of formation of this complex, beta, this complex, and this basically indicates that yes, in this particular salt nickel 2 plus is present. Am I clear? Right? There occurs the formation of a cherry red precipitate, beta. Okay, there occurs the formation of a cherry red precipitate. Am I clear, everyone? There occurs the formation of a cherry red precipitate. Okay, bacha, right? Now here are certain important points about nickel DMG complex which we need to take into considerations, right? Fine. The very first part or the very first point is very clear. You can see, beta, here the 4 nitrogen are basically surrounding the nickel 2 plus in a square planar geometry. You must have studied square planar geometry, beta, right? In chemical bonding, you must have studied square planar geometry, right? If you haven't studied it, don't worry. I will teach you in VBT. I will teach you in VBT today, Am I clear, everyone? I will teach you it VBT today, right? So here the 4 nitrogen are surrounding this nickel 2 plus in a square planar geometry, and the hybridization of nickel 2 plus is DsP2 right here. Okay, the very first point is this. Now, what is the coordination number of nickel 2 plus? Quickly tell me, what is the coordination number? How many nitrogen are surrounding, beta? 4, right? So the coordination number is 4. Right? Okay. Further, can you see any charge in this particular complex? No, there is no charge, beta. Right? Nickel is said to be in +2 oxidation state. We have 2 DMG. Right? 1 DMG is said to have a charge of -1. So 2 DMG is said to have a charge of -2. Right? So +2 -2. So what is the overall charge, bacha? Overall charge is 0. Right? What is the overall charge? Overall charge is said to be 0. Right? That is why we say that it is a neutral complex. Now, it is a water soluble complex. It has, that is why it is basically existing as a cherry or as a rosy red precipitate. Am I clear, beta ji? Right? The reaction of nickel 2 plus with DMG in presence of NH4OH is used for the test of quantitative analysis of nickel. Right? I have already told you. Fine. Further, beta, this is an optically inactive compound. Right? Basically, you must have studied that whenever there is no POS, plane of symmetry, if you have studied stereoisomerism, then you must have studied. If you haven't studied it, don't worry, I will teach you in today's class. So what I basically teach, whenever a compound do not have, right, whenever a compound do not have plane of symmetry, right, plane of symmetry, an imaginary plane which cuts the compound into 2 equal halves. For example, beta, if this particular compound, right, here we have a plane which cut this compound into 2 equal halves, right, then that is plane of symmetry. If any compounds have plane of symmetry, it is said to be optically inactive, right? So all square planar complexes, they are said to have at least one plane of symmetry, beta, right? So they will be optically inactive, right? Fine. So this is a square planar complex. It is a square planar complex. That is why it is optically inactive. Why? Because POS is present, right? Now, if I have to find total number of ring in this particular complex, can you tell me total number of rings which are present in this particular complex, beta? See, I can see a total of how many rings, beta? See, 1, 2, 3, and 4. So I can see 4 rings right here, beta. Yes, I can see how many rings? 4 rings right here. How 5, beta? I can to see 4 rings only. How 5 are possible? Could you please elaborate, everyone? How many rings are possible? I can see only 4 rings, right? So they can even ask that how many total rings are present in this particular compound, beta? Then there are a total of 4 rings which are present in this particular compound. Am I clear? There are a total of 4 rings which are present in this particular compound. Am I clear, everyone? Yes, am I clear, everyone? Quickly tell me in the chat box. Am I clear? Yes, am I clear? Yes, am I clear, everyone? Am I clear or not? Quickly tell me in the chat box. Clear? If clear, I want lot of green hearts. If it is clear, I want lot of green hearts. Okay. Now, there are a total of 4 rings. Beta, there are a total of 4 rings. Now, this point is absolutely clear. There are a total of 4 rings. Beta, right? 4 rings are present. Now, could you tell me the number of members in each ring? See, beta, if I talk about first ring, right? There are a total of 4 rings. It is clear. Now, if I talk about the first ring, it is 1, 2, 3, 4, 5, and 6. That means it is a 6-membered ring. Similarly, this will also a 6-membered ring. Yes, this will also be a 6-membered ring. Yes or no, everyone? Yes or no, everyone? Yes, ma'am. Okay. And talking about, beta, here we have 1, 2, 3, 4, and 5. So here I have 5-membered ring. Okay. So this will also be a 5-membered ring. So we have 4 ring, right? Out of 4, bacha, out of 4 we have 2 as 6-membered ring. Right, we have 2 6-membered ring, bacha. Am I clear? Right. And then we have 2 5-membered ring. Am I clear? And we have 2 5-membered ring. Am I clear, beta ji? So DMG is clear to you all. Is DMG is clear to you all. Dimethyl glyoxime is clear to you all, everyone. Yes or no? Yes or no? Is DMG clear to you all, everyone? Boliye, is it clear? Yes or no? Clear or not? Clear? Right, a bit complicated but easy topic, right? A bit complicated but easy topic. Okay, right, so this is basically the structure of DFG, which you can see right here. This is basically the structure of DFG, which you can see right here. I hope I made my point really clear to you all, everyone. Right? Is it clear to you all, everyone? Clear? Okay. So, the overall charge is -1 and the IUPAC name is dimethyl glyoxymato. Next we have is EDTA, which is ethylene diamine tetraacetate beta, ethylene diamine tetraacetate. Now, if I talk about ethylene diamine tetraacetate, I have already told you the structure of EDTA, everyone. Can you tell me the structure of EDTA beta? It's very simple. I have CH2, single bond CH2, then I have nitrogen. Then I have CH2, CO negative, CH2, CO negative, CH2, CO negative and CH2, CO negative. So, the overall charge is -4, right? And this ion is basically ethylene diamine tetraacetate ion and the IUPAC name will be ethylene diamine tetraacetato. Okay, it will be ethylene diamine tetraacetato. Is the name of the ligand clear to you all, everyone? Yes. Is the name of the ligand clear to you all? Yes. Is the name of the ligand clear to you all? EDTA. Clear? Okay. Now beta, this is a little complicated part, but after this part I will give you a break, right? But after this part I will give you a break. Now here I have completed all the negatively charged ligands, so I will give you a break. So I am giving you a break. Then I think I can teach one complicated topic before the break. Right, am I clear? If I am giving you a break, I can teach one complicated topic or I should teach it after the break. You tell me. I should teach it right now or I should teach it after the break. You tell me. Yes. But you have to promise me that you have to come back after the break. Now there are 75 students. I want after the break a total of 75 students back. Some of you are saying now, some of you are saying after break. Now. So I can see majority of now. So let's do it before break. So after this, all the negatively charged ligands are finished, right? Okay, so talking about ethylene diamine tetraacetate, which is EDTA, I have already told you beta, EDTA, right? Okay, EDTA. Fine. Now here EDTA is a hexadentate ligand beta. If I have to talk about number of donor atoms, then it has 6 donor atoms. Okay, it has 6 donor atoms. We have 2 nitrogen donor atom plus 4 oxygen donor atom. Now what happens beta? What happens that whenever we have a hexadentate ligand such as EDTA, right, it can form 6 coordinate bonds simultaneously. It can form 6 coordinate bonds simultaneously with a single metal atom. Am I clear? It can form, beta, I will teach in 5 minutes and I'll go and give you a break. Yeah, let's just complete it. Till 8:15 you will have your break, beta. I'll give you a 25 minutes long break, beta. What else do you want? I will meet you at 8:45. Right? So please be enthusiastic, yeah. Let's just do it. Please. I don't want a break. Okay. Now, listen to me, beta. EDTA is said to have 6 donor atoms, right? EDTA is said to have 6 donor atoms. Now, these 6 donor atoms can simultaneously form 6 coordinate bond, right? And these 6 donor atoms can arrange themselves around the central metal atom or the central metal ion in an octahedral geometry. How? In an octahedral geometry. Now, please, I want your full attention right here. Otherwise, you won't be able to understand. Please, full attention right here. Okay, full attention right here. Now, see, beta, see. Here, this is the central metal atom. Okay, this is the first oxygen of EDTA, which is nothing but CH. See, I have told you the structure of EDTA. It is like this. Bacha, see, you have to remember it first. CH2. You have this nitrogen, then you have 4 CH2CO negative, right? Again you have CH2CO negative and CH2COO negative. Yes or no, beta? You have 4 CH2CO negative. Yes or no? Yes ma'am. Right. Okay, so I have 2 donor nitrogen atom and 2 donor nitrogen atom and 4 donor oxygen atom. Now here this oxygen Beta, this oxygen is basically present on the carbon now, which is said to have a double bond. Now this is basically acting as a donor now, right? So this is the same oxygen. Can you see? Can you see it? Can you visualize it, beta? This is the carbon, this is the CH2 group, and the CH2 group is basically attached to nitrogen. Am I clear? And this nitrogen is itself acting as a donor. Okay, it is itself acting as a donor. Am I clear, everyone? Am I clear, everyone? Clear or not? Clear? Similarly, here I have another nitrogen. See, here I have another nitrogen. Suppose this is a nitrogen. Now this is attached to another CH2 group, which is attached to double bond O carbon, which is attached to oxygen. And this oxygen is again coordinated to this, right? Right. So I have explained you 4-1. Okay. Now beta, this nitrogen is also attached to one CH2CO group, and this nitrogen is also attached to one CH2CO group. So this is basically CH2COO negative 1, which is again coordinated, and this group is CH2C double bond O negative, which is again coordinated. Now is this structure clear to you all? Is this structure clear to you all? Yes or no? Is it clear, beta? Right? Is it clear or not? Clear. Right? Now here all the 6 donor atoms have been arranged themselves in an octahedral geometry. They have arranged themselves in an octahedral geometry. Now what happens, bacha? What happens that here we have 5 rings. Okay. Now one is this ring, beta, one is this ring. This is first ring. This is second ring. Okay. And this is the third ring. Am I clear? Now these 3 rings, they are basically present in same plane. Right? This ring and this ring, they are present in the same plane. Okay, they are present in the same plane. Am I clear, beta? They are present in the same plane. Am I clear or not, beta? They are present in the same plane. Right? They are present in the same plane. That means if you have this plane, now all the 3 rings will be lying in this plane, right? For example, this notebook is a plane. I am keeping it right here. I am keeping it right here. Now these 3 rings are present in the same plane. Am I clear, everyone? Yes, am I clear or not? Am I clear? Okay, right. And there are 2 rings. One is above this plane and one is below this plane. There are 3 rings which are present in the same plane. One ring is present above the plane and one ring is present below the plane. Am I clear, everyone? Right. So we have non-coplanar rings which are present, and we have total of 5 rings, out of which 3 are present in one plane and 2 are present in the another plane. Is this point clear to my lovely students or not? Please quickly tell me in the chat box. Yes. Is this point clear to you all or not? Yes. Is this point clear to you all or not? Clear, everyone? Clear? Okay, now here each ring is 5 membered. You can count, beta. This is 1, okay, this is 2, 3, 4 and 5. That means each ring is 5 membered. Each ring is 5 membered. Okay, each ring is 5 membered. Right, fine. Each ring is 5 membered. Am I clear, everyone? Each ring is 5 membered. Is this point clear to you all, everyone? Is this point clear to you all, everyone? Right, okay, so we have 5 membered ring, out of which 3 are present in one plane and 2 is present in one plane. Now here in this particular compound, can you see a plane of symmetry? I cannot see a plane of symmetry, and if plane of symmetry is not present, then this compound is definitely optically active. Okay, why this compound is optically active? Because there is no plane of symmetry. Am I clear? There is no plane of symmetry. That is why this particular compound is said to be optically active. Am I clear? This compound is said to be optically active. Why? Because there is no plane of symmetry which is present right here. Okay, ji. Right. Now here there are 2 applications. One application is calcium EDTA complex is used to remove lead poisoning. Now what happens then if in our blood there is lead poisoning? So we use calcium EDTA complex. Now what happens, beta? Here lead replaces calcium in this particular complex and form a complex with EDTA itself. That means instead of calcium here lead comes, and this is basically bacha not soluble in the blood, so it gets excrete out from the kidney in form of urine. Am I clear, everyone? Okay, it basically gets excrete out from the blood in form of what, beta? In form of urine. Am I clear? Okay. And the other application beta, that EDTA is used to estimate water hardness. Now we know that hard water is said to consist of calcium 2 plus and magnesium 2 plus ion. So if we will use sodium EDTA complex, beta, calcium and magnesium can replace sodium from the sodium EDTA complex. Now this reaction is basically used to estimate the hardness of water. Earlier when we used to have the chapter hydrogen, we used to do this, but now we just have to remember that it is an application. That's it. Am I clear, everyone? Yes, am I clear, everyone? Clear or not? Clear? Okay, so here we have completed all the negatively charged ligands. Now we are having a break, a lunch break, or I should say a dinner break. For me it is a lunch break because I didn't had my lunch. So for you it is a dinner break and it is of approximately 25 minutes. Okay, so we will meet after 25 minutes. So enjoy your life for 25 minutes. See you all in coming 25 minutes. Am I clear? And I want 61 students right here. All 61 should be present. Ma'am, 40 minutes. See, we can have 25 minutes to 30 minutes. I guess that's enough, beta. Okay, 25 to 30 minutes are enough, yaar. I don't think more than that is required. Fine. Okay, am I clear? 25 to 30 minutes is fine. So, I will meet you approximately at 8:45. Not earlier than that. Okay, I will meet you at 8:45. Okay, meet you at 8:45. Fine, meet you at 8:45. Fine, I want you all here at 8:45. Am I clear, everyone? Fine. So enjoy your break. Enjoy your break. We'll meet you at 8:45 and that's enough. 30 minutes are enough. I want all of you to be present here till 8:45. Okay? Fine. Mm. टेम्परेचर सही रखना सो Hi everyone, so we are back. Hi everyone, so we are back. Let me just ask everyone to rejoin on the group. Okay, so I've asked everyone to rejoin again. I hope you guys are back, right? I want a lot of green hearts for giving a huge morale to you guys. I didn't have dinner because I didn't feel like. I think I'll have dinner in the next break, which I'll give you at 11 or 11:15. So I don't want to had a dinner, so I didn't had it, right? Now all of you, please rejoin as soon as possible, as quickly as possible, right? Ask your friends to join as quickly as possible, right? I have put a message on the group and asked them to rejoin it fast, okay? So yeah, okay, fine everyone. So now let's just start this session again. So before going on the break, we have completed all the ligands which are said to be negatively charged. Now we will come to the ligands which are neutral in nature. Am I clear? Now we will come to the ligands which are neutral in nature. Now neutral ligands means beta, they are said to have a zero charge. They are said to have no charge, right? For example, if I talk about methylamine, right? I have CH3NH2, right? Now this ligand do not have any charge, bacha. If I talk about ammonia, NH3, it also do not have any charge, bacha, right? So these are basically neutral ligands. Now neutral ligands do not have any special ending. Am I clear? Whenever you will write the name of neutral ligands as per IUPAC, they do not have any specific ending. Am I clear, Rajay? So what you will add to your notes, that neutral ligands, right, in the form of note, neutral ligands, okay, neutral ligands have no special ending. Am I clear? Neutral ligands have no special ending. Am I clear everyone? Neutral ligands have no special ending at the end of their name, right? You can write it as such. Now, talking about the very first neutral ligand, beta, the very first neutral ligand is basically CH3NH2, right? Here nitrogen acts as a donor atom. It is a unidentate ligand, charge is 0 and IUPAC name is methylamine, right? Next we have is basically, bacha, is your NH3, okay, NH3. Now NH3 is ammonia, right? Its charge is 0. It is a neutral ligand. However, in IUPAC we use the name amine for ammonia. Am I clear, beta? In IUPAC we use the word amine for ammonia. Is it clear to you all, everyone? Okay. Then we have H2O. H2O is basically your water, right? It is said to have a zero charge, and in IUPAC either we say it aqua or aquo. Both are acceptable, right? Either you can use aqua, either you can use aquo. Then we have is NO, bacha. NO is nitrosyl, charge is 0. Then we have CO, carbonyl, and then we have, bacha, phosphine. Now phosphine is basically pH 3. Right, phosphine is basically pH 3. We all have seen NH3, right? So NH3 is a hydride of nitrogen. pH 3 is a hydride of phosphorus. Okay, so pH 3 is a hydride of phosphorus. The name is phosphine. Am I clear, everyone? Fine. Now here, bacha, see, if I talk about benzene, right, you must have studied in IUPAC that in benzene, Rajay, each carbon is said to have one hydrogen, right? In benzene, each carbon is said to have one hydrogen. So here we have one hydrogen, here we have one hydrogen, here we have one hydrogen, one hydrogen, one hydrogen, and one hydrogen. This is basically benzene. Am I clear, everyone? Now, if this benzene basically loses its one hydrogen, right, if its benzene loses its one hydrogen as H plus, bacha, right, it loses its one hydrogen as H plus, right, fine. Now this results into the formation of phenyl. Okay, this results in the formation of phenyl. This is basically known as phenyl. Am I clear? Now phenyl has basically a formula C6H5, right? Benzene has a formula C6H6, however phenyl has a formula C6H5, right? Now like phosphine, we have triphenyl phosphine. Now what happens if the 3 hydrogens of the phosphorus is replaced by phenyl ring? Then there occurs the formation of another neutral ligand. This is triphenyl phosphine. Am I clear everyone? Right, am I clear everyone? Fine. So here I have the another ligand which is again a neutral ligand. The name of this ligand is basically triphenyl phosphine. So it is phosphorus, one phenyl ring bacha, okay. This is another phenyl ring and this is another phenyl ring, okay. This is basically triphenyl phosphine. Am I clear everyone? Now next is basically pyridine, okay. Next is basically pyridine. It's very simple. The way you draw benzene, the way you draw pyridine, you just have to replace one carbon with nitrogen, right? So here if I replace one carbon with nitrogen, this results into the formation of pyridine, okay. This is basically the structure of pyridine. Now pyridine is basically represented as py bacha. First of all, it is represented as py, right, or it is written as C5H5N, okay, and it is basically represented as py. Like for example, ethylene diamine is represented as En, pyridine is basically represented as py, okay, right. Now next is basically ethylene diamine. It is a bidentate ligand, we have already did it. It is CH2, CH2, NH2, NH2, right. It is a bidentate ligand, that means contains two donor nitrogen atom. Either you can use the IUPAC name ethylene diamine, right, or you can even use the IUPAC name as ethane 1,2-diamine, okay. You can even use this IUPAC name. Is it okay everyone? Is it okay? Right, you can use this IUPAC name as well. Now let's move ahead bacha. Let's move to some other neutral ligands which are little complicated, right. These are not given in NCERT, however they can ask question from this, and this is not given in the NCERT, but it is important, okay. The very first is basically propylene diamine, or the name of this ligand is also propane 1,2-diamine, right, propane 1,2-diamine, and it is basically represented by the symbol Pn. How we write it? See, it's very simple. We know that propane basically consists of 3 carbon, and as per the name it has amine, that is NH2 group, at second position and at third position bacha, right. So this is CH2, this is CH, and this is CH3. Am I clear? So this is basically Pn, okay. This is basically Pn, or we can say propylene diamine, okay. It is also a neutral ligand, right. Propylene diamine, it is represented by a symbol Pn. Now if I talk about the number of donor atom beta, you can easily see that here we have 2 donor atoms. Both the donor atoms are nitrogen. Now these can coordinate simultaneously with a central metal atom or a central metal ion in the coordination complex. Yes or no? Yes or no? Ma'am, yes, pyridine is said to have one lone pair of electron. However, that lone pair of electron do not participate in resonance. Somebody if have told you GOC, that person would have definitely told you this thing, okay. The case of pyridine and pyrrole. Fine. Now bacha, here if I just look at into this particular structure, how many membered ring I can see bacha? I can see 1, I can see 2, I can see 3, 4 and 5. That means here 5 membered ring is being formed, right, and I have here 2 donor atom, that means it is a bidentate ligand, and here the 2 donor atoms are basically 2 nitrogen atoms. Am I clear everyone? Am I clear everyone? So here I am drawing the structure of some important neutral ligands. What I am doing right here, I am drawing the structure of some important neutral ligands. Fine, okay, fine. Now let's move to the another important neutral ligand. It is basically trimethylene diamine, or the other name of this particular ligand is propane 1,3-diamine. See, it's very simple. You know that propane basically consists of 3 carbons, right. It has amine, that is NH2 on first carbon and on the third carbon. That is why we are adding 1,3 right here. Am I clear? This is CH2 bacha, this is CH2, and this is again CH2. So this is basically the structure of this particular ligand, right. It is a neutral ligand, fine, and the name is either trimethylene diamine. You can see 3 methylene group right here. Methylene stands for CH2, right. Methylene stands for CH2. So you can see 3 CH2 or methylene group right here. Fine. 3 CH2 or methylene groups right here. And here we have 2 donor atoms, 2 donor nitrogen atoms, which can simultaneously form with a central metal atom. So this basically results in the formation of how many membered ring, bacha? How many membered ring? I guess it's very simple. It results into the formation of a 6 membered ring, right? It results into the formation of 6, madam. Madam, can you please send the notes here? I always upload notes on my Telegram channel as well as on our Telegram channel, which is Unacademy NEET English. Why such questions, yaar? I think now we all have got the habit, right? We all have got the habit. But I will give you the notes only when the number is maintained. I can say 60 students till the end of this marathon. Then only I'll give you the notes. Okay, right. Now let's just move ahead. Fine. Now the another ligand we have right here is bacha butylene diamine. Okay, butylene diamine or butane 2,3 diamine. Okay, butane 2,3 diamine. See, butane is said to consist of 4 carbon, bacha, right? And we have amine on second carbon and on third carbon. Okay, if this is first, this is second, this is third, this is fourth. So we have amine on second carbon as well as on third carbon. Am I clear, everyone? Yes, am I clear? Okay, right. Now here what you have to do, you just have to satisfy the valency. It is CH3, it is CH3, right? Now here it has 2 donor nitrogen atom. That means it is a bidentate ligand. It is basically in short known as BN. Okay, in short it is basically known as BN. And if I have to find the number of rings, right, the member of the rings or the number of members which are present in the ring, bacha, see, it is a metal. It is a metal. It can coordinate simultaneously to through donor nitrogen atom, everyone. Yes or no? Right. So here what I can see, beta, here we have 1, 2, 3, 4 and 5. I have a 5 membered ring which is formed right here. Okay, I have a 5 membered ring which is formed right here. Okay, everyone, fine. Let's just move ahead to the another ligand. It is basically diethylene triamine. That means you have diethyl. Ethyl stands for bacha CH2 group, CH2 group. Okay, CH2 group. Okay, so here we have 2 CH2 group, one CH2 group, right? I have another CH2 groups. Okay, so it is basically saying I have diethylene groups and I have 3 amines. Okay, I have 3 amines. Now 3 amines means 1 NH. It is basically a secondary amine. Okay, here I have the another NH2. Here I have the another NH2. Okay, so if I ask you, this is basically your diethylene triamine, okay, which is basically known as di-en, First of all, tell me how many donor atoms are present here. Quickly tell me how many donor atoms are present right here, beta. 1, 2, 3. I have 3 donor atoms right here, bacha. I have 3 donor atoms right here, bacha. Okay, I have 3 donor atoms right here. Am I correct or not? 3 donor atoms are present, bacha. First of all, yes. And now tell me how many rings are possible, beta. How many rings are possible? See, bacha, I have one metal, right? Now this metal can coordinate through this particular nitrogen. It can coordinate through this particular nitrogen. It can also coordinate through this particular nitrogen. That means that 2 rings are formed. How many rings are formed? 2 rings are formed. And if I have to find number of member in each particular ring, right? If I have to find the number of members in each particular ring, beta, some of you are correct, some of you are wrong, some of you are saying 3, some of you are saying 2. So here we will form 2 rings. How many rings? 2 rings are formed, beta. 2 rings are formed. What is the denticity of these ligands, beta? Denticity is 3, na? Right? It has 3 donor atoms, right? 3 donor nitrogen atoms, bacha, right? And if I have to find number of member in each particular ring, bacha, it is 1, 2, 3, 4 and 5. Okay, so it is also a 5 membered ring and it is also a 5 membered ring. Am I clear? Yes, absolutely correct. Many of you are saying it correct, many of you are saying it wrong. Doesn't matter. Next we have is basically, bacha, tri-en, which is triethylene tetramine. Now triethylene means you have 3 CH2, bacha, right? Suppose here I have first CH2, okay, here I have first CH2, here I have second CH2, here I have third CH2. Am I clear, everyone? Here I have 3 CH2. Is it clear to you all, everyone? Okay, right. Now here I basically have Tetraamine. Okay, here I have tetraamine. See, one NH can be drawn right here, one NH can be drawn right here, right? And similarly, we have two primary NH2 groups which can also drawn right here. Am I clear? If I have one central metal atom, okay, let's keep a central metal atom right here. Now tell me how many rings can be formed. Quickly tell me how many rings can be formed. Yes, everyone. Quickly tell me how many rings can be formed right here. Yes, how many rings can be formed? But according to me, I can see 3 rings, right? According to me, I can see 3 rings. See, this nitrogen can coordinate to this metal, this nitrogen can coordinate to this metal, this nitrogen as well as this nitrogen, right, bacha? Fine. So they can form these coordinates bond, right? There are 4 donor atoms. That means denticity is 4, right? That means we have 4 donor nitrogen atoms. We have 4 donor nitrogen atoms, right? So there are 3 rings which are formed. And if I asked you to find the number of members in each ring, okay, if I asked you to find the number of members in each ring, bacha, then see 1, 2, 3, 4, 5. Okay, so this is basically a 5-membered ring. Similarly, you can count this as well. This is also 5-membered. You can count this as well. This is also 5-membered. Am I clear? So here 3 5-membered rings are basically formed. Clear? Right? So here we have completed all the neutral ligands. This was the last, which is basically known as tri-en, last, okay, last ligand, neutral ligand. Now let's proceed to the positively charged ligand, or I should say the cationic ligands, beta. Okay. Now see, I have told you that negatively charged ligands end with what, beta? Ends with what? Ends with what? How the negative charged ligands? They used to end with O. Neutral ligands do not have any special ending. If I talk about positively charged ligand, or I should say if I talk about cationic ligands, right? If I talk about what, bacha? Cationic ligands. Now, cationic ligands are said to have a special ending of EM, right? That means at end of the name of the cationic ligands in IUPAC, we add a word EM. Am I clear? Okay. So here if I have to write the name of certain cationic ligands, the very first ligand is, bacha, hydrazinium, which I have already told you how it is formed. Okay, this is hydrazinium, right? The next is nitrosonium, which is NO+, and the third is nitronium, which is NO2+. Okay, these are the 3 positively charged ligands which we will basically see in the entire IUPAC, and that is also very rare. NCERT does not have even said that ligand can be positive. That is some extra knowledge which I am giving you. According to NCERT, we can have only negatively charged ligand as well as neutral ligand. Am I clear, everyone? Fine. So here we have completed the list of the entire ligands. Now let's come to IUPAC nomenclature. Okay, quickly I will explain. Be attentive. If you will be attentive, I swear, you know, after this class, you will be pro in writing the IUPAC name of any coordination compound. Am I clear, everyone? If you will be consistent, if you listen each and every word of mine, you will be pro. Right. Now, let's come to the next topic, which is a nomenclature of coordination compounds. Okay, this is the last topic, nomenclature of coordination compounds. Okay, see, there is a, you know, IUPAC, right? IUPAC is International Union of Pure and Applied Chemistry. Now, IUPAC have given certain recommendations, certain rules, and based on those rules, we basically name all the coordination compounds. This is the very first point of NCERT, right? That based on recommendations of International Union of Pure and Applied Chemistry, that is IUPAC, we have certain rules according to which we name a particular compound. Okay, now if I ask you a question that you have to name this particular salt, quickly tell me in the chat box what name you will give to this particular compound. Yes, quickly tell me in the chat box what name you will give to this particular compound. Yes, everyone, what name you will give to this particular compound. Yes, everyone, yes, quickly tell me in the chat box. I guess you will say, ma'am, this is NaCl, we say it's sodium chloride. Okay, we say it's sodium chloride. That means in naming of a particular salt, you are first naming the cation of the salt, which is sodium, and then you are naming the anion of the salt, which is chloride. Right, you're doing the same. You're first naming the cation and then you're naming the anion. Now, coordination complexes are also salt, beta. Right, they're also complex salt, or I should say they're addition salts. Yes or no? Fine. So here also, when you have to name them, I'm talking about mononuclear coordination complexes. Mononuclear coordination complexes means the coordination complexes which have only one central atom. Okay. First, let me be very clear. I am just talking about what, bata? I am talking about mononuclear coordination complexes, right? So in mononuclear coordination complexes, that means the coordination complexes which have only one central metal atom or only one central metal ion. In these particular coordination complexes, bacha, we first have to name the cation, the positive ion, right? Doesn't matter whether the cation is simple, whether the cation is complex. First we have to name the cation and then we have to name the anion. Am I clear, everyone? Okay. Now what do you mean by, ma'am, simple and complex cation? And ma'am, what do you mean by simple and complex negative ion or anion? Bacha, you guys know this thing. Okay. You guys know this thing. For example, okay, if I have CO, Cl3, NH3, okay, NH3, CO, Cl, NH3 whole thrice. Okay, I have CO, Cl, NH3 whole thrice. So let me make it very simple for you guys. Let's not just complicate it. Suppose it is CONH3 whole 6. Okay, CONH3 whole 6 Cl3. Right. Now please tell me what is the cation in this particular compound, beta? It is CONH3 whole 6 3 plus. It is a cationic complex. Right. First we write cation, then we write anion. That means here cation is complex and anion is simple. Am I clear, everyone? Fine. Here, what is the thing, beta? Here cation is complex. Okay. Here cation is complex. Right. Bacha, am I clear? And the anion is simple. Right. So it doesn't matter whether the cation is complex. You first have to name the cation. Am I clear? You first have to name the cation. It doesn't matter it is complex. You first have to name the cation and then you have to name the anion. Am I clear? Okay. Similarly, if you have Na3AlF6, okay, Na3AlF6. So beta, here we can see it is an anionic complex because the anion is complex, right? Here the cation is simple but the anion is complex. Again, doesn't matter, here the cation is simple. That means Na plus is a simple cation. First you have to name the cation and then you have to name the complex anion. Am I clear, everyone? Yes. Am I clear, everyone? Ma'am, I am getting confused. Beta, give me a second. Let me complete all the rules. You will get to understand. You will get to understand. Okay. Here the cation is simple. Right. Here the cation is simple and the anion is complex, right? Here the cation is simple. Okay, here the cation is simple and anion is complex. Okay, and anion is complex. But you have to be patient. You have to listen to each and every rule. Then only at end of it you will be able to give the IUPAC. Am I clear, everyone? Fine. Now listen, what I am trying to say, beta, this is a complex in which cation is complex, anion is simple. Fine. This is the complex in which cation is simple and the anion is complex. Doesn't matter whether the cation is complex or cation is simple. While writing the IUPAC name, you first have to name the cation, then you have to name the anion. Am I clear, everyone? Okay, right. Now, whenever you are naming a ligand, first of all, we always name the ligand in alphabetical order. For example, if this complex basically consists of NH3, for NH3 we use amine. Right, and here suppose inside the coordination sphere we have Cl, chlorine also, then alphabetically we know that A comes before Cl, right? So first we will write amine and then we will write chloro or chlorido. Am I clear? Okay, so we have to name all the ligands which are present inside the coordination sphere in alphabetical order. You have to keep these things in your mind. Okay, right? You now are just reading the rules, beta. We will apply in coming 10 minutes. We will apply in coming 10 minutes. You have to wait. You have to wait. You have to wait. Am I clear, everyone? Okay, right. Now, whenever you name anionic ligand, they ends with O. Okay, cationic ligands, they end with EM, and neutral ligands have no special ending. I have already told you. Am I clear, everyone? Fine. Now, whenever you are just naming the complex part, right, you are naming the ligand, and suppose the number has to be indicated for the ligands. For example, here you have basically 6 NH3, right? You want to indicate that how many NH3 are present in the name. Am I clear, everyone? Right. So in these particular cases, we use the prefixes to indicate the number. For example, if 2 ligands are present, similar ligands, suppose 2 NH3 are present, then we use the prefix di. If 3, we use the prefix tri. If 4, we use the prefix tetra. If 5, we use the prefix penta. If 6, we use the prefix hexa, right? Fine. So whenever we have to indicate the number of ligands, beta, we have to indicate the number of ligands, bacha, right? Fine. If I have to look at the number of ligands, bacha, then in that particular case, mera bacha, we have to indicate the number with the help of prefix. Am I clear, everyone? Okay, right. So what I am saying, the prefix like di, tri, penta, hexa basically indicates the number of ligands. They indicates the number of ligands. Am I clear, everyone? Am I clear, everyone? Somebody is saying, ma'am, the quality of the video is low. That is why I am not able to focus. Beta, see, whatever resources are provided to me, I am just, making it happen. I am teaching you from my heart with full energy and everything, right? And I think the quality is okay. It is something that we can adjust and we can study. It's perfectly fine. I guess according to me, it's perfect. Not that great, not that bad, right? So you have to, focus, Teju. You have to focus. That is the only thing you can do. Am I clear, Teju? Focus, beta, focus. Fine, right? Okay. Now, beta, see, there are certain ligands in which the name itself includes di, tri. Okay. For example, we have EN. We have EN, right? So EN is basically ethylene diamine, right? It is basically ethylene diamine. So it itself includes di. Okay, itself includes di, right? Then we have PH3. I have told you triphenyl phosphine, PH stands for phenyl, beta. I have told you triphenyl phosphine in which 3 hydrogen of the phosphine has been replaced by the phenyl ring. Yes or no, everyone? Yes or no, everyone? Yes or no, everyone? Yes. Okay. So if I talk about triphenyl phosphine, okay, triphenyl phosphine. Am I clear? Triphenyl phosphine. Now it itself contains the prefix tri. Right. So whenever we have to indicate the number of the ligand which themselves consist of the words like di, tri, then in these particular cases we cannot indicate the number by using the prefix di, tri, tetra, penta, hexa. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Clear? Right. Okay. So what we will use, beta? What we will use? For these ligands, we use another prefixes. For example, if we have di, okay, we have 2 ligands. So instead of di, we use bis. Okay. If we have 3 ligands, then instead of tri, we use tris. And then something which gives you a huge laughter that, ma'am, I have 4 kisses from you. So I gave you 4 kisses, right? So if there are 4 ligands, instead of tetra, we use tetra kiss. This is actually, I don't know, immense happiness this gives to students. I don't know why, but anyways, whenever we have 5, similar ligands, instead of penta, we basically use, beta, what? We use pentakis. If we have 6 similar ligands, and instead of hexa, okay, instead of hexa, bacha, we basically use hexakis. Now somebody is asking, ma'am, what does it means includes a name? See, bacha, if I write ethylene diamine, if you have 2 EN, okay, so you can't use diethylene diamine. Why? Because ethylene diamine itself contains di. So instead of that, you need to use, instead of di, you need to use bis. Okay, so you have to write bis ethylene diamine, and that also, beta, you have to put it in the bracket. For example, if you have EN2, okay, so you have 2 ethylene diamine. So first you will write bis. Okay, first you will write bis, then after bis you will write a bracket, and inside that bracket you will write ethylene diamine. Okay, ethylene diamine. Am I clear? And then you will close the bracket. Am I clear, everyone? Yes. Am I clear, everyone? Clear? 100% clear? Okay, right. Now let's just move ahead, beta. While naming the coordination compound, we always have to indicate the oxidation state of central metal atom and central metal ion. And when I have started this lecture and I have told you how to find the oxidation state, beta, I have told you that while giving the IUPAC name of the coordination compound, you have to mention the oxidation state, and that oxidation state is basically written in Roman numerals, right? Do you remember that when you used to be in a class first, suppose first A, first B, then outside your class they used to write first in Roman numeral, right? For second they used to use a Roman numeral this, Am I clear, everyone? So in a similar way, if you have to indicate the oxidation number of the central metal atom or the central metal ion, we use Roman numeral, right? For example, if the oxidation state of the central metal atom comes out to be +1, so here the Roman numeral, okay? Here the Roman numeral, here the Roman numeral, am I clear? Here the Roman numeral is written in a parenthesis, that is bracket, which is 1. Am I clear? So after the metal, you will write Roman numeral 1 in the bracket, which will indicate that the oxidation state of the metal is +1. Am I clear, everyone? Okay. So if the oxidation state of the metal is +2, then in Roman numeral you have to write 2. Right? If the oxidation state of the metal is +3, then in Roman numeral you have to write 3. Am I clear? Okay. If the oxidation state of metal is +4, then in Roman numeral you have to write 4. If it is +5, then you have to write in Roman numeral 5. Am I clear, bacha? Am I clear? Right. Okay. Is it clear to you all, everyone? Clear? Right? So here we indicate the oxidation state in Roman numeral. Okay, ji. Now let's come to the last rule. After this rule, I will teach you how to write the name and you will understand it even. Don't worry. Okay. So this rule basically states that whenever we name the complex ion, okay, whenever we name the complex ion, for example, here, if I take these two examples, in the very first example, the complex part is the cationic part. And in the second part, the complex part is anionic part, right? So how we have to name the complex part, beta, right? How we have to name the complex part? See, beta, see. First of all, whenever you name the complex part, okay, whenever you name the complex part, you have to follow a order, okay, you have to follow the order. For example, you have this particular complex, CONH3 whole 6 Cl3. This is basically a cationic complex, okay. So here, as per the rules, first we have to name the complex cation and then we have to name the complex anion, okay. So here the cation is complex. So while naming this complex cation, you have to follow a simple rule, and the rule is, bacha, first you have to name all the ligands in alphabetical order, indicate their number by using the prefix di, tri, tetra, right? Fine, you will use that prefixes, and then you will name the metal ion, okay, then you will name the metal ion, right? And the ending of the metal ion, right, in the complex, the ending of the metal ion, beta, it basically depends, okay, it basically depends on what, beta? It depends that whether it is a cationic complex or an anionic complex. Am I clear? Okay, if it is a cationic complex or a neutral complex, then metal name has no special ending, right? However, if the complex is anionic complex, then name of the metal ends with 8. Oh my god, ma'am, I am getting goosebumps. What you are saying? Please tell me an example. See, first of all, beta, I will take this complex only. I will take this complex only. Quickly tell me in the chat box, is it a cationic complex or an anionic complex? Is the cation complex or simple? Quickly tell me in the chat box, everyone. Yes, quickly tell me in the chat box. I will provide the summary, beta, don't worry. After these examples, you don't need any summary. Quickly tell me, everyone. Yes, quickly tell me. Cationic complex. It is a cationic complex. Absolutely correct. While naming the coordination compound, I have told you the very first rule is you have to name the cation, whether simple, whether complex. And here we have a cation complex, and cation is the complex part. And in naming the complex part, I have told you, first you have to name the ligands, then you have to name the metal. Now tell me which ligands are present right here. NH3. NH3 is a neutral ligand, and I have told you the IUPAC name for NH3 is basically amine, okay. And how many NH3 are present right here, beta? 6, right? So first I will write the name of ligands, which are hexaamine. Now please make this thing write somewhere that here in amine we have 2 M's. Here in amine we have 2 M's. Please make sure to write it somewhere, beta. Please make sure to write it somewhere that in this amine we basically have 2 M's, okay. We basically have 2 M's. Am I clear, everyone? Yes, am I clear, everyone? Clear? Okay, right. Now, beta, I have told you while naming the complex part, first we have to name the ligand and then we have to name the metal. We have indicated the number of ligands and we have named the ligands. Now come to the metal. Now, metal is cobalt. Metal is cobalt. Now, this particular complex is cationic complex and I have told you in the case of cationic complex, metal have no special ending. Am I clear? Metal have no special ending, right? That means here you just have to write in continuous hexa, amine, cobalt. Clear? And after writing the name of the metal, you have to write the oxidation state of metal in Roman numeral. Am I clear, beta? You have to write the oxidation state of metal in Roman numeral. Now, what is the oxidation state of metal, beta? You can find out by X method. Suppose it is X. Here we basically have 6 NH3 and we have 3 Cl. Okay, so X minus 3 equals to 0 or X is basically equals to plus 3. That means oxidation state of cobalt is plus 3 right here. So in Roman numerals you will write 3, right? Now you have written the name of complex cation. Now you have to name the anion. If it is NaCl, you write sodium chloride. Right, you write sodium chloride, and here also beta ligand is Cl, right? So you will use the word chloride right here, leave a space and write chloride. It is the name of this particular complex. Am I clear, everyone? Yes, am I clear, everyone? Now say, do we need any summary? Do we need any summary? Yes or no, everyone? Do we need any summary? I don't think we need any summary, beta. I don't think we need any summary, right? Chalo, let's come to another complex. It is Na3 ALF6. Okay, Na3 ALF6. Now, listen to me once, beta, listen to me once. Now, listen, beta, here, quickly tell me, this is an anionic complex or a cationic complex? Quickly tell me, is it a cationic complex or an anionic complex? Quickly tell me, yes, cationic complex or anionic complex? Yes, cationic complex or anionic complex? Quickly tell me in the chat box, everyone. Yes. Is it a cationic or an anionic complex? No, we don't say trichloride, beta. If you write AlCl3, what is the name of this particular compound, beta? What is the name of this particular compound, beta? Aluminium chloride? Do you say aluminium trichloride? No, you say aluminium chloride. Basic inorganic chemistry. Am I clear? We don't use trichloride right here. Okay, everyone, this is an anionic complex, beta. I have told you, doesn't matter whether cationic complex, whether an anionic complex. First, we have to name the cation. And what is the cation right here, beta? Sodium. What is the cation right here, beta? Sodium. It is a simple cation. So first we will write sodium, right? Now we will leave a space and now we will name the complex anion. Now this is a complex written in the square bracket. Same rule we will apply. First we will name the ligands in alphabetical order, indicating their prefixes. Then we will name the metal ion. So here we have 6 fluorines, and for fluorine I told you earlier, beta, that either we use the IUPAC name fluoro or florido. It's your choice. Either you use fluoro, either you use florido. Your choice. I am using fluoro. So here I will write hexafluoro. Okay. Here I will write hexafluoro. Am I clear? Hexafluoro. Then I have to write the name of metal. But I have told you, beta, that in the case of anionic complex, the name of the metal ends with 8. That means you need to add the word 8 after the name of the metal, right? For example, the name of the metal right here is aluminium, right? The name of the metal right here is aluminium. So you will add the word 8. So it will be aluminate. Okay, it will be aluminate. Am I clear, everyone? Okay, right. The naming is done, but one thing is left, that here also you have to indicate the oxidation state of the metal with the help of our Roman numeral. Here also you have to indicate the oxidation state of the metal with the help of our Roman numeral. Now what is the Roman numeral, beta? Tell me, quickly tell me. What is the oxidation state? See, it's very simple. Let it be X. We have 3 sodium. Right, each is said to have a +1 oxidation state, because alkali metal, irrespective of the fact, wherever they are present in any compound, the oxidation state is +1. Okay, so 3 into +1 plus X is the oxidation state of aluminium. We have 6 fluorine, each is said to have a charge of -1 equals to 0. So from here X minus 6 plus 3 comes out to be 0, and from here X comes out to be +3. So here the Roman numeral is 3, which is used. Am I clear, everyone? Am I clear, everyone? Now tell me, is it simple or is it complex? Yes. Simple or complex? Simple, everyone? Now tell me, do I really need to do any summary? No summary is required, beta. That is why I always say, listen to me, listen to me. I always give googly in the end. Okay, right. Now, beta, I have told you that in the case of anionic complex, right, in case of anionic complex, metals always have a special ending. Right. For example, when aluminium was present in the anionic complex, I have used the word aluminate. Similarly, for different metals, I have different names in the anionic complex. Okay. For example, if I have cobalt, then the name is cobaltate. Nickel, it is nickelate. Chromium, it is chromate. For iron, it is little different, right? It is ferrate. For copper, again, it is a little different, cuprate. For silver, again, it is little different, it is argenate. Okay, it is argentate. Okay, it is argentate. Am I clear, everyone? Fine. For gold, it is orate. For lead, it is plumbate. For zinc, it is zincate. For tin, it is tannate. And from platinum, it is platinate. Am I clear, everyone? So these are basically the name of metal with a special ending whenever you have to write the name of metal in an anionic part. Is this point clear to you all, everyone? Quickly tell me in the chat box, is this point clear to you all, everyone? Yes, clear or not? Clear? Clear, everyone? Okay, right. So you can memorize it. You can stick this in front of your study table and you can memorize them. Fine. Okay, everyone. So now let's just come to some practice, because practice makes a man perfect. I guess the very first complex we have already did, bacha, right? We have already did. So now let's come to the second complex. Here, the cation is simple, which is potassium. Okay. So first we will write the name potassium. Okay. First we will write the name potassium. Then we will leave a little space and then we will write the name of the anionic part right here. Okay. Now, what is the name of the anionic part, beta? See, it is a complex part. First, you have to write the name of ligands in alphabetical orders indicating their prefixes. Here we have only chloride, right? So here we have 6 chlorides. So what we will write, beta? What we will write? We will write hexachloro. We will write hexachloro. Am I clear, bacha? We will write hexachloro. Is this point clear? Hexachloro. And then we have anionic complex and we have platinum. But I have just told you, for platinum we write platinate. Okay. For platinum we write platinate. Right, because in anionic complex metal have a special ending of 8. So we will write platinate. Some of you have written correct, some of you have written platinum, so you have to make a correction, beta. It is platinate. Why platinate, beta? Because it is an anionic complex, and I have told you, in an anionic complex you have to give a special ending to the name of metal, right? Now, can you yourself find out the oxidation state of platinum right here? Most of you must have find it out, and it comes out to be +4, beta. Now, I am not finding the oxidation state of each and every metal. It is +4, so in Roman numeral you will write 4. Am I clear, everyone? Yes, am I clear? Okay, now let's come to the another complex. Beta, see, here we have 2 ligands, and first of all, it is a neutral complex. There is no charge on this particular complex. It is a neutral complex. Okay, here we have 2 types of ligand. One is NH3, one is NO2. 3 we have NH3, 3 we have NO2. Right. So first we will write the name of the ligands indicating their prefixes in alphabetical order. Okay. So here we have amine and nitro. So alphabetically, A of the amine comes first or N of the nitrogen comes first, beta? A of the amine comes first. Yes or no, everyone? Yes, everyone. Right. So first we will write triamine. Right, and please remember, here amine is said to have 2A. Okay, so we have triamine. Fine. Then we have trinitro. Beta, please keep one thing in mind, that in order to decide which ligands come first alphabetically, you don't have to take into consideration T or tri. You just have to take into consideration the first letter of the ligand. For example, you have amine, you have nitro. A comes first alphabetically, then comes the N, right? So you have triamine, trinitro. Okay, nitro without any gap, okay. Then you will write the name of the metal. The name of the metal is basically cobalt, and since it is a neutral complex, the name of the metal have no special ending, so you will write cobalt right here, and in the bracket you will write the oxidation state of cobalt, which is 3. Am I clear, everyone? Yes, am I clear? Is it clear to you all, everyone? Clear? Right. Okay, next we have is the another complex CuNH3 whole 4 SO4. But see, it is a cationic complex and the cation is complex. So first we will name the complex cation. In naming the complex cation, first we have to name the ligand, then we have to name the metal, right? And since it is a cationic complex, beta, the name of the metal have no special ending. Okay, so here we will write tetraamine because we have 4 NH3. So we will write tetraamine. Okay, then we will write the name of the metal. The name of the metal is copper. The name of the metal is copper. Am I clear? The name of the metal is copper. Okay, the name of the metal is copper. Is it clear to you all? The name of the metal is copper. And if you will find the oxidation state, you can find it by yourself. It will comes out to be +2, right? And since it comes out to be +2, here I will add a Roman numeral second. Okay, here I will add the Roman numeral second, and then I will write the name of the anion beta. If it is K2SO4, then you write potassium sulfate. So it is also a salt beta. So after you have named the cation, the name of the anion is written as with a gap sulfate. Am I clear? There is no gap in the naming of the complex part. Leave a little gap, write sulfate. Am I clear, everyone? Yes. Clear? Clear, 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 clear. Very good. Tetraamine copper second sulfate. Absolutely correct. Absolutely correct. Absolutely correct. Now, let's come to NIDMG whole twice. This is, I guess, nickel dimethyl glyoxime complex. Now, here, quickly tell me when I have written DMG. Now, what do you mean by DMG? It is dimethyl glyoxime. Now, name of the dimethyl glyoxime itself consists of di. Right, it itself consists of di. So I cannot use a prefix di right here for indicating the number 2. I have to use the prefix bis beta. I have to use the prefix bis beta. Am I clear, everyone? Right, I have to use the prefix bis right here. Yes or no? Yes or no? Right, and what was the name I have given to DMG? Right, I have told you the structure of DMG in detail. Right, I have told you the structure in detail. And what was the IUPAC name beta? Dimethyl glyoxymato. Dimethyl glyoxymato. That was the IUPAC name. Right, that was the IUPAC name which has been given to this particular compound. Yes or no, everyone? Yes or no? Yes, ma'am. Yes, ma'am. Yes, ma'am. Right. So here first I will write, since it is a neutral complex, okay? Since it is a neutral complex, do not contains any charge. First I will write the number and the name of ligand, right? And to indicate the number, here I will use the prefix bis, okay? Here I will use the prefix bis beta, right? So first I will write bis. Fine, then I will start the bracket because I have told you that you have to use the bracket right here, and then we will write dimethyl glyoxymato. Dimethyl glyoxymato, okay, dimethyl glyoxymato, right? Then I will write the name of the metal. The name of the metal is nickel. The name of the metal is nickel. Beta, DMG is said to have a -1 charge, right? It is said to have a -1 charge. If nickel has an oxidation state X, then we have 2 DMG, it is equals to 0. So X comes out to be +2. That means the oxidation state of nickel right here is +2, everyone, okay? The oxidation state of nickel right here is +2, right? It is +2. So in Roman numeral we will write 2 here beta, okay? So in Roman numeral we will write 2 here. Am I clear, everyone? Yes. Am I clear? Clear to everyone? Okay, right? Now let's just move ahead beta. I have NiCO whole 4. Now for CO, I have told you the IUPAC name. It is a neutral ligand, have no special ending, and the name is carbonyl, right? It is carbonyl, and here we have 4 CO right here. So beta, for 4 we use the prefix tetra, right? So it will be tetra carbonyl, tetra carbonyl, and then I will write nickel, and then in Roman numeral I will write 0. 0, Roman numeral is 0 beta. Here the oxidation state of nickel is 0. Why? Because CO is said to be a neutral ligand. Am I clear, everyone? Okay. Now next I have is NaAlF6, already done. Next is K3CrC2O4 whole thrice. Now can you tell me what is C2O4? I have just told you it is oxalate ion, and the IUPAC name for oxalate ion, it is an anionic ligand. What is the name? oxalato. What is the name? Oxalato. Am I clear, everyone? Am I clear, everyone? You can use oxalato, right? You can use oxalato. Yes or no, everyone? Yes. Okay. Now first you will write the name of the cation. It is simple cation and the name is potassium. Okay. The name is potassium. Okay. The name is potassium, and then we will write beta the complex part, right, with a little gap, and here I have trioxalato. Trioxalato, and since it is an anionic complex, so for chromium we will add the word ate. Okay, so it will be chromate. It will be chromate. It will be chromate. Am I clear? Okay, and when you will find the oxidation state of chromium, it will comes out to be +3. You can calculate it by yourself. So in bracket or in the parenthesis, we will write a Roman numeral 3. Am I clear, everyone? Okay, yes, I will give certain complexes in homework. Don't worry. Fine, I will certain complexes in homework. Let me do one thing. I'll do this. I'll do this. This is your homework. And this I will do right here because it has something special I need to tell you. Right, rest jo hai you can do it in homework. Okay, so first I have is HgCOSCN. See beta, Hg is nothing but a simple cation and the name of this cation is mercury. Okay, so what you will write? You will write mercury first. Okay, you will write mercury first. Right, right. So you have named the simple cation. Now let's name the complex anion. Now in this complex anion, I have 4 SCN. Either you write thiocyanato or you write thiocyanato S. It's your choice. Both are acceptable in IUPAC and I have already told you. Okay, so what you will write beta? You will write thiocyanato, thiocyanato, and then you will write cobaltate. Okay, next you will write cobaltate, and then in bracket you will write the oxidation state, then in bracket you will write the oxidation state, and that comes out to be +3. So in Roman numeral you will write 3. Okay, so in Roman numeral you will write 3. Any confusion, everyone? Any confusion, everyone? I think there should be no confusion. Right, can you do the second one in homework, or I should do it right here? I think I should do it right here. This and this, at least I should do it right here. Rest you can do it in your homework. Okay, rest you can do it in your homework. I think you'll be able to do it, but it's okay. See, it is a cationic complex, right, and the cation is complex. So first we have to name the cation. Same sequence, first name of ligand in alphabetical order indicating the prefix, then the name of the metal, right? And since it is a cationic complex, no special ending to the name of metal, as simple as that. Okay, right? So first here I have 2Cl and I have En. Okay, so tell me, amongst chloride or chlorido, right, we have C as the first alphabet, right? And in ethylene diamine we have E as the first alphabet. Now alphabetically, which comes first beta, C or E? I guess C comes first, right? I guess C comes first, everyone. Fine. So first we will write dichloro or dichlorido. Okay, first we will write dichloro or dichlorido. Okay, we write dichloro. Am I clear, beta? Then we have 2 En right here, right? And for En we use the prefix bis, right? So we will write 2 En bis. So we'll write bis ethylene diamine. Okay, we will write bis ethylene diamine. Am I clear, everyone? Right. After that, we will write the name of metal, which is cobalt. Okay, so we will write the name of metal, which is cobalt. I guess you can find the oxidation number by yourself. Those who have calculated it must came out to be +3. So you will write 3 right here. Am I clear, everyone? Fine. So we have named the complex cation. Now we will leave a little space and name the anion. And when Cl is present as an ion, we will write it as chloride. Am I clear? We will write it as chloride. Am I clear, everyone? Yes, Atul. Yes, Atuluru and Tillu. Very good. Okay, next beta, you can do it in homework. Now last one. This is the last which we are doing in the class. Please listen to me carefully. It is TiH2O whole 6 3+. See, it is basically an ion. It is basically an ion. Can you see it is basically a complex ion? Right? It is basically a complex ion. And this is a complex cation actually. So whenever you are writing the name, first write the name in first go. in following the same sequence. First name ligand, then name metal. Okay, so here I have 6 H2O, and for H2O I have told you I will use the IUPAC name aqua. Okay, so here I have hexa aqua. Here I have hexa aqua. Okay, hexa aqua, right? And then I will write titanium. Okay, titanium beta ji, titanium. Okay, titanium, right? You can find the oxidation state of titanium comes out to be +3, right? So you have written the name of the complex. Now, since it is an ion, right? Since it is an ion, so you will leave a little space and add the word ion right here. Am I clear? You will add the word ion right here. Am I clear, everyone? Am I clear, everyone? माले ना दिल्ली पगली पोई इकड़ा चला मंडी, क्या लिख रहे हो बेटा अपने को? आई एम नॉट एबल टू अंडरस्टैंड इवन अ सिंगल वर्ड. प्लीज राइट हिंदी डीजे टिल्लू. ओके, डीजे टिल्लू, fine. Okay, everyone, so let's just move ahead. Fine, so rest you can do it by yourself. Now let's come to the naming. Okay, now let's come to the naming, and now we are doing the naming of the complexes which are polynuclear. Okay, which are polynuclear. Okay, Dillu, why you are so upset? Hanji Dillu, what is the problem? Dillu, I am not able to understand your language. Okay, it's Telugu. Now, what is the meaning of this language? Atuluru, can you please tell me the meaning of this particular line? I am not able to get the meaning. No problem, ma'am. Lol, ma'am. Yeah, please speak the language which I can understand. Yeah, it's very difficult to teach in English. Then you are asking me to learn Telugu, Tamil, Kannada. Now, where I will go, bhai? Where I will go? Okay, they are conversing with themselves. Fine, they are conversing with themselves. Cool. Okay, everyone, so now let's come to the complexes which are polynuclear. Now, polynuclear complexes have a certain different kind of nomenclature, and polynuclear complexes are those complexes in which cation and anion both are complex. Am I clear, beta? Right? Fine. So here, if I talk about these complexes, here the cationic and the anionic part both are complex. Am I clear? Here the cationic and the anionic part are both are complex. Am I clear, everyone? Fine. Okay, for example, we have PT/Py whole 4, PTCl whole 4. So here I can see this is the first part is cation and the second part is anion, and both are complex. Am I clear, bacha? So how we will name them? In order to name them, okay, we have to keep certain things into consideration. Okay, in order to name them, we have to keep certain things into consideration. And what are those things, beta? What are those things? See, the thing is, whenever we have cobalt, okay, we have cobalt forming a polynuclear complex, it is generally assumed, okay, it is generally pre-assumed that cobalt is said to be present in +3 oxidation state. If it is present, okay, it is pre-assumed. Fine. Similarly, if in such type of complexes chromium is present, then chromium is also present in +3 oxidation state. Am I clear? Chromium is also present in +3 oxidation state. Am I clear, everyone? Okay, if copper is present in any of these complexes, it is pre-assumed that it is generally present in +2 oxidation state. Okay, it is generally present in +2 oxidation state. Am I clear, everyone? Fine. If I talk about platinum, beta, platinum can be present in +2 oxidation state as well as it can be present in +4 oxidation state, right? Generally, whenever platinum forms square planar complexes, okay, or the complexes in which the coordination number is 4, right? For example, here the coordination number is 4, it is a square planar complex, right? In those complexes, generally it is pre-assumed that platinum is said to have an oxidation state of +2. If you won't pre-assume this, you won't be able to do the nomenclature. Am I clear? If you won't pre-assume this particular thing, bacha, you won't be able to do the nomenclature. So you have to pre-assume. Clear? Okay, right. Similarly, beta, if platinum is forming a coordination complex in which the oxidation number of the platinum is 6, right? If the coordination number of platinum is 6, then you have to pre-assume, beta, that here the oxidation state of platinum is +4. Am I clear, everyone? Okay. Similarly, the same thing applies with nickel. The same things applies with nickel, beta. Here it is said to have oxidation state +2 in generally complexes with coordination number 4 and +4 in the complexes where the coordination number is 6. Am I clear, everyone? Okay, right. Fine. So these are certain pre-assumptions. Further, if I talk about Fe, beta, Fe can be present in +2 and +3 oxidation state, and if silver is present, it is usually present in +1 oxidation states. So these are the pre-assumptions which you need to take into consideration. Then only you can give the name to these particular complexes. Okay. Now here let's come to this first complex, beta. See, first pre-assumption, beta. Here, platinum is forming a complex in which the coordination number is 4. You can see the coordination number is 4 right here. Yes, everyone. So, I have told you when the coordination number is formed, we pre-assume that the oxidation state of platinum is +2. Yes or no? We pre-assume the oxidation state of platinum is +2. That means here we pre-assume that the oxidation state of platinum is +2. Now, Py is pyridine and pyridine is a neutral ligand. Right? Py is pyridine and pyridine is a neutral ligand. So, if you will find the overall charge on this particular complex, okay, if you will find the overall charge in this particular complex, beta, right, it is +2 +0. It comes out to be how much, beta? The overall charge comes out to be +2. Yes or no? Yes or no? Yes or no? Yes, ma'am. Right? Now, tell me one thing. If I have a cation with +2 oxidation number and an anion with -2 oxidation number, and I have to write the formula of the complex, will it be AB or will it be A2B2, beta? It will definitely be AB. Yes or no? It will be definitely be AB. Yes, ma'am. Right? It will definitely be AB. That means here, if nothing is written in the subscript of both the part, that means here the charge on the cation and anion is same. That means if cation is said to have an overall charge of +2, the anion will have the overall charge of -2. Am I clear? Am I clear? Am I clear? Am I clear, everyone? Am I clear, everyone? Right? Right? Clear? Okay. Now listen to me once. Here, if in this particular part, beta, if overall charge is -2, then let the oxidation state of PT be X. You have 4Cl right here. You will keep it equals to -2. So, X is equals to -2 plus 4. So, it comes out to be +2. That means inside the complex, the oxidation state of platinum is +2. Done. 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 I can breathe. I can breathe. I can breathe. Right. So, now let's write the name, beta. First, we will write the name of cation, then we will write the name of anion. Now, here the cation is complex, right. So, same order is followed. First, you have to name the ligand in alphabetical order. Okay, first you have to name the ligands in alphabetical order, right. So, here we have only pyridine, and that also we have 4 pyridine. How many pyridine do we have right here, beta? We have a total of 4 pyridine. So, we will write tetrapyridine. It is a neutral ligand, no special ending. It is tetrapyridine. Am I clear, everyone? Tetrapyridine. Now, you will write the name of metal. Since it is a cationic complex, no special ending to the name of metal. So, you will write platinum. Okay, you will write platinum. Am I clear, beta? Right. Now, you will write the oxidation state. What is the oxidation state of platinum, beta? It is second. In Roman numeral, you will write second. Right. Now, here you have named the cation. Now, you will name the anion. Okay. Now, you will name the anion. Am I clear, everyone? Here, see, if I have 4Cl right here, how many Cl right here? I have 4Cl right here, bacha. Right. So, you will write tetrachloro or tetrachlorido. Leave a little space. Now, name the anion, and then you will write here tetrachloro, beta. You will write tetrachloro or tetrachlorido. Okay, you will write tetrachloro, right. And since it is an anionic part, then you have to add the suffix ate. Okay, platinate, right. It will be platinate, right. And in Roman numeral, you will write the oxidation state, which is second. Okay, in Roman numeral, you will write the oxidation state, which is second. Am I clear, everyone? Am I clear, everyone? Clear? Clear? Okay, let's move ahead beta. Let's move to the another complex. It is PTEN whole thrice, PTCl whole 4. See, now here platinum is forming a coordination complex with EN. Now what is the coordination number of platinum in first complex? Quickly tell me in the chat box. If you guys are aware, quickly tell me what is the oxidation number of platinum in the first complex. Yes, quickly tell me in the chat box what is the coordination number. Very good, 6 beta, very good, 6. En is a bidentate ligand and you have 3 En. That means per En we have 2 coordinate bonds which are forming. So, right, 3 ENs will form 6 coordinate bonds that will make the coordination number of platinum as 6. Right. Okay. So, since the coordination number is 6 beta, I have told you to pre-assume the oxidation state as +4. Right. So, what you will do? You will pre-assume that the oxidation state of platinum right here is +4 everyone. Right, you will pre-assume that the oxidation state of platinum is +4 right here everyone. Right, okay, fine. And En is a neutral ligand. Now since En is a neutral ligand, that means this particular part will set to have an oxidation number of +4. Yes or no everyone? +4. Okay, right. Now listen to me once beta. Nothing is written in the subscript of first complex. Nothing is written in the subscript of first complex. Right? Nothing has been written. Okay, so if you have a salt in which cation is said to have an oxidation number of +4, right? Okay, and anion is said to have an oxidation number of 2 minus. So you will write it as A2B4 or you will write it as AB2. Yes or no? You will write it as AB2. Yes or no? Yes, ma'am. Yes, ma'am. And ma'am, here also nothing is written in the subscript and the oxidation state or the charge on the cation is +4. That means anion, ma'am, that means the anion is set to have an overall charge, of -2, ma'am. Okay, it is set to have a charge of -2 beta G. Am I clear? Am I clear? Am I clear? Yes or no? Yes or no? Yes or no? Yes, ma'am. You can write -2 as the overall charge. Okay, and if the overall charge is -2, you can assume the oxidation state of platinum is X. So 4 into -1 equals to -2. So from here the oxidation state comes out to be +2. That means in the second complex, okay, in the second complex the oxidation state of platinum is +2. That's it. Now you just have to name it, bacha. You just have to name it. Karthik, Krish, yes, I remember, bacha, you used to take classes from me. See, in this lecture I am telling 20% extra, 80% is the previous concept, but yes, 20% extra knowledge I am giving in this particular lecture, right? Because here this lecture is primarily based on your NEET exam. I want you to score total of 12 marks from this chapter after this session. So a little extra I am telling in this particular session, right? So it will contain a little extra for sure. Am I clear? Okay. Now, let's come here, bacha. Let's come here. See, it has 3 EN, so I'll write tris. Okay, tris. For 3 we use tris. For 2 we use bis. So it will be tris. Am I clear? Tris ethylene diamine. Tris ethylene, not ethylene diamine. This is basically ethane 1,2-diamine or ethylene diamine. Both will work. It's your choice. Ethylene diamine. Okay, then we will write the name of metal, which is platinum. Then we will write the name of metal, which is platinum, right? After platinum, we will write the oxidation state, which is 4. So in Roman numeral, we will write 4, everyone. Okay, we will write the Roman numeral 4. Fine. Then we will write the name of the anionic part. The name of the anionic part is written with a little gap. So here we have 4-chloro. So you will write tetrachlorido or tetrachloro, right? So I am writing tetrachloro. Okay, tetrachloro. Fine, tetrachloro, right? Tetrachloro platinate. Okay, tetrachloro platinate. Fine. And then you will write the oxidation state as second. Am I clear, everyone? Is it clear to you all? Yes. Is it clear to you all? Clear, everyone? Fine. So here we can consider the last. This we can do it here. Rest. This is your homework. Okay, this is your homework as well as this is your homework. Yeah, right? You have to do it by yourself. This I am doing in the class. Okay, so I have told you that for chromium and cobalt, we pre-assume that the oxidation state is +3. If the oxidation state is +3, then NH3 is said to be a neutral ligand. right? NH3 is said to be a neutral ligand. That means here the overall charge on this particular complex is +3. Right? Then ultimately on this complex the overall charge comes out to be -3. If we assume it to be X, here we have 6 cyanide, each is said to have a charge of -1 equals to -3. So from here X will comes out to be +3. Okay, that means here cobalt is said to have an oxidation state of +3. Am I clear, everyone? Simple, right? Okay, so here we have first the cationic part, complex cation. So we will write hexaamine. Okay, we will write hexaamine. Okay, hexaamine, chromium, and then in bracket we will write the oxidation state in Roman numeral, which is 3. Then we will leave a little space or a little gap, everyone. We will leave a little space and a little gap, everyone. Okay, then we will write the name of the anion. Now name of the anion is hexacyanido or hexacyano. It's your choice. I am writing hexacyano. Okay, hexacyano, right? Then you have cobalt, and for cobalt we will use 8 with cobalt since it is an anionic complex, so cobaltate, and then we will write the oxidation state as 3. Am I clear, everyone? Am I clear, everyone? Yes, right. Now here we have completed the nomenclature. If you have understood each and every point in nomenclature, then I want the rain of green hearts and the rain of purple hearts, rain of pink hearts, rain of red hearts, right? If you have got each and every topic, beta, if you have got each and every topic, quickly tell me in the chat box. Okay, so I can see a rain of green and red hearts. Okay, everyone. So you guys have got the nomenclature. Now let's just move ahead and see now the concept which I am telling you, it's little complicated. So I want you guys to completely focus. Okay, right? Now the concept which I'm going to tell you is little complicated. Again, I'm telling you, you guys have to be little focused. Am I clear? You guys have to be little focused, right? It is a little complicated complex concept, right? That is why I am telling you, just be a little focused, otherwise you'll miss it. It is not in the NCERT also, right? So if you guys think that, oh, okay, let's just leave it and later on we'll do it from NCERT, you won't be able to get it from NCERT. Okay, fine. Am I clear, everyone? Okay. Right, now let's just come to the classification. See, when I did the classification of ligands, right, initially when I did the classification of ligand, bacha, right, when I did the classification of ligands, right, so we have already done the classification based on 2 concepts, right? We have done the classification of ligands based on 2 concepts, beta. One was on the basis of denticity, beta, right? First was on the basis of denticity, right? We have classified on ligands on the basis of denticity as monodentate, bidentate, tridentate, polydentate, right? And the second classification we have done for ligands on the basis of bachaji charge. Okay, that means we have classified the ligands on the basis of charge, right? That means they can either be anionic, cationic or neutral ligands. Then I have told you that, beta, there is also a third classification of ligand, right? Haven't I told you that, bacha, there is a third classification of ligands as well, and that basically is based on electron donation or electron acceptance. That means whether, okay, that means whether the ligand is electron donor or electron acceptor. On that basis, okay, on that basis we will classify the ligands. Okay, we will classify the ligands. Am I clear, everyone? Okay, so classification of this type is based on, bacha, electron donation and electron acceptor. Now, till now, you guys have thought that ligand, ligand is said to have, right, ligand is said to have a lone pair of electron, okay, or a negative charge, right? And this ligands basically donate this lone pair to the vacant d orbital of metal, and they will form a sigma coordinate bond. Okay, they will form a sigma coordinate bond. That means till now you guys have the idea that ligand basically donates an electron pair to the vacant d orbital of the metal, and there occurs the formation of sigma coordinate bond. Till you have this idea, right? Till now you have this idea. Yes or no, everyone? Right? You have this particular idea. Anything else do you know about it? Yes, anything else do you think you know about it? I don't think so. Till now you have mere this idea that the metal and the ligand basically forms a sigma coordinate bond. Okay, sigma coordinate bond. Yes or no, everyone? Yes or no? Yes, quickly tell me in the chat box. Yes or no, everyone? Yes or no? Right? Okay, fine. So all those ligands, right? All those ligands which basically forms sigma bond, right, by donating the electrons to the vacant orbital. Okay, right. Why donating the electrons to the vacant orbital of the central metal atom, which is a d orbital? Right, all those ligands are known as classical ligands. Am I clear, everyone? What are classical ligands? Classical ligands are those ligands which basically uses sigma bond, right, which basically uses sigma coordinate bond in order to donate the electron pair or the lone pair of electron which is present on the ligand on the vacant d orbital of the central metal atom and the central metal ion. Am I clear, everyone? Okay, these ligands are basically known as classical ligands. That means classical ligands are basically sigma donors. Okay, they are basically sigma donors. That means they donate the electron to the central metal atom's vacant d orbital with the help of a sigma bond. Okay, sigma coordinate bond. Clear? Right, now example of all these ligands are, bacha, we have NH3, we have fluorine, we have water, that is H2O, we have OH minus. All these are sigma donors, or I should say the classical ligands. Am I clear? All these are sigma donors, or I can say classical ligands. Okay, then we have the another category of ligand. First type is the classical ligands, beta, and then we have the another category of ligands. These are basically non-classical ligands. Okay, these are basically non-classical ligands. Now, what is the difference between this and this, beta? Now, these ligands will definitely form, okay, these ligands will definitely form sigma coordinate bond with the central metal atom and with the central metal ion. That means here, if I have a non-classical ligand N, then it will definitely form, you know, a sigma coordinate bond right here. It will definitely form a sigma coordinate bond right here. Am I clear, beta ji? That means it is a donor through sigma bond. Okay, it is a donor through sigma bond. Okay, it will donate the electron pair. It might donate through sigma bond. I am trying to say this. Okay, fine. It will first donate the electron, right? However, okay, however, this ligand might have a pi star anti-bonding molecular orbital. Listen to me very carefully. It might have pi star anti-bonding molecular orbital which is vacant. Right. First of all, it will donate the electron pair to the vacant orbital of the metal. It will form a sigma coordinate bond right here. Okay, right. It will form a coordinate bond right here. And this ligand might have, right, a pi star anti-bonding molecular orbital. You won't be able to visualize it, beta. Right. For example, CO. For example, CO. CO has pi star anti-bonding molecular orbital. Okay. CO has pi star anti-bonding molecular orbital. Clear? Right. So, it either have pi star anti-bonding molecular orbital or it might have a vacant d orbital. Okay, it might have a vacant d orbital, beta. It either have a pi star anti-bonding molecular orbital or has a vacant d orbital. Right? Okay, and it will accept accept, okay, it will accept the electrons from the filled d orbitals of the metal either to the vacant pi star anti-bonding molecular orbital or the vacant d orbital. Am I clear, everyone? This is very difficult to understand. It's very difficult to visualize. First we need to understand that here ligand is donating the electron pair to the vacant d orbital of the metal, but here some orbitals of the metal, d orbitals of the metals might be filled, right? And these filled d orbitals of the metal might donate electrons either to the pi star anti-bonding molecular orbital of the ligand or the vacant d orbital of the ligand, and this is basically a mutual bonding. Okay, this is basically a mutual bonding, beta ji, right? And here there occurs the formation of a pi coordinate bond. Okay, so there occurs the formation of a pi coordinate bond, beta. Am I clear? Pi coordinate bond, right? Pi coordinate bond or dative bond, right? Dative bond. Why this is a pi coordinate bond or a dative bond, beta? Because here the ligand accept the electrons in ABMO or vacant d orbital by the sideways overlapping with the d orbital of the metal. Okay, now this metal might have a d orbital, na beta, right? It might have a d orbital. Now it will undergo sideways overlapping with either vacant d orbital of the ligand or the pi star ABMO, okay, or the pi star ABMO, right? So through the sideways overlapping, it accepts the electron. Am I clear, beta? Through the sideways overlapping, it basically accepts the electron. That is why there occurs the formation of pi coordinate bond, dative bond, which is also known as back bonding, okay, which is also known as back bonding. Am I clear? This is also known as back bonding. Am I clear, everyone? First of all, tell me, is this point clear or not? Or do I need to re-explain? Do I need to re-explain? Do I need to re-explain, beta? Fine. So there occurs a formation of a pi coordinate bond. Yes. Is it clear or not? Do I need to re-explain? Yes. Is it clear or not? Is it clear? Clear. Clear, 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 clear. If it is clear, I want a lot of green hearts. If it is clear, I want a lot of green hearts. Clear, everyone? Clear? Yes, it is clear. Okay, now this back bond or this pi coordinate bond or this dative bond which is formed by the sideways overlap, or I should say the pi overlap between the filled orbital and the vacant orbital, right? This is basically also known as synergic bonding. Now what is synergic bonding? Synergic bonding, that means both ways, okay, both ways. Ligand is acting as a donor as well as an acceptor. So both ways it is occurring. Whenever there occur mutual, mutual or both ways, that means it is synergic. Am I clear, beta? That is why we will write the word synergic right here. Okay, that is why we will write the word synergic right here. Fine. So this is basically synergic bond, or I should say a pi coordinate bond. And here ligand accept the electron density from the metal by back bonding and forms pi coordinate. Am I clear, everyone? Okay, so all these ligands since are acting as an acceptor. Now whoever accepts the electron is basically a Lewis acid, right? It is basically a Lewis acid, everyone, right? And since it is accepting the electron by sideways overlap or through pi bond, that is why all these ligands are known as pi acid ligands, beta. Okay, all these ligands are known as pi acid ligands. What are the example of these pi acid ligands, beta? There are lot many. I have ethene, which is CH2 double bond CH2. I have CO, I have CN, I have benzene, which is C6H6. Am I clear, everyone? Now quickly tell me in the chat box, is this concept even 20% clear? If it is even 20% clear, you will be able to make up the questions, and it is a very complicated concept. It is always given in foreign authors, high knowledge books. So if you are able to understand even 20% or even if 100% of it, then well and enough. Am I clear, everyone? Am I clear? 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 Yes, clear, clear, clear. Okay, now let's move ahead, beta. Now see, if I talk about non-classical ligands, beta, I have told you all non-classical ligands, they are pi acceptor. That means they basically accept the electrons either into their pi star anti-bonding molecular orbital or either into their vacant d orbital by back bonding, by pi coordinate bonding or by pi dative bonding. Yes or no, everyone? Yes or no, everyone? Yes. Am I clear, everyone? Right. However, these ligands also act as a donor. Okay, these ligands also act as a donor, right? Right, that means these ligands also act as a donor, right? Fine, although they are acceptor, they are pi acceptor, but these ligands also act as a donor, right? And if I talk about the donation which they are doing, the donation which they are doing, the donation could either be of sigma electrons or it could either be of pi, right? It could be either sigma donor or it could be even a pi donor. You need 2 to 3 minutes in order to grasp this concept. So please, please, please keep a little patience. Am I clear? You need 2 to 3 minutes in order to understand this concept. Fine. Okay. Let me do one thing before coming to this concept. Let me give you a little bit clear cut idea of certain important concepts. See, I have told you first, ligands donate the electron to the metal. If it is donating only through sigma bond, it is a classical ligands, right? And here the ligand might accept the electron from the metal beta, right? Fine, in the vacant orbital. Now, if that vacant orbital is pi star, okay, it is pi star ABMO, that is pi star anti-bonding molecular orbital beta, then what type of ligands are those which are said to have pi star ABMO? What type of ligands are those which are actually forming pi coordinate bond, right, in which there occurs the acceptance in pi star ABMO? What are these type of ligands, beta? The example of these type of ligands, okay, the example of these type of ligand is CO, Cn minus, NO, NO plus. Okay, so they all are pi acceptors, they all are pi acid ligands, right? And they accept, they form the back bonding or they form the pi coordinate bonding by accepting the electron into pi star anti-bonding molecular orbital of the ligand. Am I clear, everyone? Am I clear, everyone? Is this point clear? Is this point clear? Yes or no? Clear or no? Clear or no? Am I clear, everyone? Fine. Is this point clear? Okay, right? Is this point clear? Fine. So here coordinate bond is formed by, right? So here, how the coordinate bond back bond or the pi coordinate bond will form, beta? Here this will occur a sideways overlap, and the sideways overlap will occur between the d orbital of the metal and the pi star anti-bonding molecular orbital of this ligand. Clear? And since it is a sideways overlap, it is a pi bond. Since it is a sideways overlap, it is a pi bond. Am I clear? Okay, so here I am writing that the pi coordinate bond, okay, the pi coordinate bond is formed. How it is formed, beta? It is basically formed by overlapping of filled d orbital of metal. Okay, it is basically filled d orbital of metal, right? And vacant pi star ABMO of ligand. Am I clear? Of ligand. Am I clear, everyone? Okay. Now, since it is a pi bond, here the d orbital is involved and here the pi star orbital is involved. That means here the type of bonding is d pi p pi. Okay, this is basically d pi p pi type of back bonding. Am I clear? It is basically d pi p pi type of bond. Is this point clear to you all, everyone? Quickly tell me in the chat box. Is this point clear? Is this point clear? Is this point clear or not? Yes. Is this point clear? Quickly tell me in the chat box, everyone. You guys are chit chatting, yeah. You guys are not studying. I feel bad. Is it clear, everyone? Clear? Clear? Okay, right. Now, beta, here there is another class of ligands. There are some another class of ligands. Again, ligand is acting as a donor. Fine. Okay. However, whenever it accepts the electron through pi coordinate bond or pi back bond, it basically accepts in the vacant d orbital. Okay, it basically accepts in the vacant d orbital. No break till 11. No break till 11. You'll get the next break at 11. So I don't want to use any. I don't want to see any break word in the chat. Only at 11 I will give you the break. Beta, because the stream is of 12 hours, we have to complete it before 12 hours. We don't have to give 12 hours to coordination. We have to complete in 10 hours, bacha. Okay, and this chapter is big. It will demand a lot of time and attention. So I have to manage the time as well. Fine. Am I clear? Okay, so the ligand can also accept the electron in vacant d orbital as well. The ligand can accept the electron in vacant d orbital as well. Am I clear, everyone? Okay, am I clear, everyone? Fine. Now, what are those ligands which are said to have vacant d orbital? Beta, see, if I talk about all those ligands which are said to have a central metal atom, right, which belongs to third period of periodic table, then you must be, knowing this thing that in the third period of the periodic table, the 3D is not being filled. 3D is being filled from fourth period onwards, right? That means all the ligands in which the central metal atom is of third period, they are all are said to have a vacant 3D. Am I clear, everyone? Am I clear, everyone? Fine. For example, if I have PR3, right? If I have PR3, it is said to have vacant 3D, right? Similarly, you can have ASR3, right? It has vacant 4D. Okay, you have Cl minus. Now, Cl minus also has vacant 3D, everyone. Cl minus also has vacant 3D. Clear? Right. So, all these have vacant 3D. So, they can form the sideways overlap by the d orbital. Okay, right, by the d orbital. Fine. Okay, so here we will write that pi coordinate bond. Am I clear? Pi coordinate bond is formed. Okay, so here the pi coordinate bond is formed by overlapping of filled d orbitals of metals, beta, of filled d orbitals of metals, beta, right, and vacant d orbital of ligands, and vacant d orbitals of ligands, okay, and vacant d orbitals of ligand. Am I clear, everyone? Right. Now, quickly tell me in the chat box, in the previous case, the kind of back bonding was d pi p pi. Okay, the kind of back bonding was d pi p pi. Can you please tell me in the chat box what will be the nature of this type of bond? What will be the nature of this particular type of bond? Yes, can you tell me in the chat box what will be the nature of this particular type of bond? Yes, everyone. D orbital of the metal and d orbital of the ligand, sideways overlap, so it will be d pi type of bond. Okay, it will be a d pi type of bond. Yes, everyone, d pi. Am I clear? Yes, Nitya Shri, yes, Anjali, absolutely correct. D pi. Okay, d pi. Fine. Okay, now let's just come back here, everyone. Let's just come back here, everyone. Okay. See, beta, see. Now here, non-classical ligands, right? Non-classical ligands are those which are said to be pi acceptors, right? However, they act as donor as well. Right, they can act as a donor as well. Right, they can act as a donor as well. Right, now when they act as a donor, they can donate the electron either through sigma bond or through pi bond. That means they can either be sigma donor or they can either be pi donor. Right, for example, there are certain ligands which donates the electron pair through sigma bond, right, and accept the electrons through pi bond. That means they are sigma donor they are pi acceptor. They are sigma donor, they are pi acceptor. Are you getting my point? Are you getting my point? Are you getting my point, everyone? Fine. Are you getting my point, everyone? So they are sigma donor and they are pi acceptor. For example, if I talk about CO, right? CO basically donates. If CO is present, it will donate the electron pair through sigma bond, right? However, it will accept through pi bond in the vacant pi star anti-bonding molecular orbital. Am I clear, everyone? Am I clear, everyone? Fine. Okay. Similarly, I have Cn minus, I have NO, I have NO plus, right? So they all donate the electron through sigma bond and accept the electrons through pi bond. Okay, bacha, right? And that also they accept in pi star anti-bonding molecular orbital. Similarly, if I have PR3, okay, this is also a ligand. Now, it donates the electrons through sigma bond, right, and accept the electrons through pi bond. However, they accept the electrons through pi bond in vacant d orbital, since phosphorus belongs to third period, and in third period we have vacant 3d. Right, in third period we have vacant 3d, right? Phosphorus is said to have vacant 3d. Am I clear, everyone? Am I clear, everyone? Right, that means here it is a sigma donor and a pi acceptor. However, it accepts the pi electron, it is vacant 3d orbital. So here we have PR3, here we have ASR3, here we have Cl minus, Br minus, I minus, okay, Br minus, I minus, all them are just accepting the pi electrons in the vacant d orbital. Am I clear, everyone? Am I clear, everyone? Okay, so here non-classical ligands, if they are sigma donor, then they can be pi acceptor either in the pi star anti-bonding molecular orbital or in the vacant d orbital. Is this point clear, everyone? It must be clear to you all. Okay, right. Now the second category is beta, that they donates the electron through the central metal atom, but they donate it through pi bond, right? For example, if I have CH2 double bond CH2, this is ethene. Okay, so if it is coordinating through metal beta, then it will donate the pi electron to the vacant d orbital of the metal, right? Clear? And it will accept the electrons through pi back bond as well. However, it has donated not through sigma bond, it has donated through pi bond. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Okay, right, fine. So here I have many pi donors beta. I have benzene. Benzene is a pi donor. Okay, then I have ethylene, CH2 double bond CH2, again a pi donor. Then I have cyclobutadiene, again it is a pi donor. And I have cyclopentadienyl ion, also again it is a pi donor. All of them are pi acceptor, but all of them are pi donor. That means first they donate the electron pair through pi bond. Okay, now here beta, if this is the ligand, it basically donates the electron through pi bond. Fine, and accept the electrons again through pi bond. Am I clear, everyone? Am I clear, everyone? Is this point clear to you all? It must be clear to you all. Okay, it must be clear to you all. Now, here, let's just move ahead beta. So, we have studied the non-classical ligands right here. We have studied the non-classical ligands right here. Okay, let's just move ahead. Let's just move ahead. Okay. Beta, all those ligands which are basically pi donors, that means which donates the electrons through pi bond, right? In their case, we use a word heptacity. Okay, here we use a word heptacity, right, instead of denticity. Denticity used to be the number of electron pairs which was donated by one ligand, right? Now, heptacity is somewhat different. Okay, what I am trying to say beta, in the case of pi donors, what are pi donors beta? What are pi donors? I have told you certain pi donors beta. For example, benzene is a pi donor. For example, ethene is a pi donor. For example, cyclobutadiene is a pi donor. For example, cyclopentadienyl ion is a pi donor. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Right, they all are pi donor. So what I am saying beta, in the case of pi donor, here we use another word. The name of that word is heptacity, right? Instead of what? Instead of denticity. And this heptacity is basically represented by eta. The symbol of eta is this. This is a symbol of eta. Am I clear, beta? This is the symbol of eta, right? You use this symbol for viscosity in physics, beta. In chemistry, we use it as hepticity. Okay, we use it hepticity. Okay, we use it hepticity, right? So hepticity is a new word for you all. Fine. Now here, in order to tell the hepticity, beta, what we basically do, suppose I have C6H6. Right, C6H6 is benzene. Okay, C6H6 is benzene. Now, benzene is said to have 3 pi bond. Benzene is said to have 3 pi bonds. Yes or no? Benzene is said to have 3 pi bonds. Am I clear, everyone? Now, if benzene is said to have 3 pi bonds, beta, there must be resonance. And here, each pi bond is said to consist of 2 electrons. So 2 plus 2 plus 2. Here 6 pi electrons are delocalized over 6 carbon. If you have a little idea of resonance, then you will say that here 6 electrons are delocalized over 6 carbons, beta. Right? That means here we have 6 pi electrons. Right, each pi bond contributes to 2 pi electrons. Here we have 6 pi electrons, right? Okay, that means benzene is basically 6 pi electron donor, beta, right? It is a pi donor as well as it is a 6 pi electron donor, beta. Yes or no? Right? And what are the continuous carbons? Okay, what are the continuous carbons in which there occurs a delocalization of pi electrons? I can see there are 6 carbons. 1, 2, 3, 4, 5, 6. On this 6th carbon, there is a continuous delocalization. Okay, there is a continuous delocalization of what, beta? Of the pi electrons. Of the pi electrons. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Yes or no? Yes, ma'am. Okay, that means whenever we have to tell the hepticity, hepticity is 10 raised to the power x. What is this x? X basically stands for the number of continuous atoms in which pi electron cloud is delocalized. For example, here we have 6 continuous carbon atoms in which the pi electrons are delocalized. That means here, if we have to represent the hepticity, is eta raised to the power 6. Okay, it is eta raised to the power 6. Now 6 indicates that 6 pi electrons are delocalized continuously over 6 carbons. Am I clear, everyone? Am I clear, everyone? Clear? Yes, clear or not, beta? You won't find this concept easily in any book. I am telling you, please listen to it. It is very important. Next I have is CH2 double bond CH2. That is basically, beta, your ethene. Okay, ethene. That is basically your ethene. Am I clear, everyone? Okay, so it is 2 pi electron donor. Right, it is 2 pi electron donor. Why? Because we have 1 pi bond, and 1 pi bond basically consists of 2 pi electrons. We all are aware, we all have studied in organic, right? We all have studied in organic that 1 pi bond is equivalent to 2 pi electrons. Yes or no, everyone? Yes or no, everyone? Yes or no, everyone? Yes. Okay, now if these 2 pi electrons are delocalized continuously over 2 carbon, then if I have to write the hepticity, beta, in hepticity, I have to write the power 2. I have to write the power 2. Am I clear? Right? So, the name of this particular ligand, is eta 2 ethylene, or eta 2 ethene. Am I clear, everyone? Am I clear, everyone? Next is cyclobutadiene. Okay, cyclobutadiene. Now this is cyclobutadiene, beta. See here 2 pi plus 2 pi. That means it is 4 pi electron donor, right? And these 4 pi electrons are delocalized over how many carbon, beta? 1, 2, 3, and 4. That means here the hepticity is 4. That means eta is 4 right here. So it is basically known as eta 4 cyclobutadiene. Okay, eta 4 cyclobutadiene. Am I clear, everyone? Yes. Am I clear, everyone? Clear? Okay, is it clear to you all? Is it clear to you all? Yeah, I want lot of green hearts here. I want lot of green hearts here. Yes, everyone. I want lot of green hearts right here, everyone. Yes, lot of green hearts. Yes. Now let's come to the last ion, which is C5H5 minus. This is cyclopentadienyl ion. Okay, this is cyclopentadienyl cyclopentadienyl ion. Okay, this is cyclopentadienyl ion. Now this ion is said to be a little moody. Okay, it is said to be a little moody like your girlfriend, right? It is said to be a little moody, right? Your girlfriend is like that, na? Just a friend. All the girls are little moody, na? Even your mother will be a little moody. If she is happy, she'll bake 4 parathas. And if she said, I'm not in a mood, she'll say, yeah, please order something from Zomato, na? Right? So every woman is moody. You will agree to the fact? Yes or no, everyone? Every woman is moody, right? So C5H5 minus is also moody. Right, it is also moody, right. So if you will look at the structure of C5 beta, C5H5 minus, right, and you have even, you know, a little idea also of resonance. Okay, if you have even a little idea of resonance, can you please tell me what are the number of delocalized pi electron in this particular ion? Can you please tell me? Can you please tell me what are the number of delocalized pi electron in this particular ion? Yes, everyone. Yes, everyone. Yes, everyone. Can you please tell me what are the number of, somebody is saying 6, somebody is saying 4. But see, here we have a lone pair on this carbon, it is involved in resonance. So whenever a lone pair is involved in resonance, it is also known as pi electron. It is also known as pi electron. That means here we have 2 pi plus 2. How many? 6 pi electrons. How many? 6 pi electrons. But a basic organic chemistry, yaar. That means it is 6 pi electron donor. It is 6 pi electron donor. Am I clear, everyone? It is 6 pi electron donor. Yes or no, everyone? Yes or no, everyone? Yes or no? Yes, ma'am? Yes, ma'am? Yes, ma'am? Right, everyone? Right, everyone? Okay. Now, although it is a 6 pi electron donor, but it is a moody. It can either donate only this electron pair, or it can donate all these 6 pi electrons. Am I clear? So if it coordinates through this particular carbon beta, right, then it will donate only these 2 electrons to the central metal atom through the pi bond, and it will be 2 electron pi donor. Am I clear? It will be 2 electron pi donor. Is it clear to you all, everyone? Okay. And if it has delocalized one, okay, delocalized one, and donates all the 6 pi electrons through the central metal atom, then it is a 6 pi electron donor. Okay, so can you please tell me the hapticity in first and second case, beta? Can you please tell me the hapticity in both first and the second case? Yes, everyone. Can you please tell me the hapticity both in first and second case? Yes. Can you please tell me the hapticity both in first and second case? Yes, everyone. What is the hapticity? What is the hapticity? Yes. What is the hapticity? I know most of you will give me the wrong answer. Can you please tell me the hapticity, beta? Both first and the second case. Yes. What is the hapticity? What is the hapticity, beta? What is the hapticity? What is the hapticity? One correction I would like to make, whenever it basically donates these 2 electrons, the beta, then it is basically a sigma donor. That means it donates through sigma bond, right? It is donating it through the sigma bond, and whenever it donates the pi electrons, then it donates through pi bond. Okay, so here it is a sigma donor and here it is a pi donor. That is a separate concept. Now you tell me one thing. What is the hapticity? What is the hapticity, beta? While defining hapticity, I have told you that eta's power x are basically the number of continuous atoms which are involved in pi electron cloud delocalization. Right, they are basically the continuous atoms which are involved in pi electron delocalization. Yes or no, everyone? Yes or no? Yes or no? Yes or no? Yes or no? Beta, yes or no? Yes, ma'am. Right, beta, here only one carbon is involved in formation of a sigma bond, right? That means here hapticity is only one. So here the name is basically written eta 1 cyclopentadienyl, Eta 1, cyclopentadienyl, right? Or people even write it sigma C6H5 negative. Now sigma C6H5 negative means here it is donating only 2 electron pairs through sigma bond. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Yes or no? Am I clear, everyone? Clear, clear, clear. Okay, and in the second case, beta, although I have 6 pi electrons, however, these 6 pi electrons are delocalized only continuously on the 5 carbon atoms. That means in the second case, the heptacity is 5. Okay, so it is eta 5 cyclopenta dienyl ion. Okay, and here since it is forming the pi bonds, or it is acting as a pi donor, so it is pi C5H5 negative. Am I clear? Is it clear to you all, everyone? Yes, is it clear to you all, everyone? Clear? Okay, so this is the prior knowledge which I have to give you regarding classical ligands and regarding non-classical ligands. So what rating will you give it out of 10? Have you clearly understood all the concept regarding classical and non-classical ligands? What is the rating out of 10? What is the rating out of 10? Quickly tell me in the chat box. What is the rating out of 10? Yes. What is the rating out of 10? 10? Somebody is saying 1 crore. You got the concept? You got the concept? Great. Somebody is saying 7. Why 7, Rakesh? Why 9, Ritish? See, hepticity first of all applies only in the case of pi donors, beta, first of all. And hepticity is basically eta raised to the power x, and x is basically the number of continuous atoms which are involved in delocalization. Right? Fine. So that is the basic thing. That's it. It is a little complicated. However, if you will put a little bit of time to it after the class, you will definitely understand it. Am I clear, everyone? Am I clear, everyone? Fine. Okay. It might be a little confusing because you are studying for the first time. However, if you will put little amount of time and attention, then definitely you will understand it better. Right? That is why certain concepts are difficult and certain concepts are easy. And this is a little difficult concept, not that difficult concept. Am I clear, everyone? So you need to take this thing into your consideration. Fine. Okay. Fine, let's just move ahead, everyone. So now let's come to EAN. Now let's just come to EAN. EAN basically stands for effective atomic number. Okay, EAN stands for the effective atomic number. Okay, now what is this effective atomic number, everyone? What is this effective atomic number, everyone? See, effective atomic number is basically the atomic number which a central metal atom or a central metal ion holds in a coordination complex. Am I clear, beta? I am explaining it once again. Effective atomic number. See, if a cobalt is taken into consideration, the atomic number of cobalt is 27, right? However, if I take the atomic number of cobalt in a complex, then it will be somewhat different, right? Fine, it will be somewhat different, but that atomic number is basically known as effective atomic number. Am I clear? That atomic number is basically known as effective atomic number. Am I clear, everyone? That atomic number is basically known as effective atomic number. Am I clear? Am I clear, everyone? Am I clear? Tell me, quickly tell me in the chat box. Am I clear? Okay, now there is a formula with the help of which you can find the effective atomic number easily. I am giving you a formula, and with the help of this formula you can find the effective atomic number very easily. And the formula of EAN or the effective atomic number is, first you have to write the atomic number, okay, atomic number of central metal atom or central metal ion. Then you have to subtract the oxidation state, right, the positive oxidation state of central metal atom and the central metal ion, and then plus either you can do 2 into coordination number, right, either you can do 2 into coordination number, Okay, or in some of the books, instead of 2 into the coordination number, right, instead of 2 into coordination number, people write number of electrons donated by ligands. Okay, number of electrons donated by ligands. Am I clear? These are basically number of electrons donated by ligands. Am I clear? Am I clear? Am I clear? Okay, right. Now let's take one example into consideration in order to understand EN or effective atomic number. Suppose I have K4 FeCN6. Okay, now first keep one thing in your mind, beta, effective atomic number is calculated only for that metal which is present inside the coordination sphere. That means here the effective atomic number is calculated only for Fe. Okay, it's only calculated for Fe. Am I clear, everyone? It is only calculated for Fe. First thing you need to keep in mind, that it is only calculated for Fe. Right. Now suppose here what I can do, I can keep the atomic number first of all. So En is basically equals to atomic number. So atomic number of Fe is 26 minus the oxidation number of Fe. You can calculate it, it will be plus 2 beta. So you have to subtract 2 from here. Plus the coordination number is 6 beta. Why? Because each Cn will form one coordinate bond with Fe, right? So 6 Cn will form beta 6 coordinate bonds. That means the coordination number is 6 right here. Okay, so it will be 2 into 6, Raje. So 26 minus 2 plus 12. Okay, right. So it will be 26 plus 10. So here the atomic number is 36. Okay, effective atomic number is 36. Am I clear, everyone? Am I clear, everyone? So either you can do it this way, either you can do it this way, everyone, either you can do it this way, or the other method is beta. See, if I talk about 1 Cn beta, 1 Cn is 2 electron donor, right? We know that Cn is a sigma donor, right? It is a sigma donor, and 1 Cn at a time can donate 2 electrons, right? 1 Cn at a time can donate 2 electrons. That means Cn is 2 electron donor. Am I clear? So if I use the second alternative method beta in order to find the EAN, right? See, first I have to write the atomic number of Fe, which is 26. Then the oxidation state on Fe, oxidation state of Fe is -2, plus the number of electrons donated by the ligand. See, 1 Cn donates 2 electrons, and here I have 6 Cns. Here I have 6 Cns. So quickly tell me in the chat box how many electrons will be donated by 6 Cn beta. It is very simple. It is very simple. It will donate 12 electrons beta. It will donate 12 electrons beta. Yes or no? Quickly tell me in the chat box how many? 12 electrons beta. Okay. So I will do plus 12. Right, and when you will find it by this method also, the answer comes out to be 36. Am I clear? The answer comes out to be 36. Very good, Rakesh. Very good, Yarea 2.0. Very good, Nitish Kumar. Very good, very good, very good. Telugu industry, where your seriousness have gone? To Telugu industry only. Hanji. Okay, everyone. So we have calculated for K4 Fe CN6, and En comes out to be how much? En comes out to be 36. Now quickly tell me in the chat box what will be the EAN for K3 FeCN6 beta. See, if I have to find for K3 FeCN6 EN beta, the formula is first I have to write the atomic number. For Fe the atomic number is 26. Here if you will find the oxidation state of Fe, it will be +3. So minus the oxidation state plus beta 1 Cn can form 1 coordinate bond. So 6 Cn can form 6 coordinate bonds. So the coordination number is 6 right here. Okay, so 2 into coordination number, that means 2 into 6. So 26 minus 3 plus 12 beta G. It will comes out to be how much? It will comes out to be 35. It will comes out to be 35. Okay, so here the effective atomic number is 35. Is it clear to you all, everyone? Is it clear to you all, everyone? Yes, clear or not? Clear? Right? Okay. Now here, quickly find the effective atomic number in the very first complex. quickly find the effective atomic number in the very first complex, beta. See, if I talk about nickel, beta, nickel, right, is said to have an atomic number of 28. Z for nickel is 28, beta. Oxidation state of nickel right here is 2, beta, right? Oxidation state of nickel right here is 2, bacha. Am I clear, everyone? Fine, because En is a neutral ligand. Now quickly tell me what is the coordination number, beta. See, here the coordination number is 6. If you can tell it, it's okay. If you can't, then it's very simple, beta. See, if I talk about En is CH2, CH2, NH2. Okay, CH2, CH2, NH2. Now here we have 2 donor. Each nitrogen can donate 2 electrons, right? So it is basically overall a 4 electron donor. It is overall a 4 electron donor, although it is a sigma donor, but it is a 4 electron donor, everyone, right? It is a 4 electron donor, yes or no? 4 electron donors, right? If one En is a 4 electron donor, if I have 3 En, beta, 3 En will be 3 into 4, stands for 12 electron donors. That means if I have to write the electrons donated by the ligands, it will be 12, okay? It will be 12. So 26 plus 12, 26 plus 10, so it will be 36. It will be 36. Am I clear, everyone? Yes, am I clear or not? Clear? Right. Next I have is cobalt, beta. I have to find En, or I should say the effective atomic number. Now for cobalt, the atomic number is 27, right? For cobalt, the atomic number is 27. What is the oxidation state on cobalt right here, beta? I guess it is 3, right? Now see, each NH3, beta, each NH3 is 1 electron donor and it basically donates through sigma bond. If one NH3 is 2 electron donor, then here you have, bacha, 6 NH3, so that will be a 12 electron donor, right? That will be a 12 electron donors. So plus 12, beta, plus 12. So I have 24 plus 12. Again it comes out to be 36, okay? Again it comes out to be 36. Any doubt, anyone, quickly tell me in the chat box. Is it clear? Yes, is it clear, everyone? I guess in the first case I have done any calculation mistake, right? Yeah, I think I did a calculation mistake. It is, yeah, I did a calculation mistake, but I guess it is 28, right? So 28 plus 10, then it comes out to be 38, right? So make a correction, beta, it will be 38. Again, it's already 11, so a little battery got down, right? It will be 38. So please make a little correction, right? It will be 38. Hi, it will be 38. 38, 38, 38. Please make a correction. Please make a correction. It is 38, beta. Normal mathematical mistakes, you can correct it. It is 38. It is 38. It is 38. Okay. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Clear? Right? Okay. Now, let's come to the another ligands, FeCO whole 5. Now see, beta, if I have to find the En right here, this you can do it in your homework. This you can do it in your homework. I am doing for this. See, Fe is said to have atomic number of 26. In this particular coordination compound, the oxidation state of Fe is 0. Why? Because CO is a neutral ligand, right? So what we can do? We can subtract 0 from here. We can subtract 0 from here, everyone. Okay, plus each CO is a 2 electron sigma donor. It is a pi acceptor, agreed. It is a pi acid ligand, no doubt. But it is also a 2 electron sigma donor. Okay, right, fine. And here we have to take into consideration sigma donors electrons only, right? Because I have told you, in considering the coordination number, we have to take into consideration sigma bonds only, not the pi bonds. Am I clear, everyone? Am I clear, everyone? Yes. Am I clear, everyone? Yes or no? Yes or no? Yes or no? Is it clear, everyone? Okay, right. So 1 CO can donate 2 electrons. So 5 CO can donate 10 electrons, bacha. So here it will be 10. So here En comes out to be 36. Am I clear? Yes. Here En comes out to be 36. Is it clear to you all, everyone? Is it clear to you all, everyone? En comes out to be 36. Clear? Okay. Fine. Let's just move ahead, beta. Now we are taking another compound into consideration. It is basically gaseous salt. Okay, this is basically gaseous salt. Now here platinum is present. For your information, the atomic number of platinum is 78 basically. Right, fine. Now see, Here if I have to find EN beta, first I have to write the atomic number. The atomic number of platinum is 78, and then I have to subtract the oxidation state. See, what is the oxidation state of platinum right here beta? Let it be X. Let it be X. Potassium is said to have a charge of +1. Platinum is said to have an oxidation state of X. We have 3 Cl which are said to have an oxidation state of -1. C2H4 is a neutral ligand, although it is a pi donor, but it is a neutral ligand. Yes or no beta? It is a neutral ligand. Yes or no? Yes or no? Yes or no everyone? Okay, right. So this comes out to be equal to 0. So X minus 2 is 0 and X comes out to be +2. Okay, X comes out to be +2. That means here the oxidation state of platinum is +2. Okay, here the oxidation state of platinum is +2. Am I clear everyone? Am I clear everyone? Okay, so here I have to subtract 2. Now if I have to find the total number of electrons donated, beta, each Cl is a 2 electron donor, right? Each Cl is a 2 electron donor, right? Each Cl minus is a 2 electron donor, right? So if I have 3 Cl minus beta, they are 6 electron donors, right? They are 6 electron donors, right? So 6 electrons will be donated from Cl minus, and if I have to talk about bacha, CH2 double bond CH2, it is a pi donor, right? And it can donate again 2 electrons, right? So 6 plus 2, 8. That means here a total of 8 electrons are being donated. Okay, so here a total of 8 electrons are being donated. So 78 plus 6, that comes out to be 84. Am I clear everyone? Right. Next compound is basically ferrocene. Okay, next compound is basically ferrocene. Okay, next compound is basically ferrocene. Now here it is pi C5H5. Now what do you mean by pi C5H5 beta? C5H5 is cyclopentadienyl, and if it is pi C5H5, that means here all the 6 pi electrons are going to get donated beta, not just the 2 sigma electrons. Yes or no everyone? Yes or no everyone? 1 ferrocene can donate 6 pi electrons, 2 ferrocene can donate 12 pi electrons beta, right? If I have pi C5H5 minus beta, right, that means here beta, all the 6 pi electron which are involved in the resonance are donated to the metal. Yes or no? Right? So if 1 Fe is a 6 electron donor, 2 Fe will be 12 electron donor, right? 2 Fe will be 12 electron donors beta, right? So if I have to find EAN, okay, if I have to find EAN beta, it will be for Fe the atomic number is 26. Oxidation state, see, EN is said to have a -1 charge, right? So X minus 2 will be equals to 0. That means X will comes out to be +2 here. That means here the oxidation state is -2, plus we have 12 right here. So 26 plus 10. So EAN comes out to be 36. Okay, EAN comes out to be 36. Am I clear everyone? Am I clear everyone? Am I clear everyone? Yes, clear or not? Clear or not? Okay, so at 11:05 or 11, I will give you a break. Till then, please be energetic, please be enthusiastic. Okay, fine, let's just move ahead beta. Let's just move ahead. Now, beta, according to Sidgwick, Sidgwick is the one who have actually given effective atomic number. Effective atomic number is nothing but actually the actual number of electrons or actual number of atomic number which has been possessed by a metal in a coordination compound. It must be clear to you all, right? It must be clear to you all. The structure of ferrocene, oh, it's very simple here. See, structure of ferrocene, it's very simple beta. Here you have one cyclopentadienyl, it is another, this is Fe2 plus. So this is basically the structure of ferrocene. This is basically the structure of ferrocene. Sandwich compound, okay, it is a sandwich compound. Fine, it is a sandwich compound. Why? Because Fe has been sandwiched between what? It has been sandwiched between 2 cyclopentadienyl rings. So it is a sandwich compound. You can write it in your notes, although this much is not required for NEET, but you guys asked it, so I have just made it clear to you all. Okay, now let's come to Sidgwick. Now Sidgwick basically gives EAN, that means he have actually told how to find the effective atomic number of an element or a central metal atom or a central metal ion in a coordination complex, right? Sidgwick have told us and we have found it, right? Now Sidgwick have told us that whenever EAN of any central metal atom or central metal ion in the coordination complex, right? What Sidgwick have told us, beta? Sidgwick have told us whenever EAN, that is the effective atomic number, okay, that is the effective atomic number of central metal atom or central metal ion is equal to that of nearest noble gas. For example, 36 is the atomic number of krypton, right? If EAN of any central metal atom comes out to be 36, that coordination compound is said to be stable, because we know that whenever there occurs inert gas configuration, inert gas configurations are stable electronic configurations. So whenever a central metal atom or a central metal ion is said to possess EAN or effective atomic number, which is basically equals to that of nearest noble gas, okay, which is basically equals to that of nearest noble gas, my dear student. Okay, so in that particular case, bacha, what will happen, beta? That particular coordination compound will be stable. Right, now what you can do, I am giving you two compounds, this and this. You have to find EAN in both the cases, right? In the first case, when I found EAN, beta, here Fe is said to have an atomic number of 26. Now when you will subtract the oxidation state, here the oxidation state will be +2, -2. So here 1 CN is 2 electron donor, you have 6 CN, so 6 into 2, you have 12 electrons. Right, so EAN comes out to be 36, which is equals to the nearest noble gas krypton. Am I clear, everyone? Yes or no? Am I clear, everyone? Right, and in the second complex, beta, in the second complex, if I will see FeCN whole 6 3 minus, okay, if I will see FeCN whole 6 3 minus, in this particular complex, if I will find EAN, okay, if I will find EAN, fine, okay, if I will find EAN, bacha, see, atomic number of Fe is 26, here the oxidation state will be -3, plus I will have, beta, 1 CN is 2 electron donors, so 6 CN will be 12 electron donors, right? So here EAN comes out to be 35. In one case, beta, EAN is 36, and in the another case, the EAN is 35. Now you yourself tell me, beta, now you yourself tell me which complex is more stable according to Sidgwick. Which complex is more stable according to Sidgwick? Am I clear, everyone? Which complex is more stable according to Sidgwick? Quickly tell me in the chat box. Yes, everyone. First one is more stable. Why? Because here EAN is equals to the atomic number of next nearest noble gas, which is krypton. Right. So this particular compound is stable as per Sidgwick. Is it clear to you all? Yes. Is it clear to you all, everyone? Clear? Clear? Okay. Right. Now, beta, few important points which we take into consideration right here, Beta, see, electron pairs from the ligands are added to central metal atom or the central metal ion, right, in order to make the effective atomic number equal to the next nearest noble gas, right? The complete potency of the ligand is that they have to donate the electron pair to the central metal atom or the central metal ion, right, till then they complete the nearest noble gas electronic configuration. Am I clear, everyone? That is the actual, what I should say, I don't know how to say koshish in English, but that is the actual extent which actually every ligand has to do. Every ligand wants that it should donate that much amount of electron to the central metal atom or the central metal ion, that it should achieve the next nearest noble gas configuration, right, and to get a stable electronic configuration. However, still It fails in certain cases, and it fails drastically in metal carbonyls. There are many metal carbonyls, right, in which EAN basically fails. Okay, there are many metal carbonyls in which EAN basically fails. Beta, why you guys are indulged in chatting? Are these concepts are clear? If these concepts are clear, then please give me a red heart quickly. Please give me a red heart quickly if these concepts are clear. Yes, are these concepts clear to you all? Please give me red heart. Please give me red heart. Fahad, if you will skip chatting, then definitely I will repeat the last question. If you won't stop chatting, then I will definitely would repeat the next question. Right? Please, please. I know who is studying, who is not studying. Don't make me a fool. Yaar, Mohammed Asfiq, how many dinner breaks do you need, yaar? In the first half, you said you need one break. Now you're saying you need another break. How many breaks do you need, yaar? Okay, let's do one thing. I also need a break. Let's take a 15-20 minutes break here, okay? Let's take a 15-20 minutes break right here. Let's get re-energized. I also need some water. I need some food. So let's take a 15-20 minutes break. But you have to promise me that you will rejoin. You will rejoin in 15-20 minutes, okay? You will get re-energized. I will get re-energized. ठीक है, right? So we both will get re-energized, and let's take a break of at least 15-20 minutes, and let's meet in 15-20 minutes. Okay, we will continue this after 15-20 minutes. Okay, everyone. So, wow, now ma'am has actually fully been energized and had dinner. So, I hope you guys also had dinner. I had late dinner because I have to teach you till long. So, let me ask everyone to rejoin. Okay, let me ask everyone to rejoin. Hi, everyone. Rejoin. Okay, hi, everyone. Rejoin. We are starting. So, let me just put a message for all of you so that you guys can rejoin. Okay, right. Hi everyone. Hi. How are you all? And I'm so happy, extremely happy. I know this is a festival season today. You know, we had our Durga Puja and lot many things going on here and there, and still you guys are able to make it up to the classes. I guess that is the only motivation I have. Okay, that is the only motivation we have, guys. Okay, right, that is why we are being here, that is why we are here being studying, and that is the only motivation. Okay, hi Anandita, hi bacha, how are you? Okay, so before going on the break, bacha, I have told you that there are certain compounds which do not follows EAN, that is effective atomic number. For example, metal carbonyls. However, any complex, if it does not follow EAN, it actually has a tendency that it should follow EN, right? It wants to follow EN. So that is the problem with it. Right, bacha. Fine. So here, what happens? For example, if I took a metal carbonyl MnCO whole 5, okay? If I took MnCO whole 5, okay? So this is a metal carbonyl which we have right here. If I asked you to calculate EAN in this particular case, bacha, so you will say, ma'am, EAN is said to have a formula. First, we will write the atomic number of manganese. Now, the atomic number of manganese is 25, right? In this particular case, if I ask you to find the oxidation number, then beta, CO is a neutral ligand. If it is a neutral ligand, then Mn here will set to have a 0 oxidation state, so minus 0, right? Plus, if I talk about beta 6 carbonyl, see, 1 carbonyl is 2 electron donor. 6 carbonyl will be 12 electron donors. So, plus I will have 12 right here. Am I clear? So, 37 will come, bacha, right? 37 will come, yes or no? Now, the EN which is close to 37 is 36, right? Right. Now, 36 is the nearest noble gas configuration of krypton, and every complex wants to achieve EAN. Right. So, what will happen, beta? What will happen? This MnCO whole 5, okay, this MnCO whole 5 does not have a perfect EAN equal to that of the nearest noble gas of krypton. Now, what it will do, bacha? What it will do, bacha? It will basically loses 1 electron, right? It has an EN of 37, bacha. It has an EN of 37. So, it will loses 1 electron, beta. It will loses 1 electron in order to form MnCO whole 5 positive, right? Now, the EN will be 36 because it has lost 1 electron, right? And whenever someone loses the electron, that means it undergoes oxidation, and a species which is undergoing oxidation is basically a reducing agent, right? So that is the reason this MnCO whole 6, since it has a tendency to lose electrons, right, in order to achieve EN, so it acts as a strong reducing agent, okay? It basically acts as a strong reducing agent. Am I clear, beta? It acts as a strong reducing agent, right? Similarly, we have VCO whole 6, beta. V stands for vanadium, right? Can anyone tell me in the chat box what is the electronic configuration of vanadium, beta, or what is the atomic number of vanadium? Yes, quickly tell me in the chat box what is the atomic number of vanadium, everyone. Scandium, titanium, vanadium, that means 23, right? That means here, if I have to find the EAN, beta, first I have to write the atomic number, which is 23. Then the oxidation state of vanadium is 0 right here. Here we have 6 CO. 1 CO can donate 2 electrons, so 6 CO can donate 12 electrons, everyone. Yes or no? Yes, ma'am. That means here EN comes out to be 35, ma'am. Again, the EN is not perfect. That means it is not equal to that of the nearest noble gas, which is basically krypton, whose atomic number is 36. Yes or no, everyone? Yes or no? Yes or no? Yes, ma'am. Yes, ma'am. Yes, ma'am. Yes, ma'am. Yes, ma'am. Right. Now, what we will do, beta? What we will do? It will try to gain one electron. See, if I have VCO whole 6 bacha, okay, right? So, it will, since it has an EN of 35 bacha, it will gain one electron. It will gain one electron in order to form VCO whole 6 negative, right? Now the EAN comes out to be 36. That is perfect noble gas, you know, krypton's atomic number. Am I clear, everyone? Am I clear, everyone? Am I clear? Clear? Okay. Now, since it has a tendency, a huge tendency to gain this electron. Why? Because after gaining this electron, it will have En equals to the atomic number of krypton, which is stable, right? So, it has a huge tendency to gain the electron. When someone gains the electron beta, it will undergo reduction, and when someone has a strong tendency to undergo reduction beta, it is said to act as oxidizing agent, a strong oxidizing agent. Okay, so that is why beta VCO all 5, it basically acts as, okay, it basically acts as strong oxidizing agent. Am I clear? It basically acts as strong oxidizing agent. Am I clear, everyone? Yes. Am I clear, everyone? Clear? Okay, right. Now, let's just move ahead, beta. Let's just move ahead, beta. Now, there are certain metal carbonyls, right? There are certain metal carbonyls, beta, which we are going to study right now. Now, these metal carbonyls, in order to achieve EN, can even undergo dimerization. Okay, they can even undergo dimerization, right? For example, I have MnCO whole 5. Okay, I have MnCO whole 5, right? First of all, calculate the EN of MnCO whole 5, right? First of all, calculate the EN of MnCO whole 5. See, beta, manganese is said to have an atomic number of 25. Right, oxidation state of manganese is 0 right here, plus 1 carbonyl is 2 electron donors, so 5 carbonyl will be 10 electron donors. Yes or no, beta? Right. Okay, fine, it will be a 10 electron donor. By mistake, I have written the atomic number of manganese as 27. It is 25. Please make a correction. Okay, please make a correction. So, 25 plus 10, it is 35. That means here, En of manganese is 35. It wants to achieve the En of next nearest noble gas, right? So, what it will do, beta? It will undergo dimerization. Right, it will undergo dimerization. Right, what will happen that if you have MnCO whole 5, it will undergo dimerization. Okay, it will undergo what? It will undergo dimerization. Okay, it will undergo dimerization. Am I clear? It will undergo dimerization. Why it will go dimerization, beta? After dimerization, it will forms Mn2CO whole 10. Right, right, fine. That means here there will occurs the formation of this particular complex. Okay, here there occurs the formation of this particular complex. So here I have Mn, here I have CO, 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 CO. That means 2 Mn will bond the forms with themselves as well as they will form the bonds with 5 CO ligands. Am I clear, everyone? Am I clear? Okay, so here I have 1 CO, CO, CO and CO. Okay, right. Now here in this dimer, when you will find the EAN, beta, see here you have to find EAN for both the manganese, right? If you are finding that for a dimer, that means you are finding En for both the manganese. Okay, so 1 manganese is said to have an atomic number 25, 2 manganese will said to have 25 into 2. Am I clear? 2 manganese will said to have atomic number 25 into 2, right? So here we will do, beta, 25 into 2. Am I clear, everyone? Right? Okay. If I talk about oxidation state, beta, 0 for this, 0 for this. Both are said to have 0 oxidation state, right? And if I find the number of electron donated by each CO, beta, see, 1 CO can donate 2 electrons, so 10 CO can donate 20 electrons. However, people just forget that in EAN we have to take into consideration all possible electrons which are present in the complex. So here this one electron pair which is shared by both the manganese is also have to be taken into consideration, beta, right? Okay, so you have 50 plus 20 plus 2, right? 50 plus 20 plus 2, that comes out to be 72. Now this is EAN for 2 manganese. This is EAN for 2 manganese. If I have to calculate EAN for 1 manganese, what will be, beta? What it will be? It will be 72 divided by 2, right? It will be 72 divided by 2, beta, right? Fine. So if I have to find EAN for 1 Mn, for 1 Mn, bacha, it will be 72 divided by 2, and that is 36. That means here this Mn have achieved the stable En, which is 36, which is equal to the atomic number of krypton. Am I clear, everyone? Am I clear, everyone? So this point is clear to you all, everyone, right? Fine. Okay. Okay, so now let's just move ahead, beta. Let's just move ahead. Let's come to bonding in metal carbonyls. Okay, before going on the break, I have told you that carbonyl is a sigma donor. However, it is a pi acceptor. Now quickly tell me in the chat box, where does the carbonyl accept the electron pair, right? Either it accepts in the pi star antimolecular orbital or it accepts in the vacant d orbital. Quickly tell me in the chat box. Before going on the break, I have explained you. Quickly tell me in the chat box. Before going on the break, I have told you that CO is a sigma donor and it is a pi acceptor. Now quickly tell me in the chat box, where does it accepts the electron? Where does it accepts the electron? Yes, everyone. Quickly tell me in the chat box, where does it accepts the electrons? Yes, everyone. Yes, beta. Into pi star anti-bonding molecular orbital, everyone. Into pi star anti-bonding molecular orbital, everyone. Yes or no? Yes or no, right? See, don't get confused by seeing this diagram. It is given in NCERT. It basically explains the synergic bonding. See, I've already told you, beta. I've already told you that metal and CO. CO is a sigma donor, right? However, it is a pi acceptor. Okay, it accepts electrons through sideways overlap, through back bonding, through synergy bonding into its vacant pi star anti-bonding molecular orbital or ABMO. I've just told you, right? I have just told you. Yes, P. Lakshmi Gauri, absolutely correct, right? Okay. Fine. So in NCERT, this diagram has been given which shows that CO is said to have one lone pair of electrons. So it basically donates it into vacant d orbital of metal and forms the sigma bond, right? And here the metal is said to have filled d orbital, right? So this filled d orbital undergoes sideways overlap with this anti-bonding molecular orbital. This is anti-bonding molecular orbital of CO, and here there occurs the formation of pi coordinate bond, which is also known as synergic bond. Okay, which is known as synergic bond. Am I clear, everyone? Is this point clear to you all, everyone? Yes, is this point clear to you all, everyone? Clear or not? Quickly tell me in the chat box. Is this point clear to my lovely students? Yes. Is this point clear to my lovely students? Yes. Clear or not? Clear? Okay. Right. Now listen to me, bacha. Listen to me. Here, what happens that metals basically forms the back donation or do the back donation. That means donate the electron to the pi star anti-bonding molecular orbital of CO, right? Fine. Now quickly tell me in the chat box, you must have studied in chemical bonding. What happens to the bond order? If number of electrons in anti-bonding molecular orbitals increases? Quickly tell me in the chat box, what happens to the bond order when number of electrons in the pi star anti-bonding molecular orbital increases? Can anyone please tell me in the chat box? Can anyone please tell me in the chat box? Yes. Can anyone please tell me in the chat box, beta? What happens to the bond order? You must have studied in chemical bonding that whenever electrons enters into ABMO, beta, bond order decreases. decreases, right? So here we are getting the electrons in the pi star anti-bonding molecular orbital, right? So the bond order of CO bond basically decreases, okay? The bond order of CO bonds basically decreases. Now we know that beta bond order is inversely proportional to bond length, right? Bond order basically stands for the strength of the bond, right? More is the strength of the bond, shorter is the bond. You must have studied this already in various parts of MOT which you have studied in chemical bonding, okay? Right, fine. So here if bond order decreases beta, bond length basically increases, right? And listen to me once beta, whenever this metal is said to have a strong back donation, this basically strengthens this metal carbon bond, right? Whenever this metal do a strong back bonding, right? Whenever this metal do a strong back bonding, bacha, what happens? The bond strength of this particular metal carbon bond increases, and if bond strength increases, that means bond order basically increases, and if bond order increases beta, bond length decreases. Am I clear, everyone? So now let's come to a conclusion. The conclusion is stronger is the back donation, or stronger is the electron donation from the filled d orbital of the metal to the vacant pi star anti-bonding molecular orbital of this carbon which is present in the CO beta, right? Fine. Here there will occur more decrease in the bond order and more increase in the bond length. Am I clear, everyone? Is this point clear to you all? Now tell me in the chat box, when there is more back donation from metal to the vacant pi star anti-bonding orbital of CO, what will happen to the bond order? What will happen to the bond order beta? Bond order of the CO bond will get decreases, or I should say bond length increases, okay? Bond length increases. Now beta, what happens that we basically measure the bond strength and the bond order with the help of stretching frequency in NMR, right? Whenever we have to find that a particular bond is strong or a particular bond is weak, we take the help of spectroscopy. Okay, whenever we have to find that this particular bond is strong or this particular bond is weak, we basically take the help of spectroscopy. Am I clear, everyone? We basically take the help of spectroscopy. Now in spectroscopy, what we do beta? We basically find the stretching frequency. More is the value of stretching frequency, more is the bond strength, or more is the bond order. Okay, right. So more is the stretching frequency, more is the bond order. Am I clear, everyone? Yes. Am I clear, everyone? Is this point clear to you all? Yes. Is this point clear to you all, everyone? Okay. Am I clear? Right. Is it clear to you all? Fine. So that means if the back donation is more, more decrease there occurs in bond order, and if there occurs decrease in bond order, then the stretching frequency of CO bond will get decreased, right? The stretching frequency of CO bond will get decreased. Am I clear, everyone? This is very important beta. From this, once the question has been asked in AIPMT 2011. Okay, so this is important. Fine. So let's do few questions right here. First, tell me in the chat box, is this question visible properly, or I have to write it again? Is this question visible properly? I think it is visible. Okay, so the bond length of CO bond, right? The bond length of CO bond is 1.128 angstrom. Find its bond length in FeCO whole 5. Okay, so I have FeCO whole 5. Now see beta, if I have FeCO whole 5, then in FeCO whole 5 beta, what will happen? Fe will donate through synergic bonding electrons into pi star anti-bonding molecular orbital of CO, right? And there occurs decrease in bond order, right? However, there occurs increase in bond length. Now what people say is that here, if initially the bond length was 1.128, then after this the bond length will be more than 1.128. Now people will say, ma'am, then in that particular case only this option is not possible, rest all the three options are possible. Getting my point? If I ask you that in this particular complex, what will be the bond length? Okay, what will be the bond length of CO? Then you will say, ma'am, it will be definitely greater than 1.128 angstrom. You will say that, right? Fine. Then in that particular case, only first option is not possible for this question. All the rest of the three options are possible. Now here, how to move on, beta? How to get the solution? Then you need to keep in mind, beta, that here, whenever there occurs synergic bonding, although the bond length of CO bond increases, but this increase is only 2 to 5%. Am I clear? Here, the increase is only approximately 2 to 5%. Okay, here the increase is basically 2 to 5%. Am I clear, beta? And if I have to talk about 2 to 5% increases, then beta, I guess only option number D is possible, right? Right, option number C is also not possible because it is same. Option number A is not possible because it is less. B and D were the confusing options, I guess. Right, so here it is, quieter, easier to predict, beta, D for doctor, right? Okay, so here in CO, if the bond length of CO is basically 1.128 angstrom, so whenever the CO ligands is incorporated in FeCO whole 5, beta, here the bond length decreases to, bond length increases to 1.15 angstrom, right? So I have just pasted it right here. Okay, it's not clear, but I have pasted it right here. You guys can understand it. Now, I have another question. The question is, you have to tell the bond length. You have to tell the bond length of CrCO whole 6, MCO whole 6 negative and MnCO whole 6 positive. Now, before this question, I would like to ask you a single question. Okay, suppose you have M plus, you have M0, and you have M minus. My question to you guys is, if this metal basically donates the electron pair, okay, if this metal basically donates the electron pair, okay, right, if this metal basically donates the electron pair in the pi star anti-bonding molecular orbital of CO, right, my question to you guys is that in which case the donation is more? When the metal is said to have a negative charge, when the metal is said to have a zero charge, or when the metal is said to have plus charge? Quickly tell me in the chat box, when metal can effectively donate electron to the pi star anti-bonding molecular orbital of CO, when it is said to have a positive charge, or when it is said to have a zero, or when it is said to have a minus charge? Quickly tell me in the chat box, beta. How positive, yaar Ronak? How positive, beta? When the electron density on metal is more, then the pi back donation or the extent of synergic bonding is more. Yes or no? Yes. Right? That means when the metal is said to have a negative charge, in that particular case, it will able to donate more electron into pi star anti-bonding orbital. Am I clear or not? Why M plus, yaar? What brain are you guys using? What brain are you guys using? Yeah, what is this, yaar? Whenever metal is said to have a negative charge, it is said to have more electrons, right? And whenever it is said to have more electrons, it can donate effective synergic bonding. It can have effective synergic bonding. And whenever the effective synergic bonding is occurring, there is more pi back donation. Am I clear, everyone? Am I clear, everyone? Okay, right. So extent of synergic bonding order is M minus do it the most effectively and M plus do it the least effectively. Is it clear to you all, everyone? Yes. Is it clear to you all, everyone? Yes. Is it clear to you all, everyone? Yes. Clear. Okay, right. Now see, beta. Now see. Here, if in this particular case, the extent of synergic bonding is more, then in this particular case, definitely, beta, definitely here, the bond order is most decreased, right? That means in this particular case, bond length is most increased, okay? In this particular case, bond length is most increased. Am I clear, everyone? Fine. Now see, here I have T3 complexes, beta. Here I have 3 complexes. One is CrCO whole 6. Okay. The other complex is vanadium CO whole 6 negative, and the other complex is MnCO whole 6 positive. Now quickly tell me in the chat box in which of the complex the CO bond length is maximum. Quickly tell me in the chat box in which of the complexes the CO bond length is maximum. In which of the complex the CO bond is maximum. Yes, quickly tell me in the chat box, everyone. Quickly tell me in the chat box in which of the complexes the CO bond length is maximum. Absolutely correct, Madhurima. Absolutely correct, beta. See, here chromium is said to present in the neutral state. Here vanadium is said to be present in negative state, and here Mn is said to be present in the positive state. Okay, so here the best back donation can occur in the case of vanadium, right, and least in the case of manganese, right. This is the order of synergic bonding, or the order of extent of synergic bonding. Okay, this is the order of extent of synergic bonding, bacha, right. This is the order of extent of synergic bonding, bacha, right. And if this is the order of extent of synergic bonding, that means in V minus the extent of synergic bonding is most. So that means in this particular case, beta, the decrease in CO bond length, the increase in CO bond length, beta, it is maximum, right. The bond order is maximum decreased right here, and the bond length is maximum increased right here. Okay, right. So if it is A, this is B, and this is C, and if I have to give the order of bond length, okay, order of bond length, right, of CO bond, beta, right, then it will be maximum in B, then I will have A, and it will be least in the case of C. CAB is the order. CAB is the order. CAB is the order. Am I clear, everyone? Yes. Am I clear, everyone? Yes. Am I clear, everyone? Fine. Now, let's just move ahead. And come to the theories in the coordination compounds. So see, beta, here I have to study 3 theories. One is Werner theories, another one is valence bond theory, and the last one is the crystal field theory. Okay, these are the 3 theories. These are the 3 bonding theories which we have to study. Now, ma'am, why we have to study bonding theories in the case of coordination compounds, or ma'am, why we need to study bonding theories in the case of coordination complexes? See, beta, in order to explain the nature of bond. Am I clear? In order to explain the nature of bond, beta. Fine. In order to explain the nature of bond, right, between the metal and the ligand, right. In order to explain the nature of bond between a metal and ligand, beta, right, whether that bond is ionic, whether that bond is covalent, right, we need to study bonding theories. Okay, we need to study bonding theories. Why we need to study bonding theories, beta? In order to explain the nature of bond between metal and the ligand. Am I clear? Right. Now here 3 theories have been put forward in order to explain this nature of bonding. The very first was valence bond theory, the other one was Werner's theory, and the third one is crystal field theory. Okay, so now let's study them in order. The very first which we have to study right here is basically Werner's theory. Okay, so the very first theory is Werner theory. It was given by Alfred Werner. I'll be really quick. It is a very small sort of theory, beta. I'll be really quick. So Werner was a scientist. He basically have studied coordination complexes. Okay, and after studying coordination complexes, what has he found out, beta? He found out that every metal, central metal atom or central metal ion, which is present in the coordination complex, it is said to exhibit 2 types of valencies. Am I clear? Every metal, every central metal atom or every central metal ion which is present in the coordination complex, it is said to exhibit 2 types of valencies. Am I clear, everyone? It is said to exhibit 2 types of valencies, right? One valency is basically your primary valency, bacha. Okay, the very first valency is primary valency, beta, right? And the second type of valency is basically secondary valency. Am I clear, beta? The second type of valency is basically secondary valency. Now, Sir Werner was the happiest. Okay, Sir Werner were like, oh, I am at the top of the world. I have discovered two valencies possessed by central metal atom or central metal ion in the coordination complex. But later on, people got to find that primary and secondary valencies are just the fancy name. Am I clear? What people got to find, bacha? What people got to find, bacha? People got to find that here, this primary valency and secondary valency are nothing but they are just mere fancy names. Okay, they are just mere fancy name. This primary valency is nothing but the oxidation number, right? And the secondary valency is nothing but the coordination number. Am I clear, everyone? Later on, people got to find here that this primary valency is nothing but the oxidation number. Am I clear, beta? It is nothing but the oxidation number, beta, right? And the secondary valency is nothing, bacha. It is just the coordination number. Am I clear? It is nothing but just the coordination number. Am I clear, everyone? Am I clear, everyone? Right? Okay, this primary valency is nothing but the oxidation number and the secondary valency is nothing but the coordination number, oxidation number, coordination number. Okay, right, fine. Let's just move ahead, beta. Right. So basically, Werner in its theory have told us certain postulates, right? So the very first postulate was this only, right? And now let's come to the second postulate, which was basically given by the Werner. Fine. Werner basically told that primary valency is non-directional. Right. Now, what do you mean by non-directional? But a non-directional means that it is not responsible for predicting geometry. Now, think of it. If you know the oxidation number of the central metal atom or the central metal ion, bacha, can you tell the geometry of ligand around the central metal ion or the spatial arrangement of ligand around the central metal ion? Absolutely, you can't. Right. Okay, fine. So, in the second postulate, Werner told that primary valency is non-directional. Non-directional means that it does not test the geometry of the complex. It does not help in telling the geometry of the complex, beta. Class will be, I guess, 2 to 3 hours more, beta. It will take 2 to 3 hours more in order to complete the chapter. Right. Okay. So, primary valency is non-directional. Non-directional means it is not responsible for predicting the geometry. Right. However, coordination number or secondary valency is directional. That means it basically helps in predicting the geometry. Okay, it basically helps in predicting the geometry. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Right. For example, if you know the coordination number, you can easily predict the geometry of the complex. Right. For example, see, if you know that the coordination number is 2. Right. So, you will say, okay, the coordination number is 2, that means we have 2 ligands, right? And these 2 ligands might have arranged in a linear geometry around the central metal atom or the central metal ion, right? That is why we are saying secondary valency or coordination number is directional. That means it is used for predicting the geometry. Am I clear, everyone? Am I clear, everyone? Okay, right, fine. So, here I am writing the coordination number and the possible geometry. If the coordination number is 2, beta, the possible geometry is linear. When the coordination number is 3, the possible geometry is trigonal, planar. Am I clear? Okay. If the coordination number is 4, then the possible geometries are 2, beta. Either it could be square planar, either it could be tetrahedral. Okay. Either it could be square planar. Okay. Either it could be square planar or it could be tetrahedral. Okay. Or it could be tetrahedral. Am I clear? Right. Whenever the coordination number is 5, beta, again, there are 2 possible geometry. Either it is triangular bipyramidal or TBP, right? Either it is TBP, that is trigonal bipyramidal, or it is square pyramidal, bacha, or it is square pyramidal. Am I clear? Or it is square pyramidal. Am I clear, beta? Or it is square pyramidal. Clear everyone, right? So when the coordination number is 6, beta, in that particular case, the geometry or the arrangement of ligand around the central metal atom or the central metal ion is basically octahedral, okay? So here the geometry is basically octahedral, okay? So here the geometry is basically octahedral. Am I clear everyone? Am I clear everyone? Is it clear? Okay, right. Now let's just move ahead to the third postulate of Werner's theory. The third postulate of Werner theory is, bacha, that primary valency is ionizable whereas secondary valency is non-ionizable. Now what do you mean by this? See, it's very simple, beta. It's very simple. If you have a complex which is CO, Cl2, NH3, whole 4, okay, and you have one Cl outside the coordination sphere. Okay, now if I ask you, okay, if I ask you to dissociate this particular complex in water, you will say, ma'am, it will basically get dissociated as COCl2 NH3 whole thrice positive plus Cl negative. You will say, ma'am, it will ionize like this. Okay, you will say, ma'am, it will ionize like this. Yes or no? You will say, ma'am, it will ionize like this. Absolutely correct. It will ionize like this, right? Now here quickly tell me, if I ask you to find the primary valency, right? If I ask you to find the primary valency, that is the oxidation number, you will say, okay ma'am, we can take it as X, right? Here we have 2 Cl inside, so 2 into minus 1. Right, we have 4 NH3, so 4 into 0 plus minus 1 for the Cl outside equal to 0. So X comes out to be plus 3. Now quickly tell me, in order to find the oxidation number, which is plus 3, is the charge on the Cl which is present outside the coordination sphere is used, which is minus 1. Right, so this minus 1, this is basically the charge on the Cl which is present outside the coordination sphere, right? And this Cl basically contributes in calculation of primary valency or the oxidation number. Yes or no? Yes or no? Yes or no, everyone? Am I clear? Right, so this Cl is basically responsible in order to find the oxidation number. Yes or no? Yes or no, everyone? Yes or no? Yes. Okay, so here can we say that, bacha, this Cl can be ionized since it is present outside the coordination sphere, and this is also acting as a primary valency. So from here we got the conclusion, beta, that primary valency is ionizable, that primary valency is ionizable, right? However, if I ask the coordination number, beta, so coordination number are because of these 2 Cl and these 4 NH3, and these do not get ionized, beta. These do not get ionized. Why? Since they are present inside the coordination sphere, bacha. Yes or no, Raje? Right, that is why we are saying that the secondary valency is non-ionizable, okay? The secondary valency is non-ionizable. Am I clear, everyone? Am I clear, everyone? Clear? Okay, right. Now, bacha, next postulate is that primary valency is satisfied only by negative and positive ligands, right? See, oxidation number is the primary valency, and oxidation number varies only when there is either the positive charge on the ligand or negative charge. Neutral ligand does not affect, you know, the oxidation number, right? That is why we are saying that primary valency is satisfied only by negative and positive ligands, right? Fine. That means the charge on the positive and negative ligands can only be used in order to find the oxidation number, right? Talking about the secondary valency, beta, secondary valency is satisfied by everyone. Either it is neutral ligand, either it is positively charged ligand, or it is a negatively charged ligand. See, if I talk about this coordination complex, now here this Cl is a negatively charged ligand and NH3 is a neutral ligand, right? It doesn't matter whether it is negative or it is neutral. Both of them are contributing in order to find the coordination number, right? That is why we are saying whether the ligand is positive, whether the ligand is negative, whether the ligand is neutral, it will contribute to secondary valency, or it will satisfy the secondary valency. Am I clear, everyone? Okay, right. Now, beta, always keep one thing in mind, that secondary valency whenever has to be represented, it is always represented by a straight line. Okay, whenever we have to represent, beta, a primary valency, it is always represented by a dotted line, right? And there might be some ligand, okay, there might be some ligands, right, which satisfies both primary valency as well as secondary valency. For example, here if I talk about the Cl, right, here if I talk about the Cl, does this Cl helps in calculating the oxidation number? Right? Yes, it is helping in calculating the oxidation number. That means, ma'am, this Cl is helping us in order to find the primary valency. Right? At the same time, ma'am, this Cl is also helping. Okay, this Cl is also helping, bacha, what to do. This Cl is also helping us to find the coordination number as well, beta. Right? That means there are certain negatively charged ligands that help us to find the oxidation number as well as the coordination number. That means that help us to find the both primary valency as well as the secondary valency. So such ligands are represented by putting an arrow which is said to consist of a solid line as well as which is said to consist of a dotted line. Am I clear, everyone? Am I clear, everyone? Yes, am I clear? Now what do you mean by this? Now what do you mean by this? It will be clear to you in some time. Give me some time, it will be clear to you. Now here, bacha, Sir Werner have given this postulates regarding the coordination complexes. Now the question comes that, ma'am, how Sir Werner were able to give these postulates, right? How Sir Werner was able to give this postulate? So bacha, what Sir Werner have actually did, okay, what Sir Werner have actually did, he have made to react COCl3 with NH3. Okay, what he did, he made to react COCl3 with NH3, right? So what he did, he took COCl3 plus he took NH3, and when he reacted both of these compound, bacha, he was said to form lot and lot of coordination complexes. Like he was able to form COCl3 dot 6NH3. Okay, he was able to form COCl3 dot 5NH3. Okay, he was able to form COCl3 dot 4NH3. He was able to form COCl3 dot 3NH3, right? Okay, so now what that Sir Werner did, he was able to form large number of complexes, but the problem was that Sir Werner was not able to find the structure of these particular compounds, right? Sir Werner was not able to find the structure of these particular compounds. So what he actually did, he took each and every compound. For example, first he took COCl3 dot 6NH3 and he made to react this compound with excess of AgNO3. Am I clear? What he did, he made to react this compound with excess of AgNO3, and what he see, beta, he see that he obtained 3 moles of AgCl. Okay, 3 moles of AgCl. Now what happens, beta, whenever Cl minus reacts with AgNO3, whenever we have Cl minus ion and it is reacting with AgNO3, beta, it always forms white precipitate of AgCl, and plus we have NO3 negative ion. Okay, plus we have NO3 negative ion. Am I clear or not, everyone? Am I clear or not? Clear, right? So Sir Werner have obtained certain complexes. So the first complex was this. Now he made to react this complex with excess of AgNO3. So what he found 3 moles of AgCl are there, right? So from there he got the idea, beta, from there he got the idea, right, that the possible structure, okay, the possible structure of this particular complex could be CONH3 whole 6Cl3. Why? Why? Because if 3Cl3 are present outside the coordination sphere, beta, then only on ionization, okay, then only on ionization it can form CONH3 whole 6 3 plus 3Cl minus ion, and if 3Cl minus ion are present outside the coordination sphere, then only they can react with AgNO3 to form 3 moles of AgCl. So from here he proposed this structure of the very first compound. Am I clear, everyone? Am I clear? Okay, right. Now here if I have to represent the primary and the secondary valency right here, beta, see, this NH3 basically satisfies the secondary valency, that means the coordination number. Yes or no? It basically satisfies the coordination number. So here I have NH3, here I have NH3, here I have NH3, here I have NH3, here I have NH3 and here also I have NH3 beta, right? Now I have told you all the secondary valencies are represented by solid lines, right? All the secondary valencies are satisfied by solid lines, right? So here I will draw 6 solid lines, right? Talking about this Cl beta, only negative ions can use to calculate the oxidation state, right? That means only 3 Cl satisfies the primary valency, right? So if I have to represent these 3 Cl in representing the primary valency beta, right, then in that particular case I can draw it like this: first Cl, second Cl, third Cl, right? And they are basically satisfying the primary valency. Am I clear, everyone? Am I clear, everyone? Is this point clear to everyone? Please tell me in the chat box. Yes, is this point clear? If clear, then lot of green hearts, beta. Lot of green hearts, right? Beta, we have to study for 2 to 3 hours more. So if you will support me with a little bit of reactions, then I will able to continue the class more, because it's very difficult to teach a dead class, right? Okay, so please show some enthusiasm. Please tell me in the chat box, is it clear to you all or not? Yes, it is clear. Okay, great. Now here the second complex which he had obtained was Cl3.5NH3. So now when he made to react this with excess of AgNO3, he got to see that there are 2 moles of AgCl which are obtained. Now this is only possible when we have 2 Cl outside the coordination sphere. That means out of the 3 Cl, now 1 Cl has to be present inside the coordination sphere. Am I clear, everyone? Okay. So the possible structure is CONH3 whole 5 Cl, and here I have Cl2. Okay. Here I have Cl2. Am I clear, everyone? Am I clear, everyone? Okay. So if I have cobalt right here, fine. If I have cobalt right here, see, now this cobalt can have, beta, how many secondary valencies? See, this 5 NH3 are contributing to secondary valencies, entirely to secondary valencies, right? Are these NH3 are used to find out oxidation number of primary valency? No, ma'am. They are entirely satisfying what? They are entirely satisfying the secondary valency, right? And secondary valencies are basically donated by solid lines. So here I have drawn 5 solid lines, everyone. Okay. So C NH3, 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 and NH3. Am I clear, everyone? Right. Now this Cl beta, it is a negative ligand, and if it is a negative ligand, then definitely, bacha, it will help us to find the oxidation state. That means it will help us to find the primary valency, right? At the same time, since it is present inside the coordination sphere, so it will satisfy the secondary valency as well, bacha, right? It will satisfy the secondary valency as well, bacha, right? That means the Cl right here satisfies both primary valency as well as secondary valency, beta. So here I will have this solid and dash lines, right? However, the 2 Cls which are present outside the coordination sphere, they merely satisfy primary valency or help us to find the oxidation state, right? So they are shown with the help of a dotted line. Okay, so this represents 1 Cl. Okay, this represents the another Cl. Am I clear, everyone? Okay. Now, next, in the next parts, beta, I won't draw this diagram. Now, you can draw it by yourself. They are given in the NCERT. Now, I will directly tell you the structure, possible structure of the complexes. Now, when he have taken the third complex, he obtained 1 mole of AgCl, right? So, that means the possible structure for this particular complex is CONH3 whole 4 Cl2, and outside we have 1 Cl. Am I clear? Similarly, when he take the last compound, beta, he have obtained no mole of AgCl. That means here no Cl is present outside the coordination sphere. So the possible structure of this complex is CONH3 whole thrice Cl3. This is the possible structure of this particular complex. Am I clear, everyone? Am I clear, everyone? Am I clear? Okay, right. Is this point clear to you all, everyone? Fine. Now, we have studied the Werner theory, right? We have studied the Werner theory in detail. Now, let's do one thing. Let's study the electrical conductivity and number of ions concept. See, I have all these complexes which I have written on the back page. Now, what I am doing right here, bacha, here basically I have to tell the number of ions, okay, here I have to tell the number of ions which are formed in each particular complex when we add this complex into water. Am I clear? When we add this complex into water, we have to find the number of ions which are formed. For example, if I have CONH3 whole 6 Cl3, when I pour this complex into aqueous solution or into water, beta, what I will get CONH3 whole 6 3 plus I will have 3 Cl minus ions, okay, I will have 3 Cl minus ions. Am I clear, bacha? Right. Similarly, when I have CONH3 whole 5 Cl, Cl2, and when I pour this complex in aqueous solution, bacha, what I will have? I have CONH3 whole 5 Cl positive, 2 positive, plus 2 Cl minus, bacha. Am I clear? Am I clear? Am I clear? In the third case, when I have CONH3 whole 4 Cl2 Cl beta and I pour this in aqueous solution, I have CONH3 whole 4 Cl2 positive plus Cl negative. Am I clear, everyone? Am I clear, everyone? Clear, right? And when I take the last complex, okay, when I take the last complex and I pour this complex in the aqueous solution, I will have CONH3 whole thrice Cl3 itself, and it won't get dissociated into any ions. Why? Because there is nothing which has been present outside the coordination sphere. There is nothing which is ionizable right here, okay. So here we will have no ion, okay. Here we will have no ion. Am I clear? Here we will have no ion. Am I clear, everyone? Right. Now what I can see, beta, I can see that this is basically 1:3 type of electrolyte. Electrolyte is a substance which basically breaks up into ions when we put it that particular compound into the water. Okay, whenever a compound breaks up or break up into ions, whenever we add that compound into the water or in the aqueous solution, it is basically known as electrolyte. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Okay, so it is a 1:3 type of electrolyte. That means 1 cation, 3 anions, right? This one is a 1:2 type of electrolyte. This is 1:1 type of electrolyte, right? Now as we move from first complex to last complex, what we will see, beta, that here a total of 4 ions are formed, 1 cation, 3 anions. So here I have 4 ions, here I have 3 ions, here I have 2 ions, and here I have 0 ions, okay, right? So as we move from top to bottom, what is happening, beta? What is happening? Number of ions increases, okay, number of ions increases, and whenever number of ions increases, bacha, whenever number of ions increases, electrical conductivity increases. We know that ions are nothing but the charge carriers, and whenever the number of charge carriers increases, the conduct of electricity becomes easier, or I should say the electrical conductivity increases. Am I clear? So as we move from top to bottom, beta, electrical conductivity increases, right? Electrical conductivity increases. Fine. Electrical conductivity increases. Am I clear? Electrical conductivity increases. Fine. So here we have done all the major and minor important points regarding Werner's theory. Now let's come to the second theory, bacha. Now let's come to the second theory, beta, and the second theory is basically my bacha, your valence bond theory, okay. Now the second theory which we have to study is basically valence bond theory. See, when I've started the chapter or when I've started the theories, okay, when I've started the theories, I have just explained you that all these theories were basically given in order to tell the nature of metal-ligand bond. Although Werner theory have surrounded itself in order to find the primary valency or the secondary valency or the coordination number or the oxidation number. However, the rest of the two theories, right, they were so much concentrated, right. If I talk about the very first theory, which is the valence bond theory, bacha, right? Valence bond theory have take this point into consideration that, yeah, I have to tell the nature of bond which is present between metal and ligand. Am I clear? So valence bond theory have actually take this fact into the consideration that the bond between metal and the ligand is covalent, right? And the last theory which we will study in today's session, which is basically crystal field theory, that theory have basically considered the bonding, the nature of bonding between metal and the ligand to be ionic. Am I clear? Okay. So the two theories which we are going to study, valence bond theory and crystal field theory, both of these theories have taken into consideration different nature of bonding between metal and the ligand. Valence bond theory thinks that the bonding between metal and ligand is covalent, and the crystal field theory basically thinks that the nature of bonding between metal and ligand is ionic. Is this point clear to you all? First give me a green heart if this point is clear, then I will start with valence bond theory. Yes, is this point clear to you all, everyone? Yes, is this point clear to you all, everyone? Clear or not? Yes, clear or not? Clear or not? Clear? Yes, clear. P. Lakshmi, it is clear. What about Raki? What about Telugu industry? Have went to industry to find the new job. No longer D for doctor. Huh? No longer D for doctor. Yes? Or it's too late to reply. Okay. Okay, everyone. So now let's just move ahead and take into consideration the valence bond theory right here. Right. Okay. So see, every theory has certain features, certain postulates. So here also one by one we are going to study all the postulates, and then we will get to see that what are the important points which will be important. Fine. Okay. So now here if I talk about the main features, okay, if I talk about the main features of valence bond theory, now what are the main features of valence bond theory, beta? See, here it says that whenever central metal atom or central metal ion forms a coordination compound, right? Whenever central metal atom or central metal ion forms a coordination compound, they undergo the formation of covalent coordinate bond. Okay, they undergoes the formation of covalent coordinate bond. Is this point clear to you all, everyone? Right. So what does it says, beta? It says when central metal atom and central metal ion forms the complex compound, they undergoes the formation of covalent coordinate bond. Okay, they undergoes the formation of covalent coordinate bond. Is this point clear to you all, everyone? Is this point clear to you all, everyone? I hope is it clear to you all? Clear? Okay, right. Now here, beta, whenever there occurs the formation of this coordinate bond, metal basically act as electron pair acceptor and ligand basically act as electron pair donor. Okay, metal basically act as electron pair acceptor and ligand basically act as electron pair donor. Am I clear? Now since metal is acting as an electron pair donor, that means it should have a vacant orbital. Yes or no? Yes or no? Yes, ma'am. Right. And ligand, since it is acting as an electron pair donor, then it should have a filled orbital, beta. Right. Then it should have a filled orbital. Yes or no, beta? It should have a filled orbital. Yes or no? Yes, ma'am. Right. Okay. Now the question comes that, ma'am, what kind of vacant orbital does the metal should have in order to form effective overlap with the ligand in order to form the covalent bond or the coordinate covalent bond? Beta. Now here comes the answer to this. Here comes the answer to this. Bacha, what happens before forming, before forming the coordinate covalent bond, right? Before forming the coordinate covalent bond. Am I clear, everyone? Before forming the coordinate covalent bond, metal basically undergoes hybridization. Am I clear, bacha? Metal basically undergoes hybridization. Okay, right? So metal basically undergoes hybridization before forming the coordinate covalent bond with the ligand. That means here the vacant orbitals which basically participates in overlap with the filled orbital of the ligands are nothing. They are just the hybrid orbitals. Am I clear? They are nothing but just the hybrid orbitals. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Clear? Okay, that means the vacant d orbitals present on the central metal atom, they undergo hybridization before forming bond with the ligands, right? Fine. Once the hybrid orbitals are formed, then in these hybrid orbitals, beta, ligands donate the electron pair in order to form the covalent coordinate bond. That means here ligand is said to have a filled orbital and metal is said to have a vacant orbital. Now this vacant orbital is basically the hybrid orbital. Okay, this is basically the hybridized. This is basically the hybridized vacant orbital. Okay, this is basically the hybridized vacant orbital. Am I clear? This is basically the hybridized vacant orbital. Am I clear? Fine. That means the orbitals, the vacant orbitals which are involved in formation of coordinate bond with the ligands, they are basically the hybridized orbitals. Clear? Okay, now the question comes, ma'am, why hybridization occurs, beta? Then always take this point into consideration. You must have studied in chemical bonding, bacha. The point is that whenever there occurs the overlap between hybrid orbitals, the overlap is effective, right? So in order to have an effective overlap between metal and ligand, bacha, right, in order to have effective overlap between metal and ligand, bacha, what will happen? The metal has to undergo the hybridization. Am I clear? The metal has to undergo the hybridization. Is this point clear, bacha? Okay, right. Is this point clear? Fine. Now, depending upon the coordination number, beta, right, depending upon the coordination number, the metal will undergo hybridization, right? See, suppose if the coordination number is 2, okay, the coordination number is 2, right? That means the metal has to form 2 coordinate bonds with the ligands, right? That means metal needs to have 2 vacant orbitals, right? And those 2 vacant orbitals should be hybrid orbitals. Now tell me the hybridization in which 2 hybrid orbitals are being formed, beta. sp. Whenever there occurs sp hybridization, there occurs the formation of 2 sp hybrid orbitals. Now each sp hybridized orbital can act as a vacant orbital in order to form the coordinate bond with the ligand and can accept the electron coming from the ligand, right? So depending, okay, so depending upon the coordination number, beta, right, whatever is the coordination number, that many amount of orbitals of the metals undergo hybridization in order to form the equivalent amount of hybrid orbitals. Am I clear, everyone? Am I clear, everyone? If this point is clear, please tell me in the chat box. Is this point clear or I need to repeat? Yes. Is this point clear, beta? Is this point clear? Yes. Is this point clear? Yes. Clear or not, everyone? Is this point clear or not? Clear? Right? Clear? Okay, is it clear to all, everyone? Yes, it is clear, ma'am. Yes, it is clear, ma'am. Clear. Okay, great. See, beta, see, whenever the coordination number is 2, right, that whenever the coordination number is 2, that means central metal needs to have 2 vacant hybrid orbital. So in that particular case, the hybridization is sp, right? And in that particular case, the geometry of the coordination complex will be linear, right? Whenever the coordination number is 3, beta, it needs 3 vacant hybrid orbitals, right? So in that particular case, the hybridization will be sp2, and in this particular case, the geometry will be trigonal bipyramidal. Clear? Okay, whenever the coordination number is 4, beta, right, whenever the coordination number is 4, beta, then in that particular case, 2 types of hybridization might occur. One is dsp2 and the other one is sp3, right? Either it is dsp2 or it is sp3, there occurs the formation of 4 hybrid vacant orbital which can forms 4 bond, right, with the 4 ligands. Clear? Now in this particular case, beta, whenever the hybridization is dsp2, the geometry is square planar, and whenever the hybridization is sp3, the geometry of the coordination compound is tetrahedral. Am I clear, beta? In that particular case, the geometry of the coordination compound is basically tetrahedral. Is this point clear, everyone? Is this point clear, everyone? Quickly tell me in the chat box. Is this point clear? Right? Now, question comes, ma'am, that which d orbital is basically participates in hybridization right here, then beta we know that there are 5 d orbitals. However, whenever there occurs the formation of dsp2 hybridization, bacha, there occurs the involvement of dx square minus y square orbital. Okay, so here the d orbital which is involved is basically dx square minus y square. Okay, so here the d orbital which is basically involved is dx square y square. Is this point clear or I need to repeat? Yes, is this point clear or I need to repeat, everyone? Clear? Okay, now whenever the coordination number is 5, bacha, whenever the coordination number is 5, then in that particular case either there occurs the sp3d hybridization or dsp3 hybridization, right? Fine, in both of these hybridization, the d orbital which is involved in the mixing is basically dz square. Am I clear? The orbital which is involved in the mixing is dz square. Am I clear, everyone? Okay, it is dz square. Fine. So whenever the hybridization is sp3, bacha, the geometry is trigonal bipyramidal, and whenever the hybridization is dsp3, beta, in that particular case the geometry is, my dear students, square pyramidal. Okay, now there comes the last coordination number, beta. Whenever the coordination number is 6, that means here we have 6 ligands which needs to donate 6 electron pairs. That means here we need 6 vacant hybrid orbitals. So in that particular case, beta, hybridization is sp3d2. Whenever there occurs the sp3d2 hybridization, that means 1s orbital, okay, 3p orbital and 2d orbitals are undergoing mixing. Right. So whenever 6 atomic orbitals are undergoing mixing, they will form 6 vacant hybrid orbitals, and in each vacant hybrid orbitals, beta, there occurs the donation of electron from each ligand. Okay, each of the 6 ligands. Fine. So here, bacha, the hybridization could be sp3d2. Okay, it could be sp3d2 or d2sp3, right? In the mixing, beta, the d orbitals which are basically involved are dx square minus y square plus dz square. Am I clear? It is dx square minus y square plus dz square. Is it clear to you all, everyone? Yes. Is it clear to you all, everyone? Clear? Yes or no? Clear? Clear, everyone? Fine. Now here, beta, whether the hybridization is sp3d2 or whether the hybridization is d2sp3, in both the cases, bacha, the geometry of the coordination compound is octahedral, right? You can take any of the cases. In any of the cases, the geometry of the coordination compound will be octahedral. Okay, everyone, fine. So now let's just proceed ahead. Let's just proceed ahead. Now you must be wondering that, ma'am, why you have written d at the last here and why you have written d at the first here. Similarly, why d has been written at the last here and here d has been written at the first, beta. So there is a logic behind it. Okay, there is a logic behind it. See, we know that in order to form, beta, either sp3d2 hybridization or d2sp3, right, you need 1s, you need 3p and you need 2d orbitals. Am I correct, beta? Right, you must have studied VSCPR theory, hybridization theory in chemical bonding, right? So there you guys have definitely studied that in order to form 6 hybrid orbitals, 1s, 3p and 2d orbitals have to undergo mixing. They have to undergo the mixing, intermixing. Yes or no, everyone? They have to undergo the intermixing. Right. Now, bacha, here the orbitals, the atomic orbitals which are involving in the intermixing, they might be at times are of different principal quantum numbers, right? For example, I have 3d subshell, right? I have 4s subshell and I have 4p subshell. Okay, I know that in 3d subshell I have 5 d orbitals, which beta, one is dxy, dyz, dxz, dx square minus y square, dz square, right? Okay, out of which I am taking 2d orbital. One is dx square minus y square and the other one is dz square. Okay, so what I am doing, I am taking 2 3d orbitals. Clear? Here the principal quantum number n is 3. For 3d subshell, the principal quantum number n is 3. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Clear? Right. When I talk about 4s beta, here the principal quantum number is n is equals to 4, right? And here I am taking bacha 1 4s orbital. Talking about 4p beta, here the principal quantum number n is basically equals to what? It is basically equals to 4, right? And I am taking 3p orbitals from this 4p subshell, right? So when these will undergoes intermixing beta, here since the inner D is involved in the hybridization, 3D is involved in the hybridization, right? So here the hybridization comes to be D2sp3, right? However, when there occurs the mixing between the orbitals of same principal quantum number, okay, whenever there occurs the intermixing between principal quantum numbers of same, okay, between the principal quantum numbers, between the atomic orbitals of same principal quantum number. Is the screen is clear beta? I don't know, in my this thing it is showing a little hazy and a blur. Is the screen clear to you all, everyone? Yes. Am I perfectly clearly visible or it is a bit hazy? Clear? That there must be a problem in the PC only. Now it is clear, perfectly clear, perfectly clear, okay, perfectly clear, yes, perfectly clear, cool, perfectly clear, okay, right. So here, beta, suppose I have 4s, suppose I have 4p, suppose I have 4d, okay, so now here, all these subshells are said to have same principal quantum number, which is n is equals to 4, right? So I am taking 1 s orbital, I am taking 3 p orbital and 2 d orbital, and they are undergoing intermixing to form sp3d2. That means whenever the hybridization is d2sp3 beta, here inner d orbital is involved, okay, here inner d orbital is involved. Am I clear? Here inner d orbital is involved, right? Whenever the hybridization is sp3d2, here outer d is involved. Am I clear? Here outer d is involved, okay, here outer d is involved. Am I clear beta ji? Am I clear? Right? So whenever there occurs the involvement of inner d, right, whenever there occurs the formation of inner d orbital beta, there occurs the formation of inner orbital complex, okay, there occurs the formation of inner orbital complex, okay, there occurs the formation of inner orbital complex. Am I clear, everyone? Am I clear? Right? And whenever there occurs the involvement of outer d orbitals, right, whenever there occurs the involvement of outer d orbitals beta, then there occurs the formation of outer orbital complex, okay, then there occurs the formation of outer orbital complex, okay, then there occurs the formation of outer orbital complex. Am I clear, everyone? Yes. Am I clear? Am I clear, everyone? Okay, right, fine. Now let's just move ahead, everyone. Let's just move ahead, everyone. Now bacha, see, you have to understand one thing. If you want the inner d orbitals to participate in the hybridization, suppose you want 3d to participate in the hybridization, then that 3d should be vacant, or that 3d should be empty. Then only it can participate in hybridization. Never the filled orbitals undergoes participation in hybridization. You have to keep this thing in your mind, okay? What I am trying to say, please listen to me. Please listen to me. It's a very important point, beta. Whenever you want inner D, suppose you want 3D to get involved into the hybridization beta, then you have to make sure that that 3D should be vacant. Only vacant orbitals can participate in the hybridization, not the filled one. Not the filled one. In coordination compounds, always the vacant orbitals participates in hybridization. Please make sure to remember this point. Please make sure to remember this point. Am I clear? Why I can see very less green hearts? Is any doubt is there? Why I can't see more green hearts? Yes, why I can't see more green hearts? Bacha, show some enthusiasm, show some energy. What are you doing? Yes, what are you doing? Bacha, show some energy, show some energy. Show some green hearts. Yeah, that is the spirit. That is the spirit. That is the spirit. Very good, Deepika. Very good, Yarya. Very good, P. Lakshmi. Yes, that is the spirit. That is the spirit. That is the spirit. Keep it up. Okay, right. Now, I have explained my point. Now listen to me, beta. In the coordination complexes, we will see in CFT, beta, what happens that the d orbitals, right, they are said to consist of electron pairs. We have a coordination compounds in which we have a central metal atom or a central metal ion. Now this central metal atom or a central metal ion is said to consist of d orbitals, right, and this d orbitals might contains electrons, right, they might contains electrons which are d electrons, right, okay, and we have ligands, beta, right. In the same coordination complex we have ligand. Now ligands, they are either said to be negatively charged or they are said to have lone pair of electrons, right. So think of it, d orbital of the metal have electron, ligand is said to have negative charge, so there might be a repulsion, a sort of repulsion which is occurring right here, beta. Now more is the repulsion, okay, more is the repulsion which is being caused by the ligand to the d electron, more is the field strength of the ligand, okay, more is the donation strength or more is the field strength of the ligand, okay, right. Now what do you mean by, beta, donation strength? Donation strength means more repulsion, donation strength means more repulsion, okay, more repulsion, clear. Now on the basis of the fact that whether the ligand is able to apply more repulsion or whether the ligand is able to apply less repulsion, we classify ligands into two categories. Am I clear, everyone? We classify ligands into two categories. Am I clear, everyone? One are your strong field ligands. Am I clear? One are your strong field ligands. Now they are able to apply more amount of repulsion. Okay, they are able to apply more amount of repulsion, right? So these are strong ligands or strong field ligands, right? Generally, the ligands which have carbon and nitrogen as a donor atom. Am I clear? Am I clear, everyone? Am I clear, everyone? So generally the ligands which have carbon and nitrogen as a donor atoms are strong ligands. Okay, right? And beta, the second category is weak ligands. So generally the ligands which are said to have oxygen, sulfur and halogen as a donor atom, they basically act as weak ligands. Okay, they basically act as weak ligands, right? Now what is donation strength, beta? Again I am repeating, the ligands tends to apply repulsion to the electrons which are present in the d orbital of the central metal atom or the central metal ion. Depending upon the extent of repulsion, beta, we classify the ligands are two types: strong ligands, that means which are applying more repulsion, right? Weak ligands which are applying less repulsion. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Okay, am I clear? Am I clear? Okay, right? Am I clear? Fine. So here I am giving you an order. Here I am giving you an order. In this particular order, beta, what is happening? What is happening? What is happening, beta? Here, I am giving you an order. In this particular order, what is happening, beta? In this particular order, actually, the ligands have been arranged, right, in increasing order of their donation strength. Okay, so first we have our carbon donors, then we have the nitrogen donors, then we have the oxygen donors, then we have the sulfur donors, and at the last we have the halogen donors. Am I clear? Talking about the nitrogen and carbon donors, beta, they are strong ligands, right? Generally they are strong ligands, and generally beta G, halogen, sulfur and oxygen, they are weak ligands. Generally they are weak ligands, although the order might be varied. But generally halogen are weak ligands. Now X halogen right here could be fluorine, it could be bromine, it could be chlorine, it could be iodine. Am I clear, bacha? Am I clear? It could be your fluoride, chloride, bromide, iodide, right? Generally carbon and nitrogen donors are strong ligands and halogen, sulfur and oxygen donor are weak ligand. Is this point clear, bacha? Is this point clear? Yes. Is this point clear to you all, everyone? Is this point clear to you all, everyone? Clear or not? Clear? Okay, right? Clear. Now, in CFT, there is actually a series, okay? In CFT, there is actually a series, and this series basically explain the increasing order, the increasing order of donation strength or the increasing order of repulsion of all the possible ligands which are given in NCERT, and that particular series is spectrochemical series, right? That particular series is spectrochemical series. Although this series is given in CFT, but we can use this series in VBT. Okay, we can use this series in beta VBT. Am I clear, everyone? Am I clear, everyone? Okay, so here I have that order. Give me a second. I will paste it there. I will paste it there because it is missing from my slide. Just give me a second, beta. Yes. This is the order. Okay, this is the order. This is the order. It will take 1 to 2 minutes, beta. Please have patience. It will take 1 to 2 minutes. Where is the order? Oh God, where it is there? I missed it, I guess. Where it is, where it is. Yes, it is there. So let me take it a bit upwards. It will take 2 to 3 minutes, okay? Give me a second. I have to paste this order there. Extremely sorry for this, bacha. I don't know how this slide have actually shifted. I actually myself don't know. Almost done. Ma'am is playing right here. You can also play with me, but I will be needing 2 to 3 minutes. Okay. Yes. Done. 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 Perfectly done. Okay. So now let me just keep all the information which is important for me, and rest I am deleting all the information so that my lovely students do not get confused. Okay. Right. So I am keeping only that information which is useful to me. Rest I am deleting all the information. Okay. Rest I am deleting all the information. Just give me a second. Sorry for this, but it has to be done. Okay. It has to be done. Otherwise, you guys will get confused, because this all points I have to explain in CFT, which I will discuss in coming half an hour approximately. Okay. Okay, so this is basically spectrochemical series. This is basically spectrochemical series. Okay, so I have basically explained you, bacha, what I have basically explained you. I have explained you that nitrogen and carbon donor are generally strong ligands, whereas halogen, sulfur and oxygen donor ligands, they are generally weak ligands, right? And in spectrochemical series, beta, ligands have been arranged in order of increased donation strength, right? That means here the ligands which are said to be giving more repulsion to the central metal atom or the central metal ion, beta, right? Central metal atom or the central metal ion, bacha, right? They are placed ahead in the spectrochemical series, right? Now here you can see, beta, here you have CO, which is carbon donor. Here you have a carbon donor. Okay, then you have a nitrogen donor, and then again nitrogen donor. Then you have oxygen donors, right? Then you have oxygen donors, and then there is a little fluctuation. Although after oxygen donor you should have sulfur donor, but fluorine comes ahead of sulfur donor, which is S2 minus. Am I clear, beta? Then you have halogen, and then you have SCN. Although SCN is a sulfur donor, it should have come ahead of Cl minus, but still it is placed like this. That means there is a little bit of fluctuation, right, in the increasing repulsion order here as well. There is a little bit of fluctuation. Okay, there is a little bit of fluctuation. Am I clear, everyone? There is a little bit of fluctuation. Why? Because this is an experimental order, beta. This is an experimental order, right? That is why I have given you the general order right here. This is a general order, and this is basically the experimental order with the actual order which is there, right? And here there are certain fluctuation. At some of the places, sulfur should have been ahead of halogen, but it is behind of that of halogen. Oxygen should have been ahead of sulfur, but it is behind that of oxygen. So there are certain few exceptions. Fine. Okay. Okay, everyone. So here this is the order. Now, what happens, bacha? Whenever a ligand is said to be a strong ligand, or a ligand which is said to have more repulsion is present. Okay, whenever the ligand of more repulsion is said to be present, that ligand have a chances of pairing up the electrons in inner D. Right, they have a tendency to repel the electrons, and whenever it repels the electron, it basically pairs up the electrons, and whenever it pairs up the electrons, the inner 3D becomes vacant, and whenever inner 3D becomes vacant, beta, it participates in hybridization. So in that particular case, the hybridization comes out to be D2sp3. Okay, in that particular case, the hybridization comes out to be D2sp3, and in that particular case, bacha, the coordination complex which was being formed is an inner orbital complex. Okay, so in that particular case, the coordination complex which has been formed is an inner orbital complex. Am I clear, bacha? It is an inner orbital complex. Am I clear, everyone? Okay, right. Am I clear? Fine. Am I clear, everyone? Okay, so here whenever the coordination number is 6, the hybridization either could be D2sp3 or could be sp3d2. If D2sp3 is there, then it is inner orbital. If sp3d2 is there, it is outer orbital. Clear? Now, whether inner orbital will form or outer orbital will form, it will depends upon ligand repulsion strength, ligand donation strength. If the ligand is strong field, it might cause pairing. In that particular case, inner d orbitals are participating in hybridization, so inner orbital complex will form. Right, if the ligand is weak, it won't be able to do the pairing. Am I clear? And if it won't be able to do the pairing, then beta, unfortunately, the outer d orbital has to participate in the hybridization. In that particular case, sp3d2 hybridization will be there. So in this particular case, outer orbital complex will be formed. Am I clear? Right, beta. And whenever we will write the electronic configuration for the central metal atom or the central metal ion in the coordination complex, if in that electronic configuration, beta, we have any unpaired electron, right? We have any unpaired electron, then in that particular case, beta, the coordination complex which is formed is paramagnetic. Okay, so in that particular case, the coordination complex which is being formed is paramagnetic. Am I clear, beta? And when we write the electronic configuration of a central metal atom or a central metal ion in the coordination complex, and here all the electrons are being paired up. Okay, here all the electrons are being paired up and there is no unpaired electron, then in that particular case, the coordination complex is said to be diamagnetic. Am I clear, everyone? Now here I am telling you a trick. With the help of this trick, you can find whether the complex is inner orbital, whether the complex is outer orbital, right? So what I am doing right here, I am telling you this trick for all the coordination complexes which are said to have a coordination number of 6, okay, which are said to have the coordination number of 6. Now look at it carefully, beta. Now suppose we have a coordination complex, okay, suppose we have a coordination complex. Now the coordination number of this particular complex is 6. Right, it consists of central metal atom or central metal ion. That central metal atom or the central metal ion should belongs to 3D. Okay, right, it should belongs to 3D. Am I clear, beta? The central metal atom or the central metal ion which is present in the coordination complex should be belonging to 3D. That means it should be from 3D transition series. It could be manganese, it could be zinc, it could be copper, it could be nickel, it could be chromium. Am I clear, everyone? Right, and further, beta, this central metal atom or this central metal ion should have oxidation state of +2. Okay, this central metal atom or this central metal ion should have the oxidation state of +2. Okay, beta, then in that particular case, Raje, we have only oxygen and nitrogen donors as strong field ligands. That means here in oxygen, extremely sorry, I have said a wrong line. I am rectifying it, beta. Right. So what I am saying, whenever we have a complex of coordination number 6, central metal ion in that particular complex of 3D, oxidation state of central metal atom or central metal ion as +2 beta, right. So in that particular case beta, here carbon donors, that means CO and Cn minus, they both will act as a strong field ligands. All the nitrogen donors, oxygen donors and halogen donors, they will act as a weak field ligand. Is it clear everyone? Is it clear everyone? Yes. Is it clear? If it is clear, give me green hearts in chat box. If it is clear, give me green hearts in the chat box. Clear everyone? Clear everyone? Clear? Okay. Now, if I have a complex in which the coordination number is 6, central metal ion is again of 3D, right? The oxidation state on central metal ion is +3. Okay, the oxidation state on central metal ion is +3. Am I clear everyone? The oxidation state on central metal ion is +3. Am I clear everyone? Fine. In this particular case, beta, carbon donors are CO and Cn. They both are carbon donors, and nitrogen donor, which is NH3. All of them will be acting as a strong ligand or a strong field ligand. Clear? Right? H2O beta, H2O, which is an oxygen donor. It might behave as strong field or it might behave as weak field. It is said to behave as strong field ligands only in the case of cobalt 3+. Okay. So in the case of cobalt 3+ beta, if you are having an octahedral complex, right, then only in the case of cobalt 3+, all the oxygen donor, okay, all the oxygen donor, whether you have H2O, whether you have C2O4 2- or whether you have OH-, all these oxygen donor will act as a strong field ligands. Am I clear? They will act as a strong field ligands. Is it clear to you all everyone? Is it clear to you all everyone? Clear or not? Clear? Okay, right. And if I talk about halogen donors beta, if I talk about halogen donors beta, that means iodine, bromine, chlorine, fluorine, they will behave as a weak field ligand. Okay, they will behave as a weak field ligand. Am I clear everyone? Yes, am I clear? Okay, so are these points clear to you all everyone? Are these points clear to you all everyone? Clear? Okay, fine. So now let's do the questions. Now see beta, if you have to solve the question based on VBT, there are certain steps you need to follow. Okay, first of all, I will see the complex. I have been given this complex. This is ferrocyanide ion, FeCN whole 6, 4- ion. Okay, right. Now in this complex, first you see that what is the oxidation number of the central metal atom or the central metal ion, right? Suppose I found out the oxidation number of the central metal atom or the central metal ion is +2, right? You can found by X method. If the oxidation state of Fe is X, we have 6Cn, so 6 into -1 equal to -4. So from here X minus 6 equals to -4. So from here X comes out to be +2. Okay, X comes out to be +2. Am I clear? Okay, am I clear? Fine. So here that means Fe said to be present in +2 oxidation state. Okay, so the very first job is that you have to find the oxidation state of central metal atom or central metal ion. Am I clear? You have to find the oxidation state of central metal atom or central metal ion. Okay, the very first job is this. Clear? The very first job is this. Fine. So here if I talk about Fe beta, what is the valence shell electronic configuration of Fe bacha? It is basically 4s2 3d6, right? So if I have Fe2 plus bacha, the electronic configuration will be 3d6. Why? Because if I have to form +2 oxidation state beta, then definitely 2 electron has to be eliminated from 4s, right? Then definitely 2 electrons has to be eliminated from 4s, right? So in this particular case, electronic configuration comes out to be 3d6, right? So in this particular case, electronic configuration comes out to be 3d6, right? So if I have Fe2 plus, okay, if I have Fe2 plus beta, right, and here I have 3d of Fe2 plus, here I have 4s of Fe2 plus, and here I have 4p of Fe2 plus. Am I clear beta? Okay, so I've been asked to follow a sequence. In that sequence, first I have to find the oxidation number of central metal atom or the central metal ion, and the second step is to write the electronic configuration of the given oxidation state. I have done both the things, and then also I have written these things. Am I clear, everyone? Now, the next step is that you have to see the coordination number. Here the coordination number is 6. If the coordination number is 6, then hybridization could either be sp3d2 or d2sp3. Now, whether it will be sp3d2 or d2sp3 beta, it is decided on the basis of the fact that whether you have a strong ligand or whether you have a weak ligand, right? So it is basically decided by whether the given ligand is a strong ligand or a weak ligand, right? Now here I have Fe2 plus and here I have Cn minus. Now quickly tell me in the chat box, I have told you that for 3D series transition metal atom or a transition metal ion, right? I have told you that for a 3D series transition metal atom and the transition metal ion, right, if the oxidation state is +2, then in that particular case, Cn is going to act as a strong field ligand. Yes, Cn is going to act as a strong field ligand. So in this particular case, beta, Cn will act as a strong field ligand, right? Okay, that means here Cn will act as a strong field ligand, and if it is acting as a strong field ligand, beta, then it can cause pairing, right? Earlier, if I talk about Fe2 plus, it is said to have 6 electrons in 3D beta. It is said to have 6 electrons in 3D beta. Now, whenever Fe2 plus is forming complex with Cn, that means we have Fe in this particular coordination complex, bacha, right? We have Fe in this particular coordination complex beta. Here Cn acts as a strong field ligand. Now, if Cn is acting as a strong field ligand, then it can cause a pairing of electrons. If Cn is acting as a strong field ligand, then it can cause a pairing of electron, and if there occurs the pairing of electrons, beta, how the pairing will occur? This electron will go here, this electron will go here. So I will have 1, 2, 3, 4, 5, 6. Right now here the 2 inner 3D is available, 1 4s is available, 3 4p are available. Now they will undergo hybridization. Okay, they will undergo hybridization, and which hybridization they will undergo, beta? They will undergo D2sp3 hybridization. Okay, they will undergo D2sp3 hybridization. Am I clear? They will undergo D2sp3 hybridization. Am I clear, everyone? Yes. Am I clear, everyone? Am I clear, everyone? They will undergo D2sp3 hybridization. Okay, right, fine. Now, whenever they will undergo, if 6 atomic orbitals are combining, right, they will form 6 D2sp3 hybrid orbitals, right? They will form 6 D2sp3 hybrid orbitals. So, if it is D2sp3, this is again D2sp3, this is again D2sp3, this is also D2sp3, beta, this is also D2sp3, and this is also D2sp3. I have 6 D2sp3 hybrid orbital, and beta, here Cn minus act as a 2 electron donor, right? I have told you whenever there occurs a formation of sigma coordinate bond, every ligand basically acts as a 2 electron donor. I have told you earlier in this class. Yes or no, beta, right? So in each D2sp3 hybrid orbital, beta, there occurs the overlap with the filled orbital of the ligand, which contains 2 electrons, right? That means each ligand, each Cn minus will donate 2 electrons, right? Each Cn minus will donate 2 electrons into D2sp3, right? And there occurs the formation of 6 sigma coordinate bonds, okay, between the hybridized orbitals and the filled orbitals of the ligands. Okay, right? Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Yes. Am I clear? Okay. Am I clear? Fine. So here this complex will be formed. Okay, now quickly tell me what is the hybridization of this particular complex, beta? What is the hybridization? It is D2sp3, right? Next, bacha, next. Is it an inner orbital complex or an outer orbital complex? Ma'am, it is an inner orbital complex. Why? Because inner 3D is involved in the hybridization. That is why it will be a inner orbital complex. Okay, it will be a inner orbital complex. I hope this point is clear to you all. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Okay. Further, bacha, can you see any unpaired electron right here? All the electrons are paired, right? All the electrons are paired. If all the electrons are paired, beta, such complex is said to be a diamagnetic complex. Okay, such complex is said to be a diamagnetic complex, right? Whenever we have a strong field ligand, beta, strong field ligand always cause pairing of electrons, so there are always less number of unpaired electrons. And whenever the number of unpaired electrons are less, the spin of the complex is less. So such complexes are known as low spin complexes. Okay, such type of complexes are known as low spin complexes. Am I clear? Such type of complexes are known as low spin complexes. Am I clear, everyone? Right. Further, beta, there is a formula of finding the magnetic moment, right? I have told you in D block, beta, magnetic moment, okay, magnetic moment mu is basically calculated with the help of a formula which is root of n into n plus 2 Bohr magnetron. Okay, the formula is n into n plus 2 Bohr magnetron. Now n right here basically stands for, beta, number of unpaired electrons, right? N basically stands for number of unpaired electron, beta. Yes or no? N basically stands for number of unpaired electrons, Rajay. Yes or no? Yes, here N basically stands for number of unpaired electrons. Fine. So now here, look at the electronic configuration. Is there any unpaired electron? No, all the electrons are paired. That means here number of unpaired electron is 0. So when you will put 0 in the above formula, beta, 0 into 0 plus 2. So from here the magnetic moment comes out to be 0 Bohr magnetron. Okay, so from here the magnetic moment comes out to be 0 Bohr magnetron. Am I clear, everyone? Yes, am I clear, everyone? Clear or not? Clear, everyone? Is it clear? Yeah, it must be clear. Now let's just move ahead. Let's come to the another complex, which is FeH2O whole 6 3 plus, right? So first step is, beta, I have to see which central metal atom is present. It is Fe. It is said to have an electronic configuration of 4s2 3d6, bacha, right? The electronic configuration is 4s2 3d6. Am I correct? It is said to be 4s2 3d6. Yes or no? Yes or no? Yes, ma'am. Yes, ma'am. Yes, ma'am. Okay, right. Now here, if I talk about beta Fe3 plus here, if I talk about Fe3 plus right here, beta, okay, so if I talk about Fe3 plus right here, bacha, it will be formed by the loss of 3 electrons. That means 2 from 4s and 1 from 3d. So here the configuration will be 3d5. Beta, I have told you for plus 3 oxidation state, Baraje, for plus 3, H2O can act as a strong field ligand only in the case of cobalt 3 plus. For Fe3 plus, H2O will act as a weak field ligand. Please keep this thing in mind. For plus 3, beta, for Fe plus 3, please keep this thing in mind that H2 will be a WFL, weak field ligand. Okay, right? Now, if I talk about, beta, Fe plus 3, okay, so it is said to have 5 unpaired electrons in 3D, right? 4s is vacant, 4p is vacant, 4d is vacant, right? Now here, if we have Fe3 plus in this particular complex, which is FeH2O whole 6 3 plus. Am I clear, beta? Am I clear, beta? Am I clear? Yes. Am I clear, everyone? Okay, right. So here you have to see the coordination number, beta. Coordination number is 6. That means either the hybridization could be sp3d2 or it could be d2sp3, right? Either the hybridization could be sp3d2 or either it could be d2sp3, everyone, right? There could be one of the two cases. Either it is sp3d2 or it is d2sp3, everyone. Am I clear? Right. So now here, since H2O is acting as a weak field ligand beta, it won't be able to cause any pairing in 3D. So ultimately, the outer d orbitals have to be utilized in order to undergo hybridization. So 1,4s, 3,4p and 2,4d will be involved in hybridization beta. Am I clear? Am I clear? Am I clear? To form 6 sp3d2 hybrid orbital. In each sp3d2 hybrid orbital, water will donate 1 electron pair, and there occurs the formation of 6 coordinate bonds right here, and we will have an octahedral complex, right? So here we have sp3 d2 hybridization. The complex is octahedral. Okay, the complex is octahedral. Further beta, I have unpaired electrons, so the complex is paramagnetic. Okay, the complex is paramagnetic. Further beta, here there are a lot of unpaired electron, and the ligand is weak field. Whenever the ligand is weak field beta, whenever the ligand is weak field, there are lot of unpaired electrons. So the spin is high, right? The spin is high. That means here beta, it is known as high spin complex. Okay, it is known as a high spin complex, right? Whenever a ligand is strong field, it causes pairing, right? So there are lesser number of unpaired electron. That is why in the previous case, the complex which was formed was basically a low spin complex, right? However, in this particular case beta, high spin complex will form. Okay, right. Now since here outer d orbital is involved, so it is outer orbital complex. Very good, it is outer orbital complex. Okay, it is outer orbital complex, right? And here the number of unpaired electron n are 5. So you can find the magnetic moment mu. The formula will be 5 into 5 plus 2 Bohr magnetron. Okay, so it is root 35 Bohr magnetron. So from here the magnetic moment Q can be calculated. Am I clear? From here the magnetic moment mu can be calculated. Am I clear, everyone? Am I clear? Okay, am I clear, everyone? Yes, am I clear or not? Clear? Right? Okay. Now, next beta, I have FeCl whole 6. FeCl whole 6. So here beta, Fe plus 2 is present. Now, do one thing. Tell me directly. Okay, tell me directly. Here, whether the complex is inner orbital or the outer orbital, whether the hybridization is D2sp3 or sp3d2. Tell me directly, everyone. Tell me directly. Here I have Fe2 plus. Okay, so Fe2 plus is said to have an electronic configuration of 3d6, right? That means if I have Fe2 plus in 3d beta, in 3d I have 6 electrons. Okay, I have 6 electrons, right? This is 4s, this is 4p, this is 4d. Quickly tell me in the chat box beta. Yes, outer. Very good beta. I have just told you for plus 2 oxidation state and for plus 3 oxidation state beta, right? If the central metal atom is of 3d series, then Cl is going to act as a weak field ligand. If Cl is going to act as a weak field ligand, it won't cause any pairing, right? And if it won't cause any pairing beta, then 3d will not be available in order to participate in hybridization in FeCl whole 6 4 minus complex. Am I clear? Then ultimately beta 1,4s, 3,4p and 2,4d have to be involved in the hybridization, right, in order to form D2sp3 hybrid orbitals. So here I have 6 D2sp3 hybrid orbitals. Okay, there I said to have bacha 6 D2sp3 hybridized orbital, and in each D2sp3 hybridized orbital beta Cl will come and donate its 1 electron pair, right? So it is D2sp3 hybridized complex bacha. It is octahedral. By mistake I have written D2sp3 beta, it is sp3d2. Extremely sorry. I think this much minor errors are allowed at 1 p.m. Okay, so this much minor errors are allowed at 1 p.m. So it is not D2sp3, it is sp3d2. I myself have told that the outer D will be involved. So the hybridization will be sp3d2, and in each sp3d2, 1 electron pair will be donated by Cl minus ion. Am I clear, everyone? Okay, no problem. Fine. So here the hybridization is sp3d2 and the complex is octahedral, right? The complex is octahedral. It is said to be an outer orbital complex. Okay, it is said to be an outer orbital complex. Further, it is said to have lots and lots of unpaired electrons. So, it is paramagnetic in nature. Okay, it is paramagnetic in nature. Further, beta, it is high spin complex. There are 4 unpaired electrons. So, you can yourself found the magnetic moment. It's easy now. It's easy. Am I clear? Okay, right, fine. Now, next we have is Fe Cn whole 6 3 minus beta. So, here I have is Fe plus 3 beta. Now, Fe plus 3 is said to have 3d 5 electronic configuration, right? Fe plus 3 is said to have 3d 5 electronic configuration. That means 3d have 5. This is 4s. This is 4p. Now here beta, Cn minus is said to act as a strong field ligand for plus 3 transition metal ion. If that transition metal ions belongs to 3d series, right? So here Cn act as a strong field ligand. If Cn act as a strong field ligand beta, so whenever Fe is present in this particular complex beta, what will happen? It will cause pairing of electron, right? So these 2 electrons will get paired beta. These 2 electrons will get paired, right? So here I will have 2 inner 3D available to participate in hybridization, right? Okay, so here there occurs which hybridization beta? D2sp3, right? So D2sp3 outer orbital complex is formed. Okay, outer orbital complex is formed. Now since it is having 1 unpaired electron beta, so it will be still be paramagnetic, because P Lakshmi, it won't be diamagnetic beta. Yes, it is a low spin complex. So whenever you have a strong field ligand, the resulting complex is definitely a low spin complex. However, it still has 1 unpaired electron beta. Okay, it still has 1 unpaired electron, and if it still has 1 unpaired electron beta, then it will definitely be paramagnetic in nature. Okay, it will be definitely paramagnetic in nature. Am I clear? It will be definitely paramagnetic in nature. Am I clear? It will be definitely paramagnetic in nature. Okay, clear? It will definitely be paramagnetic in nature. Easy squeezy, lemony juicy, right? Yes, it is easy squeezy. Okay, so now here I have one of the important complex beta. This is very important. Why? Because here people generally commit mistakes. Okay, so it is MnCn whole 6 3 minus. Okay, so it is MnCn whole 6 3 minus. What I am doing, I am completing VBT for the complexes in which the coordination number is 6. Then I will take a break of 5 to 10 minutes. Then I will do the complexes with coordination number 4 and crystal field theory. Then again a 5 to 6 minutes break, and then the coordination isomerism. But the class will go till 3 or 3:30. 3 or 3:30. It will extend to 3 to 3:30. It will get extended to 3 to 3:30. Okay, I have to complete this chapter in one go. So it will take 3 to 3:30. Fine. Okay. Am I clear, everyone? Fine. Okay. So here I have Mn. Here I have Mn plus 3. See beta, if I talk about Mn as such in general, now Mn is said to have Z25, and whenever I have to write the valence shell electronic configuration for Mn, okay, it is 4s2 3d5. Okay, it is 4s2 3d5. This is the general electronic configuration of Mn. Am I clear? This is the general electronic configuration for Mn, which is 4s2 3d5, which is 4s2 3d5. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Okay, right. So if I have to write the electronic configuration of Mn plus 3, okay, Mn plus 3, then here 2 electrons will get eliminated from 4s, and bacha, 1 electron will get eliminated from 3d. So it will be 3d4, right? That means if I have Mn3 plus bacha, the electronic configuration will be 3d4. That means in 3d I have 4, this is 4s and this is 4p. Am I clear? This is 3D, this is 4s, this is 4p. Okay, right? Now, if I talk about for +3 oxidation state beta, right, for +3 oxidation state, I have just told you that CN is said to behave as a strong field ligand. And what student thinks that, ma'am, if CN acting as a strong field ligand, then in MnCN whole 6 3 minus, ma'am, there will occur the pairing, and here the 2 electrons will get paired, and here the hybridization will D2sp3. You are absolutely correct. The hybridization will definitely be D2sp3. But my question is, earlier there were 4 unpaired electrons, right? If I will do the pairing of mere just 1 electron, bhai, if I do the pairing of just mere 1 electron, okay, that means this electrons gets here. Then also the 2,3D will be available for hybridization, right? Then also the 2 inner D will be available for hybridization, yes or no? Still the 2 inner D are available for hybridization, yes or no, beta? They are still available for hybridization, yes or no? Yes, ma'am, they are still available for hybridization, right? Okay, fine. So why to do the excessive pairing? Pairing also takes bacha energy. So that doesn't mean that how many electrons you have, you will cause the pairing of them. No, you will do the pairing of only those electrons which will make you available the inner D. Now here, by pairing just 1 electron, we have 2 inner D. Am I clear? Okay, right. So it is said to be a paramagnetic compound. Why? Because it is said to have 2 unpaired electrons, right? So here, beta, again D2sp3, inner orbital, okay, D2sp3, inner orbital, right? And the resulting complex is paramagnetic, okay? And the resulting complex is paramagnetic. Am I clear, everyone? The resulting complex is paramagnetic. Am I clear, everyone? Am I clear, everyone? Clear? Okay. Fine. Next I have is CO, H2O whole 6 2 plus beta. See, here we have cobalt 2 plus, right? And I have told you, beta, I have told you just for cobalt 3 plus, okay, just for cobalt 3 plus, H2O can act as a strong field. If you have cobalt 2 plus, it will act as a weak field ligand, okay, it will act as a weak field ligand, right? So in this particular complex, beta, here H2O will definitely act as a, weak field ligand, okay, it will act as a weak field ligand, right? So if I have cobalt, beta, it is said to have a configuration, valence shell electronic configuration of 4s2 3d7, right? So if you have cobalt 2 plus, beta, the configuration turns out to be 3d7. That means you have 7 electrons here, okay? So here in the case of cobalt 3 plus, you have 7 electrons, 1 2 3 4 5 6 7 in 3d, beta, okay? This is 4s, okay, this is 4p, and this is 4d, okay, this is 4d. Am I clear, everyone? This is 4d, right? This is 4d. Am I clear? This is 4d. Okay, bacha, this is 4d. Now here, bacha, since this H2O is acting as a weak field ligand, so here 1 4s, 3 4p and 2 3d will get involved in hybridization to form sp3d2 6 hybrid orbitals. That means here the hybridization is sp3d2, and if here the hybridization is sp3d2, beta, it will be a outer orbital complex, okay, it will be a outer orbital complex, and it will be a paramagnetic complex since it has 3 unpaired electrons, okay, it will be a paramagnetic complex. Am I clear? It will be a paramagnetic complex. Am I clear? It will be a paramagnetic complex. Am I clear, everyone? Okay, fine. Okay, so let's just move ahead to COH2O 3 plus, okay, COH2O 3 plus. Now here beta, I have cobalt 3 plus, and I have told you for cobalt 3 plus, H2O will act as a strong field ligand, okay. So here H2O will act as a strong field ligand. Am I clear? Here H2O will act as a strong field ligand. Dinesh Bishnoi ma'am, English. Beta, this is an English channel, so I have to teach in English. Am I clear? I'm so sorry, I have to teach in English because this is an English channel. Okay, right, fine. Okay, so here I have is cobalt 3 plus, bacha. Here I have is cobalt 3 plus. Fine. So if I have cobalt whose Z is equals to 27, the electronic configuration is 4s2 3d7. Clear? If I have cobalt 3 plus, the electronic configuration turns out to be 3d6. Okay, so here the electronic configuration turns out to be 3d6. Okay, so this is cobalt 3 plus. So here I have 6 electrons. Okay, 6 electrons. Now here H2O is going to act as a strong field ligand. So whenever you have this particular complex, right? So when CO is present in this particular complex, beta, there will occur the pairing of these two electrons, right? There will occur the pairing of this particular electron. So here there will occur the pairing, right? After pairing, 2 3d, 1 4s and 3 4p will undergo hybridization to form 6 d2 sp3 hybridized orbital, and it will be an inner orbital complex which is diamagnetic. Why it is diamagnetic, beta? Because there is no unpaired electron. Okay, it is an inner orbital complex first of all. It is an inner orbital complex first of all, beta. Right, and it is diamagnetic in nature, and it is diamagnetic in nature. Am I clear? And it is diamagnetic in nature. Am I clear, everyone? Am I clear, everyone? Clear? Okay, it is diamagnetic in nature. Okay, so now let's just move ahead, everyone. Let's just move ahead, everyone. Here I have written two complexes, right? One is cobalt 3 plus, another one is cobalt 2 plus. So for 3 plus, NH3 is a strong field ligand. For 2 plus, NH3 is a weak field ligand. Fine. So here, since NH3 is acting as a strong field ligand, beta, so here the hybridization will be D2sp3 and here will be sp3d2. Okay, so we can just add on to our, notes. Fine, these two are important complexes. Okay, everyone. So the last but not the least, I have to make you write one important note right here. The important note is, beta, if you have D0, D1, D2, D3 configurations, beta, then in these configurations, the central metal atom or the central metal ion, okay. So if we have central metal atom or central metal ion, Telugu industry, ma'am, please explain textbook questions. Beta, all these are questions of NCERT. If you will open the NCERT, you will find these questions only given, right? So these are the only questions which are given in NCERT. I have took all the possible example. So what else do you want? Huh? What else do you want? I have taken into consideration all examples of NCERT. What else do you want? Do you want extra? Yes, it box questions, beta. If I am telling you an example, you can practice them by yourself. I have taken into consideration 20 examples. Rest 10 examples should be done by you. Right? Then why I am telling you the concept? Why I am telling you the concept? Yes, why I am telling you the concept, bacha? Am I clear what I am trying to say? Am I clear what I am trying to say? Clear? Okay. Now, so if I have D0, D1, D2, D3 configuration of the central metal atom or the central metal ion. Okay. So if I have D0, D1, D2, D3 configuration of the central metal atom or the central metal ion, bacha. So in these particular case, always two inner 3D will be available. Right, here always two inner 3D will be available, right? That means they will always undergo D2sp3 hybridization, and they always will form inner orbital complex. Okay, they will always form inner orbital complexes. Am I clear, everyone? Am I clear, everyone? Clear? Okay, for example, you have scandium 3 plus. Now scandium 3 plus, how many electrons in scandium 3 plus? Beta, scandium is said to have a configuration of, beta, scandium is said to have a configuration of 4s2 3d1. So if it has scandium 3 plus, then here I have D0 beta. In scandium 2 plus, I have D1. Okay, in titanium 2 plus, I have D2. Okay, and in vanadium 2 plus, scandium, titanium, vanadium, I have D3 configurations beta. Clear? So here I have 3D0, here I have 3D1, here I have 3D2, here I have 3D3. So here, in any of the configuration, the inner 2D will always be available. Okay, the inner 2D will always be available. So they will always formed inner orbital complex, and here always the hybridization is D2sp3. Am I clear, everyone? Am I clear, everyone? Okay, if you have D4, D5 and D6 configurations, okay, if you have D4, D5 and D6 configurations beta, clear? Here whether the complex will be inner orbital, whether the complex will be outer orbital, that depends upon the ligand. Okay, if the ligand is a weak field ligand, if the ligand is a weak field ligand, beta, then that weak field ligand won't cause pairing, and if it won't cause pairing beta, then ultimately outer D will be used and the hybridization is sp3d2. Am I clear? The hybridization will be sp3d2. Clear? The hybridization will be sp3d2. Okay, right. Talking about strong field ligand beta, strong field ligand. Talking about strong field ligand beta, it will cause pairing and the hybridization will be D2sp3. Clear? After that we have D7, D8, D9 and D10 beta. Right, you have D7, D8, D9 and D10, whether the ligand is strong field, whether the ligand is weak field. Okay, right, for both beta, strong field ligands and weak field ligands, whether you have strong field, whether you have weak field beta, here never the inner 2D will be available. So ultimately the outer 2D has to be involved. Am I clear? So here always the hybridization is sp3d2. For example, you have zinc 2 plus in this particular complex. Now zinc 2 plus are said to have 10 electrons in 3D. Am I clear? It is said to have 10 electrons in 3D. Right? Now if it is said to have 10 electrons in 3D beta, then definitely the outer D will participate. So here definitely the hybridization will be sp3d2. Okay, so here the hybridization will be definitely sp3d2. Am I clear, everyone? Am I clear, everyone? Clear? Okay, right. So here we have completed the coordination number 6 in VBT. Coordination number 4 is left, which is merely of 10-15 minutes. Then we will do CFT, which is of 45 minutes to 50 minutes, and then 1 hour we have reserved for the isomerism. That means total we will be needing 2.5 to 2.5 hours maximum. Okay, so we will be able to complete this chapter. So here I am taking a break of 10 minutes because I need to breathe. So here I am taking a break of 10 minutes. We'll meet you after 10 minutes. Please make sure to join the session for my morale boost after 10 minutes. Am I clear? So please rejoin after 10 minutes. Am I clear, everyone? Okay. So let's meet after 10 minutes. Hi everyone, we are restarting. Okay, so we are restarting it once again. Everyone, please rejoin. Everyone, please rejoin. Everyone, please rejoin. Okay, okay, everyone. So we are restarting. We are restarting. Can I see all of you right here? Can I see all of you right here? If you guys are still here, then please send me some green hearts so that we can proceed ahead, okay, so that we can proceed ahead. Hi P Lakshmi, Gauri, Madhurima, hi bacha, hi. Okay everyone, so we are restarting it once again. We are restarting it once again. Hi Radha, sorry I took 2 to 3 minutes extra. Extremely sorry for this. Okay everyone, so we have completed till coordination number 6, right? Now let's come to coordination number 4 beta. See, if I talk about coordination number 4 Rajay, then here we have to study. Here when this session will get over beta, this session will get over in 2 hours approximately, like 2 hours or something, 3:30 or 4 it will take. Right, it is a big chapter and I have covered all the topics, so it will take some time, right everyone? Okay, so let's come to the coordination number 4. So beta, in the case of coordination number 4, we can have two possible hybridizations. Either it could be sp3 or it could be dsp2. Fine, okay. So whenever we have sp3 hybridization beta, in that particular case, okay, in that particular case Rajay, the geometry of the resultant complex is basically tetrahedral, okay. So the geometry of the particular complex is tetrahedral. Okay, and if we have dsp2 beta, in that particular case the geometry of the resultant coordination compound is square planar, right? It is generally square planar, right? But just see, it's very simple thing that whenever dsp2 hybridization is involved, in that particular case inner D is involved, and inner D is involved when it is available, and generally strong field ligands creates inner D, right? So generally strong field ligands basically undergoes the strong field ligands basically causes the pairing, due to which there occurs the availability of inner D orbital, and then there occurs the hybridization dsp2. Am I clear? However, in the case whenever we have a weak field ligand, but a weak field ligand won't cause any pairing, right, of the inner D electrons, and ultimately S and P have to undergo hybridization. So in that particular case we have sp3 hybridization and the geometry is said to be tetrahedral. Am I clear? And the geometry is said to be tetrahedral. Okay, right. Now here ma'am, in order to decide whether we have sp3 hybridization or whether we have dsp2 hybridization, ma'am, we need to have an idea regarding the ligand, right? Whether it is strong field, whether it is weak field. So for that I am giving you an order beta. So for coordination number 4, okay, this is for the coordination number 4 bacha. For coordination number 4, if you have central metal atom or central metal ion of 3D, and this central metal atom or central metal ion is said to have +2 oxidation state, okay, this central metal atom or central metal ion is said to have +2 oxidation state bacha, right? In this particular case, keep in mind that we have all nitrogen donors and all carbon donors. Carbon donors are CO and CN, okay, and nitrogen donors are En, NH3 beta. They will act as a strong field ligands. However, oxygen donor, that means you have H2O, and halogen donors, that means fluoride, chloride, bromide, iodide, they will act as a weak field ligand. Am I clear everyone? Okay. Similarly beta, if we have a coordination complex, okay, which is said to have coordination number 4, right? Here central metal atom is of 3D and it is said to be present in +3 oxidation state, beta, then all the ligands, whether halogen, whether oxygen, whether nitrogen, whether carbon, all these will be the strong field ligands. Am I clear everyone? Okay, right. Now if I talk about beta all the complexes in which the coordination number is 4 and the central metal ion is either of 4D or 5D series, okay, 4D transition series or 5D transition series, then irrespective of the oxidation state, whether it is +2, whether it is +3, whether it is +4 beta, all the ligands will act as a strong field ligand. Am I clear everyone? Am I Clear everyone? So I made the point very clear. Fine. Now let's just move ahead. Beta. Here is one important point, that with palladium 2 plus and platinum 2 plus, beta. See, palladium 2 plus belongs to 4D and palladium 2 plus belongs to 4D and platinum 2 plus basically belongs to 5D, beta. Here, see, if they belongs to 4D or 5D series, beta, it doesn't matter which ligand is present, right? Irrespective of the nature of the ligand, beta, right? We don't care which ligand is present, right? It will act as a strong field ligand, right? It will act as a strong field ligand, okay? So whenever palladium 2 plus, platinum 2 plus, since they belongs to 4D series and 5D series, beta, then it doesn't matter, beta, which ligand we have in the complex with coordination number 4, it will, beta, act as a strong field ligand, and here always the hybridization will be DsP2, bacha, and here always the square planar complex is formed. That's it. Okay. Here always square planar complex is formed. That's it. Am I clear, everyone? Clear? Okay. Right. For example, I have NiCN whole 4 2 minus. Okay. I have NiCN whole 4 2 minus. Right. So here I have, bacha, nickel 2 plus, central metal ion is nickel 2 plus. Okay. Right. If I talk about nickel, beta, in general, nickel is said to have an atomic number of 28, right? And if I talk about the valence shell electronic configuration, Rajay, it is said to be 4s2 3d8. Okay, it is said to be 4s2 3d8. Am I clear, everyone? It is said to be 4s2 3d8. Now, if I have nickel 2 plus, beta, if I have nickel 2 plus, then 2 electrons will be lost from 4s, so I will have 3d8, right? That means if I have Ni2 plus, bacha, I will have 1, 2, 3, 4, 5, 6, 7, 8 electrons. So I have 3d8 configuration. It is 3d, it is 4s, it is 4p. Okay, it is 3d, it is 4s, it is 4p. Am I clear, everyone? Okay, right. Now here, bacha, if I talk about Cn, I have just told you, beta, for +2 oxidation state, if the transition metal belongs to 3D, Cn is said to act as a strong field ligand, and if it is said to act as a strong field ligand, beta, there will occur pairing of electrons. Okay, this electron will get paired, beta, when nickel is present inside the complex NiCN whole 4 2 minus. Am I clear, bacha? Am I clear? Okay, so now the inner D and 4s and, bacha, 2 4p. Okay, so inner 1 3d, 1 4s and 2 4p will undergo hybridization, bacha, which is DsP2, right? And there occurs the formation of square planar complex. Okay, there occurs the formation of square planar complex. Okay, there occurs the formation of square planar complex. Am I clear? Okay, there occurs the formation of square planar complex. This is diamagnetic with no unpaired electron, right? And we do not define inner orbital and outer orbital for coordination number 4. It is merely defined only in the case of coordination number 6. Am I clear? We do not define inner orbital and outer orbital for coordination number 4. Am I clear, everyone? Okay, fine. So let's just move ahead, bacha. Let's come to NiCl whole 4 2 minus. Let's come to NiCl whole 4 2 minus, bacha. Okay, now here if I talk about NiCl whole 4 2 minus, bacha, see, for nickel 2 plus, Cl will act as a weak field ligand, right? It will act as a weak field ligand, right? So if I have nickel 2 plus, bacha, right, it is said to have a configuration of 3d8. That means here I have 8 electrons in 3d, bacha. Here I have 8 electrons in 3d, bacha, right? So when I have this nickel in this particular complex, which is NiCl whole 4 2 minus, bacha, here we have 4s and 4p only available to participate in hybridization. Why? Because 3d is not available, it is filled. right? Cl is weak field, it won't cause any pairing. So ultimately here beta 1 4s and 3 4p will undergo sp3 hybridization. That is why the geometry of this particular complex is tetrahedral. Am I clear? The geometry of this particular complex is tetrahedral. Is it clear or not? Clear everyone? Clear? Okay, it must be clear to you all, everyone. Now let's just move ahead. Let's move to the another complex, which is NiCO whole 4. Okay, which is NiCO whole 4. We are soon about to over VBT beta. Then we will basically study CFT. Right, we will complete CFT in 1 hour anyhow. We will complete it in 1 hour anyhow. Okay. Now, I have NiCO whole 4 beta. Here nickel is said to be present in 0 oxidation state beta. Okay, right. That means in 4s I have 2 electrons and in 3d I have 8 electrons. Okay, so here 2 electrons are available in 4s and in 3d I basically have 8 electrons. Am I clear beta? Right, this is the electronic configuration of nickel 2 plus. But see, here the coordination number is 4. So either the hybridization should be DsP2 or sp3d2. Sorry, here either the hybridization is DsP2 or sp3. Two possibilities are there, right? Now this depends upon ligand now beta, right? Now here CO act as a strong field ligand. I've just told you, right? Here CO act as a strong field ligand, and if it is acting as a strong field ligand beta, what it will do? It will basically cause pairing of these two electrons. So it will come here and here. Okay, right? Now even after pairing, the D is not available to participate in hybridization, right? That is why ultimately here 1s and 3p will undergo hybridization, right? Here 1s and 3p will undergo hybridization to form 4sp3 hybrid orbitals. Am I clear? To form 4sp3 hybrid orbitals. Am I clear, everyone? Okay. Fine. So here the hybridization is sp3 and the complex form is tetrahedral. Okay, the complex form is tetrahedral. Am I clear, everyone? Is it clear? Okay, fine. Let's just move ahead, bacha. Now here comes in very important complex, which is CuNH3 whole 4. See bacha, I have told you for +2 oxidation state. Okay, for +2 oxidation state, I have already told you, Rajay, NH3 said to behave as a strong field ligand. Right, for +2 oxidation state, I have already told you, bacha, for +2 in octahedral, for +2 in the complex of coordination number 4. Right, here NH3 is said to behave as a strong field ligand. I have already told you, Rajay. I have already told you. Yes or no? Yes, ma'am. Yes, ma'am. Yes, ma'am. Okay, right. So here I have copper 2 plus beta. If I talk about copper in general, it is said to have a valence electronic configuration of 4s1 3d10. It has an exceptional electronic configuration, right? So if I have copper 2 plus bacha, it is said to have 3d9 electronic configuration. That means in copper 2 plus, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. Now you must be thinking, ma'am, although NH3 is said to behave as a strong field ligand, right? Although NH3 is said to behave as a strong field ligand, however, bacha, there is no pairing which is possible right here. That means ultimately here 1s and 3p have to be utilized in hybridization, and here the hybridization should be sp3. Right, but experimentally it has been observed beta, that the hybridization of this particular complex is D2sp3. Right, now why it is D2sp3 beta? Because it is a phenomenon which has been observed by Huggin. According to Huggin, Huggin is a scientist, right? Huggin is a scientist. So Huggin have observed one phenomena. He have observed that it has been found experimentally that this one electron which is present in 3D gets excited to 4p. Okay, so the one electron which is present in 3D gets excited to 4p. Right, now when it gets excited to 4p beta, so here I have one D available, one S available, 2p available, and here the hybridization is DsP3. sp2, and hence the resultant complex is square planar. Okay, hence the resultant complex is square planar. Am I clear? Hence the resultant complex is square planar. Okay, right. Now we have a last complex, PDCl whole 4 2 minus beta. Here we have palladium 2 plus. See bacha, I have already told you that for palladium 2 plus bacha, you have any ligand. Now since palladium is a 4D series, that ligand will behave as a strong field ligand. That means Cl will behave as a strong field ligand right here. Okay, this will behave as a strong field ligand here. If I talk about the electronic configuration of palladium beta, it is basically 4D10 5s0. It is said to have an exceptional electronic configuration. I hope you guys are aware. Okay, it is said to have an exceptional electronic configuration. I hope you guys are aware of this particular fact. Okay, right. It is said to have an exceptional electronic configuration, Rajay. The electronic configuration is exceptional. I have told you in D block. It is krypton 4D10 5s0. It is the only D block element which is said to have 0 electron in 5s. Okay, which is said to have 0 electron in 5s. Fine. So whenever I have palladium 2 plus beta, here 2 electrons will get eliminated from 4D. So I have 8 electrons right here. Okay, so this is 4D, this is 5s, and this is 5p. I have how many electrons, bacha? I have 8 electrons right here in the case of palladium 2 plus. Right now here, since Cl is going to act as a strong field ligand right here, bacha. Okay, since Cl is going to act as a strong field ligand right here, bacha. So this will cause the pairing, and there occurs the pairing of the electron. So ultimately I have 1 4D, 1 5s and 2 5p orbitals available for D2sp3 hybridization, and the resulting complex is square planar. Okay, hence the resulting complex is square planar. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? The resulting complex is square planar. I hope I made my point clear, everyone. Okay, right, fine. Let's just move ahead, beta. See, let's just move ahead. So here I have given certain conclusions which I have told you in today's class. You can go home and revise it. I have given you certain conclusions. Right, so now let's come directly to crystal field theory or CFT. Now quickly tell me in the chat box, is VBT clear to you all? Now can you attempt the questions of VBT? Can you attempt the question of VBT? VBT is clear to you all, everyone? Is VBT clear to you all, everyone? Yes, is VBT clear to you all, everyone? Right, you guys can attempt the questions of VBT, right? Okay, great. So now let's come to CFT. Now this is basically crystal field theory, bacha. This is basically crystal field theory. Now crystal field theory was basically given by Vleck and Bethe. The full name was Hans Bethe and John van Vleck. Okay, these two scientists. Number one, Hans Bethe. The another scientist was John van Vleck. These both have basically given crystal field theory. Okay, these both have given crystal field theory. Right, now crystal field theory basically assumes that the bond between metal and ligand is purely ionic. Am I clear? What does the crystal field theory basically assumes, beta? Crystal field theory basically assumes that the bond between metal and ligand is ionic. Am I clear? It basically assumes that the bond between metal and ligand is ionic. Am I clear, everyone? First point is clear to you all. First point is clear to you all. Clear? Okay, right. Now here, first assumption I have already explained you that here metal ligand bond is assumed to be ionic in nature. Right. Now, bacha, if it is ionic, then we know that ionic bond is nothing but it is the electrostatic forces of attraction or electrostatic forces of interaction. Am I clear, everyone? Right? Ionic bond is nothing but it is electrostatic forces of attraction or electrostatic forces of interactions, everyone. Yes, ionic bonds are nothing but the electrostatic forces of attraction, everyone. Am I clear? right? And these electrostatic forces of attraction are between ligand and the metal, right? Now what does this theory basically assumes, beta? It assumes that here metal is said to behave as a positive point charge. Okay, here metal is said to behave as a positive point charge, right? So metal is said to behave as a positive point charge. And ligand, beta, if the ligand is negatively charged, okay, if the ligand is negatively charged, bacha, then the ligand is said to behave as a negative point charge. Am I clear, beta? If the ligand is said to be negatively charged, and it is said to behave as a negative point charge, right? Now some of you may argue that, ma'am, we have negatively charged ligands such as Cl minus, Cn minus, F minus, Br minus. Okay, they can behave as a negative point charge, ma'am, and there will existing electrostatic forces of attraction as per CFT, right? That means there occurs ionic bond between metal and ligand as per CFT. Okay, but ma'am, what about those ligands which are neutral, right? For example, you have H2O. Okay, for example, you have H2O. Beta, electronegativity of oxygen is more than that of hydrogen, right? That means here oxygen, beta, oxygen is said to have a partial negative charge. Why? Because electronegativity of oxygen is more in comparison to that of hydrogen, right? So oxygen is said to have a partial negative charge, right? And a hydrogen is said to have partial positive charge. Okay, now this dipole or this neutral ligand, okay, this neutral ligand, bacha, will basically behave as a dipole. Why it will behave as a dipole? Because here is partial positive and partial negative charges which are existing, and this dipole will point the central metal atom or the central metal ion from the negative pole. That means here, if water is taken as a neutral ligand, then beta, it will point through the side of oxygen through the central metal atom or the central metal ion, and there also there will be existing electrostatic forces of attraction. Am I clear, everyone? Am I clear, everyone? Fine. So second postulate must be clear, that here metal is considered as a positive point charge and ligands are basically consisting as a negative point charge, right? If ligands are negatively charged or anionic, then they are considered as a negative point charge, and beta, if the ligand is neutral, then they behave as dipole, and then they point the central metal atom or the central metal ion from the side of the negative pole, okay, from the negative side or the negative pole of the dipole. Am I clear, everyone? Is this point clear to you all? Yes. Is this point clear to you all, everyone? Clear? Okay, right. Now let's just move ahead. Let's just move ahead. Now see, bacha, this electrostatic forces of attraction between metal and ligands occur only when there occurs the formation of coordination complex or there occurs the formation of coordination compound, beta. Am I clear? Am I clear? Am I clear? Yes. Am I clear or not? Clear? Right. Now think of a situation, beta, when central metal atom or central metal ion is not said to form the coordination complex or complex compound, beta. In that particular case, bacha, in that particular case, if the central metal atom or the central metal ion is said to consist of 5d orbitals, which are dx square minus y square, dz square, dxy, dyz, dxz. Okay, now these 5d orbitals are said to be degenerate or they are said to have equal energy. Okay, they are said to have equal energy. Am I clear, everyone? They are said to have equal energy. Am I clear, everyone? Right. Now this is the case when the metal is isolated. Okay, this is the case when metal is isolated. Here metal is not forming the complex. In that particular case, it is said to have 5d orbitals, dx square minus y square, dz square, dxy, dyz, dxz. In this particular case, beta, there is no electrostatic forces of attraction, either attraction or repulsion between the central metal atom or the ligand, right? And here the 5d orbital of the central metal atom or the central metal ion are degenerate. That means they are said to have equal energy. Okay, they are said to have equal energy. Am I clear, everyone? Clear? Okay, right. Now think of a situation. Think of a situation. First, the central metal atom or the central metal ion was isolated, right? The central metal atom and the central metal ion was isolated. Now, ligand starts approaching the central metal atom and the central metal ion. However, the ligands are still at an infinite distance, or I should say they are far away from central metal atom or central metal ion. However, they have started approaching. Okay. Now think of a situation. Think of a situation, everyone. Think of a situation. The d orbital of the central metal atom and the central metal ion, bacha. Okay. It is said to consist of electrons, right? It is said to consist of electrons, right? Talking about the ligand, it is said to have either partial negative charge if it is a dipole, or it is going to have complete negative charge if it is an anionic ligand, right? So, the negative charge on the ligand and the electrons which are present in the d orbital of the metal, bacha, right? They will definitely going to repel each other, right? They will definitely going to repel each other. Now, once the metal was isolated, that means once the metal was not forming the coordination complex, bacha, in that particular case, there was no repulsion between the electrons which are present in the d orbital and between the negatively charged ligand, right? Fine, there was no repulsion. All the 5 d orbitals were said to be degenerate, right? All were said to be degenerate, having equal energy. Now, when the ligand starts approaching, now still the ligands are at infinite distance, so there will be a little repulsion between the negatively charged ligand and the electrons which are present in the d orbital of the metal, and because of this repulsion there will occurs a little increase in the energy of the 5d orbital of the central metal atom or the central metal ion. However, when the ligands are far enough, we consider that the ligands are surrounding the central metal atom like a sphere, right, in a symmetrical manner. Okay, all the ligands are surrounding the central metal atom or a central metal ion in a symmetrical manner. Am I clear, everyone? Fine. However, since they are approaching, there will be certain repulsions, and whenever there is repulsion, there always occurs increase in energy. So the energy of the 5 degenerate d orbitals will still be same, but it will basically get increased. Am I clear? It will basically gets increased. Is this point clear to you all, everyone? Yes. Is this point clear to you all? Clear, everyone? Okay. Is this point clear? Any doubt, anyone? Any doubt, anyone? I don't think there should be any doubt. It must be clear to everyone. Fine. So here I have written the 5d orbitals in an isolated gaseous atom or ion are degenerate. That means they are said to have equal energy, right? They are said to have equal energy, right? When a spherically symmetrical field of ligand, that means ligands are approaching the central metal atom and the central metal ion, but they still are far away. In that particular case, the field provided by the ligand is said to be symmetrical in nature. Okay, right, fine. However, since the ligand will repel the d orbitals, so there will occurs the raise in energy. However, still the 5d orbitals are said to have equal energy. However, their energy has been raised a little bit. That's it. Am I clear, everyone? Am I clear, everyone? Yes. Am I clear, everyone? Clear? Okay. Clear? Now, beta, if I assume that the complex which is going to form is an octahedral complex. Okay. What I am assuming now, the complex which is being formed, right, is going to be an octahedral complex. Then tell me how many ligands will approach. How many ligands will approach the central metal atom or the central metal ion? Quickly tell me in the chat box how many ligands will approach the central metal atom and the central metal ion. Yes, quickly tell me in the chat box, everyone. Quickly tell me in the chat box. Yes, everyone. Quickly tell me in the chat box. If I assume the complex to be octahedral, then how many ligands will approach central metal atom or central metal ion, beta? 6 ligands, right? 6 ligands, absolutely correct. 6 ligands, beta. Right, 6 ligands, right? Fine. Okay. So now, bacha, earlier what was the condition? Earlier the condition was that the field of the ligand was symmetrical. Okay, the field of the ligands was symmetrical, but now when the ligands are close enough, right, they will surround the central metal atom or the central metal ion in an octahedral manner, in an octahedral geometry. Okay, so if this is the central metal atom or the central metal ion beta, right, if this is the central metal atom and the central metal ion beta, then here the ligands will surround the central metal atom or the central metal ion in an octahedral geometry. Am I clear? In an octahedral geometry. Am I clear, beta? In an octahedral geometry. Clear? Clear? Okay. Bacha, it is basically assumed that here this axis, okay, here this axis is basically your x-axis, bacha. This axis is basically your y-axis and this is basically your z-axis. That means this is basically x, y and z-axis and this is basically your origin. Okay, this is basically your origin. This is plus x, then this will definitely be minus x-axis. Okay, this will be minus y-axis and this will be minus z-axis, bacha. Now the ligands are close enough. They are surrounding the central metal atom or the central metal ion, beta, in the octahedral geometry, right? And it is assumed, beta, that ligands are approaching the central metal atom or the central metal ion along x, y and z axis. Am I clear? Along x, y and z axis. Now, tell me one thing, beta. If I talk about the 5 set of d orbital, what are 5 set of d orbitals which are present in the central metal atom? Okay, this is the central metal atom, beta. This is the central metal atom. Quickly tell me what are the 5d orbitals? What are the 5d orbitals which are present in the central metal atom or the central metal ion? You will say, ma'am, they are dx square minus y square, dz square, right? Fine. And we have dxy, dyz, dxz, right? These are the 5d orbitals, beta. These are the 5d orbitals. Now, if I talk about the x square minus y square orbital, beta, right? Here, if this is x-axis, this is y-axis, bacha, the lobes of dx square minus y square orbital lies along x and y axis. Okay, so this is basically dx square minus y square orbital. Okay, so the lobes of dx square minus y square orbital lies along x and y axis, right? Talking about, bacha, dz square orbital, then it is said to have a baby Suther sort of shape, right? Here we have this 2 lobes and here we basically have a Suther shape of donut ring which is present, right? And this axis is basically z axis. Okay, now this is dx square minus dy square and this is dz square orbital. Okay, bacha, right? Now, both of these orbitals, since their lobes are pointing along x-axis, y-axis and z-axis, that means along the axis, bacha. So, these are basically known as axial orbitals. Am I clear? These are basically known as axial orbitals. Okay, these are basically known as axial orbitals. Okay, these are basically known as axial orbitals. Am I clear? Okay, these are basically known as axial orbitals. Yes, everyone. Yes, everyone. Yes, yes, yes. Right. However, if I talk about, beta, dxy, right? Fine. If it is suppose x-axis and this is y-axis, then their lobes basically lie between the axis. Okay. Similarly, if I have dyz, then I will have, bacha, z-axis and y-axis, and here their lobes lie between the axis. Am I clear? Their lobes lie between the axis. Similarly, if I have dxz, beta, this is z-axis and this is x-axis, and there also the lobes lies between the axis. Okay, there also the lobes lie between the axis, right? So these are non-axial orbitals. Am I clear, bacha? Right? These are non-axial orbitals. Am I clear? These are non-axial orbitals. Okay, these are non-axial orbitals. Am I clear, everyone? Okay, now listen to me, beta. Listen to me. Right here, listen to me once, bacha. Listen to me once. The lobes basically represents the electron density. right? The lobes basically represents the electron density. That means if we have the x square minus y square and the z square orbitals, here lobes are pointing along the axis. That means electron density lies along the axis, right bacha, right? Similarly, bacha, similarly, here, similarly, I have dxy, dyz, dxz orbital bacha. Here, lobes lie between the axes. That means here, the electron density lies between the axes. Right? Fine. Now tell me one thing. Beta. This central metal atom or the central metal ion is said to have these 5d orbitals. One are axial orbitals whose lobes lies along the axis, whose electron density lies along the axis, right? And here I have 3 non-axial orbital whose electron density lies between the axis, right? So whenever the field of the ligand is octahedral, this is basically an unsymmetrical field. Okay, whenever the ligands approach the central metal atom in an octahedral field, now the field becomes unsymmetrical. They are close enough. The field is unsymmetrical, beta. So what will happen? Beta? What will happen? These ligand, since they are negatively charged, they will apply repulsions to the d orbital, and more repulsions will be caused to the d orbitals, which basically lies along the axis. Why? Because ligands are approaching along the axis, along the x, y and z axis. Clear? That means dx square minus y square and dz square will suffer more repulsion now. Right? However, dxy, dyz, dxz, right? Their lobes, their electron density lies between the axes, so they will suffer less repulsion. Am I clear? They will suffer less repulsion, bacha. They will suffer less repulsion, bacha. Am I clear? Okay. They will suffer less repulsion. Fine. Now they are suffering more repulsion, they are suffering less repulsion. So now the 5d orbitals will no longer remain degenerate, but they split up into 2 sets. Am I clear? They will split up into 2 sets. Am I clear, everyone? They will split up into 2 sets. Am I clear, everyone? Okay, they will split up into 2 sets, and this splitting is basically known as crystal field splitting. Okay, the splitting is basically known as crystal field splitting. Okay, the splitting is basically known as crystal field splitting. Now we can understand this with the help of this energy diagram. Now here on x-axis we are drawing energy, and energy is increasing right here, and here on the right side we are having the metal ligand distance, beta. So as we move left, the metal ligand distance basically decreases. Okay, the metal ligand distance basically decreases as we move left to right. Right, as we move left to right, the distance between metal and ligand basically gets decreases. See, it's very simple, beta, it's very simple. When the metal was free, isolated, beta, right, isolated, that means ligands are at infinite distance, right, ligands are at infinity, far beyond. Clear? Ligands were at infinite distance, beta. Okay, in that particular case, the 5d orbitals were degenerate. Now, ligands are coming somewhat closer, right? Now, they are no longer at the infinite distance. They are coming somewhat closer. Am I clear? They are coming somewhat closer. So, this field is basically assumed like a sphere or a symmetrical field. Okay, right, fine. Am I clear, everyone? Yes, am I clear, everyone? Okay, fine, everyone. Is this point clear? Okay, is this point clear? So now what will happen, beta? Now here the field is symmetrical, however ligands are approaching, that means repulsion will be there, so the energy of the 5d orbital will get increased, right? Now when the ligands are coming closer, beta, the metal ligand distance is decreasing. That is why as we are moving left to right, the metal ligand distance is getting decreased right here. The metal ligand distance is getting decreased right here. Am I clear? Right? Now suppose the ligand surrounds the metal in an octahedral field. Okay, the ligand surrounds the metal in an octahedral field. In an octahedral field. Now beta, in octahedral field, what will happen, bacha? The axial orbital will suffer more repulsion and the non-axial orbital will suffer less repulsion. Now since the axial orbital will suffer more repulsion, beta, the 5d orbitals will no longer remain degenerate, but they get splits, right, into two sets, right? One set is of higher energy, right? The set which is of higher energy is the one which basically suffers more repulsion from the ligand, and this set is basically the axial set. Okay, this set is basically the axial set, which is the x square minus y square and dz square set. Am I clear, beta? These two set is known as doubly degenerate set, and it is represented by Eg. It is represented by Eg. G stands for G-rate, right? Since octahedral field is said to be the one which is said to have symmetry elements such as central of symmetry and plane of symmetry. Am I clear? So whenever any geometry is said to have symmetry elements, the word G-rate is used. Okay, so this is basically Eg. Eg stands for doubly degenerate. Okay, Eg stands for doubly degenerate. Am I clear, everyone? Eg stands for doubly degenerate. Clear? Okay, clear, everyone? Clear? Right. Bacha, the non-axial orbital, which is dxy, dyz, dxz, they suffers less repulsion. Okay, they suffers less repulsion. Now since they suffers less repulsion, beta, their energy will be lower. Okay, their energy will be lower. So these will be three non-axial orbitals. There will be three non-axial orbitals which are dxy, dyz and dxz. Okay, it is dxy, dyz and dxz. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Is it clear to everyone? Okay, right, fine. Now these are non-axial orbitals, and since we have three orbital of equal energy, they are known as triply degenerate. Okay, so here we write T2G. Here we write T2G. It is just the representation, beta, nothing else. Am I clear? Okay, right. Now if you have to find the difference between these two sets, okay, the difference in energy between these two sets is basically del naught. Here O stands for octahedral. Okay, and this del naught is crystal field splitting energy. Okay, this is crystal field splitting energy. Am I clear? This is crystal field splitting energy. Am I clear, beta? This del naught is basically crystal field splitting energy. Am I clear? Okay, this is crystal field splitting energy. Right. Okay, beta. Now, see, this is basically the average energy state, right? Whenever the ligands are surrounding in a symmetrical manner, beta, this is said to be an average energy state, and this is also known as barycenter. Okay, this is also known as what, beta? This is also known as barycenter. Am I clear? This is also known as barycenter. Clear? This is also known as barycenter. Is this point clear, everyone? Is this point clear? This is also known as barycenter. Any doubt, anyone? Any doubt, anyone? Quickly tell me in the chat box. Any doubt, anyone? Yes, any doubt, anyone? Any doubt? Yes, any doubt, or is it clear? If it is clear, I want lot and lot of green hearts. If it is clear, I want lot and lot of green hearts. If it is clear, I want lot and lot of green hearts. Yes. Clear or not? Clear or not? Clear? Okay. Right. Now this energy difference which you can see right here, beta, I can prove it, but there is no point of proving. You just have to remember it, right? Because you don't have to go into this much detail. Now this difference is basically equals to plus 3 by 5 del naught. Okay, this difference is basically equals to plus 3 by 5 del naught. Am I clear, everyone? Right, and this difference is basically equals to minus 2 by 5 del naught. Am I clear? Minus 2 by 5 del naught, and del naught is nothing but the crystal field splitting energy in an octahedral complex. Am I clear, everyone? Am I clear, everyone? Yes, am I clear, everyone? Clear? Right, I guess this point is clear to you all. This point is clear to you all, everyone. This point is clear to you all. Okay, I hope the crystal field splitting in the case of octahedral complexes are clear to my lovely students. Okay, it is clear to my lovely students. Now beta, next we have to do is basically the electronic configuration in octahedral complexes as per CFT. See bacha, here you have to learn certain terms. The first term which you need to learn is basically pairing energy. Okay, the first term which you need to learn is basically pairing energy. Now what is pairing energy beta? Keep in your mind, pairing energy is the energy required for pairing. Am I clear? Pairing energy is nothing but it is the energy required for pairing of electron, right? Whenever we have to pair the electron in a single orbital, the energy which is required to do so is basically known as pairing energy. Is this point clear, beta? Right? In order to learn how to write the electronic configuration in octahedral complexes as per CFT, we need to be aware of pairing energy. Am I clear, everyone? Yes, am I clear, everyone? Is this point clear? Is this point clear? Okay, fine. Now, bacha, you need to learn one thing. You need to learn one thing. Okay, you need to learn one thing, that their electronic configuration depends in the case of octahedral complexes as per CFT between the balance between crystal field splitting energy and pairing energy. Okay, but see, if a ligand is a strong field ligand, then always keep in your mind the strong field ligand is said to give more repulsion, and if the repulsion is more, the splitting is more and the del naught is more. Am I clear? What you need to keep in mind for strong field ligand, okay, for strong field ligand, del naught is high, or I should say crystal field splitting energy is high. Am I clear, everyone? Okay, and for weak field ligand, okay, for weak field ligand beta, del naught, or I should say crystal field splitting energy or crystal field splitting energy for octahedral complexes, del naught, it is said to be low. Okay, so here del naught is said to be low. Am I clear, bacha? Here del naught is said to be low. Am I clear? Am I clear? Am I clear? Okay, here del naught is said to be low. Am I clear, everyone? Okay, right? Am I clear, everyone? Fine. Now listen. Now listen, beta. Here, if you have a weak field ligand, the del naught will be very less. Okay, del naught will be very less, or I should say the gap between Eg and T2G is very less. Okay, the gap between T2G and Eg is very less. Okay, the gap between T2G and Eg is very less. Okay, right. So here if we have T2G beta, here we have Eg. If the ligand is a weak field ligand beta, then this del naught is less. This del naught is less. Okay, that means it is very easy for the electron, right, to cross this energy barrier. Now, what do you mean by this? What do you mean by this, beta? Suppose you have a complex, in which central metal atom or central metal ion is said to have one electron. Okay, that means here the configuration is D1 of the central metal atom or the central metal ion. Now, here we have to fill the electrons, beta. See, here we basically follow Aufbau rules. Aufbau rule says that first the orbital of lower energy is filled, then the orbital of higher energy is filled. Okay, further it also states that beta, further it also follows Hund's rule. That means each orbital first should be singly occupied, then the pairing starts. Am I clear? Okay, so they basically follow Hund's rule as well. They will follow Hund's rule as well. Right. Now here if I have one electron beta, I have D1 configuration. Now this D1, one electron can come here. Okay, if I have D2 configuration beta, then first this electron will come here. Why? Because first each orbital should be singly occupied, then the pairing will start. If I have D3 configuration beta, now this electron will go here. Am I clear, everyone? Am I clear, everyone? Now listen, beta. Here, del naught is small. If del naught is small, it is very easier if I have fourth electron to cross this energy barrier and goes into Eg. It's very easy, beta. The fourth electron can easily goes to Eg. So here, beta, del naught is so small. Okay, del naught is so small that beta it will be very very less than pairing energy, right? So if you want to pair the fourth electron here beta, if you have to pair the fourth electron here beta, you require lot of energy. So what's easier? What's easier? The easier thing is that this fourth electron should goes into Eg. Right. Similarly, if you have d5 beta, the fifth electrons will goes into Eg. Now each orbital is singly occupied. Hund's rule is obeyed. Now the pairing has to be start. Okay. So if I have d6, then here d7, d8, d9, d10. Am I clear everyone? Am I clear everyone? Am I clear everyone? Yes. Is it clear everyone? Okay. Right. Is it clear everyone? Fine. So when the ligand surrounding the central metal atom is a weak field ligand. Okay, whenever the ligand surrounding the central metal atom is a weak field ligand, in that particular case del naught is very very less than pairing energy, right? Del naught is very very less than pairing energy. So what will happen beta? First the 3 electrons goes into T2G, right? Then the next electron, fourth and fifth electron goes to Eg. That means first 3 electrons will go here, fourth will go here, fifth will go here. There won't be any pairing in the T2G. Why? Why? Because pairing is high and del naught is less. Whatever is less energy requiring, that occurs. Right? Whatever things require lesser energy, that thing will definitely occurs. Am I clear everyone? Am I clear? Quickly tell me in the chat box. Am I clear? If I am clear, please give a green heart everyone. If I am clear, please give a green heart everyone. Please give a green heart everyone. Yes. If I am clear, please give a green heart everyone. Is anyone listening? Yes, Raki. Very good, Raki. Very good, Raki. Very good, Raki. Okay, right. So now, next if I have T2G beta. So in T2G, 6th, 7th and 8th electron will go beta. Right, fine. So now, every orbital is singly occupied. Hund's rule is follows. Above rule is also follows. Right. Now here, beta, forced pairing will occur. That means 6th, 7th, 8th electron will go right here. Now again, bacha, the another electron will have to go to Eg, right? Right. So 9th and 10th electron will go to Eg. Okay, 9th and 10th electron will goes to Eg. Am I clear everyone? Am I clear everyone? Clear? Okay, right. So is the distribution of electrons in T2G and Eg is clear? Right. Fine. When the ligand is a weak field ligand, here del naught will be less, pairing will be high. So electron will first come to T2G. When T2G is singly occupied, then it will go to Eg, right? When both T2G and Eg are singly occupied, then they will occur pairing, and that is how we get this configuration. Am I clear everyone? Okay, right? Now, the second case beta. Now, the second case, it's when the ligand is a strong field ligand beta. See, when the ligand is strong field ligand bacha, then in that particular case bacha, here in that particular case, del naught is high. Okay, in that particular case, del naught is high. Okay, del naught is high, and del naught is very high in comparison to that of pairing energy. Del naught will be very high in comparison to that of pairing energy. Am I clear? Del naught will be very very high in comparison to that of pairing energy. Right? Del naught will be very very high in comparison to pairing energy. So if it is Eg, right, and if it is T2G bacha, right, if this is Eg and this is T2G, this is T2G and this is Eg, by mistake I have written, this is T2G and this is Eg. Okay, right. Now T2G is said to consist of 3 orbitals and Eg is said to consist of 2 orbitals beta. Right, so what will happen right here? See, it's very simple beta. First, if we have 1 electron, it will go to T2G. Second, T2G. third T2G. Hund's rule will be followed. Now here del naught is high, so it is very difficult for the fourth electron to cross this energy barrier and then go to Eg. So what will happen, beta? What will happen? There will occur the pairing of electron in the case of fourth, fifth and sixth electron. Now once T2G is completely filled, then we don't have any other option. Electrons ultimately have to go to Eg, right? Now what will happen, beta? This is seventh electron, this is eighth electron, this is ninth and this is 10th electron. Am I clear, everyone? Fine. So here what will happen, beta? First, second, third, fourth, fifth and sixth electron will go to T2G, and once T2G is completely filled, okay, and once T2G is completely filled, then bacha, the seventh, 8th, 9th and 10th electron will goes to Eg. Am I clear? Bacha, the 7th, 8th, 9th and 10th electron will goes to Eg. Is this point clear to you all? Yes. Is this point clear to you all, everyone? Clear? Okay. Is this point clear to you all, everyone? Fine. Now see, here I have certain electronic configurations of central metal atom and central metal ions. Right, here I have written certain electronic configurations of central metal atom and central metal ion, bacha. Am I clear? Right, suppose the central metal atom is said to have D1 configuration, beta. It doesn't matter now whether the ligand is strong field or weak field. Right, one electron will go to definitely T2G. Right, there is only one electron that will definitely goes to T2G, bacha. Right, that will definitely goes to T2G. Right, so here the configuration is T2G1. Similarly, if you have D2, doesn't matter you have strong field, weak field, beta, the configuration is T2G2. If you have D3, doesn't matter, the configuration will be T2G3. Right, bacha? See, it's very simple. This is your T2G and this is your Eg. Okay, this is your T2G and this is your Eg. Am I clear? This is your T2G and this is your Eg. Am I clear, everyone? Okay, so whenever the ligand is either strong field or weak field, it doesn't matter in the case of D1, D2 and D3 configuration, beta. If it is T2G1, that means there is only one electron in D orbital, it will goes to T2G, 2 again T2G, 3 again T2G. Am I clear? Right. However, in D4 configuration, beta, now if the ligand is weak field, now weak field ligand won't cause any pairing, that means electron will goes into Eg. Right. So here the configuration is T2G3 Eg1. Right. However, if the ligand is strong field, beta, if the ligand is strong field, the strong field ligand has high pairing energy, so it will cause strong field ligand is said to have low pairing energy and high del naught. Right, strong field ligand is said to have low pairing energy and high del naught, so it is very easier to pair. Okay, or I should say strong field ligand will cause pairing of electron, bacha. Right, it will cause pairing of electron. So in this particular case, beta, all the 4 electrons will goes to T2G and Eg will have 0 electrons. Talking about D5 configuration, bacha, talking about D5 configurations, bacha. See, here into the case of D5 configuration, if the ligand is weak field, beta, if the ligand is weak field, what will happen? This is 1, 2, 3, 4, 5. Okay, right. So the configuration is T2G3 Eg2. And when the ligand is strong field, beta, there will occur pairing of electron. All the electrons will go to T2G and Eg is said to have 0 electrons. Okay, Eg is said to have 0 electrons. Right, Eg is said to have 0 electrons. Am I clear, everyone? Yes. Very good, Rakhi. Very good. Now, if I talk about D6 configuration, beta, if I have a strong field ligand, right, then in the case of strong field ligand, there will occur pairing, so all the 6 electrons will go to T2G and Eg will have 0 electrons, right. However, if I have a weak field ligand, beta, then what will happen? The configuration is T2G 4 Eg2. Okay, the configuration is T2G 4 Eg2. I hope this point is clear. I hope this point is clear. In the case of D6 configuration, okay, next we have D7, beta. If I have a strong field ligand, then it will cause the pairing of electron. So here all the 6 electrons in T2G will be paired and we will have 1 electron which will go to Eg. Now if I have strong field ligand, then this is the configuration. In the case of weak field ligand, beta, in the case of weak field ligand, beta, what will happen in the case of weak field ligand, bacha? What will happen in the case of weak field ligand, bacha? Now here in the case of weak field ligands, what will happen? I will have 5 electrons in T2G and 2 electrons in EG. Okay, I have 5 electrons in T2G and 2 electrons in EG. Am I clear? Right. Now talking about D8 configuration, beta, it doesn't matter in D8 configuration. It doesn't matter in the D8 configuration whether you have a strong field ligand or a weak field ligand. It will be T2G 6 EG 2. Okay. Similarly in D9 it doesn't matter strong field, weak field, it is T2G 6 EG 3. Right, and similarly in D10 configuration it doesn't matter, we have T2G 6 EG4. Am I clear? It doesn't matter. It doesn't matter. Is this point clear to you all, beta? So now can you write the electronic configuration in T2G and EG in the case of octahedral complexes? Yes or no, everyone? Yes or no? Can we write the electronic configuration, everyone? Can we write the electronic configuration, everyone? Yes. Am I clear or not, everyone? Clear? Okay. Clear? Right? Fine. Okay, everyone. So now let's just move ahead and comes to crystal field splitting in the case of octahedral, in the case of tetrahedral complexes. We have already completed the octahedral. Now before coming to these, beta, these are certain questions in which you have to write the electronic configurations into T2G and EG as per, okay, T2G and EG as per CFSE, that means crystal field splitting theory or crystal field splitting theory, right? Okay, so what you have to do right here, beta, see, you have cobalt plus 3 here, right? Here you have Fe plus 2 and here you have copper plus 2, bacha. Okay, if I talk about cobalt plus 3, beta, cobalt is said to have an electronic configuration of 4s2 3d7. So if it is cobalt plus 3, beta, that means I have 6 electrons here. I have 6 electrons in 3d. How many electrons, beta? I have 6 electrons in 3d. Am I clear, everyone? I have 6 electrons in 3d. Yes or no? Yes, I have 6 electrons in 3d. Fine. If I have Fe2 plus, beta, again I have 3d6 configuration, and if I have copper 2 plus, I have 3d9 configuration. Now in the first case, beta, with cobalt plus 3, Fe is said to behave as a weak field ligand. Now if Fe is said to behave as a weak field ligand, then tell me what is the configuration in T2G and EG. Beta, I have 6 electrons, right? F minus is said to behave as a weak field ligand. Now in the weak field ligand, beta, the configuration for D6 is T2G4 EG2. Okay, so the configuration is T2G4 EG2. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Yes or no? Yes or no? Yes, beta. Cn is said to behave as a strong field ligand with Fe2 plus. I have just told you. Now if it is behaving as a strong field ligand and I have 3d6, beta, then all the electrons will get paired and I have T2G6 and EG0 configuration. Am I clear, everyone? Right. Now here I have CuNH3 whole 6 2 plus, beta. Now NH3 is said to behave as a weak field ligand for plus 2. Right, NH3 is said to behave as a weak field ligand for plus 2. However, in 3d9 it doesn't matter. It doesn't matter whether NH3 is strong field or weak field, beta. Here the configuration is T2G6, T2G6 and EG3. T2G6 and EG3. Beta, cobalt 3 plus, chromium 3 plus, NH3 act as a strong field. Yes, beta, for chromium 3 plus, NH3 will act as a strong field ligand. For any plus 3 3D transition metal atom, right, we have NH3 behaving as a strong field ligand. This is the doubt. I hope it is clear right now. Now don't spam. Okay, right. I hope this example is clear to you all, everyone. I hope this example is clear to you all, everyone. Right. Now, bacha, here the AC is not working, so I am doing one thing. I am taking a break of 5 minutes and just asking the guards to switch on the AC. So I will meet you after 5-10 minutes. Now this is the last break of this session, right? After 5-10 minutes, I will restart. There is, I guess, 30 minutes will be taken by the crystal field theory in the case of tetrahedral complexes, right? And then I will start with coordination isomerism. I am taking 5 minutes break. The AC is not working right here. I have told the guards several times, now I have to inform. Okay, just a second. Okay, everyone. So now this was the last break. Now we will end this chapter and we'll end this marathon, right? So let's just restart. I hope you guys are there. Fine. So I was just checking the AC. Fine. So it wasn't working properly and the board was just hanging a lot, right? So I have to check with the AC and it was not at all working. Fine. Okay, everyone. So now let's just come to crystal field splitting in the case of tetrahedral complexes. See, bacha, if I talk about the ligands, ligands always approach from axial directions only, right? So in tetrahedral complexes also, ligands generally have a tendency to approach from the axial directions, but they failed right here. Right. In octahedral complexes, ligands have approached the central metal atom or central metal ions through the excesses. Okay. They have approached through the excesses. Right. In tetrahedral ligands, they also want to do the same, but here the approach is little different. Okay. Here the approach is little different. Why? Because this approach basically depends upon geometry, beta. This approach basically depends upon geometry. Now, what happens, beta, if we basically assume that we have a cube and in the center of the cube, we have M plus ion, okay? In the center of the cube, we have M N plus ion. Now, here, bacha, what will happen? Now, here, what will happen? Listen to me very quickly, beta. On each alternative corner of the cube, that means if you have this corner, here ligand is present and from here the ligand is approaching, then on the other corner the ligands won't be present, right? And if on this corner ligand is not present, then in this particular corner ligand will present, right? And if this corner ligand is present, here it won't be present, here it will be present. And similarly, if here it is present, here it won't be present and it will be present right here. Am I clear, everyone? Okay, so here from the alternative corners, beta, what is happening? Ligands are approaching, right? Now these corners do not lies along x, y and z axis, okay, right? Now this is suppose your z axis, this is suppose your x axis and this is suppose your y axis and this is the origin, okay, and this is basically the origin. Am I clear, everyone? This is basically the origin, right? Right. So what we will observe, beta, what we will observe that here now the four ligands which are approaching in a tetrahedral manner, okay, now the four ligands which are approaching in a tetrahedral manner, beta, here these ligands will be at a distance of approximately a root 2 by 2 from axial orbital of the central metal atom or the central metal ion, beta. Now what is this A, bacha? See, if you have assumed this as a cube, then A is the edge length of the cube, okay? A stands to be the edge length of the cube, right? So the ligands when approach the central metal atom in the tetrahedral geometry or in the form of tetrahedral field, beta, now these ligands are basically at a distance of A root 2 by 2 from the axial orbitals. Am I clear, everyone? Right? And if I talk about these ligands, beta, then they are at a distance of A by 2, okay? They are at a distance of A by 2 from non-axial orbitals. Now quickly tell me, this is the distance of ligand from axial orbital and this is the ligand of this is the distance of ligand from non-axial orbital. Now which distance is more? I guess this distance is more, right? This distance is more. So when the distance between the ligand and the orbital is more, beta, the repulsion will be less, right? That means here non-axial orbital suffers less repulsion, beta ji. Right. I think I have said the vice versa thing. I am repeating it once again. Extremely sorry. I have said the vice versa thing. I am repeating this concept. Extremely sorry. Extremely sorry. I have said the vice versa thing. So the ligands are at a distance of A root 2 by 2 from axial orbitals and they are at a distance of A by 2 from non-axial orbitals. Am I clear, everyone? Am I clear, everyone? Right. Now, bacha, now here which distance is more, above or below? Definitely the above distance is more. Earlier I have said the wrong thing. I am recorrecting it. I am extremely sorry. Beta, the above distance is more and this distance is basically less. Now if this distance is more, beta, this distance is more, that means here the separation between the ligands and the axial orbital is more, and if the separation between the ligands and the axial orbitals is more, bacha, is more, there will be less repulsion. Okay, that means their axial orbital will suffer less repulsions, right? Whereas non-axial orbitals beta, they are going to suffer more repulsion. Okay, they are going to suffer more repulsion. Am I clear, everyone? Am I clear, everyone? Is this clear to you all? Is this clear to you all? Okay, so whenever we will draw the crystal field splitting diagram, beta, see, this is an isolated central metal atom. Okay, isolated central metal atom, right? Now, if this central metal atom is present in tetrahedral symmetrical field, beta, then here what will happen? What will happen, beta? Here the energy of the 5d orbitals will get increased. Here the energy of the 5d orbitals will get increased. Now, suppose the ligands are approaching the metal in an tetrahedral manner, then in this particular case, beta, then in this particular case, what I will see? I will see that non-axial orbitals will suffer more repulsion, and if they will suffer more repulsion, beta, their energy will get increased, right? Their energy will get increased, right? Their energy will get increased, fine. Okay, so this is basically 1, 2, 3, this is dxy, dyz, dxz, okay, right? And they basically are represented by T2. Here G is not used because G-rid is used when the geometry is set to be containing the elements of symmetry. Tetrahedral geometry do not contains plane of symmetry, beta, right? That is why the word G-rid cannot be used with it. So it is T2. Am I clear? Here I will have, bacha, here I will have your axial orbitals which are said to suffer less repulsion, so their energy is also less. Okay, right, fine. Okay, now this distance between, energy gap between, bacha, T2 and E, this is basically E. Okay, dx square minus y square and dz square is basically E, right? So the energy gap between T2 and E, this basically stands for del T. This basically stands for del T, which is crystal field splitting energy in tetrahedral complexes. Am I clear? This is basically crystal field splitting energy in tetrahedral complexes, right? Am I clear? Am I clear? Okay, this basically represents again the barycenter. Okay, this basically again represents the barycenter. Am I clear? This basically represents the barycenter, beta. Okay, now here this energy is plus 2 by 5 del T. This energy gap is plus 2 by 5 del T, right? And this energy gap is minus 3 by 5 del T. Okay, so you just have to cram it, nothing different. Okay, so this is basically E, doubly degenerate, this is T2, triply degenerate. Here G is not used because tetrahedral does not have the elements of symmetry. So this is basically splitting in the case of tetrahedral complexes. But here there are certain important points which we need to take into consideration, right? Which we need to take into consideration. Okay, which we need to take into consideration. Splitting in the case of octahedral complexes is always greater in comparison to that of tetrahedral complex. The reason is simple. In octahedral complex, beta, we have 6 ligands. In tetrahedral complexes, we have 4 ligands. Then definitely 6 ligand will give more repulsion and 4 ligands will give less repulsion. So that is why crystal field splitting in octahedral complexes is always more in comparison to that of tetrahedral complexes. So that is written, that is an important point of NCERT, right? That crystal field splitting in the case of tetrahedral complex is less as compared to that of octahedral complexes. Why? Because, bacha, in first thing, the tetrahedral complexes has lesser number of ligand. Second thing, second important point is also there, beta. In tetrahedral complexes, you can see none of the ligand is directly approaching, okay, the d orbital. right? Fine. None of the ligand is directly approaching the d orbital. From axial also and from non-axial also, there is a little bit distance, right? In the case of axial, the distance is a root 2 by 2, and in the case of non-axial, it is a by 2. So there is a little distance. There is not any direct approach of the ligand towards the d orbitals. Am I clear, everyone? Okay, so here definitely the repulsion will be less. So that is the case, beta. That is the case. Tetrahedral complexes are said to undergo less splitting, or del T is less than del naught, right? In actual, del naught is basically equal to 9 by 4 into del T. Am I clear? Right? Or we can even say that del T is 4 by 9 times of del naught, right? Or we can even say that del T is basically 4 by 9 times of del naught. Is it clear, everyone? Is it clear, everyone? Clear? Okay. Right? Is it clear? Clear, everyone? Is this point clear? Any doubt, anyone? If it is clear, I want lot and lot of green hearts. If this point is clear, I want lot and lot of green hearts. I want lot and lot of green hearts. Now, Bacha, in the case of tetrahedral complexes, the splitting is so less that del T is so small. And if del T is so small, beta, then energy gap can easily be crossed, right? So here no pairing occurs, right? There is no pairing occurs. And if no pairing is occurring, beta, if no pairing is occurring, then definitely the complex which are formed are of low spin. Right, what I am trying to say, del T is so small, beta, right? This del T is so small that the electron can easily cross this energy barrier and can go from E to T2. There is no pairing, and if there is no pairing, beta, then definitely there won't be occur the formation of low spin complex. So generally the complexes of high spin only will be formed. Am I clear? So generally the complexes of high spin will only be formed. Am I clear? So this is a point written in NCERT. Now let's just move ahead, beta. Now let's come to the factors affecting CFSE. This is the last topic of CFSE. Then we'll begin with the last topic, which is coordination isomerism, which will get over in 1 hour or something. Am I clear, everyone? Am I clear, everyone? Why anybody is giving a laughing reactions? Is something funny happening over here? My face would be a little funny because I am tired, but nothing else is funny right here. So why I am getting laughter reactions right here? Why I am getting laughter reactions right here? Okay. Fine, everyone. Let's just move ahead. Now let's come to the factors affecting CFSE, or the factors affecting crystal field splitting energy, or crystal field stabilizing energy. Okay, now let's come to the factors affecting CFSE. Now see, bacha, here the value of del naught, or I should say the crystal field splitting energy in the case of octahedral complexes, basically depends upon the strength of the ligand. If the ligand is strong, it is said to cause more splitting, del naught is high. If the ligand is field, the splitting will be less, del naught will be less. Am I clear? Okay, so when the ligand is a strong field ligand, bacha, del naught is high. Okay, del naught is high. And when the ligand is weak field, beta, del naught is low. Am I clear? Del naught is low. Is it clear? Del naught is low. Right? Okay, fine. And bacha, there is a series which is known as spectrochemical series. Now spectrochemical series have basically arranged the ligand on the basis of their field strength, on the basis of their repulsion. Right? Okay, now this series is basically known as spectrochemical series, and in these series, as we move from left to right, beta, the ligand field strength increases. That means ligands which are on the extreme right are strong field, and on the extreme left are basically the weak field ligands. Right? This is purely an experimental order. Right? This order is on the basis of increasing CFSE, which is caused by these ligands. As we move left to right, the CFSE, I should say the crystal field splitting energy, del naught increases, right? And this order is purely experimental. Am I clear, everyone? Fine, you don't have to cram it, you just can visualize it. That's it. Okay, right, fine. Let's just move ahead, bacha. Now, here I have told you that CFSC depends upon the nature of ligand, right? And which ligand is strong field, which ligand is weak field, we can find on the basis of spectrochemical series, right? For example, we have three complexes, 1, 2 and 3. If you will visualize these complexes, the metal is same in all the three complex, Fe, 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 okay, right? When you will visualize these complexes, in all these complexes, Fe is said to exhibit +3 oxidation state, okay, right? That means the charge or the central metal atom or the oxidation state of the central metal atom is also same, right? Here the coordination number is also same, here also 6, here also 6, here also 6. Okay, so the coordination number is also same in all the three complexes, right? So here the coordination number, or I should say geometry, is also same. However, the ligand is different, right? Now, if I have to ask you to arrange these ligands in order of increasing CFSC as per spectrochemical series, bacha, I can easily see that Cn minus is said to be the strongest. Then I have NO2 minus beta. Then I have H2O. Then I have H2O. Yes or no, beta? Right? So that will be the order of del naught for these particular complexes, right? Please keep this thing in mind. Del naught is directly proportional to ligand field strength, okay, ligand field strength. Ligand field strength means that if a ligand is a strong field, del naught will be high. That is why del naught of this particular complex is the highest and this particular complex is the lowest, right? First of all, del naught is directly proportional to ligand field strength, okay, ligand field strength. Okay, further beta, further, listen to me once, further, more is the del naught, more is the stability of the complex. So if you have to arrange these complexes on the basis of stability also, so del naught is directly proportional to stability, okay. More is the del naught, more is the stability. More is the stability. Am I clear? More is the del naught, more is the stability. Am I clear? More is the del naught, more is the stability. Okay, right? Fine. Now, let's come to the another factor, beta. Let's come to the another factor, right? Let's come to the another factor which affects CFSC, and that is basically charge on central metal atom or central metal ion. Okay, charge on central metal atom or central metal ion, right? See, bacha, in the very first complex, the central metal atom or the ion is same, in second also it is same, it is Fe, right? Ligand is also same, Cn in both the cases, Cn minus in both the cases. Coordination number is also same, 6 in both the cases. Okay, however, if I look at the oxidation number, then in first complex it is +3 and in the second complex it is +2. Now, more is the oxidation number on the central metal atom, more is the Z effective, more is the attracting tendency of the metal to the ligands, more is the repulsion, more is the del naught. That means higher the charge, higher the del naught, right? That means this complex is said to have higher del naught in comparison to this particular complex. Am I clear, everyone? Am I clear, everyone? Yes. Am I clear, everyone? Clear or not? Clear? Right? Okay. So now let's come to the another case, bacha. Let's come to the another case, bacha. See, beta, as we move from first transition series to second transition series to third transition series. Now, first transition series is 3D series, then we have 4D series, then we have 5D series, beta. First transition series starts from scandium, ends from zinc. Right, 4D transition series starts from yttrium, ends from cadmium. 5D transition series, beta, first we have lanthanum, then we have lanthanides, then we have hafnium, and then it goes up to mercury. Okay, so what happens, beta, as we move from 3D series to 4D series to 5D series, beta, what happened due to poor shielding of D and F electrons, Z effective increases. Okay, Z effective increases. Now, if Z effective increases, beta, then again del naught will get increases, right? If Z effective is getting increased, beta, the del naught will get increases, right? Here del naught will get increases. I have told you the logic, right? In fact, what happens, beta, that all the ligands, all the ligands does not depend upon their nature. If they are forming a complex with a central metal atom or the central metal ion of 5D series, beta, here del naught will be so high that that ligand will definitely behave as a strong field ligand. Am I clear? That ligand will be definitely behave as a strong field ligand. Am I clear? Okay, right, fine. So we have done this particular factor, Now let's come to the last topic, beta. Now let's come to the last topic, which is isomerism in coordination compounds. See, I have told all the important points right here, but if you want to learn more important points, beta, regarding CFSE, then I have given a detailed lecture also, which is available on the same channel. The playlist has been created. You can watch that lecture. This is, since it is a one shot, so I have completed just the important factors. Okay, right. So now we are coming to the last topic. It will take, I guess, 1 hour or something in order to complete this topic. And this topic is basically coordination isomerism. Okay, this topic is basically coordination isomerism. See, now what is this coordination isomerism, beta? Bacha, if I talk about isomerism, the phenomenon of isomerism is exhibited by isomers, right? Now what are these isomers, beta? Isomers are two compounds which are said to have same molecular formula, right? That means isomers are the compounds which are said to have same molecular formula, right? Fine. Now isomers are the compounds which are said to have same molecular formula, right? Isomers are the compounds, isomers are the compounds which have same molecular formula, okay, which have same molecular formula. Right. However, the isomers although have same molecular formula, but they differs on the linkage of donor atom, right? They are said to have same molecular formula, right? But they differs, okay? But they differs if in the linkage of the donor atom, but they differs in the linkage of the donor atom, okay, but they differs in the linkage of the donor atom, beta, right? Then they are said to exhibit structural isomerism, or such isomers are said to be structural isomers, right? For example, see, for example, I have two complexes written right here. Now in the first complex, bacha, and in the second complex, if I compare, the molecular formula is same. The molecular formula is same. But in the first complex, beta, here CO is linked through sulfur, right? And in the second complex, CO is linked through nitrogen, right? So both the complexes basically differ on the linkage atom, right? On the linkage atom. So such isomers, beta, such isomers which are said to have same molecular formula, but they differ in the linkage of donor atoms, beta, they are said to be structural isomers, and this phenomena is known as structural isomerism. Am I clear? Okay, right. Now, if I talk about, beta, stereoisomers, now see, stereoisomers are those which are said to have same molecular formula, right, but they differ in the arrangement around central metal atom or the central metal ion, right? Fine. So they differs in arrangement around central metal atom or central metal ion, then such isomers are known as stereoisomers, and this phenomenon is known as stereoisomerism. Okay, this phenomenon is basically known as stereoisomerism. Any doubt, anyone? Yes, any doubt, anyone? Any doubt, anyone? Any doubt? Yes, any doubt? Is it clear? I hope this is clear to you all, everyone. I really hope it is clear to you all, everyone, right? Now this arrangement is basically the spatial arrangement. That means arrangement of ligand in 3D. Okay, this arrangement is basically spatial arrangement, right? That means arrangement of ligands in 3D, right? So the molecular formula of two isomers are same, but the spatial arrangement of ligands around the central metal atom differs, right? Okay, so if they differs in spatial arrangement, okay, they differs in spatial arrangement, let's make it more clear. Spatial arrangement, then they are said to be stereoisomers of one another, and this phenomenon is known as stereoisomerism. isomerism. Okay, bacha. Right. Now here we will study 4 types of structural isomers and 2 types of stereoisomers. Right. We have 4 types of structural isomers, bacha. We have linkage isomerism, we have coordination isomerism, we have ionization isomerism, and we have solvate isomerism. And if I talk about stereoisomerism, beta, I have geometrical isomerism and I have optical isomerism. Am I clear? I have geometrical isomerism and I have optical isomerism. Fine. Okay. Now, let's first start with structural isomerism. So, the very first type of structural isomerism is basically the linkage isomerism. Beta. See, linkage isomerism occurs in those coordination compounds, bacha, which basically contains ambidentate ligands, okay, Now, I have told you, beta, ambidentate ligands. What were the example of ambidentate ligands, beta? We have Cn minus and we have Nc minus. Clear? Okay, so here although they are monodentate, but they can ligate or coordinate either through carbon or through nitrogen, but at one time they will either coordinate from carbon or coordinates from nitrogen. So they are said to be ambidentate ligand. Am I clear, bacha? They are said to be ambidentate ligand. Am I clear? They are said to be ambidentate ligand, right? Okay, they are said to be ambidentate ligands. Fine. So, whenever a coordination compound is said to consist of beta G ambidentate ligand, then it is said to exhibit linkage isomerism, right? Fine. For example, I have COH2O whole 5, okay, I have COH2O whole 5, bacha, okay, or I should say I can take some other example because I have already taken that examples on the next slide. So I can take CONH3 whole 5 and here I have NO2, okay, here I have NO2, okay, right. Outside the coordination sphere, suppose I have Cl2, right, I have this particular compound, right, this particular coordination compound, and I have this particular coordination compound, it is CONH3 whole 5, this is ONO, okay, this is ONO, and this is Cl2, right, this is Cl2. In one of the complex, the coordination is through nitrogen, and the other complex, the coordination or the linkage is through oxygen. Although the molecular formula of both the isomers are same, however, they differ in the linkage of the donor atom, right. In one of the complex, the linkage occurs from the nitrogen side, and in the other complex, the linkage occurs from the oxygen side, okay. So, these both isomers are said to be linkage isomers of one another, okay. They are both said to be linkage isomers of one another. Now, similarly, you have COH2 whole 5 SCN 2 plus and COH2 whole 5 NCS2 plus. Now, both of them are also linkage isomers. Why? Because molecular formula of both the isomers are same. However, in one of the complex, the coordination occurs through sulfur, and in the other complex, the coordination occurs through nitrogen. So, both of them will be linkage isomers of one another. Is this point clear, everyone? Is this point clear? Okay, right. Now, how the question will come, beta? How the question will come? They will give you a complex and they will ask, tell the possible number of linkage isomers, okay? Tell the possible number of linkage isomers. So, how we will solve this question? See, beta, if I have this particular complex, it has 2 CN, that means 2 ambidentate ligand. Now, there are 3 possibilities, right? In one of the complex, bacha, both the ligands are present in form of Cn minus. That means here the donor is carbon. That means here the coordination occurs through carbon, right. So, here which complex will form, beta? Here AgCN whole twice, complete negative will be formed. Now, the other possibility is, beta, 1 CN, okay, 1 C. What I have did in the first case, I have taken 2 CN and both the CN, the coordination is occurring through carbon. Okay, the coordination is occurring through carbon. Now, in the another case, what I am doing, beta, in another case, what I am doing, bacha, first ligand is coordinating through carbon and the second ligand is coordinating through nitrogen. Am I clear? The first ligand is coordinating through carbon and the second ligand is coordinating through nitrogen. Okay, right. So, here the complex will be AgCN and NC whole negative. Okay, fine. What is the third possible linkage isomer which could exist right here, beta? What is the third possible linkage isomer which could exist right here, beta? Here both the ligands coordinates from nitrogen and are present as NC negative. Okay, and they are present as NC negative. Am I clear? And they are present as NC negative. Am I clear, everyone? Yes. Am I clear? Am I clear? Clear? Okay, both are present as NC negative. So these three isomers are possible. Okay, so how many isomers are possible, bacha? 3 isomers are possible. Clear? Okay, similarly they could have asked to form the linkage isomers in this particular coordination compound. See, here I have 2NO2. Now this NO2 can coordinates to nitrogen or can coordinates to oxygen. Suppose we have first NO2 and another NO2. Okay, now suppose there is a possibility that in both the cases, beta, here the ligand links through nitrogen. Fine. So there occurs the formation of complex PTNH3 whole twice NO2 whole twice. Right. Now the other possibilities is both links through oxygen. Right. So here the coordination complex which will be formed is PTNH3 whole twice ONO whole twice. Am I clear, bacha? Okay. Right. What is the third possibility, bacha? What is the third possibility, bacha? The third possibility is one links through nitrogen and the other links through oxygen. Right. That means here we have PT NH3 whole twice. One is ligating from nitrogen and the other one is ligating through oxygen. Okay, and the other one is ligating through oxygen. Am I clear, everyone? The other one is ligating through oxygen. Yes, is it clear or not? Right. So how many isomers, how many linkage isomers are possible, beta? Here I have 3 linkage isomers which are possible. Okay, here I have 3 linkage isomers which are possible. Okay, here there are 3 linkage isomers which are possible. Is it clear, everyone? Is it clear? Okay, I have 3 linkage isomers which is possible. Fine, let's just move ahead, everyone. Let's just move ahead. I can take the another case as well. I can take the another case as well. I can take the another case as well. Okay. So this is the another case, everyone. This is the another case, everyone. I guess there is some printing error. So let's just correct the complex. The complex is written wrong right here. Let me just correct the complex. Okay, so the complex is CO NH3 whole 4, right? Here I have one CN ligand, here I have one NO2 ligands, right? So this is the complex. Okay, I have one CN ligand and I have one NO2 ligand. Okay, so this is the complex, bacha. You have to tell me how many linkage isomers are possible. Now see, beta, NH3 is not a ambidentate ligand. However, CN and NO2 are ambidentate ligand, right? First of all, what we will see, beta? First of all, what we will see, CN and NO are both ambidentate ligand. Okay, CN and N2 are both ambidentate ligands. Am I clear, bacha? Right? CN and NO2 are both ambidentate ligand. First point is clear. First point is clear. Okay. So now, beta, what are the possibilities? First possibilities is that here the coordination occurs through carbon and here through nitrogen. Second is in first in carbon and second in oxygen. Third is from nitrogen and the fourth is nitrogen and oxygen. So I guess there are only 4 possibilities, right? And since if there are only 4 possibility, beta, only 4 isomers are possible. Okay, so here only 4 linkage isomers are possible. Am I clear, everyone? Am I clear, everyone? So you can do this one as well. Here also it will have 4 isomers similar to the previous one. Okay, it also has 4 isomers similar to the previous one. Now let's basically come to the second type of structural isomers, beta. Second type of structural isomer is coordination isomerism. Okay, second type of structural isomers is basically coordination isomerism. Okay, right. Now the coordination isomerism occurs in those complexes in which the cation and anion both are complex. Am I clear? Okay beta. Coordination isomers, coordination isomerism basically occurs in those coordination compounds in which cation and anion both are said to be complex. Okay, here the cation and anion are both are said to be complex. Am I clear everyone? Fine, fine. For example, see, I have these two complexes. Both these two complexes are said to be polynuclear complexes. That means that cation and anion both are complex. The molecular formula of both these complexes are same. However, they differ in the distribution. Okay, they differs in the distribution of ligand around the central metal atom. Right. Here in first of the complexes, we have 6 NH3 around cobalt and 6 CN around the chromium. However, here we have 6 NH3 around the chromium and 6 CN around the cobalt. Okay, so the molecular formula is same. However, the distribution of ligands differ entirely in both the complexes. So whenever the molecular formula is same, however, distribution of ligands in the complex cation and complex anion differs, then such isomers are known as coordination isomers, and this phenomenon is basically known as coordination isomerism. Am I clear everyone? This phenomenon is basically known as coordination isomerism. Is it clear? Yes, is it clear? This phenomenon is basically known as coordination isomerism. Am I clear everyone? Am I clear everyone? Yes, am I clear everyone? Am I clear everyone? Clear, 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 clear. Okay, can we proceed ahead? Can we proceed ahead? Yes, let's just proceed ahead, bacha. Let's just proceed ahead. Let's just proceed ahead, beta. Now see, here we basically have to tell you that how many coordination isomers are possible in these particular complex. See, here bacha, this is basically complex cation and complex anion, and you have to tell that how many coordination isomers are possible. How many coordination isomers are possible? Okay, how many coordination isomers are possible? Okay, see, whenever you draw the possible number of coordination isomers, first make sure that net positive charge on cationic complex should equal to net negative charge on the anionic complex. The very first thing is beta, net positive charge on the cationic complex should be equal to net negative charge of the anionic complex, first thing, right? And charge on none of the complex should be 0. Okay, the charge on none of the complex should be 0. Am I clear? The charge on none of the complex should be 0. Okay, so let's start beta. First we have this complex CONH3 whole 6 and we have CrCN whole 6. Okay, we have CONH3 whole 6 and we have COCN whole 6. Am I clear everyone? Am I clear everyone? Clear? Okay, so if you will find the net positive charge on this complex beta, it will be +3 and the net negative charge on this complex will be -3. So here the net positive charge and net negative charge is equal. Now we have to form the possible number of coordination isomers. So what we can do beta, what we can do, we can exchange NH3 and CN ions right here. Now suppose what happens that one CN goes right here and one NH3 comes right here. So we have CONH3 whole 5 CN. Okay, we have CONH3 whole 5 CN, bacha, right? And we have CrCN whole 5 and then I basically have NH3 right here. Okay, I basically have NH3 right here. Now if you will find the overall charge, okay, if you will find the overall charge on cation it is +2 and on anion it is -2. Okay, so this is a second possibility, right? Yet another possibility is beta, here one more CN goes here and one more NH3 goes here. Okay, so we have CONH3 whole 4 CN2 and I have CrCN whole 4 NH3 whole twice. Am I clear, everyone? Am I clear, everyone? Okay. So here this particular complex will have +1 charge and this particular complex will have a -1 charge. Okay. So this is the another possibility. This is the another possibility. Okay. Right. Now, you will say, ma'am, let's do one thing. Let's replace one more NH3 with Cn. So this is NH3 whole thrice and this is Cn whole thrice. Okay. Now here we have Cr, Cn whole thrice and NH3 whole thrice. Now, bacha, this set is not possible. Why it is not possible? Because here the charge on the cationic part and the charge on the anionic part will be 0. Okay. Here the charge on the cationic part and charge on the anionic part will be 0. I have told you, beta, only those possibilities are there in which the net positive charge on the cation and the net negative charge on the anion are equal, but none of them should be equal to 0. That means this possibility cannot occur. This possibility cannot occur. This is not possible. Okay, this is not possible, right? Okay, ma'am. So now let's do one thing. Let's just basically bring one more Cn right here. Okay, so I have CONH3 whole twice, Cn whole twice. Okay, right, CONH3 whole twice, Cn whole twice. Fine. I think here I will have one NH3 lesser. I have NH3 twice and I have Cn whole 4. Now, bacha, because we are bringing one more Cn right here. We are bringing one more Cn right here. So, I have CONH3 whole twice, Cn whole 4. Am I clear, bacha? Right. So, when I will find the net charge, it will be -1 and here it will be CONH3 whole 4, Cn whole twice. Okay. So, here the charge is +1. Now, this is the cationic part and this is the anionic part. Still, the charge on both the parts are equal. So, they will exist. So, 1, 2, 3 and this is 4th one. Okay. Let's see the another possibility, beta. The another possibility is CONH3. Okay. Then I have Cn whole 5. The overall charge is -2. And the next one is, bacha, the next one is CrNH3 whole 5 and this is Cn. The overall charge is +2. Okay, the overall charge right here is +2. Again, this is also possible. This is also possible. Last possibility is you have Cn whole 6 and you have CrNH3 whole 6, right? Here the overall charge is -3 and +3. So here if I ask about the total, it is 1, 2, 3, 4, 5 and 6. That means how many isomers are possible, beta? How many isomers are possible? 6 isomers are possible. Okay, 6 isomers are possible. Now, ma'am, is there any short trick? Yes, there is a short trick, beta. See, when you know that around the central metal atom and around the central metal ion only monodentate ligands are present. Okay, when around the central metal atom or around the central metal ion only monodentate ligands are present, then there might be two possibilities. First is both the central metal atoms are same, however the ligands are different. Then in that particular case, beta, number of coordination isomers are equals to n/2. Okay. And the second possibility is, beta, both the central metal atoms are different and both the ligands are different. In that particular case, the coordination isomers are n. Like here, beta, both the metals are different, both the ligands are different. So here the coordination number is 6, beta. Here the n is 6. Okay. So here the number of coordination isomers are also 6. Am I clear? Here the number of coordination isomers are also 6. Am I clear? Okay. Right. Fine. Now, let's take the another case, beta. Here the central metal atom is same, however the ligands are different. So, the number of coordination isomers will be 6/2, that is equals to 3. Okay. So, we can directly find out, beta, we can directly find out. Here also the central metal atom is same, however the ligands are different, right? So, here also, beta, number of coordination isomers will be n/2, that is 4/2 equals to 2. Am I clear, bacha? Am I clear? See, this is the case in which the two central metal atoms are same, but the ligands are different, beta, right? Right. When the two central metal atoms are same and the ligands are different, the coordination isomers are n by 2. N stands to be the coordination number, right? So in both the other two cases here, the coordination isomers are beta n by 2, that is 3 and 2. I hope it is clear to you all. I hope this is clear to you all. ठीक है, okay. Yes, bacha, if somebody wants to sleep, they can go. You can watch the recording later on. It's about to get complete. It is about to get complete. Those who can wait can wait. Those who wants to go can go. Now next is the ionization isomers. Now ionization isomers are the isomers which are said to have same molecular formula. However, they give different ions once they are ionized in their aqueous solution. For example, we have these two complexes. They are said to have same molecular formula. However, when these ionizes, beta, the first complex gives PTNH3 whole thrice Cl plus Br minus. Am I clear? Plus Br minus, right? And the second complex on ionization gives PTNH3 whole thrice Br plus Cl minus, right? So the molecular formula of both the isomers are same. However, both of them gives different ions on ionization, so they are set to exhibit ionization isomerism. Okay, they are set to exhibit ionization isomerism. I hope this point is clear. I hope this point is clear. I hope this point is clear. Now let's come to the last isomerism. It is solvate isomerism or hydrate isomerism, beta. Now this isomerism occurs when we have H2O as a ligand. Now H2O can act as a solvent and it can act as a potential ligand, beta. Right, fine. Now this is known as both solvate isomerism and hydrate isomerism. Clear? If the solvent is specifically water, beta, then in that particular case we say it as hydrate isomerism. Fine. Am I clear? Am I clear? Okay. Now you can see, beta, I have two complexes. One is COH2 whole 4 Cl2 Cl.2H2 and the other complex is COH2 whole 5 Cl Cl2 dot H2. Now in both the complexes I can see, beta, here water can act as a potential ligand. So water which is present as a solvent, as water of crystallization, can come inside the coordination sphere, right? So these two complexes are said to have same molecular formula, but in one of the complex H2O is acting as a solvent and in the other complex H2O is acting as a ligand. So it is basically hydrate isomerism or solvate isomerism. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Okay, fine. So now let's just move ahead, beta. Let's just move ahead to the another isomerism, which is stereoisomerism. Okay, stereoisomerism. Fine. See, I am giving you one question. It is the homework, right? The answer of this particular question, I will write it. You just have to go and check it whether your answer is right or not. You have to tell the number of hydrate isomers possible in this compound. I know you guys won't be able to do it, but that's why I want you to apply the brain. Am I clear, everyone? Fine. So now let's come to the last topic, which are basically stereoisomerism. Now what are stereoisomerism, beta? They have same molecular formula or chemical formula, but they differ in the spatial arrangement or the orientation of ligand around the central metal atom or the central metal ion in 3 dimension. Am I clear, everyone? Okay. Now, if I talk about stereoisomerism, beta, it is of two types. One is geometrical isomerism. Okay, one is geometrical isomerism and the other one is optical isomerism. Okay, the other one is optical isomerism. Now stereoisomerism will be studied in both coordination number 4 and coordination number 6. In coordination number 4 we basically study tetrahedral complexes and square planar complexes, and in coordination number 6, beta, we study octahedral complexes. Am I clear? We study octahedral complexes. Now, let's just move ahead, bacha. First, let's study about geometrical isomerism. See, beta, in geometrical isomerism, what happens? The molecular formula is same, right? But the relative position of ligand around central metal atoms differ. Okay, am I clear? The relative position of ligand around central metal atom or central metal ion differs. For example, if the two ligands surrounds the central metal atom or I should say central metal ion at the angle of 180 degree. That means if relative position of two ligands are at an angle of 180 degree. Beta, this is basically known as trans geometrical isomer. right? And if the two ligands are at the angle of 90 degree beta, then this is basically known as cis geometrical isomerism. That means in trans the two ligands are opposite to each other, right? And in cis the two ligands are adjacent to each other. Am I clear, everyone? Am I clear, everyone? Now here we can see that cis trans isomerism is exhibited only when there is a angle between ligand metal and ligand of either 180 or 90 degree, right? Now you tell me, is geometrical isomerism is possible in tetrahedral complex? No, no, they're not possible. It is not possible. Am I clear, everyone? It is not possible. Why? Because in tetrahedral complexes, beta, there is no 90 or 180 degree angle possible. Here only an angle of 109 degree 28 minutes is possible, mera bacha. Okay, right. Here only the angle of 109 degree and 28 minutes is possible. Right. Suppose I have a metal. Okay, suppose I have a metal. Here I have a ligand, 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 right? Here only we have beta 109 degree angles. There is no 90 angle which was possible. So if there is no 90 angle which is possible, that means there is no possibility of geometrical isomerism in the case of tetrahedral complexes. Okay. Further, homoleptic complexes do not give the geometrical isomerism. You will get to know in some time why. Okay, right, fine. Let's just move ahead, everyone. Let's just move ahead, everyone. Right, now I have explained you that geometrical isomerism or cis trans isomerism is not exhibited by homoleptic complex, right? It is not exhibited by homoleptic complex. Okay, not exhibited by, non-exhibited by homoleptic complex. Okay, it is not exhibited by homoleptic complex, bacha. Am I clear? It is only exhibited by heteroleptic complexes. Am I clear? It is only exhibited by heteroleptic complexes. Am I clear? Okay, so geometrical isomerism only occurs in heteroleptic complexes. Okay, now if I talk about tetrahedral complexes, I have already explained you there is no geometrical isomerism which is possible in tetrahedral complexes. However, in square planar complexes, geometrical isomerism is possible. Now here we have to decide the cis trans position, beta. See, if I have a square planar complexes and this is a central metal atom or the central metal ion, beta, this is ligand 1, suppose this is ligand 2, this is ligand 3 and this is ligand 4. Okay, now this angle is basically 180 degree, beta, right? This angle is basically 180 degree, right? When the two ligands are opposite to each other, for example, L2 is opposite to L4, right? L1 is opposite to L3. That means they are present at an angle of 180 degree. Okay, that means if the ligands are present at L1 and L3 position, beta, they are said to be trans to each other. Similarly, if ligands are present at L2 and L4 position, they are said to be trans, beta. Okay, they are said to be trans. However, if we have two adjacent ligands, right? For example, we have L1, L2, we have L2, L3, we have L3, L4, we have L4, L1. They are said to be present adjacent to one another at an angle of 90 degrees. So they are cis to each other. Okay, they are cis to each other. Am I clear? They are cis to each other, right? So here if I have, bacha, L1, L2, okay, I have L2, L3, okay, I have L1, L2 I have already done, L1, L2 I have already done. I have L3, L4 and I have L1 and L4, beta. Now they are said to be trans. Okay, they are said to be trans. Am I clear? They are said to be trans. Fine. So cis and trans position in square planar complexes are clear to you all, beta. These are trans position, these are trans position. This is cis, this is cis, this is cis and this is cis position. Clear? Trans means opposite to each other. Cis means adjacent to each other. So in coordination number 4, beta, tetrahedral complex, no GI, square planar complex, GI is possible. I have explained you cis and trans position. I hope it is clear. I have explained you cis and trans position. I hope they are clear. Okay, right. Now let's just move ahead and come to beta octahedral complexes. See, in octahedral complexes also GI is possible beta. Here if you have central metal atom, this is ligand 1, this is ligand 2, this is ligand 3 and this is ligand 4 beta, this is ligand 5 and this is ligand 6. Now this is basically coordination number 6 and we know that in coordination number 6 we have octahedral complexes. Okay, I am talking about coordination number 6 in which we have octahedral complexes in which we have 6 ligands. Okay, how many ligands do we have right here? We basically have 6 ligands, bacha. We basically have 6 ligands. Now if I have to ask you about cis and transposition beta, there will be 3 transposition. This is transposition, this is transposition and this is transposition. Okay, so here if I talk about L1 and L4, they are trans to each other. Okay, L2 and L3, they will be trans to each other. Fine. And if I talk about L5 and L6, they are also trans to each other. So these positions are transposition. Okay, these positions are transposition. Now let's just talk about cis position. Now what are cis position beta? L1 L2, L2 L4, L3 L4 beta, L1 L3. First of all, these 4 positions are cis positions. Okay, right. So I have cis position, I have L1 L2. Am I clear? I have L2 L3. Okay, I have not L2 L3, L2 L3 to are trans. I have L2 L4. Okay, I have L2 L4. Then I have bacha L3 and L4. Okay, I have L3 and L4, right? And then I have L1 and L3. I have L1 and L3. Okay, these positions are first of all cis positions. Okay, further beta, if I talk about this ligand will be at a 90-degree angle from this as well as this. Are you getting my point? Are you getting my point, beta? See, if you have to visualize an octahedral complex, then how is the octahedral complex, bacha? See, here you have a central metal atom or a central metal ion, right? Right, in this plane, at the center you have central metal atom or the central metal ion, and each of the corners you have the ligands. Now, one ligand is present above the plane and the other is present below the plane. Now, the ligand which is present above the plane is at the 90-degree angle from all the 4 ligands which are lying on these planes, right? And the ligand which is lying below the plane is also at a 90-degree angle from all the 4 ligands which are present in the same plane. Am I clear, everyone? Okay, am I clear, everyone? Fine. That means here, if I have L5 L1, if I have L5 L3, okay, if I have L5 L2, and if I have L5 L4, okay, if I have L5 L4, now all these positions are basically your cis positions. Okay, these positions are said to be cis positions, right? These positions are said to be cis positions. And if I talk about beta L6, now L6 with L2, L1, L3 and L4 again is going to be present as cis position. Okay, so if I have L6 and L1, I have L6 and L3. If I have L6 and L2, and if I have L6 and L4 beta, they are also present at a cis position. Okay, they are also present at a cis position. I hope am I clear? I hope am I clear? Right. So now let's come to optical isomerism. Now let's come to optical isomerism beta. Right. So I am starting with optical isomerism. So let's just complete optical isomerism. Let me have a sip of water. So finally, we have came to almost the last topic and we are about to over this chapter. I'll try to complete it in 40-45 minutes, right? So that I can shut the recording by 5 so that we can have the recording of this particular session. Otherwise, the recording of this particular session won't be get uploaded on the YouTube, right? Am I clear, everyone? Okay. Now, let's come to the optical isomerism, bacha. Now, let's come to the optical isomerism, bacha. See, when the coordination compounds are said to have same molecular formula, right? However, they basically differ in the tendency to rotate the plane polarized light. Okay, they basically differ in the tendency to rotate the plane polarized light. Am I clear, everyone? Fine. So you have two isomers. The molecular formula of two isomers is same, right? And you must have studied in organic chemistry. There are certain isomers, okay, which have a tendency to rotate the plane polarized light. Now the compounds which are said to have the tendency to rotate the plane polarized light are optically active, and these compounds are said to exhibit the phenomenon of optical isomerism. Am I clear, everyone? Right? The compounds which have a tendency to rotate the plane polarized light when it is passed through them, beta G, such compounds are said to be optically active, and such compounds are said to exhibit optical isomerism, right? So whenever we have two coordination compounds, they are said to have same molecular formula, they have similar structure formula, but they basically differ in their ability to rotate the plane polarized light. Suppose one of the isomer rotates the plane polarized light towards right, and the other isomers basically rotate the plane polarized light towards left, then such isomers are basically known as optical isomers. Am I clear, everyone? Such isomers are known as optical isomers, and this phenomenon is basically known as optical isomerism. Am I clear? This phenomenon is basically known as optical isomerism. Am I clear, everyone? Fine. So what I have said I have two isomers. Bacha. Right? Both isomers have same molecular formula, but both these isomers differ in their ability to rotate the plane polarized light, beta. Right? One rotates the plane polarized light towards right, and the other one rotates the plane polarized light towards left. So both these isomers are said to be optical isomers. Okay? Both these isomers are said to be optical isomers. Right? Okay. Now there is one isomers which basically rotate the plane polarized light towards right. Clear? This isomer is basically known as dextrorotatory. Am I clear? This is basically known as dextrorotatory. Okay. And there is one isomer which basically rotates the plane polarized light towards left. This is basically known as levorotatory. Okay. This is basically known as levorotatory. Now, do you think it is possible to every time pass a plane polarized light through a compound and then to find out that whether it is optically active or not, right? And if it will be optically active, then only it is going to exhibit the phenomenon of optical isomerism. It is highly tedious process, and it is not actually done. What we actually do, beta, we see that two conditions must be satisfied, right? If we have a compound, right, suppose we have any compound, right, if that compound lacks plane of symmetry, okay, if a compound lacks plane of symmetry, right, it lacks plane of symmetry, right, that means POS is absent, okay, that means POS is absent. If POS is absent, then the compound is said to be optically active, and if the compound is optically active, then it will exhibit optical isomerism. If this particular compound is dextrorotatory, it will have another compound which is levorotatory, and this dextro and levo, I should say the two isomers, will be non-superimposable mirror images of each other, right? For example, you can see my two hands, beta. When I try to keep my first hand over the second hand, do they superimpose? No, they won't superimpose. In a similar manner, dextro and levo do not superimpose. Right. Now, ma'am, the question which comes in my mind is, ma'am, that what is this plane of symmetry? Okay. The question which comes in my mind is, ma'am, that what is this plane of symmetry? Okay, because the plane of symmetry is an imaginary plane which, when passes through a compound, cuts the compound into two equal halves. For example, if I have this notebook, I pass an imaginary plane from the center of this notebook. Now this plane, okay, this plane will cut this notebook into two equal halves, yes or no? Right? So this notebook will said to contain a plane of symmetry. Now if I will find a plane of symmetry, beta, if I will find a plane of symmetry, then compound is optically inactive. It won't exhibit optical isomerism. However, if plane of symmetry is absent, okay, however, if plane of symmetry is absent, in that particular case, beta, in that particular case, compound is said to be optically active. Okay, the compound is said to be optically active, and it will exhibit the phenomenon of optical isomerism, right? If the compound is optically active. Okay, everyone, I hope this point is clear. Right? Fine. Now, if I talk about square planar complexes, beta, square planar complexes never show optical isomerism. Y stands for optical isomerism. Why? The reason is simple, beta. If I talk about square planar complex, beta, in square planar complex, what we have? We have a plane. Right, in the center of the plane we have the metal, and on the corners we have the ligand. So if I pass an imaginary plane, then definitely one plane which will be possible, that will cut each ligand and the metal into equal halves. So this thing and this thing are mirror images of one another. Right, that means in square planar complexes POS exists, and if plane of symmetry exists, then square planar complexes will definitely won't show optical isomerism. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Okay, right, okay. Now, in order to understand the isomerism, bacha, there are certain representation which I have to explain you, which I will use. Right, the first is, beta, if I am using M represents metal. If I am using A, B, C, D, E, F, these are nothing but the monodentate ligand. If I write A represents the symmetrical bidentate ligand, and if I use AB represents the asymmetrical bidentate ligand. Am I clear, everyone? AB stands for the asymmetrical bidentate ligand. But I am trying to be fast, fine, but I am a little tired, so I will complete it in 30-40 minutes. Don't worry, in 30 minutes I will maximum complete it. I guess by 4:30 we will end the session. Okay, Yaria, he was there since the starting of the session, so he must be tired. I understand, I truly understand, right? I truly understand. Okay, right? Now, see, bacha, if I talk about A type of ligand, I have told you it is a symmetrical bidentate ligand. For example, you have oxalate, beta. Okay, you have oxalate. Now, oxalate is a symmetrical bidentate ligand. Okay, this part is a mirror image of the above part. So, it is a symmetrical bidentate ligand, right? So, it is represented as AA. Similarly, ethylene diamine, beta. Ethylene diamine, you have NH2, CH2, CH2, NH2. Now, ethylene diamine is again a symmetrical bidentate ligand, so represented as AA. Talking about AB, AB is basically asymmetrical bidentate ligand. For example, you have glycine, beta, right? In glycine, one side we have NH2 and on the other side we have CO negative. So, it basically represents an asymmetrical bidentate ligand and it is represented as AB. Am I clear? It is basically represented as AB, right? So, now let's come to the coordination number 4, which are square planar complexes. So, I have already told you square planar complexes won't exhibit geometrical isomerism. They will only exhibit which isomerism, beta? They will only exhibit which isomerism, beta? By mistake, I have written geometrical, beta. Extremely sorry. Square planar complexes do not exhibit optical isomerism. Why? Because they are said to have plane of symmetry. So, they can exhibit only which isomerism, beta? They can exhibit only, okay, they can exhibit only geometrical isomerism, okay? They can exhibit only geometrical isomerism. Am I clear, everyone? They can exhibit only geometrical isomerism. They cannot exhibit optical isomerism. Why? Because they are said to have a plane of symmetry. Fine. So, here we have the very first category of square planar complex, beta, Ma4. Right. Now, since it is a homoleptic complex and in homoleptic complex GI is not possible, beta. Right. For example, you can take a replica of this. Right. Ma4 means you have a central metal atom and you have 4 same monodentate ligands. So, the complex PTNH3 whole 4 2 plus is similar kind of this compound. Right. So, here you have metal, here you have A, here you have A, here you have A, here you have A. So, this is basically an homoleptic complex and in the starting of this session I have already told you, bacha, homoleptic complex do not shows geometrical isomerism. Okay. Homoleptic complexes do not shows geometrical isomerism. So, no GI is possible. OI was already not possible because square planar complexes do not basically forms optical isomers, so here GI also not possible. Am I clear? See, beta, whenever you have a metal, right, so opposite to this A we have this A. Now, so we can write A is opposite to A and opposite to this A we have this A, right. So, whenever you exchange any of the two A's, beta, the next complex which will be formed right here is MAA, MAA. That means these both are identical, beta. Here also opposite to A we have A, here also opposite to A we have A. So, these are identical, beta, right. So, there is no no isomerism possible in this particular case. Am I clear, everyone? Am I clear, everyone? Now next is MA3B or MAB3. The replica of this is PTNH3 whole thrice Cl plus. Okay, so here I have A and B. Okay, bacha, right? Now here if I write it, I have on opposite to A I have A, right, and opposite to this A I have B. Now suppose I exchange this A and B. Okay, suppose I exchange this A with this B. So here I have MAB and AA. Okay, right, that means here I have A and here I have B. Now are these compounds different, beta? No, these compounds are not different, they are identical. Okay, why they are identical? Because here also opposite to A we have B, and here also opposite to A we have A. So these two compounds are identical. That means MA3B do not shows any geometrical isomerism. Okay, so there is no GI possible. There is no GI possible. OI was to वैसे भी not possible. Am I clear, everyone? Fine, let's just move ahead. Let's take the another complex Ma2B2. The similar complex is PTNH3 whole twice Cl2. Okay, the similar complex is PTNH3 whole twice. The similar complex is PTNH3 whole twice Cl2. Am I clear? Yes, am I clear, beta ji? Right. So see, if I look at this particular complex, beta, if I look at this particular complex, now you can yourself see, beta. You can yourself see if you have a metal here. Okay, if I have a metal here, beta, then I have 2A. So let's keep first the 2A opposite to each other, and I have 2B. So let's keep the 2B opposite to each other. Okay, so here I have M. Opposite to 1A, I have A, and opposite to 1B, I have B, right? Opposite to 1B, I have B. Now, suppose I exchange A with B, okay? I exchange A with B. Now, here, on opposite to A, I have B, and opposite to A, I have B. Am I clear, bacha? Am I clear? That means here, A will come, here B will come, here A will come, and here B will come. So here opposite to A I have B, and opposite to this A I have B. Am I clear, beta? Right, that means here two geometrical isomers are possible. Yes or no, beta? Here two geometrical isomers are possible. Yes or no? Yes or no, everyone? Here two geometrical isomers are possible. Am I clear, everyone? Am I clear, everyone? Okay, so here 2GI are possible. Here 2GI are possible. Am I clear, everyone? Okay. Okay, so here 2GI are possible, or two geometrical isomers are possible, because when we exchange one A with B, beta, the another set is formed, which is not similar to the previous one. Okay, right. Now let's just move ahead, beta. Let's come to MA2BC. It is similar to that of the previous one, beta. Here suppose opposite to A I have A, and opposite to B I have C, beta. Right. So here what is there? Opposite to A I have A, and opposite to B I have C. Now suppose I exchange A with B. Okay, I exchange this A with this B. What will happen, beta? Now opposite to A I have B, and opposite to another A I have C. So a different compound is formed, beta. Right. Okay, so the different compound is formed, beta. Now this and the previous one, they are said to be geometrical isomer of one another. Right. Now this and the previous one, they are said to be the geometrical isomer of one another. Okay, so here we have 2GI which are possible, or two geometrical isomers which are possible. Am I clear, everyone? Am I clear, everyone? Am I clear, everyone? Clear? Okay, now let's just move ahead and come to MABCD. Now this is a little bit complicated, so please have full focus, full attention right here. Okay, so here I have MACD. Now see, if I look at it, beta, here opposite to A I have B, right, and opposite to C I have D. See, I have two possibilities. I have two possibilities, right? One possibility is I can exchange B with C, right, and the second possibility is I can exchange B with D. There are two possibilities, beta. One possibility is I can exchange B with C, right? And the second possibility is I can exchange B with D. So let's write both the possibilities, beta. First possibility is MAC, okay, MAC BD, right? And the second possibility, beta, exchange B with D. So I have MAD BC. Am I clear, everyone? Am I clear, everyone? Clear or not? Clear? That means here, three isomers are possible, beta, right? In the first case, I have opposite to AB. In the second case, I have opposite to A as C, beta. Okay, here I will have D, here I will have B, right? Okay, now here opposite to A, I have D, right? Opposite to A, I have D. Okay, and here I basically have B and here I have C. Now these are the three isomers which are possible. So there are three GIs which are practically possible. Am I clear, everyone? Three GIs which are practically possible. How many GI, beta? Three GI which are practically possible, right? So what I have done, beta, I have curated a table, right? I have curated the table in which I have written all the cases and all the possible number of GI. So you can directly cram this table and you can do all the questions. Okay, right? Now let's just move ahead, beta. See, now suppose I have a central metal atom and I have two symmetrical bidentate ligand. For example, I have PTEN whole twice. Okay, I have PTEN whole twice. Am I clear? I have PTEN whole twice, right? Here I have a symmetrical bidentate ligand. Now the symmetrical bidentate ligand could be oxalate, it could be ethylene diamine, beta. Any is possible, right? See, here if I have a symmetrical bidentate ligand, two symmetrical bidentate ligand, beta, then you can yourself understand, na, is any GI possible? No GI is possible, beta, because here, you know, if you try to swap the positions also, then also opposite to A you will have A, and opposite to this A you will have donor atom A. Am I clear, everyone? So here no GI is practically possible. No GI is practically possible. Okay, right? There is no GI which is practically possible, right? Similarly, if you have MAA, this is a symmetrical bidentate ligand, and here you have BB. Okay, here you have BB, right? Here you have BB, beta. Here also no GI is possible. Here also no GI is possible. Why? Because, beta, whenever a bidentate ligand is present, it will always come to cis position, yaar, right? So you have to arrange this in cis position only. You can arrange in this cis position, this cis position, and this cis position. Am I clear? So in all the possibilities, opposite to A donor atom, you have B, and opposite to this A donor atom, you will have B. So there is no difference. Okay, there is no difference. Am I clear, everyone? Am I clear, everyone? Fine. So no GI is possible. No GI is possible. Okay. Next we have is symmetrical bidentate ligand AA. Okay, we have symmetrical bidentate ligand AA and we have B and C. Here also, beta, no GI. Here also no GI. So the conclusion is, in square planar complexes, if you have even one symmetrical bidentate ligand, no GI is possible in the case of square planar complex. Am I clear? So if the square planar complex contain even just one GI, okay, if a square planar complex contains even just one GI, beta, okay, what I am saying if a square planar complex contain even one symmetrical bidentate ligand, I am repeating once again, I have said the incorrect thing. The correct thing is, if the square planar complex contain even the one symmetrical bidentate ligand, then in that particular case, beta, no GI is possible, right? Here you have one symmetrical bidentate ligand, no GI, right? Here you have one symmetrical bidentate ligand, no GI. Here you have two symmetrical bidentate ligand, again no GI, okay? Again no GI, again no GI, right? So you can write a conclusion, right? Okay. However, if you have a asymmetrical bidentate ligand, beta, suppose you have a asymmetrical bidentate ligand and then you have two monodentate ligands BB, okay? Then you have two monodentate ligand BB, or you can have, bacha, two different ligands as BC as well. Am I clear, everyone? Okay. Now here in this particular case, if you will try to find GI, will GI be possible? Tell me, will GI be possible right here? Beta, will GI be possible right here? See, this AB have to come in the cis position only. Now, if it has to come in the cis position, beta, then opposite to A you will be having B, and opposite to B again you will having the B. So here again no GI. Okay, here again no GI. Am I clear? Here again no GI. No GI is possible. Okay, bacha, no GI is possible. Fine. No GI is basically possible in this particular case. I hope am I clear? I hope am I clear? Yes, I hope am I clear? Is this thing clear, beta? Please quickly tell me in the chat box. If it is clear to you all, I can proceed ahead. If it is clear to you all, I can proceed ahead. Please give me an indication in the chat box whether it is clear or not. Please give me an indication in the chat box whether it is clear or not. Yes, is it clear or not, bacha? Is it clear or not? Clear or not? Clear? No GI is possible? Okay, right, fine. Now, let's come to the last case, beta. Here we have an unsymmetrical bidentate ligand AB, right? And here I have two different ligands. One is C and the other one is B. One is C and the other one is basically B. Okay, so here 2GI is possible. The other one you can replace C with B, right? You can replace C with B, right? You can replace C with B. So here in opposite to A we have B, opposite to B we have C. And in here, in this particular case, beta, in the second particular case, we can have opposite to A, C, and opposite to B, bacha, we can have small b. So these two cases are different. So these two will be geometrical isomers of each other. So they will be exhibiting 2GI. Okay, they will be exhibiting 2GI. Am I clear, everyone? Fine. So if I have to sum up, okay, if I have to sum up, right, if I have to sum up, beta, I have told you in the first, second and the third case there is 0 GI. Okay, there is 0 GI. What about MAB whole twice? What about MAB whole twice, beta? What about MAB whole twice, beta? They will show GI. Okay, they will show GI. Can you tell me the number of GI? Yes, can you tell me the number of GI? MAB whole twice. Everyone, MAB whole twice, beta. MAB whole twice. Right, MAB whole twice will exhibit geometrical isomerism, bacha. Now, if you'll ask me that how many, then 2, beta. Okay, 2. Right, 2. Right, 2. I have told you na, beta. I have MAB, MAB. Now, what you can do, you can swap. Here you can have B, here you can have A, and you can keep this intact. Okay, you can keep this intact. So here opposite to A I have B, opposite to A I have B, here opposite to A I have A, opposite to B I have B. Right, so I have told you they will exhibit 2 geometrical isomers. Right, this will exhibit 0 and this will exhibit 2 geometrical isomers. So you can cram this table and solve any question. Okay, you can cram this table and solve any question. Fine. Okay, so now let's come to the tetrahedral complexes, beta. Always keep one thing in mind, that tetrahedral complexes do not show geometrical isomerism, and only 3 tetrahedral complexes can show optical isomerism, right? One is MABCD, other one is MAB whole twice, and the other one is MABBC. Here AB stands for the unsymmetrical bidentate ligand. Okay, here AB stands for the unsymmetrical bidentate ligand. Am I clear? Fine. Tetrahedral complexes do not show GI. Only 3 tetrahedral complexes can show optical isomerism. I have written on the screen. Right? So coordination number 4 done and dusted. Now let's come to coordination number 6. Okay, coordination number 6. Now see, in coordination number 6, beta, the very first condition is, bacha, the very first condition is that if you have, you know, any two ligands which are opposite to each other, same, right? If you have any same ligand present on transposition and you have only any one such arrangement, right? For example, you have a complex M in which you have 2 monodentate ligand AA and you have 4 monodentate ligand BB. So even if you have one A opposite to A, beta, one A opposite to A, then in this particular complex, beta, you will get one POS. You will get one plane of symmetry, right? See, this will pass like this. Okay, so this will cut this molecule into 2 equal halves. So you will have one POS definitely. right? So if one POS is definitely present beta, then this compound is said to be optically inactive and it will never exhibit optical isomerism. Clear? Right? Fine. Similarly, if you have two transposition which are similarly occupied or in the same way occupied. For example, this transposition is occupied by BB and this transposition is also occupied by BB. So you have two similar transposition. Okay, you have two similar transposition. So here also beta, one POS will be present. See, for example, if you have A at the center, here you have B, here you have B, here you have B, here you have B. One beta G, A is present above the plane, 1 A is present below the plane. So you can pass a plane of symmetry that will cut this molecule into two equal half. Okay, half B, half B, half M, half B, half B, 1 A above and 1 A below. So here you will have one POS. Am I clear? So if you have two similar transposition, then also beta POS exist and this is optically inactive. Am I clear beta? Right. And if non-coplanar rings are present, for example, you have this particular types of compound beta. Okay, so if non-coplanar rings are present, right, due to presence of a symmetrical or an unsymmetrical bidentate ligand, then here POS is not possible, and if POS is not possible, such compound is optically active, and if such compound is optically active, it will exhibit optical isomerism. Am I clear everyone? Am I clear everyone? Okay, okay, fine, okay, fine. Now here, for your clarity, I have made the table already, but now I am going to individually discuss all the cases quickly and complete this in within 10 to 15 minutes so that I can end this live and you can save this recording. Otherwise, this recording won't be available if the session exceeds 12 hours. Okay, fine. So first we have Ma6 beta. Right, I have told you homoleptic complexes do not exhibit geometrical isomerism. So Ma6 won't exhibit any geometrical isomerism, no GI. Right, and here but I have told you if even one transposition is occupied by same ligand, one POS is definitely possible. However, here all the transposition are similar. Okay, so here definitely one POS will be possible, so there will be no OI. Okay, there will be no OI. Am I clear everyone? Am I clear? Next we have is Ma5B. Okay, I have Ma5B. Okay, I have Ma5B beta, Ma5B. Now if I talk about Ma5B beta, see, here there is no GI possible, here there is no OI possible. Why? Because beta, in order to have transposition or a cis position, at least you have two different ligands, right? But here this is not possible. Am I clear? Here there is no GI, here there is no OI. Okay, no GI, right? No GI beta, no OI. So no geometrical isomerism is possible, no optical isomerism is possible. Am I clear? No geometrical isomerism is possible, no optical isomerism is possible. Why geometrical is not possible? What is the reason for not exhibiting geometrical isomerism beta? See, it's very simple beta. See, if you have M, right, if you have M, then opposite to A you have B. Right, opposite to this A you have A, right, and opposite to this A again you have A. Okay, so if you replaces any of the B with the A, so again you will have MAA, AB, AA arrangement. That means again you have opposite to 1A, opposite to 1AB, opposite to 1A. So these are similar arrangement beta. So here geometrical isomerism is not possible, right? And I have told you beta, even if you have two similar transpositions, see, here you have two similar transposition, then here one POS will definitely come, and if one POS will definitely come, it will be optically inactive, and if it will be optically inactive, it won't form optical isomerism. So no OI is possible right here. Okay, no OI is possible right here. Now let's move to the next complex, which is Ma4BC. Okay, Ma4BC. Okay, Ma4BC. Now bacha, here if I take Ma4BC, now what will happen? Here I will have 4A monodentate ligand, 1B and 1C. Will it show GI? No, it won't show will it show OI? No, it won't show OI. Why it won't show OI? The reason is simple, beta. I have told you, whenever you have two similar transposition, okay, whenever you have two similar transposition, one POS is definitely possible. And even if one POS is possible, beta, then that compound is optically inactive, so it can't show optical isomerism. So here OI, that is optical isomerism, is not possible. What about GI? It is possible, beta. See, if I look at B and C, they are at the angle of 180 degree. Now if I have B and C at the angle of 90 degree, beta. Okay, so here I have B and C, here I have A, here I have A, here I have A, here I have A. This is trans and this is cis. Okay, this is trans and this is cis, beta. Right, so two geometrical isomers are possible. So how many GI are possible, beta? 2 GI are possible. Okay, 2 GI are possible. Am I clear? 2 GI are possible. I hope this is clear to you all, everyone. I hope this is clear to you all, everyone. Fine. Let's just move to the another case. Let's just move to the another case, beta. This is basically MA3B3. Now this is a special case. Okay, this is a special case. This is a special case of facial and meridional, beta. If I have A3B3, okay, I have A, I have A, I have A, I have B, I have B, I have B. See, if you try to make an octahedron, it is said to be somewhat like this. Okay, so in this particular coordination compound, what I can see here, the three similar ligands, three similar A ligands are basically present on one of the face of octahedron. Okay, if you look at the octahedron, beta, it is said to have 8 faces. Now this is one face, right? Okay, this is one face. Now if on one safe face we have three similar ligand, beta, right? This type of isomer is basically known as FEC or facial isomer. Okay, so this is basically FEC or facial isomer. Okay, this is said to be FEC or facial isomer, right? And if I have three similar ligand present along the meridian of the octahedron, now this is meridian. Okay, this is basically the meridian. Now along this meridian I have A and A, right? Okay, so this is basically a type of geometrical isomerism which is known as meridional. Okay, this is basically known as meridional. Fine, this is B, this is B, this is B, this is basically known as meridional. Am I clear? Right, now it has a short form FEC, it has a short form MER, FEC and MER, FEC, facial and meridional. Okay, facial and meridional. Can we move ahead, everyone? Can we move ahead, everyone? Okay, now let's come to the another case, beta. This is MAA whole twice B2. Now see, here I have two symmetrical bidentate ligands. Right, here I have B, here I have B. Now see, what is happening that, beta, here the 2B are present at the transposition. Here the 2B are present at the transposition. Right, okay. Now these 2B can also be present at a cis position. Right, they can be present at a cis position, bacha. Right, fine. So this is the trans isomers and this is the cis isomers. Okay, right, this is the trans isomers, so this is the cis isomers. So they exhibit GI. There are 2 GI are possible. How many GI, beta? 2 GI are possible. 2 GI are possible. 2 GI are possible. Am I correct? 2 GI are basically possible. Okay, now if I ask you, is this isomer optically active, is trans is optically active, then you will say no, ma'am, we have two similar ligand present on transposition, and whenever we have two similar ligand present on transposition, ma'am, there is one plane of symmetry which is possible. Right, now this has a POS, beta, so this is not optically active, so it won't show optical isomerism. Okay, it won't show optical isomerism. Right, however, if I talk about the cis compound, now cis compound, beta, it is said to be optically active. Why? Because it do not contain POS, right? It do not contain POS, so it is said to be optically active, so it is going to exhibit optical isomerism. Right, so if you will ask me the number of stereoisomers, I will say it is to be 3. Why? Because, beta, here I have two geometrical isomers, this and this, cis and trans, they are stereoisomers, right? And, bacha, if I talk about the cis one, it is optically active. So a non-superimposable mirror image of this particular isomer will exist. If this is dextro, the non-superimposable mirror image will be levo. So total of 3 stereoisomers are possible in this case. Okay, right? If I'll ask you how many optical isomers, you will say, ma'am, 2. How many? Geometrical, ma'am, 2. How many stereo? How many stereoisomers, beta? That is geometrical plus optical. You will say, ma'am, 3. You will say, ma'am, 3. Okay. Why? You will say it as 3. Am I clear, everyone? Fine. Okay. See, it is the case, beta. It is the case. So here I have taken the example of this particular complex, which is COAN whole twice Cl. Right, you can easily see right here, beta. You can easily see right here, beta. What you can see right here? Here you have 2Cl on the trans position, and here you have 2Cl on the cis position. Now the trans position is the optically inactive one, so it won't have any non-superimposable mirror image. It will have a superimposable mirror image. However, the cis one is optically active. It will have a non-superimposable mirror image. If this is dextro, this is levo. If this is levo, this is dextro. Then 1, 2 and 3. How many stereoisomers, beta? I have 3 stereoisomers. Am I clear? I have 3 stereoisomers. Okay, right, fine. So here we have just, done one type of isomers. So here I am taking the another example. Fine, here I am taking the another example, bacha, which is MAABC. Now, if I talk about MAABC, beta, the example to that is CONH3 ClEn. Now, see, En are fixed. What we can do, we can have Cl and NH3 once at cis position and once at trans position. Now, if I talk about the trans position one, beta, it will have a plane of symmetry, so it is optically inactive. However, cis do not have a plane of symmetry, so it will have a non-superimposable mirror image. So here also 1 plus 2 plus 3. How many stereoisomers are possible, beta? 3 stereoisomers are possible. Okay, 3 stereoisomers are possible. Am I clear, everyone? 3 stereoisomers are possible. Is it clear to everyone? Fine. Okay, so this is regarding stereoisomers. Now we have completed the optical and the geometrical isomerism as well. And now let's come to the end of this session. I hope this session was clear. I've tried to make it clear, right? I've tried to make it clear. Okay, so now we are about to end this session. I hope everything is clear to you all. Bacha, if you actually like this session, then do hit the like button and do leave a comment. Right, and it was fun teaching you all. We'll meet in the next marathon. Till then, take care. Have a good day. Bye bye. Okay, take care.